I'll take an example of a computer network and show you how does the actual things work in computer networks. Why IP address is, IP address will have two parts. One part is called network ID and other part is called host ID. Therefore, you how to send a packet from one host to other host, and there are two ways. It is also called as casting. Subnetting is nothing but dividing a big network into many small networks. The propagation delay is same either if the data is data packet or acknowledgement. The reason is rules for forming CIDR blocks, which means what are the advantages and disadvantages of stop and wait is, so broadcast links means, so what is the main response, what are the main response of such a layer is authentication and what is the need and why should we really need this IPV6. The main responsibility of computer networks is to enable two processes which are in the same computer. I'll take an example of a computer network and show you how does the actual things work in computer networks. Let's say you are in India and this is somewhere one network, Airtel network in India, and this is your host means your computer. See, this is the network. Let's assume this is the Airtel network in some region in India, and this is your host and this is a process. Okay, process. So what is it? Network, and within a network there are many hosts, and one of the hosts is your computer and the other one is within a host there are many processes, and one process is you have opened your web browser and you have typed say google.com. Now you want to go to Google and get a web page, and assume that Google's network is in California somewhere in US, and this is the network in which Google is present, and now inside that network one of the server is Google server, this is the host, and one of the process is the server which you want to connect, which means from your process at home you want to connect to the process of Google in order to get the web page, right? So what did you type in your web browser is www.google.com. Now when you type this that name, domain name, that domain name has to be converted in such a way that you are going to identify the network here. See, which means your request has to start from here and it has to first reach the destination network, isn't it? It has to reach the destination network, and after reaching the destination network your request has to reach the host, destination host within the network, and after reaching the destination host it has to reach the destination process, right? Therefore step 1 is your request has to reach the destination network, and step 2 is your request has to reach the destination host, and step 3 is your request has to reach the destination process. There are 3 steps involved in here, right? So in order to identify the network, the destination network and destination host, you have actually given only www.google.com, the domain name, right? So you gave only this www.google.com, and now using this name, this domain name, we have to identify the network and then the host and then the process, right? So somehow we have to convert this domain name into some numbers so that it can be identified. So there has to be a service which converts the domain name into IP address. Why IP address is, IP address will have two parts. One part is called network ID and other part is called host ID. Therefore using network ID we can reach the target network, and using host ID we can reach the target host, and then in order to reach the process we need something called as port number. Since you are talking about web service which is HTTP, all the web services will be run at port number 80, that is globally known. So everyone knows that if it is a web service it is 80. Therefore in order to reach the process the port number will be used, which is already predefined as a well-defined port, right? So this is how it happens. First thing is your domain name has to be converted into IP address, and your IP address is going to have two parts. One is network ID and other is host ID. Network ID is used to reach the network and host ID is used to reach the host. And then in order to reach the process we actually need the process number also, which is nothing but port number, and most of the port numbers are already predefined and they are fixed, right? And for the well-known services, since it is a well-known service, it is fixed. If it is not a well-known service, you should even know what is the port number at which the target server is running. For example, FTP it is 21, SMTP it is 25. So likewise, we have all the for well-defined ports, for well-defined services, we have well-defined port numbers. Now the step is, how are we going to convert this domain name into IP address? So in order to do that, see, one thing is, if you know the IP address directly, you can contact the service server, but then it is very difficult to remember the IP numbers, right? Because we cannot we are good with remembering the names rather than remembering the numbers. That is why your ISP, internet service provider, is supposed to provide you with a service called domain name service, which means inside your network itself, it is supposed to configure a domain name server. So before actually contacting the Google, you will actually contact the domain name server and ask for the IP address of what is the IP address of google.com, and now DNS is going to return you the IP address of google.com. Once you get the IP address of google.com, you can directly reach it. Now this entire procedure, which is converting the domain name to IP address, is actually an overhead. See, we wanted to reach Google, we didn't want to reach DNS, but then we had to reach DNS because we want to convert it, right? Therefore this entire step is called DNS overhead. So what we generally do is, we don't go to DNS all the time. We generally do it for the first time, and then we save the IP address in our computer for some time, and whenever it has expired, generally we use a log for some time, and whenever it is expired, again we will go to the DNS. So first time when you are contacting any server, sometimes the service will be late because there is DNS overhead. Second time if you use the service, then it will be straightforward. Yeah, now we shall see how to send a packet from one host to other host. There are two ways. It is also called as casting. So casting, it is of two types. One is unicast. So unicast means sending a packet from one host to only one particular host is called unicast, and other is called broadcast. Broadcast is sending a packet from one host to many hosts. That is called broadcasting. Okay, let's see about unicasting. Let us say there is a network, and the network's ID is 11.0.0.0. So what do you mean by 11? 11 is nothing but class A, isn't it? If you look at the range of class A, you must be remembering this. Class A range is 1 to 126. and class B ranges 128 to 191, and class C ranges 192 to 223, I think. Yeah. Okay. Now if you look at this class A, this 11 belongs to class A, therefore network ID is first 8 bits and the host ID is next following 24 bits. So network ID is 8 bits and host ID is 24 bits, and say this is class A. Now we have a host in this. Let us say the IP address of this host is 11.1.2.3. From this host I want to send a message to one host in the other network, only one host. So say the other network is 20.0.0.0. Again this is class A, that is why we are having the network ID as 20 and the host ID part is 0. So whenever I have all zeros in the host ID part, that represents the network ID. That is the reason we are never going to use the first IP address as any valid IP address to any host. So always the first IP address is reserved so that it could be used as the network ID of the entire network. So either you take a block or a network or subnet, we are never going to use first IP address. That is why we can configure only number of IP addresses -2. I'll tell you why we are not even going to use the last IP address. I'll tell you why we are not going to use it later. Let us say there is one more host here and the host IP address is 20.1.2.3. If you want to send a message from this host to this host, which means 1 to 1, it is also called as unicasting. In that unicasting, we are going to have a packet and in this packet we are going to put the data and destination address and source address. In the source address we are going to put this number, and in the destination address we are going to put this number. This is nothing but unicasting. Unicasting is sending a message from one host to the other host, right? So one thing you have to observe is, if it is class A network, in the network ID part it is a valid number, and in the host ID part it is all zeros. This number is used to represent the entire network. Here also the same, right? And now we see what is broadcasting. There are two types of broadcasting. One is called limited broadcasting and other is called directed broadcasting. So we shall see what limited broadcasting and what directed broadcasting is. Say we have a network and we have a host. From this host, if I want to send a message to all the other hosts in the same network, then it is called limited broadcasting. From a host, I want to send a message to all the other hosts in the same network, then it is called limited broadcasting. So what is the problem with this limited broadcasting is, let us say this is a class A network 11.0.0.0. Then how many hosts will be there in this network? Nearly 2 power 24, which is nothing but nearly 16 million, right? Which means this host has to send out 16 million packets if it uses unicast way. If it has to send it to each host one by one, it has to nearly use 16 million packets, which is really a impossible, right? 16 million packets you have to send, it is really, practically you could do it, but still it is going to hurt the hardware and software. So that is why what we do is, we do something called as limited broadcasting. Using the feature called limited broadcasting packet, if you send one packet, that will be automatically distributed to all the hosts. How to do it is, if you want to send any packet with such a capability, which is called limited broadcasting, let us say IP address of this host is 11.1.2.3, then this host will create a packet and put the message whatever it wanted to send, and in the source address it is going to fill its IP address, which is nothing but 11.1.2.3. In the destination address it has to send the message to everyone in the host, everyone in the network, right? That is why in the destination address it is going to say it wants to send to all, therefore it is going to put all ones, 32 bits of all ones, which means 1 1 1 1 1 1 1 1 so on, 32 bits. If I encode it into dotted decimal number, it is going to be 255.255.255.255. So why 255 is 8 ones is nothing but 255, right? So if you send out any packet with destination address is 255, 255, 255, 255, that packet will be received by everyone in the network, in the same network. That is also called as limited broadcasting. Therefore limited broadcasting is, a host wants to send a message to all the other hosts in the same network. That is why it is called limited broadcasting. And next one is directed broadcasting. Let's see what the directed broadcasting is. So now you understood that the number 255.255.255.255 is reserved and it can never be assigned to any host. The reason is that number represents broadcast address. Limited broadcast address is 255.255.255.255. This number should never be assigned to any host, because this number represents some other meaning, right? Next one is directed broadcast. Directed broadcast is, a host in a network wants to send a message to all the other hosts in some other network. So say this network is 11.0.0.0 and this network is 20.0.0.0, right? Now if you observe this is also a class A network. How many hosts are there? Nearly 2 power 24, which is nothing but 16 million hosts are there. But then I want to just send a message, one packet, and that has to be distributed to everyone in this particular network. It is different from the previous one. In the previous one, limited broadcasting is used to broadcast from this host to everyone in the same network. In the directed broadcast, it is from this host to everyone in the other network. That is how this is different. So what you should observe here is we are not going to send a packet to the same network, we are sending a packet to the different network. In order to do that, this host, let us say the IP address of this host is 11.1.2.3. This host is going to create a packet and it is going to put the message in the packet. In the source address, source IP address, it is going to put this number 11.1.2.3, and in the destination IP address, you know that you have to send a packet to everyone in this particular network. Therefore, what is the network ID? 20, valid network ID. And whom do you want to send it in this? To everyone, to all. That is why in the host ID part, we are going to say all. All means all ones. If I put all ones, it is going to be 255.255.255, right? So if I use this address, then this packet will be delivered to everyone in network 20. Inside network 20, all the hosts, right? So we are never going to use a IP address which contains all ones in the host ID part, right? So directed broadcast address is a valid, in the network ID part we are going to have a valid IP, valid number, and in the host ID part we are going to have all ones, right? So we have seen three kinds of numbers. This is called a network ID, right? Network ID is nothing but the number which is used to represent the network. So don't get confused with the network ID part and host ID part of the IP address. This is nothing but the network number. An IP address which is used to represent the entire network is sometimes also called as network ID, right? So network ID is nothing but, in the network ID part we are having a valid number, and in the host ID part we are having all zeros. Therefore, all zeros in the host ID part is not a valid IP address which you can assign to any host that represents the entire network, and all ones in the host ID part, it is used to represent directed broadcast address of a network. So even though practically we are having, let us say 2 power n IP addresses in a network or a block, we are not going to configure 2 power n hosts. The reason is two addresses have to be removed. One address is for network ID and the other address is for directed broadcast address. Therefore, in class A, even though 2 power 24 IP addresses are present per network, we are going to have 2 power 24 minus 2 hosts only per network. In class B, even though 2 power 16 IP addresses are present per network, we are going to configure only 2 power 16 minus 2 hosts. And even in class C, even though we are having 2 power 8 IP addresses per network, we are going to have only 2 power 8 minus 2 hosts configured. Therefore, in exam, just be clear about whether they are asking about the IP addresses or the hosts configured. Okay, fine. We shall see next coming to what is subnetting and all. We have seen that class A contains nearly 2 power 24, which is 16 million, and class B contains 2 power 16, which is 64,000, and class C, the smallest class, also contains 256 IP addresses, which means 254 hosts can be configured. In many of the cases in practical at industry, what happens is we don't want very big networks. The reason is maintenance will be very difficult. So if you see, let us say we have a class A network. So in class A network there are nearly 16 million hosts, right? So if I have 16 million hosts in one network, then for a network administrator, management of all these things is going to be, all these many hosts is going to be a headache, right? So first thing is, maintenance of a very big network is going to be really a headache. And second thing is, we want to provide some security within the network, within the same network. Let us say in your office, in your company, we have 4 departments, and one department is developers, and other department is testing, and other department is maintenance, and other is HR department. So we don't want all the departments to access any common servers. For example, if there is any code server, we want to protect this code server from the other departments, right? So in this case, we don't want to leave the network loosely. So one thing is, if I have a very big network, Maintenance is going to be very difficult, and second thing is security is going to be one more second issue. That is why even we have a big network, we are going to divide into many smaller networks. This is called subnetting. Subnetting is nothing but dividing a big network into many small networks. Advantage is maintenance of smaller networks is easy compared to maintaining one big network, and second thing is we could provide security to some particular network from the other networks. Okay, and this is about the subnetting. Even subnetting is having some advantages, but it also gets along with it some disadvantages too. So disadvantages, first thing is, if you have a single network, one big network, in order to reach a host, we needed 3 steps. One is identification of the network, identification of the host, and then identification of the process. So in order to reach the process, there are only 3 steps required. But now if you have a subnetting, which means if you have a very big network which is divided into smaller networks, then the identification problem is complex, which means you have to reach the network first, and then you have to reach the subnet, and then you have to reach the host, and then you have to reach the process. Right, here we have 4 steps involved. In case of subnetting, here there are only 3 steps. So advantages are there as well as disadvantages are there, but then advantages are more prominent, and so we even go for subnetting. So I'll take an example and explain you how subnetting works. Let us say you bought a class C network, and a class C network, as you know, contains 8 bits in the host ID part, which means 256 IP addresses and 254 hosts, right? So let us say that this is a class C network, 200.1.2.0, that is the network ID, and this entire part is network ID, and this 8 bits is host ID. Now how many bits are the host ID in class C? It is generally 8 bits, right? So 8 bits are in the host ID part. 1, 2, 3, 4, 5, 6, 7, 8. So using 8 bits, how many parts can I divide how many IP addresses do I get? 2 power 8, which is 256. How many hosts can I configure? 2 power 8 minus 2, 254. Why? Because the first address is given as network ID and the last address is given as directed broadcast address. Therefore, these 2 IP addresses are generally not used, right? And in the remaining, we have 8 bits, right? So in these 8 bits, I would like to divide this entire 254 or 256 IP addresses into 2 parts. If I have to divide the number space into 2 parts, how many bits should we choose? 1 bit. So I am choosing the first bit among the 8 bits. If I choose 1 bit, we are actually dividing the entire number space into 2 halves. So the first half contains 1, 2, 3, 4, 5, 6, 7, 8. The first half contains 0, that is the starting bit, and the second half contains 1. 1, 2, 3, 4, 5, 6, 7, 8. Second half contains 1, right? Now, what about the 7 bits, the range? What is the range of IP addresses that fall in the first half, and what is the range of IP addresses that fall in the second half? So if you look at the range of IP addresses that fall in the first half, I have to start with all zeros, these 7 zeros, right? So the range is 0, 0, 0, 0, 0, 0, 0, 1, it is 1, 0, 0, 0, 0, 0, 1, 0, this is 2, so on, 1, 2, 3, 4, 1, 2, 3, this is 7 ones, which is nothing but 127. So the range of addresses in the first half is 0 to 127. Now what about the range of addresses in the second half? 0, 0, 0, 0, 0, 0, 0, 7 zeros, and moreover we have a 1 here. Therefore the first address is 128. Next one is 0, 0, 0, 0, 0, 0, 1. This is 129. So on, 1, 1, 1, 1, 1, 1, 1. So all 8 ones. Here 7 ones are there, already 1 is there. Therefore this is going to be 255. So in the first subnet the addresses are from 0 to 127, and in the second subnet the addresses are from 128 to 255. So always remember, see, previously what is the network ID? The network ID is 200.1.2.0. 2, this is the network ID, and the remaining 8 bits were host ID, right? 1, 2, 3, 4, 5, 6, 7, 8. The remaining 8 bits were host ID, but then this bit is taken for subnet ID part, which means this bit is used to define the subnets. Since we have taken one bit, how many subnets we got? 2 subnets. And now the remaining part is the new host ID. Previously the host ID was completely 8 bits, but now one of the bit is given for subnet ID. Therefore the resulting host ID part is now containing only 7 bits, right? According to the definition of network ID, whenever I put all zeros in the host ID part, it is going to be the network ID, right? Therefore, if I put all zeros in the host ID part, it is going to be the network ID for this network. So for this subnet, the subnet ID is nothing but 200.1.2.0, the first IP address. And now what about the last IP address, 200.1.2.127? This last IP address is always directed broadcast address for this particular subnet. Therefore, this particular subnet's network ID is 200.1.2.0 and the directed broadcast address is 200.1.2.127. And what about this? The second subnet's network ID is always the first IP address, 200.1.2. What is the first IP address? 128. Why so? Because in the host ID part we have all zeros. And what about the directed broadcast address? It is nothing but the last address. What is the last address here? 200.1.2.255. Got it? So for the second subnet, this is the network ID and this is the directed broadcast address. For the first subnet, this is the network ID and this is the directed broadcast address. Now for the network as whole, this entire part is 200.1.2.0 is network ID and 200.1.255 is the directed broadcast address. So there is a confusion here. Whatever was the network ID of the first subnet, that number is also the network ID of the entire network, and whatever is the directed broadcast address of the last subnet, that is also the directed broadcast address of the entire network. There is a confusion, right? So now if I say 200.1.2.0, what do you think I mean? Do I mean that I am talking about the entire network or the first subnet? And second thing is, if I send out a packet with IP address 200.1.2.255, am I sending out that packet as a directed broadcast address to the entire network or only to the second subnet? That depends, right? In order to resolve this ambiguity, you have to see how they are actually arranged. See this? Whenever we do any subnetting, we get a router. This is called internal router, and your ISP is going to provide you internet connection from the external router, and now this is your internal router. Let us say this is one subnet and this is other subnet, and in this subnet you have addresses from 0 to 127, and in this subnet we have addresses from 128 to 255, and this is the network ID for this subnet and this is the network ID for this subnet. 127 is the directed broadcast address for this subnet and 255 is the directed broadcast address from this subnet. Now whenever I say .0, do I mean the entire network or only the first subnet? That depends on where you are standing. If you are inside the organization, then you know that the network is divided into two subnets. Then whenever you say 0, it means that you are actually talking about the subnet. If you are outside, then you are not aware that there are subnets inside the network. Therefore, whenever you say 0, it means that you are talking about the entire network. That depends on the perspective, whether you are inside or you are outside. So if you are inside a network, okay, then you mean to talk about the subnets. If you are outside a network, you are talking about the entire network as a whole. Now if a packet is coming from within the network and if it has to be sent to .255, it means that it is the directed broadcast address to this network. If a packet is coming from outside network, which means if the packet is coming on this interface, okay, and now if the packet has to be sent to .255, then this router understands that that packet has to be broadcasted to the entire network. If a packet is coming from this interface and if the destination IP address is .255, then the router understands that that has to be sent only to this, right? and if a packet comes from this interface, if the destination IP address is 127, then the packet will be broadcasted only to this network, right? So depending on whether you are inside or outside, the actual IP addresses will be interpreted accordingly. Okay. Now one more question is, how many IP addresses are now usable here? So initially we had 256 IP addresses in class C. If you use them in a one single network, then total number of hosts you can configure is 254. Now whenever I do some this subnetting, now we got two subnets. Each subnet has 128 IP addresses, but then we will not be able to use all 128 IP addresses. We are going to use only 126 IP addresses. So overall we are not going to get 254 hosts, we are going to get only 252 hosts, which means because of subnetting there is even a loss in the number of IP addresses. The reason is every subnet is going to waste two IP addresses, one for the subnet ID as well as one for the directed broadcast address. Okay, so in order to divide this entire network into two subnets, we are choosing one bit and we got two subnets. Let us say I want to divide the entire network into 4 subnets. Then how many bits should I be choosing? If I want 4 parts, I have to choose 2 bits, right? Yeah, so in the previous example we have seen that we wanted to divide a network into 4 parts where all the parts were of same size, right? So we did this. In previous example we had taken one network and we divided into half first, and size of each part is same, equal, right? And then we divided it into 4 parts, and again the size of each part was same, right? So if you remember, we got 64 IP addresses in each part. Now let us say I want to divide the network into 4 parts, but then my requirement is different. In the sense, I want to divide into maybe not 4 parts, 3 parts like this. I want to divide a network into 3 parts in such a way that one part will get 128 addresses, and other part will get 64, and the other part will get 64, right? So if I do such a kind of subnetting where the subnet sizes are different, it is called variable length subnet masking, VLSM. The reason is whenever the size of the subnets are different, every subnet is going to get a different subnet mask. That is why it is called variable subnet. Okay, so let's see one example here. So let's take the same network 200.1.2.0. So this is the network ID, and this network I want to divide into 3 parts in such a way that first part will contain 128, second part 64, and third part 64. First of all, do we have these many IP addresses in the network put together? Yes. 64 plus 64 is 128, 128 plus 128 is 256. We definitely have these many IP addresses required in our network. Now the thing is, how are you going to divide them in such a way that one part will get 128 and the other part will get 64 and 64. So one thing you can observe like this. One thing is, how many bits do we have in host ID part? 8 bits, right? So let us say these are the 8 bits in host ID part. Now if I want 3 subnets, how many bits should I choose from the host ID part? In general, if you choose 1 bit, we are getting 2 subnets. If I choose 2 bits, we are getting 4 subnets. Here I wanted 3 subnets, therefore I need at least 2 bits. I need to choose at least 2 bits in order to get 3 subnets. In fact, we get 4 subnets here, right? If I choose 2 bits, I get 4 subnets, and the size of each subnet is, actually there are 60 bits, 6 bits remaining in the host ID part. Therefore size of each subnet is going to be 2 power 6, which is nothing but 64 IP addresses. But then this is not what I wanted. What I wanted is only 3 subnets, and each subnet size should be 128, 64 and 64. Therefore this kind of organization or this kind of arrangement is not going to work. We should think about some other methods. One method is this. The way we classified class A, class B, class C, class D addresses, the same way we could do here. So what I could do is, initially I'll choose first bit in the 8 bits, I'll choose 1 bit. Whenever I choose 1 bit, I am dividing the entire IP addresses into 2 parts. One part will contain 0 in that part, and other part will contain 1, isn't it? Now in the remaining half, wherever there was one bit chosen as 1, I'll choose the second bit in such a way that the second bit will be 0 for one subnet and the second bit will be 1 for the other subnet. Right? Now if you look at this one, the subnet ID is going to be 0, and how many bits are remaining for the how many bits are remaining is 7 bits. So since 7 bits are remaining, 2 power 7, 128 addresses are possible here. And how many bits are remaining in the host ID part? 6 bits. Since 6 bits are remaining, 2 power 6, 64 is possible, and here also 6 bits are remaining, therefore 2 power 6, 64 bits or 64 IP addresses are possible. This is one way to do it. So if you follow this method, what is the subnet ID of this subnet? Subnet ID is always the first IP address, right? So in this subnet, if you see, it is going to be 200.1.2.1234567 First one is going to be 0. First bit you have already fixed it as 0. So now you get from all zeros 7 zeros to 7 ones. So if you look at that, it is going to be 200.1.2.0 is the first IP address, and 200.1.2.127 is the last IP address, and totally we got 128 IP addresses, out of which the first IP address is nothing but the subnet ID of this subnet, right? And now if you look at this subnet, the next one, so it is 200.1.2.1234567 First two bits are fixed as 10, and how many bits are remaining? 6 bits, and these 6 bits can run from all zeros to all ones, right? Now the first IP address is nothing but 200.1.2.1 followed by 7 zeros, which is 128, and the last IP address is nothing but 200.1.2.128 plus 63, which is 191. Therefore this IP address 128 is the subnet ID of this second network, and the directed broadcast address for this network is 191, and the directed broadcast address for the first network is 127, right? So now this one, for the next subnet, we are going to again have the same way, 200.1.2.1234567 and the first two bits are going to be 11, and the remaining 6 bits can run from all zeros to all ones, 1 2 3 4 5 6, all zeros to 1 2 3 4 5 6. So this is nothing but 200.1.2.192, and this is nothing but 200.1.2.255. Therefore this one is nothing but the subnet ID of this network, and this address is the directed broadcast address of the third network. Therefore we got 3 networks and the subnet IDs and the required sizes. Now my question is this the only answer possible, or is there any other answer also? And before going to that, let us see about the subnet mask also. So what about the subnet mask? Subnet mask contains all ones in the network ID part and host ID part. So coming to this network, already we have 24 bits in the network ID part, and then 1 bit in the subnet ID part, and again 7 bits in the host ID part, right? Therefore this network has 24 ones, which means 255.255.255 dot followed by 1 bit is chosen for subnet ID part. Therefore if I choose 1 bit and all the remaining bits are zeros, it is going to be 128. Therefore for this subnet, this is the network ID and this is the subnet mask, right? And coming to this subnet, already 24 bits are there in the network ID part, and I have chosen 2 bits for the network ID, subnet ID, and the 6 bits are there for the host ID part. Therefore for the first 24 bits we are going to have 24 ones, which means 255.255.255 dot. In the host ID part, only 2 bits are chosen for subnet ID part. Therefore in those 2 bits, if I write 1, we are going to get 192, and the remaining 6 bits are going to be zeros, which means this is the subnet mask and this is the network ID, right? And for the third one, this one, Again the same thing applies. Subnet mask is nothing but how many bits did we choose for subnet ID? 2 bits. Therefore subnet mask is already 24 bits are there in the network ID part, along with the 2 bits are there in the subnet ID part. Therefore even for this network also the same 255.255.255.192 is the subnet mask. So if you observe this, the networks which are having same sizes will get the same subnet mask, and the networks which are having different sizes will get the different subnet mask. Since for this subnetting we are getting variable length subnet masking, it is also called as VLSM, variable length subnet masking. Whenever the subnet sizes are different, the subnet mask sizes will be different, and therefore they will be called VLSM, variable length subnet masking. Okay, so one more thing you should observe here is we are having one bigger network and 2 smaller networks. So whenever the network size is bigger, the subnet mask will be smaller. The reason is, in the subnet mask, number of ones will decide the number of zeros. If number of ones increases, then the network size obviously decreases. Or you can even think of it this way. Given a subnet mask, number of zeros will give us the size of the network. So for a bigger network, number of zeros will be more and number of ones will be less, which means the subnet mask will be smaller in the number, right? And for a smaller network, number of zeros will be less and number of ones will be more, therefore subnet mask will be larger in the number, right? So this is one way of getting 3 subnets. One other way of getting 3 subnets is, maybe I'll show you this. The same way, first is you can choose 1 bit, which means that can be 0 here and that can be 1 here. Instead of dividing the one side, you can choose the other side, which means in this 0 side only you can choose the second part, which means 0 0 and 0 1. So in case if you have used this subnet masking, then what is the size of this? 64. Why 6 bits are remaining in the host ID part? 64. And what is the size of this? 128. Now what is the network ID of this? 200.1.2.0 only. Why 00 followed by all zeros? What is the network ID of this? 200.1.2.64. Why? Because 10 followed by 6 zeros. That is the first IP address. And what about the network ID of this? 200.1.2.128. Okay. And now what about the subnet mask? Subnet mask is we have to put all zeros in the network ID part, and then wherever in the subnet ID part you have to put all ones in the network ID part and all ones in the subnet ID part. So in this network we already know that 24 bits have to be ones, which means 255.255.255. We have chosen 2 bits from the host ID part for the subnet ID. Therefore if I choose 2 bits, it is going to be 128 plus 64, which is 192. Even for this network it is same. What is it? 255.255.255.192. And what about this? For this network only 1 bit is chosen for subnet ID part. Therefore subnet mask is going to be 255.255.255.128. Therefore these are the network IDs and host ID part. These are network IDs and subnet mask. If you look at both the examples, both are right. So given any question that if they are asking you to divide them into 3 subnets of unequal sizes, you can either do it this way or this way. Both are fine. Okay. So we are going to get 2 kinds of answers here. Now how does the routing table? So let's say we are following the division as shown in this example here, right? Then what about the subnet mask or routing table of the internal router? So routing table should contain, one is network ID, subnet mask and interface, right? So this is what, which means we have now 3 networks, 1, 2, 3, and the router which is connecting all 3 networks. Okay, this is the network and this is the external router, right? So what is the network ID, subnet mask of each one is? Network ID of this network is 200.1.2. of this first network is 0, and the subnet mask is 255.255.255.128, and let us say interface is A, and the network ID of the second network is 200.1.2.128, and the subnet mask is 255.255.255. You can know the subnet mask, which is 192. The reason is 2 bits are chosen here. And the third one is 200.1.2.192 is the network ID, and the subnet mask is 255.255.255.192. Let us say B and C. And again you will have one more entry, which is default entry, which is 0.0.0.0, right? And the default entry, let us say, is D. So now in this routing table, if you look at it, now we are going to have variable subnet mask, which means subnet mask is of variable length, right? So again the rules are same. First you take the network ID, the destination IP address, and it with the subnet mask, and if it matches with the network ID, then you send it over that interface, whatever interface is connected. If there are two matches, in this case, whatever is the longest match, see in these three, the longest subnet mask is 255.255.192. Therefore the longest one is going to get the highest priority. If there are two matches, go for the longest one. If there is only one match, go for it. If there is no match, go for the default entry, right? So this is also called as variable length subnet masking. Coming to this classful classification, this class A, class B, class C, there is a problem in this. See, I'll just show you. Let us assume that this is the entire space of IP addresses, 2 power 32. With 32 bits, the IP addresses possible is 2 power 32 IPv4, right? Now what we did was, we initially have chosen first bit, and the first bit can be 0 this side, and the first bit can be 1 this side, right? And now we have divided the entire address space into 2. We call it class A, right? And then we have chosen the second bit. The second bit can be 10, or the second bit can be 1, which means 11, and we call it class B. And again we have chosen the third bit. The third bit can be 0, or the third bit can be 1, which means 111. We call it class C. And now this again 110 and 1111. This is class D, and this is class C. So that is how we got all the classes, right? So then what we did was, we divided again these classes into networks of different sizes, which means we are again cutting this entire class A part into networks such that size of each network is 2 power 24, which is nothing but 16 million. And here also in class B, again we have divided this entire class B into networks where size of each network is 2 power 16. And even class C also we divide into small networks, and where the size of each network is 2 power 8, right? So if you want to take a class, you go for the smallest class, right? So if you want to buy a class of IP addresses from IANA, see all these IP addresses are generally with IANA, Internet Assigned Number Authority, who is having this entire control over IP addresses. Now if you want to buy a class, let us say in your office, if you want to configure a class, then you are going to get the smallest one, assume that. So you have to buy the smallest one. So what is the size of the smallest class? The size of any class C network is 2 power 8, which is nothing but 256 IP addresses. So you are going to get 256 IP addresses if you buy the smallest network, right? Therefore, what if I want to go for even a smaller size? So the problem with this classful classification is, it is like this. It is a big cake which has already been cut. Now if you want to buy any piece, you have to take the entire piece. Even if your need is 100, you have to go for 256 only. Let us say your need is 300, then you have to go for class B. If you buy a class B, it is going to give you nearly 64,000, right? And that is why there is no flexibility. So the next classification says that till 1990s people used to use this classful classification, and then what people thought was this classful or using class A, class B, class C is not flexible, therefore they have come up with classless. Classless means they are not going to divide anything, the addresses into class A, class B, class C. They will be left as it is, and whenever you want any IP addresses, then you can ask for the exact number of IP addresses you want. Then they will cut the address space and they will give you whatever block you wanted, irrespective of where it falls, class A or class B or class C. This is called classless or CIDR. So CIDR is like this. We are not going to have any more classes now. We are just going to, whenever any user asks me for IP addresses, I am going to assign those many IP addresses to the user, right? And this is also called as block. Okay, so now there are no classes, which means given an IP address we cannot know whether it is class A, class B or class C. So what is the disadvantage of not having classes is, if I give you an IP address and if you know that it is class A, you could say that 8 bits is network ID and 24 bits is host ID part, isn't it? And if you know that it is a class B network, you could say that 16 bits is network ID and 16 bits is host ID. And if it is class C network, you can say that 24 bits is network ID and 8 bits is host ID part. So this is the advantage of having classful classification, which means the division inside is implicit and no one need to specify you that. But coming to this classless, now there are no classes here, right? So then the problem here is, given an IP address, what part is going to be network ID and what part is going to be host ID? That is the main difficulty. So given a IP address from the classless CIDR block, what could be the block ID or network ID? It is sometimes also called as block ID. Since they are called blocks, I am going to call it block ID instead of network ID. And what could be host ID part, right? So this is the main confusion coming to CIDR. So just to avoid this confusion, we are having a CIDR notation in which we say that an IP address is a.b.c.d. This is dotted decimal representation, as you know before, / we are going to have a number n. This number n indicates what is the number of bits that are present in NID, network ID part. For example, if you say IP address is 20.10.50.100/20, it means that in this in the block in which this IP address is present, the number of bits used for network ID part is 20 bits. That is the meaning of it. If the number of bits used in network ID part is 20 bits, total bits are 32, right? And now number of bits used in network ID part is 20 bits. Therefore, how many bits will be used in host ID part? So 32 minus 20, which is nothing but 12, right? Therefore, in this address, if 20 is the network ID part, then host ID part will be 12 bits. Therefore, the block in which this address is present contains number of IP addresses which are 2 power 12. So given this IP address, you can know that 20 bits are there in the network ID part and 12 bits are there in the host ID part present in the block in which this IP address is present. This is also called as CIDR representation. CIDR representation. This is the way we should represent the IP addresses currently. So currently we are using CIDR, which means we don't have, even though this number 20 says that it belongs to class A, but then it is no more belonging to class A, which means you should not say that first 8 bits are network ID and 24 bits are host ID. You should look at this slash number. This /20 says that the network ID part is 20 bits and host ID part is 12 bits. Therefore, the size of the block in which this particular IP address is present contains even 2 power 12 IP addresses, right? So if given a.b.c.d/n means that n bits are there in the network ID part, and so host ID part contains 32 minus n bits. Therefore, total number of IP addresses present in this block will be 2 power 32 minus n. That is the total number of IP addresses present in the block. Okay. So now let's see how to form these CIDR blocks. Okay, I'll show you next how to form a block of CIDR. Okay. Now we have seen that there is something called a CIDR block, which means the IP addresses are not now cut into parts, they are left as it is. Therefore, whenever a user asks for an IP address or a block of IP addresses, we are going to dynamically cut the IP addresses here and we are going to give it to the user. This is called a block. Now there are some rules that you should follow when you are doing this block. I'll tell you all the rules for CIDR blocks, and then I'll tell you why each rule is important. Okay, so rules for forming CIDR blocks, which means you cannot form the CIDR blocks randomly. All the CIDR blocks are supposed to follow these rules. First rule number 1 is all the IP addresses should be contiguous. So what do I mean by contiguous is, if you are starting the IP address from some number, then the next IP address should be the next number, and the next IP address should be the next number. There should not be any interleaving, which means you can say, if you have the first IP address as .10, next IP address should be .11, .12, .13, so on, like this. Okay, they should be contiguous. There should not be any gaps, which means you cannot take some part from here and some part from some other area, and then you can say that these two form a block. So that is the first rule. And the second rule is, whatever IP addresses you are going to ask for, the block size should always be a power of 2, which means you should not ask for a random number. You should not ask for 100 IP addresses. You should ask for 128, or you should not ask for 50. You should ask for 64, right? So always you should ask for a power of 2, this one. So why do you think that we are using power of 2 is, it is very, very simple. See this, even in operating systems, the size of a page is always a power of 2. If you observe, we are always had this page size as 512 bytes or 1024 bytes, and why do you think that we never had this 500 byte page or 1000 byte page instead of 512 and 1024 is, the reason is this. If I have, let us say, I'll take a number 1010, or let me say 1011. So this number is nothing but 11, right? So if I divide this number, if I want to divide this number with 2, which means 2 power 1, what will be the remainder? This entire number is 11. If I divide with 2, the remainder will be 1, and the quotient will be 5, isn't it? 2 into 5 plus 1, right? And similarly, if I divide this number with 2 power 2, which is nothing but 4, then the remainder will be 3 and the quotient will be 2. If I divide it with 2 power 3, which is 8, if I divide 11 with 2 power 3, then the remainder will be 3 and the quotient will be 1. If I divide this number with 2 power 4, then the remainder will be 11 and quotient will be 0. So understand this, there is a number and I am trying to divide it with powers of 2. If I divide this number with 2 power 1, then the remainder I am getting is 1 and the quotient I am getting is 5, which means if I divide any number with 2 power 1, then the least significant 1 bit is the remainder and the most significant remaining bits are nothing but the quotient. That is why the remainder is 1 and the quotient is 5. 101 is 5, right? If I divide this number with 2 power 2, then the remainder will be 3 and the quotient is 2. The reason is, when you divide it with 2 power 2, then the least significant 2 bits is going to be the remainder, which is nothing but 1, which is 3, and the most significant remaining bits 10 is going to be the quotient, which is nothing but 2. If I divide it with 2 power 3, then the least significant 3 bits is going to be remainder and the most significant 1 bit is going to be quotient, which means 1 is nothing but 3 and the most significant 1 is quotient. If I divide this number with 2 power 4, then the least significant 4 bits, which is nothing but 1011, is going to be the remainder and the most significant remaining bits, there is nothing remaining, therefore it is quotient. So what did you understand from this? You understood that if I have a n bit binary number, n bit binary number. It is important. The number should be binary. If I have a n bit binary number and if I divide it with 2 power k, a number in a power of k, then the remainder is nothing but least significant k bits is the remainder and the most significant n minus k bits is the quotient. And what if the number is a decimal number? If the number is decimal number, then dividing with 10 powers is easy, isn't it? Just check this. If I have 1, 2, 3, 4, if I divide it with 10 power 1, then the least significant one digit is remainder and the most significant remaining digits are quotient. If I divide it with 10 power 2, which is 100, then the remainder is 34 and quotient is 12. If I divide with 10 power 3, then the remainder is 2, 3, 4 and the quotient is 1. If I divide with 10 power 4, then the remainder is 1, 2, 3, 4 and the quotient is 0, right? That is why, since the IP address is a binary number, if you take the size of a block as power of 2 power n, then it will be easy for us to divide the number. Dividing is nothing but choosing the least significant k bits and then this, which means, let us say, if the block size is 2 power 5, you know that IP address is already 32 bits. Now it is very easy to divide into host ID part and block ID part. Since the block size is 2 power 5, the least significant 5 bits is going to be the host ID part and the most significant remaining bits, how many ever? 28 I think, 27. This is nothing but block ID. Therefore, finding out the block ID is very easy if the size of the block is a power of 2. Similarly, finding out the page number is very easy if the size of a page is power of 10, power of 2. And moreover, finding the size number, block number, or if you remember that CO, there is something called as tag. Finding out the tag is very easy if the size of the block is a power of 2. That is why in computer science, since the addresses are always binary numbers, we go for sizes always in power of 2. So that is the reason this second rule applies, that the block size should always be a power of 2. Now since the block size is power of 2, we can completely utilize the host ID part. And now the third rule is first IP address in the block. So whatever block you have formed, the first IP address should be divisible by size of the block. Not just divisible, it should be evenly divisible. It should be evenly divisible by size of the block. I'll tell you why this third rule is important. The third rule says this: if you have a IP address, the first IP address in this block should be divisible by size of this, which means 2 power n, whatever, 2 power n or 2 power k. So it should be divisible by this number. So what do I mean by this is, when there is a n bit number, let us say there is 32-bit number, this one is 32-bit number. If this 32-bit number has to be divisible by 2 power n, then the remainder has to be 0, right? So whenever you divide any number, any binary number with 2 power n, the remainder is nothing but the least significant n bits. Now if this number has to be evenly divisible by the size of the block, it means that the remainder should be 0, which means the least significant part should always start with all zeros in the host ID part. That is the reason. The reason is why we are going for this kind of third rule is, if we start the first address with all zeros in the host ID part, then this first address could be used as the block ID. If you remember, network ID or block ID or subnet ID is always the part containing all zeros in the host ID, right? So that is the reason why we are asking that, why we are specifying the rule that the first IP address should be divisible by size of the block. Now if the first IP address is divisible by size of the block, always the first IP address is going to start with all zeros in the host ID part. Therefore this IP address could be used as the block ID, and now all the next one will be 0 0 0 0 followed by 1, so on 1 1 1 1 1 1 in the entire host ID part. So if I start with all zeros in the host ID part, I could actually utilize the entire host ID part. If you start from any other number in the middle, by the time I reach all ones, I will not be getting 2 power n IP addresses. See, there are n bits. If this n bit starts with all zeros, which means the first IP address starts with all zeros, then only I can get 2 power n numbers. If this n bits doesn't start with all zeros, if it starts with any other random combination, then I don't think that we could reach the all ones easily. I mean, even by the time you reach the all ones, what happens is you are going to get some gap, which means you will not be getting 2 power n IP addresses, right? So I'll just summarize what we have seen till now. See, whenever you want to create a CIDR block, we have to keep in mind that we follow these 3 rules. First rule is all the IP addresses should be contiguous, which means you should not create blocks here and there. Second rule is you should ask for a power of 2. The IP address, the block should be a power of 2. The reason is if the block is a power of 2, then it will be easier for us to divide the IP address into block ID and host ID without actually using a division, just the number of bits. And the third rule is first IP address in every block should be evenly divisible by size of the block. The reason is if I divide the first IP address, if the first IP address is evenly divisible by, let us say, size of the block 2 power n, then it means that the least significant n bits are all zeros. If the least significant n bits are all zeros, and if that is the starting address, then I can go till all ones. Right? If I have n bits starting from all zeros going to all ones, then only I can get a combination of 2 power n IP addresses. If I don't have this starting as all zeros, let us say if you are randomly starting somewhere 0 1 0 0 0 1, by the time you reach all ones, you will not get your full count. What is that you wanted? You wanted a block of 2 power n. That is why you should start with all zeros in the first IP address and go till all ones in the last IP address. Let's talk about what are the various delays that we have in computer networks. Delays means the time, right? So one thing is transmission delay. First one is transmission delay. Okay, so I'll write it as TT. So TT denotes transmission delay. So what is transmission delay is, let us say this is a host and this is the link, right? This is the channel or the internet or whatever, right? So let us say this is the host and this is the propagation medium. Transmission delay is nothing but the time taken to transmit a packet, let us say this is the data packet, onto the outgoing link is called transmission delay. Okay, understand this? The time taken to transmit the packet, the data packet from a host onto the outgoing link is called transmission delay. See, whatever I am saying is informal definition. For formal definitions, you please refer the textbook. This informal definition is enough to understand the concept. So understand, transmission delay is nothing but if there is a host and if it is having a data packet, the time taken by the host to put the data packet onto the outgoing link is called transmission delay, right? So how to find out the transmission delay is this way. If the bandwidth is 1 bit per second, which means every second I can send 1 bit, I can put 1 bit onto the link, right? Then if the data size is 10 bits, then what will be the transmission delay for this data? The transmission delay for this data is, in every 1 second I can put, see, bandwidth is saying that in 1 second we can transmit 1 bit. That is what bandwidth says. Bandwidth says how many bits we can transmit in 1 second, right? It is nothing but 1 bit per second. Now I have to send 10 bits. So how much time will it take? 10 seconds. Therefore transmission delay for this data of 10 bits is 10 seconds. That is what you should understand. So if the size of the data packet is, let us say, L bits, size of the data packet is L bits, and the bandwidth is capital B bits per second, then what is the time taken to transmit this data of size L bits is L by B seconds. How? L is bits and B is bits per second. When you divide bits by bits per second, seconds is going to come up, right? Therefore, even by looking at the values, Even by looking at the units, you can understand what is the formula. So formula for transmission delay is L by B. So transmission delay depends on two things. One is length of the packet and other is bandwidth of the network. If the length of the packet is too big, obviously transmission delay is going to be very big, which means the time taken to put a big packet onto the outgoing link is generally more. And if the bandwidth is high, then the transmission delay is less, which means if the bandwidth is very high, you can transmit the packet faster, right? So let's see one problem. One problem is, if length of the packet is 1000 bits and the bandwidth is 1 kbps, okay, then what is the transmission time? Transmission time is nothing but L by B, and L is given as 1000 bits and bandwidth is given as 1 kbps. 1 kbps means 1000, which means you get 1 second. If the question is, if the length of the packet is 1 kb, not 1000 bits, 1 kb, and if the bandwidth is 1 kbps, then what is the transmission time? So transmission time, do you think that both the questions are same? Do you think that we should get only 1 second? I think the answer is not the same. The reason is, whenever the length of the packet is given in terms of k, it is actually 1024 bits, and the bandwidth is given in k, it is 1000. Okay, therefore the answer is 1.024. One point you have to note here is, whenever data is given as k, it means that it is 1024. If the bandwidth is given as k, it means that it is 1000. Whenever data is given as m, it is 1024 into 1024. Bandwidth is given as m, it is 10 power 6. Data is given as g, it is 1024 into 1024 into 1024. And bandwidth is given as g, it is simply 10 power 9. Therefore, one thing you should understand is, always data is expressed in powers of 2 because we are having in bits, and bandwidth is expressed in powers of 10. The reason is, bandwidth depends on frequency, and frequency is generally measured in decimal, and data is measured in bits, and bits are generally in powers of 2. That is why here data is always in powers of 2 and bandwidth is always in powers of 10. So transmission delay is nothing but the time taken to send a packet, not sending, the time taken to put a packet onto the outgoing link, right? And now once the packet is here, then the packet has to be delivered to the other side, right? Which means the last bit has to reach the other side. That is called propagation delay. Now we shall see what is propagation delay. Say there is a sender and there is a receiver. Okay. Now sender wants to send a packet to receiver. We have already seen that when the data packet is with the sender, the time taken by the sender to put the data packet onto the outgoing link, this time is called transmission delay TT, right? And whenever you transmit the packet, it doesn't mean that the packet is received by the destination. The packet is still here, and I know first bit has traveled to some distance, but the last bit is still here. Now when can you say that the packet is completely received by destination is when the last bit of the packet has moved to the destination, which means this one bit, the final bit, the last bit, has to physically cross the entire link, right? That it has to physically make a journey from one end of the wire to the other end. So this time is called propagation delay. Therefore, propagation delay is time taken by the signal or one bit to reach from one end of the link to other end of the link is called propagation delay. What are the factors that this propagation delay depend on is, one is distance. If the distance of the link is too much, then obviously the propagation delay is going to be very high. And second thing is velocity, right? If the speed of the signal is very high, then it could reach the other end fast. Therefore, propagation delay TP is generally distance divided by velocity. And most of the fibers right now are optical fibers. Inside the optical fibers, signal travels with the velocity of light, and generally the velocity of light is 3 into 10 power 8. So V, the velocity of light is 3 into 10 power 8. In case of optical fibers, it doesn't travel with this much speed, it travels with 70% of this speed, which means 0.7. Therefore, velocity of the signal inside the optical fiber is 2.1 into 10 to the power 8 meters per second. This is the velocity of the light inside the optical fiber. So propagation delay is distance divided by velocity, and velocity in case of optical fibers is 2 into 10 power 8 meters per second, and these parameters will be given to you in the exam. You need not by heart what is the velocity, that will be given. In case if they don't give it, you assume that it is 2 into 10 power 8 meters per second. Okay. Now Tp equal to d by V. Let's solve one question here. Let us say the distance d is 2.1 kilometers and the velocity is V is 2.1 into 10 to the power 8 meters per second. Then what is propagation delay Tp? The propagation delay Tp is distance by velocity. What is distance? 2.1 into 2.1 kilometers, which is nothing but 2.1 into 10 to the power 3 meters divided by 2.1 into 10 to the power 8 meters per second. The reason why I converted both of them into kilometers to meters is so that I can apply the formula easily, right? So both of them have to be in the same units. Now it is nothing but 10 to the power minus 5 seconds, right? So generally answer, you got the answer as 10 to the power minus 5 seconds. So generally answer will be either in milliseconds or microseconds. So how to convert this 10 to the power minus 5 into either milliseconds or microseconds is, if you think about milliseconds is nothing but 10 to the power minus 3, right? So if you don't know how to convert it, just for the sake of just some shortcut, I'm just saying it. Most of you must be knowing it still. So if you want to convert this 10 power minus 5 into milliseconds, you know that there has to be 10 to the power minus 3, and if you don't know whether to multiply or divide it or how to take it, just do both, which means 10 power 5 into 10 power minus 3 divided by 10 power minus 3. Now you combine these two so that this one will be millisecond. So if I combine these two, it is going to be 10 to the power minus 2 milliseconds, right? If you want to convert it into microseconds, if the answer is 10 to the power minus 5 seconds, and if you want to convert it into microseconds is 10 to the power minus 6. So again you can do the same thing, 10 to the power minus 5 into 10 to the power minus 6 divided by 10 to the power minus 6. Now you combine these two. If you combine these two, I think you will get it as 10 microseconds. Minus 6 is microseconds, right? So either the answer is 10 to the power minus 2 milliseconds or 10 microseconds. Answer will be either in milliseconds or microseconds, right? Therefore, if a packet has to be received by the destination, there are two times involved. One time is transmission delay, where you are going to put the packet onto the outgoing link. That depends on length of the packet as well as the bandwidth. I mean size of the packet and bandwidth, which means here the Tt equal to L by B. And then once you place the packet onto the outgoing link, the last bit in the packet has to physically travel from one end of the wire to the other end of the wire. For that time, it is going to be propagation delay, and the propagation delay formula is d by v. Okay. So now the total time taken for us to send a packet from source to destination is Tt plus Tp. Okay. So one thing you have to observe is, you have to remember is, the size of the packet will be in powers of 2. In case if the size of the packet is k, it is 2 power 10, and the bandwidth is in powers of 10, because the bandwidth is generally measured in terms of frequencies. Therefore it is base 10, and here distance and velocity, you have to convert both of them into same units, like meters and meters per second, or kilometers and kilometers per second, right? Now let us say the packet is now received by the destination, the receiver. Once the packet is received by the destination, the packet will not be processed by the destination immediately. The reason is, your packet is going to go and sit in something called as queue, right? So there will be a buffer in which all the packets that you have sent to the destination are going to go and sit, and whenever the receiver has time, the processing time, then it is going to take the packets one by one from the queue. So the amount of time any packet sit in the buffer and wait before being processed is called queuing delay. Queuing delay. And you know about this other part, the transmission delay and propagation delay. We have the formulas to evaluate it, but then in order to find out the queuing delay, what is the exact formula? We don't have any formula for this. Therefore, in general, we are not going to calculate the queuing delay. And the next thing is, the packet will be taken by the receiver and then it will be processed. That is called processing delay. And again, processing delay also doesn't have any formula. That depends on the speed of the processor. See, queuing delay and processing delay, both of them depend on the speed of the processor that the receiver is having. If the speed of the processor is very high, then the queuing delay will be less and even processing delay will be less, right? So there are the various delays. So one delay is transmission delay, and other delay is propagation delay, and the other delay is queuing delay, and the other delay is processing delay. And for these two terms we have the formula, and for these two we don't have the formula. Therefore, in most of the numericals we consider these two terms as 0. That is the only reason. So since we don't have any exact formula to represent these two, we are going to consider them as zeros, right? So we shall see some problems on this. Let's see flow control methods. Flow control means if there is a sender and a receiver, sender will keep on sending the packets and the receiver will be receiving it. But the problem is, sometimes the receiver's processor could be slow, that even if you are sending data, the receiver will not be able to consume the data at the rate at which the sender is producing it. Then what happens is, let us say this is the buffer available at the receiver. Then you are going to send packet number 1, packet number 2, packet number 3, packet number 4. All the packets are being sent. Now the buffer is completely full. Now if you send one more packet, packet number 5, there is no place for it to accommodate it, therefore it will be discarded. 6 will be discarded, 7 will be discarded, which means you should not send the packets at such a high rate that the receiver is not able to handle them. You should only send the packets at a rate that the receiver could receive them, right? Which means you should always send the packets in such a way that receiver will be able to receive them and process them, right? So flow control methods allow us so in such a way that sender will always follow the receiver. It is also called as closed loop protocol, which means sender will send the packets only if the receiver is in a position to receive it. So simplest flow control method is, the simplest one is this. You send packet number 1 and now packet number 1 will be received, and once the packet number 1 is consumed, then let it ask for the packet number 2. Let it say that yes, I received the packet number 1, and then you send the packet number 2. Then you will send the packet number 2. It will receive the packet number 2 and will say that I have received the packet number 2, and only then you send the packet number 3, which means what should sender do is, it should send one packet and then stop and wait until the receiver says that I am done, you can send the next packet. This is called stop and wait. So stop and wait is the simplest flow control mechanism in which sender will send one packet and then stops and waits for the receiver to acknowledge, then only it will send the second packet. So what are the advantages and disadvantages of stop and wait is, it is very simple to implement. And what is the disadvantages, I will show you using a timeline diagram. So I am going to use this diagram throughout. This is the timeline. Okay, this is the sender at the sender side and at the receiver side. Let us assume that time is going to start at 0 and the time is going to increase down the lane. Okay, and now say you have started transmitting the packet, sender has started transmitting packet at this time and it transmitted the data till this point. This is nothing but TT, transmission time or transmission delay. Now whenever you start transmitting the first byte, after some time the packet will be received by the first byte will be received by the destination and the last byte will be received by the destination, right? This entire time is again TT only, but if you take this time is nothing but the time taken by the last bit to reach from one end of the wire to other end of the wire. It is nothing but TP. Okay, zoom in, and now after the packet has been received by the destination, now the destination is going to wait for some time, which is called queuing delay. There will be queuing delay and processing delay, but then for the sake of simplicity we are not taking it. Maybe even if you take it, it is going to be 0, right? So let's say there is something called as queuing delay, TQ, and then there is something called as processing delay, T process. Okay, and after that what the receiver will do is, receiver will consume the data and the consumption is over. Then the receiver will start transmitting the acknowledgement. Now this is nothing but transmission TT for acknowledgement. Acknowledgement will be transmitted. Now the acknowledgement will reach the other side, and again this delay is nothing but TP. Okay, so if you look at the total delay at one side or the other side, the total delay is starting from this point TT in order to transmit the data, plus TP for propagating the data, and then queuing delay and processing delay, and again one more TT. Why is this TT? This TT is for acknowledgement. TT is for acknowledgement, and then again the acknowledgement has to come from the other side to this side, therefore TP. So total time taken, if you are using stop and wait in order to send one packet, in this total time we are sending only one packet. One packet is being sent and the acknowledgement is going to be coming back to you. So this is the total cycle time taken to send one packet. If you have to send the second packet, again you have to repeat the entire procedure starting from where you left it, right? So what is happening is, the total time taken to send just one packet is, one is TT, and this TT is for data, plus TP, this is the propagation time, plus TQ, queuing delay, plus T processing delay, which means the receiver will examine who is the sender and he will appropriately prepare the acknowledgement, and then TT for acknowledgement, and then propagation delay for acknowledgement. Now in this we don't know what the queuing delay is, therefore just make it 0, and we don't know how much will be the processing delay. These are all practical values, we don't have any theoretical formula, that is why I am making them as 0, or assume that these values are 0, right? And now what are remaining? This TT and TP and TP. If you observe this TP and TP, this TP is for the data and this TP is for the acknowledgement. Now will they be same or different? Will the propagation delay be same for data and acknowledgement? It is. The propagation delay is same either if the data, it is data packet or acknowledgement. The reason is, whether it is data packet or acknowledgement, we are just simply sending one packet, isn't it? And the propagation delay depends on the last bit's time, which means one bit. Either that bit is present in the data or in the acknowledgement, propagation delay is going to be same. Therefore TP is going to be same either it is for the data or acknowledgement. So total time is nothing but transmission time for the data plus 2 into TP plus transmission time for the acknowledgement. And now in most of the cases, generally acknowledgement size will be very small compared to the data size, which means if the transmission delay for data is in seconds, then the transmission delay for acknowledgements you will get in microseconds, which means the transmission delay for acknowledgement will be very negligible. In that case, if the acknowledgement size is negligible, you can make it 0, right? So in case if the acknowledgement size is negligible, I'm trying to have it as 0. But in some cases, sometimes we use something called as piggybacking. Piggybacking means we are going to send the acknowledgement on the data packet which is coming from the other side. Therefore, then the acknowledgement transmission time will be equal to the data packet's transmission time. So in that case, where the acknowledgement transmission time is equal to data packet's transmission time, we are going to have this acknowledgement transmission time as equal to transmission time for data. But in most of the problems in computer networks, acknowledgement size is negligible. So you could either take it as 0, that depends on the question really. Now what is remaining then? Total time is TT plus 2 into TP. This is the total time taken to send one packet, right? So simply put, you can understand it this way. We are transmitting a packet. This is sender is going to send the packet, and then the packet is going to be propagated, and then this, which means the sender is going to transmit the packet and then stop at this point and wait for the acknowledgement, isn't it? The last bit of the packet is moving and then the acknowledgement is coming. This entire time is nothing but stop and wait. So you transmit the packet and then stop and wait. So because of this stopping and waiting, there is inefficiency, isn't it? I could have sent even more packets in this gap, but then I'm forcefully stopping. That is why it is all inefficiency, which means we are actually using this TT time efficiently and then we are waiting for this time completely. That is inefficiency, right? So if I want to find out the efficiency, always remember efficiency is equal to useful time in all the protocols. Efficiency is equal to useful time upon total cycle time. Total cycle time. Now what is useful time here? So useful time is TT upon, what is the total cycle time? TT plus 2 into TP. Now if you want to find out the efficiency, this is the formula that we should use. Just to simplify it, I am going to divide numerator and denominator with TT. Then what I get is 1 upon 1 plus 2 into TP by TT. Dividing numerator and denominator with TT, that equal to 1 upon 1 plus 2A, where A is TP by TT. So I am using A just for the sake of simplicity, where A is nothing but TP upon TT. So this is the formula for efficiency. Therefore, in case of stop and wait, efficiency of the stop and wait protocol is 1 upon 1 plus 2A. Now, once we have seen the efficiency, what is the throughput that we are achieving? Throughput means, generally, in case of operating system also we talk about throughput. In operating system, the throughput is number of processes that we finish per 1 second. And in case of CO, computer organization, again we talk about throughput. In CO, the throughput is number of instructions that are executed per second, right? And in case of computer networks, the throughput is nothing but number of bits that we are actually able to send per second. Therefore, throughput is equal to I'll just derive it. Throughput equal to how many bits am I able to send per second using this protocol. So if you look at this, in a total time of TT plus 2 into TP, I am able to send only one packet, right? So I am able to send L bits in a total time of TT plus 2 into TP. Sometimes throughput is also called as effective bandwidth or bandwidth utilization. So throughput has various names: effective bandwidth or bandwidth utilization or throughput. It is nothing but number of bits that we are sending per second. In a total time of TT plus 2 into TP, I am able to send L bits. Therefore, total throughput is L upon TT plus 2 into TP, right? Now, I'll just convert this, apply some conversions. I'll multiply this with bandwidth and divide it with bandwidth. Then what is it? L by B. L by B is nothing but TT, isn't it? Transmission time. So in place of L by B, I am writing TT divided by TT plus 2 into TP into bandwidth. I am writing bandwidth separately. Now you divide numerator and denominator using TT. Then what do I get? 1 upon 1 plus 2A into bandwidth. So this is nothing but efficiency, right? Therefore throughput is efficiency into bandwidth. So effective bandwidth or throughput or bandwidth utilization, it is always going to be efficiency into bandwidth. So these are the two important formulas coming to this stop and wait. One is what is the efficiency? Efficiency is 1 upon 1 plus 2A, and second is what is throughput? Throughput is efficiency into bandwidth. Therefore in order to find out the throughput or bandwidth utilization, you have to first find out the efficiency and then multiply with bandwidth. Next one is capacity of a channel. Capacity of a channel, or sometimes it is also called as a wire, or sometimes it is also called as a link. Okay, so whatever it is, I mean to say the capacity of the transmission medium. So if you consider it like this, a link or channel or wire, now how many bits can this link hold? So before going to that, I want to tell you about two types of channels: full duplex and half duplex. So full duplex means, in the previous example I have shown you that it is stop and wait. So we are sending data in one side and other side is sending the acknowledgement. Therefore you are not going to send the data when the acknowledgement is being transmitted, which means either data will go in this direction or the data will come in the other direction. So there is no way that in stop and wait data is being sent in both the directions. But many of the channels are actually configured in such a way that, or actually made in such a way that, the sending and receiving can happen simultaneously without any collisions. They are called full duplex. So now consider that this link is full duplex, which means data can go in one direction and from the other direction also data can travel without any collisions. Now I want to find out the capacity of the wire or link or the channel. So how can I find it out is, so you can visualize it this way. Let us say this wire is carrying the bits and all the bits are inside it. Okay, and suddenly you take a snapshot of it and now you count the number of bits that are present inside this link at maximum. That is called capacity of the link. Again, let us say that link is operating at its maximum capacity, which means all the bits are being filled. Now you stop it and now you count the number of bits that the channel is holding. That is called the capacity of the link. So how can we find out the capacity of the link mathematically is, one thing you should observe is, if the length of the channel is high, obviously one thing is capacity is going to be high. Even in physics, capacity depends on the capacity inside depends on the length of this one, right? And then one more thing is area of cross section, right? Area here in this one, area of cross section is nothing but bandwidth and length is nothing but propagation delay. How we could get it is, let us assume that the link is having 1 bit per second, 1 bps bandwidth. It means that in every second we can put 1 bit onto the link in every second. Okay, and now after 1 second this bit will move forward, isn't it? So after 1 second this bit will move forward and we shall put the next bit. After 1 second this bit will move forward and we shall put the next bit. So on, the first bit will keep on moving forward direction and every 1 second 1 bit will be added, right? Therefore the number of bits that can be present in this channel depends on how many seconds you have for the first bit to come out of the link. Again, understand this, if the bandwidth is 1 bit per second, it means that every second I can put 1 bit onto the channel, right? And every 1 second that 1 bit will move somewhat forward. I don't know how much distance, it will move forward and the second bit will be placed. Therefore the number of bits that can be placed in this channel depends on how many seconds we have in this channel, and the number of seconds in this channel depends on nothing but what is the propagation delay of the channel. If the propagation delay is 10 seconds, it means that by the time first bit comes out of the link, I can put 10 bits there, right? Therefore, the capacity of a channel depends on two things. One is bandwidth and other is propagation delay, TP, right? So the capacity is bandwidth into propagation delay. How did we get it is, maybe you can think of it this way. Let us say capacity of the channel is, bandwidth of the channel is 1 Mbps, which means in 1 second I can put 1 million bits. So I am putting 1 million bits in 1 second. Let us say these are all 1 million bits, and after 1 second these 1 million bits will move forward, and I can put the second copy of 1 million bits, and after 1 second these 1 million bits will move forward and the second million bits will move forward, and I can put the third copy of 1 million bits, right? Similarly, I can keep on adding the 1 million bits at every second. So by the time the first copy of 1 million bits comes out of the link, which is equal to the propagation delay, I can put those many 1 million bits. Therefore, depending on the propagation delay, we can multiply 1 million bits into propagation delay to find out the capacity of this link, provided that we are counting this link as half duplex. In case if it is full duplex, we can push the data from both the sides, which means from this side we are going to get some bits and from this side we are going to get some bits. Therefore, in case of full duplex, capacity is equal to 2 into bandwidth into TP. In case of half duplex, capacity is equal to bandwidth into propagation delay. Now what is the problem with stop and wait is, even though we know we have this capacity as bandwidth into propagation delay, we are not going to use the entire capacity of the link. The reason is, if you take stop and wait is operating as only one packet per time, which means we will send one packet at any time, and when the packet is being transmitted and when it is moving in the channel, we are not going to fill the channel with other packets. For some time packet will be here, 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 right? So in this time I am not able to send more packets, right? So even though the capacity of the link is this much, I'm just using only one packet. So stop and wait is actually having a disadvantage in case when the channel capacity is very high and we are not able to use it. So if the channel capacity is very high, generally that is called thick channels, or sometimes they are also called as thick pipes, right? You can consider thick pipes. Thick pipes means if the bandwidth into delay product is high, then they are called thick pipes. In case of thick pipes, our channel is able to carry lots of data, but then we are sending only one packet, right? So in case of thick pipes, stop and wait is having a disadvantage. In case of thin pipes means our channel is not having very huge capacity, and in that case stop and wait can be used. So efficiency of stop and wait is less in coming to thick pipes, and efficiency of stop and wait is more coming to thin pipes. Even if you find out, if you want to do this efficiency, you can see efficiency like this. Efficiency of stop and wait is 1 upon 1 plus 2a, and a is nothing but 2 into TP by TT, and TT is nothing but L by B, which means 1 upon 1 plus 2 into TP divided by L into B. Now check this factor, 2 into TP into B. This entire factor is actually capacity of the link, isn't it? If the capacity of the link is very high, then the efficiency of stop and wait is very less, isn't it? Why? 2 into TP into B, if this factor is very high, then efficiency is going to fall down. Therefore, for thick pipes, our efficiency is going to be very less in case of stop and wait. Let's see how we could improve this. We can improve this by using a method called pipelining. I'll show you with an example. Let's see about pipelining now. So the main reason for the inefficiency of stop and wait is this. In a time of TT, in one transmission time, in TT seconds, we could transmit one packet. Okay, there is nothing news in this. So in TT seconds, I could transmit one packet, and in 1 second, I could transmit 1 upon TT packets, isn't it? Try to follow this. In one transmission delay, I could transmit one packet, which means in this time I could put one packet onto the outgoing link, right? Whatever the protocol is. And therefore in 1 second, I am just dividing both the sides with TT. In 1 second, I could transmit these many times. Now if you remember, in stop and wait, what is the total time that we are spending in order to send one packet? In order to send one packet, first we are transmitting the packet and then waiting for the packet to go to the other side and then the acknowledgement coming back, which means the transmission time plus 2 into TP time. This is the total time we are spending in order to send just one packet, isn't it? Therefore in this time, if I actually transmit as many packets as possible, how many packets I could send? That is my question. Which means in a time of TT plus 2 into TP, how many packets I could send? In 1 second, if I could send these many packets, then in these many seconds, I could actually send TT plus 2 into TP divided by TT packets, isn't it? So what is this? This is 1 plus 2A packets, where A is TP upon TT, right? So in the total time, in the total time that we are spending in stop and wait to send one packet, I could have sent 1 plus 2A packets. But then in stop and wait, we are transmitting only one packet, isn't it? I could have transmitted these many packets in this time, but I am transmitting only one packet in stop and wait. That is the efficiency was, I could have transmitted 1 plus 2A packets, but I am transmitting only one packet. That is why the efficiency is 1 upon 1 plus 2A. Now if you want to increase the efficiency of stop and wait, it is clear that you transmit more number of packets during this time. So how could I make this efficiency 100%? If I transmit 1 plus 2A packets in the time taken to transmit 1 plus 2A packets, which means if the numerator is also going to be 1 plus 2A, then the efficiency is going to be 100%, isn't it? So in order to solve this question, or in order to increase the efficiency of stop and wait, you have to increase the number of packets sent, which means don't send, see this. In stop and wait, what we are doing is we are transmitting one packet and then we are waiting for the acknowledgement of the first packet to come back, right? And this entire time we are not doing anything, completely nothing. We are just simply waiting. So in order to increase the efficiency, you even use up this complete time, right? So if you can transmit the packets even during this time, if you could fill the pipe completely with packets even during this time, then the efficiency can be increased. There is no waiting time, right? So what is efficiency here? Total transmission, useful time upon total time. So useful time is going to be equal to total time. So which means we are going to use the complete time. Then the efficiency is going to be 100%, isn't it? So in this case, we are not actually sending one packet and waiting for the acknowledgement. We are sending a window of many packets, that is called a window. So when we send more than one packet, that is generally called a window. We are sending a window of packets and we are waiting for the acknowledgement of the first packet. Once we get the acknowledgement of the first packet, then the window will slide and take the next packet. I'll take an example and explain you how the windowing or how the pipelining is going to be implemented now. Let us say in a stop and wait protocol, or between a sender and receiver, the transmission delay is 1 millisecond and the propagation delay is 1.5 millisecond, which means there is a sender and there is a channel and there is a receiver. Now if the sender has to transmit a packet onto the outgoing link here, the time taken for this is 1 millisecond, okay? And now for the last bit to go there and reach the other side, any one bit, it is going to be 1.5 millisecond, okay? So that is what is given in that is what is the input given. Now if I apply stop and wait protocol, what will be the efficiency? It is clear that if I apply stop and wait protocol, it is going to be 1 upon 1 plus 2a. So 1 upon 1 plus 2 into a is tp by tt, which is 1.5. So which is nothing but 1 upon 4, right? So that is the efficiency if I use stop and wait. Now if I have to increase the efficiency, let's see what we could do. Let us assume that this is the timeline diagram, this is at the sender side and this is at the receiver side. Okay, the timeline diagram which you know already. And now it is given that transmission delay is 1 millisecond. So let us say this is 1 millisecond, and after transmitting, the first bit has to go there and again the acknowledgement has to come back. For this total time, the total time taken is 2 into TP, which is also sometimes called as round trip time. Remember that round trip time is twice the propagation delay. So in the exam they will even give you round trip time sometimes. Okay, so this entire round trip time is going to be 3 milliseconds. Why? Because propagation delay is 1.5 millisecond, therefore round trip time is going to be 3 milliseconds. Now observe this. We are able to send one packet, and in stop and wait, after sending one packet, we are waiting for the acknowledgement before sending the second packet. How much time are we waiting? 3 seconds. So what is the total time? 1 second plus 3 seconds, 1 millisecond plus 3 millisecond. Total time is 4 millisecond, out of which we are transmitting only one packet. That is why the efficiency is 1 upon 4. Total time is 4 millisecond, out of which we are transmitting only for 1 millisecond. Therefore, efficiency is 1 upon 4. If you have to increase the efficiency, it is pretty clear that instead of waiting for these 3 milliseconds, you use this these 3 milliseconds also. How could I use these 3 milliseconds? Is transmit data in these 3 milliseconds. So in these 3 milliseconds, I could transmit 3 more packets. 3 more packets, and the timing will be so perfect that by the time, in this question the timing is so perfect that by the time acknowledgement for the first packet comes back, you have transmitted the fourth packet, right? So let us say this is packet number 0, packet number 1, packet number 2, packet number 3. Now by the time you are sending the fourth packet, packet number 3, you are getting back the acknowledgement of 0. So how long should I save the packet number 0 is till I get back the acknowledgement of packet number 0, isn't it? So till this point I should save packet number 0. The reason is, if the packet number 0 is lost on the way, I might have to retransmit. Therefore in the window is nothing but the buffer. In the sender side, in a buffer, I have to save packet number 0. For how long? Till I get back the acknowledgement. But in the meanwhile, I am even sending packet number 1, right? So I have to save packet number 1 too, right? And I am sending packet number 2 also, so save it. Packet number 3 also, so save it. So the minimum window size at the sender side is, at least it should contain 0, 1, 2, 3. The reason is, these are the maximum outstanding packets. These are the unacknowledged packets, right? Now what happens is, at this point we received the acknowledgement of 0. Therefore you will be sure that 0 is successfully delivered at the receiver, and you need not wait for the, once the 0 is delivered, you need not actually save it in your buffer, so you can discard it. So you can discard packet number 0, and in the buffer you can make space for packet number 4, which means at this point you can send packet number 4, and the timing will be so exactly set in such a way that by the time you send packet number 4, you will get back the acknowledgement for packet number 1. By the time you send packet number 4, you will get back the acknowledgement for packet number 1. So what does it mean? It means that packet number 1 is safe at the receiver side. Therefore at this point you could actually let packet number 1 go and make the space for packet number 5. So which means currently the outstanding packets are 2, 3, 4, 5, right? Which means at this point we are transmitting packet number 5. And now by the time you transmit packet number 5, you will get back the acknowledgement for packet number 2, isn't it? Therefore you could actually let packet number 2 go, and in the window you could have packet number 6, which means you could start transmitting packet number 6. So if you see the way the window is moving, it is actually sliding. Initially it contains 0, 1, 2, 3, and again it's slided, and now it contains 1, 2, 3, 4, again it's slided, and now it contains 3, 4, 5, 6. Now it will slide, right? So whenever at any point, see this, let us say our next packets are 7, 8, 9. Now at any point in this diagram, first of all you should note that this is also called as sliding window protocol. The reason is window is sliding, and second thing is window is nothing but the buffer which is used to hold the packets. Why should we hold the packet? Because in case if there is any error in the packet on the other side, or if the packet is lost, I might have to retransmit it. That is why I have to hold it at least for the time till I get the acknowledgement. Once I get the acknowledgement, I can free it up, and the acknowledgements are coming one by one, which means the window will be freed one by one. So whenever a packet could be removed from the window, I could put the next packet in the window. Therefore it is called sliding window protocol, because it is simply sliding. Now I want you to observe some few points here. What are the packets that are present in the window now? Inside the window, the packets present are 3, 4, 5, 6, isn't it? And what are the packets that are present to the right of the window? To the right of the window, packets present are 0, 1, 2. What are the packets present to the left of the window? To the left of the window, the packets present are 7, 8, 9. What can you say about the status of these packets? Now the packets which are present to the right of the window are already transmitted and they are acknowledged, and the packets which are present inside the window are just being transmitted, but they are not yet acknowledged. That is why we are still waiting for the acknowledgement. And what are the packets present to the left of the window? They are yet to be transmitted. So we know what is the maximum size of the window. Why should we need the maximum size of the window is it is nothing but the buffer that is required at the sender side. So how many packets should I be saving in my buffer before discarding those packets is that depends on how many packets you are transmitting, right? So in this example, the number of packets I am transmitting is nothing but 1 plus 2a, isn't it? In order to increase the efficiency or maximize the efficiency, I am sending 1 plus 2a packets. Therefore, in sliding window protocol, for maximum sender utilization or for maximum utilization, sender window side should be 1 plus 2a packets. Okay. So now my next doubt is how many sequence numbers? These are all numbers, right? Packet number 0, packet number 2, 3, 4, 5, so on. I am going like this. How many sequence numbers am I using? Given the liberty, I could use sequence number till infinity, but then the problem is these sequence numbers have to be stored in the header field of the packets in a field called sequence number field. So if I am using larger sequence numbers, then the space taken up by header is going to be very high. So I want to use as minimum sequence numbers as possible to implement the sliding window protocol. So first thing is, in order to increase the efficiency, the window size has to be 1 plus 2a, and next thing is, in order to decrease the header size, the sequence number should be as less as possible. So how many sequence numbers are required in this case? For this example, we shall see now. Let's take the same example where tt equal to 1 millisecond and TP equal to 1.5 millisecond. Let's take the same example and see how many sequence numbers do I need in minimum, right? So we have seen that the total time is like this. I'm sending packet number 0, packet number 1, packet number 2, packet number 3, and after transmitting packet number 3, if the transmitting is over, I'm getting the acknowledgement for packet number 0. So that is how I set it, right? So if you see the window, inside the window I'm having 0, 1, 2, 3, right? This is the outstanding packets, because I have to save all the packets 0, 1, 2, 3 unless until they are acknowledged. Currently packet number 0 is acknowledged, which means I can remove packet number 0 and I can include next packet. what should be the sequence of next packet, sequence number of next packet, that is important. So you are sending the next packet, which is actually the fourth packet, right? I mean 0, 1, 2, 3, the number should be 4, but if you observe it, I have already sent 0 and that 0 is consumed, and now 0 is not in use. Therefore you could actually reuse 0 again. If I do that, I need not go for large number of sequence numbers, which means I could actually use packet number 0. The reason is packet number 0 is out of the window, it is already being consumed. So even if I send again 0, then the receiver will understand that this is the next 0, which means it is different from the first 0. Why? Because it has already taken it and it has consumed it. So I can reuse packet number 0 again. By the time I finish transmitting packet number 0, acknowledgement for packet number 1 will arrive, right? Which means I can send next packet. When the acknowledgement for packet number 1 has arrived, it means that 1 is already received, consumed and acknowledged, which means number 1 is available again. So when you are going to take the next packet, you need not take the packet number, new packet number. You could again reuse packet number 1, which means the next packet number could be 1. By the time you finish transmitting packet number 1, you will get the acknowledgement for packet number 2, which means you can send the next packet with the sequence number 2. Got it? So in this example, you can observe that with just 4 numbers we could complete the transmission of any number of packets. What is the advantage of using only 4 numbers is the sequence number field needs only 2 bits now. See, if I need numbers 0, 1, 2, 3, then how many bits do I need in the sequence number field? 2 bits. Why? With 2 bits I can produce all these numbers. If I am using very large number, then I need more bits in the sequence number field on the packet, which is obviously a wastage. So I want to limit the usage of sequence numbers. Therefore, in order to increase the efficiency of stop and wait by using the concept called pipelining or sliding window protocol, I'm going to conserve the usage of sequence numbers. So in a sliding window protocol, what is the maximum sender window size to get the maximum efficiency? It is 1 plus 2a. Then what is the minimum number of sequence numbers required for this transmission? It is 1 plus 2a. If it is the minimum number of sequence numbers required, then my next question is, what is the minimum number of bits? Minimum number of bits required in sequence number field. Minimum number of bits required in sequence number field to get these many numbers is log 1 plus 2a base 2. If I have these many bits in the sequence number field, I could get these many sequence numbers, right? So it is better that you have seal here. The reason is, if you get, let us say if the answer is you are getting it as 10.5 bits, which means you need at least 10.5 bits to get these many sequence numbers, then obviously 10 bits are not sufficient and you cannot give 10.5. therefore the answer is 11. So this floor is going to be applicable. Okay, so I'll take one problem and I'll explain you about this clearly. In order to increase the efficiency of stop and wait using sliding window protocol, window size is 1 plus 2a, and the minimum number of sequence numbers required if you have to send 1 plus 2a packets is 1 plus 2a. Otherwise what happens is, if your window size is 4 and if you don't have 4 sequence numbers, inside the same window you are going to repeat 2 numbers. Let us say I have only 2 sequence numbers and my sender window size is 4. Then what happens is, you are going to send 0, 1 and again 0, 1. And now at the receiver side, there is a chance that these 2 zeros will arrive at the same time, isn't it? Because while the first 0 is still alive, which means when it is being transmitted, you are sending second 0. That is why we cannot repeat the same numbers in a window, but you should at least have these many different sequence numbers, right? And then once you are sure that one sequence number is received and consumed, then only you can reproduce the same number. Like in the previous case, if you are sending 0, 1, 2, 3 and if you are sure that packet number 0 has been received and consumed, then only you can reproduce packet number 0. You are not supposed to use the same sequence number unless you are sure that it is already consumed. Therefore, you should at least have these many sequence numbers, 1 plus 2a. If you have more than this, it is fine. See, if your window size is 4 and if you have 100 sequence numbers, then it is fine, but the point is you should not have less than this. And there is no point in having more sequence numbers too. When you are sending only four packets, why do you want to have 100 sequence numbers? And next thing is, if you have to send these many sequence numbers, what should be the size or number of bits in the sequence number field? Number of bits in the sequence number field is 1 plus 2a base 2. Let's talk about access control method. Access control method. Till now we have seen the flow control, right? In general, there are two kinds of links. One is broadcast link and other is point to point link. Okay, so broadcast links means I have a common channel to which many stations are connected. Okay, this could either be wireless also. And point to point means I have a source and I have a destination, and both are connected by a single wire. So this is called point to point channel and this is called broadcast channel. Now coming to this point to point channel, there is no much difficulty here. The reason is, if this link is full duplex, means if the data can go in both the directions and at any time it can go in both the directions, then there is no problem with this. So sender can send the data and receiver can receive the data, and both of them can transmit at any time. There is no problem in this. But coming to this broadcast links, the problem is, since many stations are accessing the same channel at the same time, what will happen is, let us assume that stations are A, B, C, D, E, something like this. Now if A is transmitting the data and at the same time if E is transmitting the data, then there will be a collision, right? Which means the access to this link has to be controlled in such a way that at any time only one station has to transmit the data, or even if more stations are transmitting the data, there should be no collisions. So they are called access control methods. Access control methods means whenever I have a broadcast channel, only one station should send the data, or if more than one station is sending the data, there should be no collisions inside the channel. If you could somehow make this happen, then it is called access control methods. There are various ways access control methods have been implemented. I'll show you all the methods one by one. So coming to access control methods, I'll be discussing about access control methods which are useful in practice, practically used, and moreover I'll try to teach it in a simple manner, not complicated and not getting into too much technical details like in phase, out of phase and all this. If you are interested in learning more about access control methods, you please refer to the book Horizon. So here I am not going to get into more details. Whatever I teach here is going to be good enough for any kind of interviews or gate. So let me say, first one is TDM, time division multiplexing. So this is the simplest access control method. So assume that this is the timeline. Time is starting with 0 and it is increasing this way. Now what does this method say is, you divide the entire time into something called as slots. These are all called slots. Okay, and now you give each slot to each station in a round robin manner. Let us assume that we have a broadcast channel and 4 stations are connected to this. Station number 1, station number 2, station number 3, station number 4, right? Then what does this method say is, divide the time into slots and assign each slot to each station, which means this slot will be given to 1, second station, third station, fourth station, and again this process will continue in a round robin manner, which means again station 1, station 2, station 3, so on. Okay, and now what should be the size of each slot? That is one thing you should observe. So size of each slot should be, how much time should we give to each station is, if you give some time, that station should be able to transmit the data and then that last bit transmitted should get out of the link, right? So in worst case, this station could be present at one end of the channel, then from one end of the channel that last bit has to go out of the other end of the channel. Therefore the time taken for this is TP. So total time that should be given to each station so that they'll be able to transmit one packet, and for that packet to get out of the link is TT plus TP. Here for all these protocols I have one assumption. My assumption is that all the stations wants to send packets of same size, therefore TT is constant for all the packets. That is not a practical assumption, but in order to analyze it in a useful, in an easy way, I am assuming this. And then TP is nothing but worst case time. If the station is connected at the one end of the wire, then if the bit has to get out of that wire, then the time taken is TP. So for every station the slot time is, one is TT, time taken to transmit the packet, and then TP, time taken for the last bit to come out. So time is divided into slots and each slot is given to each one, and after station 1 accesses the, while station 1 is accessing the link, no other station will be given the access. Therefore at any time only one station will be accessing the link, and so there will be no collisions with other stations, right? And once after this one slot is over, then the station 2 will get the same slot, TT plus TP, and after station 2 is over, station 3 will get this slot, again TT plus TP. Okay, so what will be the efficiency, or how are we utilizing the link here? What is efficiency? Efficiency is always this. Efficiency is equal to cycle time. Cycle time is whatever is repeating over and again. So cycle time and useful time. In the cycle time, how much time are you able to use it? So efficiency is always useful time upon cycle time. So if you look at it in this case, time is divided into slots, and every slot is given to a station, and a station is going to use it for TT and then wait for TP. So what is the cycle here? What is repeating over and again is every cycle is repeating over and again, isn't it? This cycle is repeating again, this cycle is repeating again. Therefore cycle time, if you observe here, is TT plus TP. So cycle time is TT plus TP, and useful time is, we are transmitting one packet, which means TT. Therefore efficiency is 1 upon 1 plus A, dividing numerator and denominator with TT, where A is TP by E. Now we have seen that efficiency of TDM is 1 upon 1 plus A, where A equal to TP by TT. Okay, so let's see a problem on this. So if the question is given as, generally they will give you length of the packet and then bandwidth and distance and velocity, using which you can find out TT value and TP value. I am directly giving you that. So if TT equal to 1 millisecond and TP equal to 1 millisecond, if this is the case, and if they ask you for the efficiency of TDM, then it is nothing but 1 upon 1 plus A, so which is 1 upon 1 plus 1. So TP by TT is 1, right? Therefore it is 1 by 2, 50% efficient. Okay, and they will continue the question with this. If the bandwidth is given as 4 Mbps, then what is the effective bandwidth of throughput? So effective bandwidth is efficiency into bandwidth, so which is nothing but 50% into 4 Mbps. So it is going to be 2 Mbps, right? So effective bandwidth is going to be 2 Mbps. Now this one you understood. So effective bandwidth is this, which means even though we are having 4 Mbps, we are not going to use it at a rate of 4 Mbps. We are going to use it only at a rate of 2 Mbps. Now the next question is, if n stations are connected to the TDM network with this configuration, where TT is this, TP is this, and bandwidth is this. If n stations are connected, and if each station needs 1 kbps, or let us say 2 kbps. If n stations are connected to this network, and if each station requires 2 kbps bandwidth, then how many maximum stations can be connected to this network. Understand this, to the given configuration, if you are using a channel, now I am saying that if n stations are connected to this channel and each stations require 2 kbps bandwidth, then how many maximum number of stations can be connected to this channel? That is the question. So let us assume that there are n stations, then every station requires 2 kbps, and this should be equal to the available maximum. What is the available maximum? 2 mbps. So 2 mbps is equal to n into 2 kbps, right? Therefore you are going to get n as 1000. So you can connect a maximum of 1000 stations to this network, right? So that such questions are possible in this TDM. Now coming to TDM, we have seen that we are reserving these slots for some stations, because of which there could be disadvantages, right? So let's see about the disadvantage of TDM. So disadvantage of TDM is, we have a channel and we are dividing the entire time into slots, and we are giving away the slots to stations, right? Now the problem with this reservation method is, whenever you reserve a station, a slot for a station, the station might not use it completely. The reason is, it is not always true that every station will have some data to transmit. It might not have some data to transmit at all. Then in that case, whatever slot you have given is going to be wasted. Okay, so this problem is always there with reservation. Therefore disadvantage of TDM is reservation. Whenever a station gets a chance to transmit, which means it gets the slot, but then it doesn't have any data to send, so this entire slot is going to be wasted. So that is why we go for the next method. Let's now see the next method, where we don't reserve. This is called polling. Polling means this. So instead of directly giving some time to someone, we just ask who wants the time. Then they'll say, I want the time. Then if someone asks, then only we are going to give the time. So assume that we have the same broadcast channel and many stations are connected to this. Now in this case, we are not going to reserve any slot. What we do is, let us assume that this is the timeline. What we do is, first we conduct a method called polling, and polling is nothing but selecting someone among A, B, C, D. Let us say I have selected station A. After I choose one station, then I will give it the chance. How do I select this station is, only if the station wants to transmit the data. If the station doesn't want to transmit the data, it is never going to participate in polling. So don't worry about the polling algorithm, just worry about the time taken to polling for this polling algorithm. Discussing about the polling algorithm itself is out of the scope of this course. I don't want to discuss about it, but what I mean to say is, in order to pick some station among these, we need to apply a method called polling. So after polling, let us say A1. So for this, time taken is T poll. Okay, and after a station gets the chance, if a station is picked up by polling, then I am going to give that station the chance to transmit, which means station A will get the chance to transmit, and then that transmitted packet has to go out of the link, right? So one station, if it has to get the access to the link, it has to participate in polling, for which some time is wasted, and then it gets the chance to transmit the packet, and then it gets the chance to propagate the last bit. Now before giving the if for the next station to get the same thing, again the next station has to get again involved in polling, which means again the next station should get involved in polling, and then the next station will get the chance to transmit and then propagate. This will keep on happening, right? So what is the advantage of this method is, no slot is ever wasted. The reason is, we are giving this slot only for the required stations. And second thing is, there is a disadvantage in this method. The disadvantage is, it is not a fair sharing, which means if a station A wins in the first polling, it might win again in the second polling. So because of which some of the stations might starve. but we wanted efficiency, we want the link utilization or link efficiency to be maximum. Therefore this method is preferred in that case. So what is the efficiency of this method? So efficiency of this method is same. Always efficiency is same. So what is it? Cycle time. You have to find the cycle time and then you have to find the useful time. So now I want to find out the cycle time and then I want to find out the useful time. Then the efficiency is nothing but useful time upon cycle time. So how can I find out useful time upon cycle time is, just see the cycle here, what is repeating over and again. So if you see this process, polling, transmission, propagation, and again polling, transmission, propagation, and again polling, transmission, propagation, right? Therefore cycle is nothing but polling, transmission and propagation. Therefore cycle time is time taken for polling plus time taken for transmission plus time taken for propagation. And among this entire time, what is useful time? Useful time is time taken for transmission, right? Therefore efficiency is Tt upon T pole plus this one. So again the same kind of questions can be asked. So they will give you the time taken for polling and they will give you the time taken for transmission and propagation, and in most of the cases propagation delay will be negligible. That is why they might not give you propagation delay, they will give you transmission delay and they will give you polling time. Then the efficiency is Tt upon T pole plus Tt in case the propagation delay is negligible. In case of LANs, propagation delay is very small because the link length is very small, therefore propagation delay will generally be small. So in that case Tt upon T pole plus Tt. So anyway you can substitute the values in this and find out the efficiency, and then now they might give you the bandwidth, and again the effective bandwidth is effective bandwidth or throughput or utilization. Bandwidth utilization is again efficiency into bandwidth. It is always going to be same, right? And one more thing is, after finding out the efficiency, then effective bandwidth, then they will say that there are n stations and every station wants so and so bandwidth. Then how many stations we could connect at maximum, like the one we have previously seen. The same thing could be applied. Now what is the disadvantage of this method? The disadvantage of this method is polling, the polling time. So before actually transmitting, we should waste for some time in order to select a station. So why are we doing this? We are doing this to stop the disadvantage of TDM, which was reservation, right? So now if we even don't want to do polling, and if you want to give the chance to stations which wants to transmit the data, then we shall see the next method now. Let's talk about the errors in computer networks. So there are two kinds of errors. When you are sending a packet, basically why there will be errors is, one thing is the entire packet will be lost. So packet loss is very condition is a condition which is not very rare. It is it is possible. The reason is, only reason for the packet loss is congestion. So when you are sending, let us say there is a router, and when you are sending many packets to the router, or when many packets are being sent to the router, sometimes what happens is the entire buffer of the router gets filled and the processor is not able to process the packet so fast. Then in that case the packets will be dropped, and that is one reason why the packets will be lost. And other reason is, other reason for errors is, you will be able to receive the packet, but inside the packet either one bit or more bits will get corrupted, right? So the reason for this kind of errors is, maybe while the packet is being transmitted on the channel, there will be disturbance from in the external environment like thunderbolt or any frequency changes, because of which some part of the packet will get corrupted, right? So which means there is either a burst error means some few number of bits got corrupted, or there could be sometimes only a single bit error because of a small voltage fluctuation. So whatever it is, whenever the packet is lost, we are able to know it. There are various methods like acknowledgements, and we have seen that collision detection and all, and we could say that the packet is lost and we could ask for the retransmission. But the other case is, when the packet is received, how can you be sure that all the bits inside the packet are correct? So there is a chance that some of the bits may got might have got corrupted. Then how are we going to handle it? So this is nothing but error handling. So I'm not going to talk about packet loss. Packet loss will be handled by the protocols, other protocols we have seen till now. But then we are going to talk about the bit losses, which means whenever a bit gets corrupted, then what is that we are going to do with that that bit or a few bits. These are error handling methods. Error handling is, traditionally it has been of two types in data communications. One is error detection. Error detection means we know that some part of the data has been corrupted, and we only know that the packet is having some corrupted bits, and we don't know which part of the packet is corrupted or which bit got corrupted. See, in case if you know which bit got corrupted, you would correct it also, right? But error detection says that we only know that the packet got corrupted and we don't know where the corruption is. Okay, and the other method is error correcting methods. Error correcting methods say that we know that there is some error in the packet and we even know where the error is, which means we have the capability to self-correct the packet, right? So these are the two mechanisms. Now in case if you find out that there is a error in the packet and if you are not able to correct it, then only one solution is there. What is it? You have to ask for retransmission, right? And coming to error correction methods, in case if you find out that there is a error in the packet, and even if you can find out the location of the error, you need not ask for retransmission, you will correct the packet yourself, right? So in this case, retransmissions are required. Retransmissions means you should ask the sender to resend the packet because you came to know that there are some errors in the packet, right? Now coming to these error detection methods, one popular or one most important method is the simple one. Maybe you might have even seen this. So when you are typing when you are creating any account in Gmail or any other website, they'll ask you one thing: type the password, right? Enter the password, and again they will ask you re-enter the password. Why? The reason is, when you are typing the password for the first time, you must be having some password in your mind and you might have typed some password here because you will not be able to see it, right? It will be all in dots. Now then if there is a mismatch in the password in your mind and the password which you typed, if they directly put it in their database, then what happens is later when you try to re-enter the password and log in onto the website, you will never be able to do it because the password you remembered is different from the password which you typed. Now in order to catch it, if they again ask you to type the same password which is in your mind, there is no less probability that you might type it wrong 2 times, right? Now what happens is, let us say you have typed it wrong first time and you have typed it right next time. Then what will they ask? Are they going to take your second password as the valid password, or they are going to ask you to retype both of them? They are going to ask you to retype both of them, right? Why? Because they don't know whether the first copy is right or the second copy is right. Therefore you have to do the same again. Now the same method can be applied here. So send the data once and send the same data second time. If the first copy of data compared with second copy, if they both are different, in case if both the copies are different, then you can easily find out that one of the copy got corrupted, but then you will not know which copy, either the first copy or second copy. Then what should you do? In this case, you are detecting that there is an error and you should ask for retransmission, right? And the problem with this method is, if you have to send 1 million packets, right, you are sending 1 million plus 1 million, 2 million packets, which means the data is going to be double, the traffic is going to be double, all the devices, networking devices have to be doubled, right? But then the error condition is, out of 1 million, only one packet will generally the error condition is 1 in 1 million, which means the bits will get corrupted only in one packet if you are sending 1 million packets in practice, right? So for that 1 in 1 million packets, you are going to send 1 million packets again in order to just protect one packet. Obviously this method is not used practically. This method can be used, if you are trying to save some. In RAID techniques, you might have seen this. This is one of the levels of RAID techniques inside your computer, in computer organization, right? So next method is Parity checking. Parity checking is either you carry, you must be knowing about it well. Either you count the number of zeros or number of ones, and you try to make either number of ones as even or number of ones as odd. Now when you are sending this in this way, if there is a change in one of the bit, then the bit count, finally it will not agree, because you are trying to make it as odd or even, but then it will be a different number. So parity checking is not very powerful, but then it is in practice for a long time, and there are various versions of it. One is vertical parity checking, and other is horizontal parity checking, and there are various ways you could play with this parity checking. And then the third method is CRC, cyclic redundancy check, and fourth method is checksum. So these are the various methods, various popular methods, even though we have many more, but these are the popular ones. Coming to error correcting methods, first thing is Hamming code. So about Hamming code, I'll discuss it in algorithms course. We have Hamming codes in algorithms, and even we have a Hamming code in digital too. So I'll either discuss in algorithms or digital. But what you should understand here is, coming to this Hamming codes, if I have to send a data of 1 KB, I have to add 0.5 KB, half KB extra redundant data. That is the disadvantage, and moreover it takes lot of time to compute the computationally it is going to take a lot of time. So one disadvantage is, if I had to send 1 KB, I have to send half KB extra data, which is redundant, which means if I have to send 1 million packets, I have to send 500,000 extra packets. This is all redundant and this is all useless, isn't it? Why to send 500,000 packets if 1 million packet is going to be sufficient? So this is the disadvantage. Disadvantage is I have to send 500,000 extra packets just to find out the error in 1 million packet. Therefore, in practice, in computer networks, coming to computer networks, we are never going to use Hamming codes. So in computer networks, we are going to use, one is CRC and other is checksum. These two are most popularly used methods in computer networks, and Hamming code is rarely used. Hamming code is never used in computer networks. The reason is, one is computationally infeasible, and second is lots of amount of extra data, right? So now we shall see what CRC is and what checksum is. Okay, I'll explain CRC with an example. CRC, where first C means cyclic, and R means redundancy. C means check. Okay, so why is it called cyclic redundancy check is, first of all, we are going to use something called as cyclic codes. So since we are going to use cyclic codes, it is called cyclic. What are cyclic codes? I'll discuss it in digital because it requires a lot of number system analysis. And next one is redundancy. Redundancy means we are going to have the actual data to which I am going to add some redundant amount of bits. That is why it is called redundancy. And last, check. So check means the receiver is going to check whatever you have sent. That is why it is called cyclic redundancy check, right? Cyclic means it is cyclic code. Redundancy means we are going to add extra bits, and finally receiver is going to check whatever you have sent. Therefore, it is called cyclic redundancy check. I'll take an example and I'll show you. Let us assume that there is a sender and there is a receiver. Okay, this is happening at the sender side, and there is a receiver. Sender has to send some data to receiver, and the data is 101111, something like this, simple data. In practice, no, we have KBs and MBs of data, but for this example, just keep it simple. Assume that this is the data, which means 7 bits of data is there, and both as sender and receiver will know a common number called as CRC generator. So assume that CRC generator is 4 bits, and this is the CRC generator. CRC generator 1101. Then what will sender and receiver do is, at the sender side, it will compute the CRC using this CRC generator. Now if the CRC generator is 4 bits, understand this, if the CRC generator is 4 bits, we are going to add 3 zeros at the end, which means we are going to append 3 zeros. Why? If CRC generator is 4 bits. In case if the CRC generator is 5 bits, we add 4 zeros. In case if the CRC generator is n bits, we are going to add n minus 1 zeros, right? And this is 3 bits is the CRC we are going to get. Now we are going to apply exclusive ORing. So before going to this, I'll just discuss about exclusive OR, represented by this symbol called exclusive OR. So exclusive OR is also called as modulo 2 sum. So what is modulo 2 sum is, you add the numbers and divide it with 2 and find out the remainder. That is called modulo 2 sum. If I have 1 and if I want to find out 1 exclusive OR 1, then the result is add both of them and divide it with 2 and take the remainder. If I add 1 plus 1, I get a result of 2. And what is the remainder of 2 when divided with 2? It is 0. 1 exclusive OR 0. Then it is 1. 0 exclusive OR 1. Then it is 1. 0 exclusive OR 0. It is 0, right? Why? You just add them and take the remainder after dividing with 2. So if I have 1 1 1, if I apply exclusive OR, what will be the output? 1 1 1 is nothing but 3, and 3 when divided with 2 is, remainder is 1. 1 0 1, if we add 1 0 1, what is the output? 1 plus 1 is 2, and 2 when divided with 2 is, remainder is 0. And 1 0 0, what is the output? 1. Why? Because sum is 1 and remainder is 1. Alright, so now I am going to use this exclusive OR in order to find out the CRC. So CRC generator is 1101 and the input is this. Now I want to find out the CRC. So how we could do it is 1101. I'm applying the exclusive OR. If I apply 1 and 1 exclusive OR, it is going to be 0, and this one 1. 1 1 0 1 1 1 is 0. Okay, and you write the remaining number 0 1 1 0 0 0 0 1 1 1 2 3, right? Always start again from the leading number, leading one. So leading one is this, right? So start again applying the exclusive OR from this point using the CRC generator, which means 1 1 0 1. Then what do I get? 1 exclusive OR 1 is 0, 1 exclusive OR 1 is 0, 0 0 is 0, 0 1 is 1, and this is 1 1 0 0 0. Then again you apply it from the leading one. Leading one is here, 1 1 0 1. Then what do we get? 1 exclusive OR 1 is 0, 1 exclusive OR 1 is 0, 1 1 is 1 0 is 1, 1 0 is 1, and then 0 0. 1 1 0 1. Again one more time, right? So it is 0 0 0 1, right? Now if you try to apply from the leading one, you will not be able to apply it, therefore you have to stop here. See, when should you stop is from the leading one. If you count the number of bits, there should be at least 4 bits. If you have anything less than that, you have to stop the procedure. From the leading one, there is only 1 bit, therefore you have to stop it. After stopping it, the least significant 3 bits is going to be CRC. Why only 3 bits? Because CRC generator is 4 bits. So if CRC generator is 4 bits, CRC is always 3 bits. If CRC generator is n bits, then CRC is n minus 1 bits. So in this case, since the CRC generator is 4 bits, CRC is 3 bits. So these 3 zeros which you have appended are going to be replaced with 001, and this will be the CRC along with the data that will be transmitted, which means the data that will be transmitted to the receiver side is actual data, which is 1011011. Along with it, 3 bits are appended. So what are the 3 appended bits? 001. 001. So this part is CRC, and this part is actual data that is being transmitted. Now what will receiver do is, receiver will check if the data that is transmitted is right or wrong, which means if there are any errors or it is fine. So for that it is going to use the same method. 1011 is the CRC generator. See, remember, CRC generator is well known to both sender and receiver. It is not used for cryptography, therefore you need not keep it secret. It is actually known to both the parties, and both the parties will apply it to find the CRC. Now again it is going to be applied. 1101. What do we get? 0 1 1 0, and write the remaining bits. 0 1 1 0 0 1 1 1 0 1. So what is it? 0 0 0 1 1 1 0 0 1, right? And again write from the leading bit. So leading bit is this, leading one is this from here, 1 1 0 1. Then what do you get? 0 0 1 1 0 1, again from the leading, 1 1 0 1. Then what do you get? 0 0 0 0, right? So if the data with the CRC is right, which means if there is no error in the data, then the CRC you get will be zeros. If you get all zeros as CRC, then the receiver will be sure that there is no error in the data. Let us assume that you are sending the data and there is some error in the data. Then what happens? So let us say this is the entire data that has to be transmitted, and because of some error, some bit got corrupted. So say this bit, the third bit, instead of 0 1, it got corrupted to 1, which means the receiver got a error corrupted packet, and the packet is 1 0 0 1 0 1 1 0 1. So we got a mistake here, right? So this bit got corrupted. This is supposed to be 1, but now it changed to 0. Then what happens because of this? What is the problem because of this? See it. CRC generator is 1101. Then I am applying CRC again. This is all happening at the receiver side. 1101. So if you exclude your 1 and 1, it is going to be 0 1 0 0. Okay, I am simply applying the exclusive only. Write down the remaining bits, 0 1 1 0 1, and again start from the leading one. Leading one is here, 1 1 0 1. Okay, now apply exclusive again, which means 0 1 0 1 1 1 0 0 1. Again start from the leading one, 1 1 0 1. Then what is it? 0 1 1 0 1 0 0 1 1 1 0 1. Then what is it? 0 0 0 0 0 0 1, right? Now you have to stop it here, because from the leading one the number of bits are not 4, there is only 1 bit. Therefore the CRC we got is 3, which means the final answer we got is not zeros. So you should not call it a CRC, but I know I'm just saying that. So the remainder is not 0, therefore we can say that something went wrong in the question. But then the problem is we don't know what went wrong. Okay, so CRC will be able to detect the error, but it will not be able to correct the error. The main responsibility of computer networks is to enable two processes which are in the same computer. So actually two processes will generally be in same computer and they want to communicate. In that case, we have a concept called as inter-process communication by operating systems, isn't it? If client and server are present in the same host, they can communicate directly with a concept called as inter-process communication. And the entire purpose of computer networks is both the process will be present in different hosts, and now they want to communicate with each other. And so we want to provide the hardware and software to these two processes in such a way that they will feel as if they are actually in the same host, which means they should think as if they are communicating with a process which are present in the same host, even though they are present in the others, right? So the entire purpose of the hardware and software is to see that the message will go from client to the server as if the message goes from client to the server in the same host, and the reply should come back from the server to the client as if it comes back from server to client in the same host. Then if this is the case, then what are the responsibilities that everything put together should provide? Everything means the software as well as hardware put together. What are the responsibilities or functionalities they should provide to this client and server? So let's see what are the functionalities required. So in order to have communication possible between two processes which are present in two different hosts, which are present in two different locations, we have various functionalities. So what are the various functions needed is, there are two types of functions or two classes of functions. So some functions are mandatory. Mandatory means they should be provided to every process independent of what they are doing, right? And some functionalities are optional. Optional means you need not provide them to everyone. In case if they are needed, the process has to take care of it, which means we are not going to provide in the general purpose software and hardware some of the functions. So depending on that, we are going to divide it into two parts. One is called mandatory. Mandatory means these functionalities have to be provided to every function or every process, right? And other functions are called optional. Optional means not every function, not every process will need these optional functions. Only the process which need these functions will be providing to them. So let's see the mandatory functions. So one is error control. Error control is definitely mandatory. Why? Because when you send a message, we should be sure that the message is not garbled in the on the transmission. And then flow control is mandatory. We cannot overflow the buffers at the receiver, right? And access control is mandatory. In case of broadcast channel or multi-access link, no two stations, only two stations should be able to send and receive messages, not more than that, right? Therefore access control is mandatory. And if you write like this, there are many functionalities: multiplexing and demultiplexing. So multiplexing and demultiplexing is we shall see it at transport layer. So which is nothing but taking a message and giving, which means in our computer there are going to be many processes, and when a message comes, it has to be sent to only one of them, right? And a message goes, we have to collect them from all the processes and send it through one channel. So one to many and many to one functionalities have to be provided, right? And there are various addresses used. So addressing. So if I keep on writing like this, there are many functionalities which have to be definitely provided, which are all mandatory. And coming to the optional functionalities, there are some functionalities which are generally optional. So one such functionality is encryption. Not every encryption and decryption, right? Not every application needs encryption and decryption. If you are watching a general purpose HTTP, general purpose web servers or web pages, you don't need every web page to be encoded, right? Encrypted. And checkpointing. Checkpointing means when you are downloading some files, we want to maintain some checkpoints. If the file is too small, then the checkpointing is not required. In many of the cases, files are not too big that we want to transfer. Therefore, only the applications which are dealing with very big files have to take care of this. We are not going to provide them as a general purpose functionality. They are specific functionalities which have to be implemented by the actual servers, right? And routing. Routing is also optional. So why is routing optional is, even if we don't have routing tables, we could use a concept called as flooding, which means at a router, even if we don't know which way to send a packet, we could use a concept called as flooding. So flooding is taking an incoming packet and sending it on all the outgoing packets is called flooding. So routing decides which way to send. If I don't know which way to send, I could use flooding and I could send it to all the ways. Therefore routing is also optional. It is not mandatory. So if you require routing, we'll provide it, right? It is a surprising thing, right? So in computer networks, routing is an optional functionality. Why? The reason is, even without having the routing, you could still be able to communicate the message using flooding. So if I go on writing like this, there are many functionalities which are optional. So there are some functionalities which have to be definitely provided by hardware and software of the computer networks, and there are some functionalities which are not very important for every process, right? So if I write all these functions, there are nearly 70 such functions. I could write all of them. I'm not going to write anyway, but if I write all the functions, there are nearly 70 such functions. And now when we have these many functions to be implemented, these are the requirements, right? Then we should think about how to implement them. So there are various reference models which talk about how to classify these functions and where to implement them, or what are the functionalities which are closely related and what are the functionalities which are not related closely. So depending on all these functionalities and their groupings, there are several reference models, and one such reference model is, one important reference model is ISO-OSI. So they are going to say about what are the various functionalities at each layer. They are going to divide all the functionalities into various groups, and they say that each group is assigned to one layer, and now implementing a layer is nothing but implementing those functionalities. And the next important one is TCP/IP, and the next important one is ATM. So there are various models, X.25, right, IEEE mainly deals about LAN technologies, nonetheless, so on. These are all called reference models. So in these all reference models, in our syllabus we have ISO-OSI and TCP/IP. So I'll be discussing about ISO-OSI and TCP/IP in detail. Okay. Yes, now we shall discuss the most popular topic in computer networks. I think you must be knowing about it. ISO-OSI, International Standards Organization Open System Interconnect, right? ISO-OSI model is been proposed as a standard in which what they are saying is, when you have these many functions to implement, it is better to put all the functions which are closely related into one group, so that it will be easy for you to implement them, and it will be easy for us to communicate with the other layers also. Let's see all the layers, and then we shall discuss about the functionalities implemented at each layer. So one is physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. Count them: 1, 2, 3, 4, 5, 6, 7. 7 layers are proposed by ISO-OSI. And why this layering system is proposed is, it is nothing but divide and conquer. If we have 70 functions to implement, we are dividing them into 10 each, I mean roughly into some numbers, and then we are implementing the closed functions together. It is also one advantage of layering is divide and conquer is possible, which means we are dividing a very big problem into many small problems and then implementing them and then conquering them in small problems. And second thing is, encapsulation is possible. Encapsulation means what? If we have some closely related functions, we are going to implement them at one place, and all the variables and functions required to implement these are all protected in one layer. You need not, they will not be scattered all over. Therefore, when you change a variable or a function in one layer, it doesn't affect the other functions, right? And abstraction is possible. Abstraction means at data link layer, you need not worry how the network layer is implemented. So without worrying about how it is implemented, you can know what it is implementing, which means abstraction is nothing but we are not shown the details. They'll just show us what are there, which means they'll just say that this functionality is implemented in network layer. If you want to use this functionality, call this function, and what is there inside this function, you don't know, right? Which means that is called abstraction. Even in Java, you have something called as API, right? What is API? We'll be given the programming interface, which means some functions without telling what is there inside the function. So for example, if you write printf, right, do you really know, or have you ever seen how printf is implemented internally? No, we don't care about it. What we care is, we want the printf function, and what we don't care is how it is implemented. That is called abstraction. Now abstraction is also possible with this, right? And then it is also possible for testing is also made easy, which means you could actually test every layer independently without worrying about what is there in the other layer. So if the entire software is in one layer, the problem is how could you go and test every layer, a small functionality. In order to test a small functionality, that might be having a rippling effect in the entire layer. So limiting every functionality to one layer, testing every functionality is easy, right? So these are all the advantages of layering. Now let's see the main important points about layers, then we shall get into details about each layer. So first one is, the important point about physical layer is it is only about hardware. So physical layer deals only with hardware. There is no software of any kind. And data link layer contains both hardware as well as software, which means data link layer deals with the hardware directly as well as it contains some software as well. And network layer is very complex. The reason why network layer is complex is it is going to implement the complex algorithms, which are routing algorithms. Routing algorithms are the most complex algorithms known in computer networks. And transport layer is a thick layer. The functionalities are not complex, but the total number of functionalities are very large, which means complex. If you look at the entire code, the number of lines which are written at transport layer are generally very high compared to any other layer, and moreover every host is going to contain transport layer, and all the hosts need not contain the network layer all the functionalities. Like routing will be generally be present on the routers, not on the end hosts, but transport layer is generally present on all the hosts. And then session layer. So session layer, presentation layer, application layer, these are mainly proposed for user interactiveness or for the user's convenience. So they doesn't have anything much to do with the entire network. They are actually provided for the user advantage, which means they will make many things easy for the user, right? So this is all about all the 7 layers. How to remember these 7 layers is, one way is, in one of the books, I don't remember which book, it is given that please do not touch Steve's pet alligator. Please do not touch Steve's pet alligator. You can use that one. Or while I was teaching in one of the classes in North India, one of the students told me that you could even remember it in the other way. Please do not touch Sachin's Patni Anjali. So maybe Sachin's wife could be Anjali. So that is also one way to remember it. Anyways, I think this is the most popular concept, and you know how to remember it, and I think you already did it in your exams, right? BTech exams. So few other things which I want to share before going into this is, don't focus on data link layer and physical layer. You need not read about it much. This is mainly important for electrical students and communication students mainly. For communication students, there is a concept called as data communication, where they are going to look into physical layer, the transistors, resistors, all those stuff, and we need not worry about it. And data link layer, we have something called as encoding, and in encoding, in phase, out of phase, wave formats, frequency, everything is there. We need not worry about it. So don't focus on physical layer and data link layer much, which means don't read these 2 layers in any of these books. Just stick to whatever I teach you in these video courses, and focus more on network layer and transport layer. I am going to teach almost everything which is required for network layer and transport layer, everything required in the videos. I'll make them self-sufficient for Git. In case if you are interested in going into this computer networks, if you are interested in going into computer networks as a researcher, or if you are already doing a project in your masters, or if you want to get into Cisco or anything, if you want to have a career planned in computer networks, then yes, you can read about network layer and transport layer in any book. Every book is good for that, but no book is really complete for Git. Whatever I am going to do in the class, that is going to be self-sufficient. But for extra information, it is always better that you could read, if you could read, right? And the textbook I suggest is Tannenbaum and Forozon. One is Tannenbaum, Computer Networks by Tannenbaum, which is also good for these 2 layers, and other is Forozon. You can follow any of them, or there is no need to follow anything if you are focused only about Git, okay? And application layer, there is too much to read about it. Application layer, generally the HTTP, FTP, SMTP, everything, and that is not, that entire information will not be useful for Git. So whatever is required for Git, I'll again teach it in the class. In case if you want to learn more about this application layer protocols, the best source is Wikipedia, or there are lots of tutorials available online. You need not actually go to a textbook and read. And anyway, if there is any concept and if you want in-depth information, and if you are not willing to concentrate on any, or if you want more than what is being there taught in the textbooks, the best resource is RFC. Google out about RFC. Request for comments. Request for comments is the best place where you can find out everything about every concept that is being taught in computer networks. I follow RFCs, and you too, if you could get a chance, if you want to learn more, you can refer to this. For Gate, let's keep it simple and you just watch my videos. For Gate, only my videos are enough. Okay. Yes. Now let's talk about this physical layer first. Physical layer, right? So physical layer deals with electrical, mechanical, functional and procedural characteristics. Electrical, mechanical, functional and procedural characteristics of physical links. So see, this is all theoretical concept. So what you could do is, whenever I'm saying some points, you better pause the video and write it down. So what is that I'm saying? Physical layer is electrical, mechanical, functional and procedural characteristics of physical links. So what is the real meaning of all these points is, it is going to talk about how the physical links are, and then if the physical link is of so and so type, how to convert the signal. Which means, if the physical link is copper, if you are going to send the messages over copper wires, obviously the messages have to be converted into electrical signals. And if the message is of optical fibers, right? I mean, if the link is optical fiber, then the signals are converted into light. If it is wireless means in wireless communications we generally use electromagnetic waves, right? So depending on what is the type of link it is, the signals are converted into appropriate ways, like electrical or light or mechanical. And then it is going to deal with functional properties. Functional properties means what are the types of transmissions, which means there are various types of transmission modes. So you might have heard about simplex transmission, right? So there will be a sender and there will be a receiver, and simplex means only one way is possible. For example, simplex, you could think of it like this: you have a television at home, and maybe these days you don't have an antenna. I think yes, you are having this Tata dish or something, but that is full duplex. Previously what used to happen is, they used to have a television at home and they used to have an antenna at the terrace, and from antenna signal used to come to television only in one direction. That is called simplex. So either your wires could be simplex or half duplex. Half duplex means a sender will be there and a receiver will be there, and the sender can send the message to receiver, as well as receiver can also send the message to sender, which means it is inappropriate to call them sender and receiver, because both are going to send the messages, but you cannot send at the same time, which means when in one direction data is going on, the other side they should hold, and when other side the data is coming on, the other side they should hold. So the best example, this is called half duplex, right? So the best example for half duplex is, you might have heard about this walkie-talkies. You might have seen with the policemen, they will be having some device, a phone kind of device, and they'll speak something and say over, and the other side will say something and say over. Over means, see, from my side I send the data, I am not going to speak, and the other side will going to send the data. That is called half duplex. Previously also we used to have computer links in which we can send data only in one direction, not in both the directions. And right now we have full duplex links. Full duplex links means anyone can send data and they can send at the same time, which means both the sender and receiver can send the data at the same time. It is called full duplex, right? So depending on the type of transmission mode you are using, our physical layer is going to hold the data. If it is simplex, only one side it will send it. If it is half duplex, if the data is not coming from other side, then only it is supposed to send it. If it is full duplex, then we are going to send it anytime. And here also we are going to see many other properties, we shall see them later, right? So for now, understand that physical layer is going to deal with all of this, right? And as of now, by default, every link is full duplex. So in gate questions, we are not going to see anything about simplex or half duplex. Assume that everything is full duplex. Whenever any question is given, if nothing is given about the link, it is by default full duplex. And then physical layer also deals with topologies. So topologies means you must have seen many topologies, and communication in every topology is different, right? So one topology possible is bus. Physical layer also deals with topologies. So topologies means how are you going to connect various computers, right? So one topology possible is bus. Bus means we are going to connect all these stations like this. And another topology possible is star. To a central hub we are going to connect these stations, right? And other topology possible is ring, right? And there are various other topologies possible. There is also a combination of them. Combination means you can have a hybrid. To bus you can connect star. It is called as tree or hybrid, like this, isn't it? So there are various topologies. Even mesh is there. Mesh means this. So if you look at them, the most commonly used previously was bus and now it is star. And ring, hybrid and all the others, yes, they are used but then not that frequently. Previously they used to use the bus and currently they moved on to star. Okay, so this is all about the physical layer. And other important property of physical layer is it is also going to deal with something called as encoding. Encoding means given ones and zeros in bits, how are you going to convert them to waves and send them? That is called encoding. So encoding is also used. Encoding is dealt at physical layer, right? So what is encoding is, if we have a signal like this, 1010 is the bits, what is the bit pattern or what is the waveform you are going to generate for 1, for 0, for 1, 10, for 0, like that, right? And in our syllabus we have two popular representations. One is Manchester encoding and other is differential Manchester encoding. In Manchester encoding, we are going to have 1 and 0. 1 is represented with this Z and 0 is represented like this. Okay, so if I have a signal like this, 1 0 1 0, then 1 is represented like this and 0 is represented as inverse Z, and 1 is represented as Z and 0 is represented as inverse Z, right? So Manchester encoding says that 1 is Z and 0 is inverse Z, therefore that signal representation looks like that, the waveform, right? And differential Manchester is also there. Differential Manchester. In our syllabus we have only these two encodings, so don't focus more on all these encodings. The reason is they are not very important for gate, but only things which will be important is they might ask you such question. Given a wave, how does it look like in Manchester representation given these bits, or how does they look like in differential Manchester encoding? In differential Manchester encoding we have this one, we have a wave like this or a wave like this. Both of them are going to represent 0, and a wave like this or a wave like this, both of them are representing 1. What is the main difference between 0 and 1 in differential Manchester is, in 0 this starts with a edge. So when you start with a edge, that is 0, and when there is no edge, that is 1. So edge is 0, no edge is 1. That is the main difference between Manchester and differential Manchester. In differential Manchester we have two representations for 0, and in Manchester we have, differential Manchester we have two representations for 1. Here we have unique representations, right? And now if you look at this, how to differentiate between 0 and 1 is, 0 is always going to start with a edge and 1 is not going to start with a edge, right? So if I have 1 0 1 0, how do you represent it using differential Manchester is, 1 is going to be represented like this, and 1 is, if you have used this, See, for 1, either I could go with this or go with this, right? And for 0, I could go with this or go with this. But once I have chosen this one for 1, I have no other choice. I have to go with this. Why? For 0, I should get a edge. Therefore, edge is possible only if I go like this, isn't it? And for 1, no edge. No edge means there has to be no edge. Therefore, only representation possible is this. And for 0, there has to be an edge, right? So how can I put an edge? If I go with this, I cannot go with an edge. If I go with this, edge is possible. Therefore, like this. Or one other way is, if you have taken, instead of this one for 1, if you have taken this one for 1, then how does it look like? So this is 1, no edge. And now for 0, there has to be edge. So from this point, if I have to get a 0, if I have to get a edge, then only possibility is this one, isn't it? Then only possibility is this one. And now for 1, there has to be no edge. No edge means only possibility is this one. If I go with this one, I have to drop down and there will be an edge. If I go with the first one, there will be no edge, right? And for 0, there has to be no edge. And for 0, sorry, there has to be edge, which means you are going to go with this one, the first one. So this is how it is represented. Maybe I'll take one more example and explain you how to represent zeros and ones. Let us say I have 1 1 0 0. I want to see how does this Manchester differential Manchester work. So for 1, either you could go with this one or this one, anything is fine, and depending on which one you choose, we are going to get two types of waves. So let's say I am going with this first one. First one means for 1 I am going to go with this. And what about 1? If there is no edge in the beginning, that is 1. Yes, this is 1, and again there is a 1, so there should be no edge. So I cannot go with the same representation for the second one, because that will lead to edge. So there should be no edge. Therefore I have to go with the second representation of 1, which means like this. See this? In the beginning there is no edge. In the beginning there is no edge. Therefore it is 1. And what about 0? 0 should have a edge. So look at this. Which one should I pick? First one or second one? The second one will have no edge. Therefore I am going to go with this one, no edge. Sorry, edge. So for 1 there is a, for 0 there is a edge, right? And again there is a 0, and I need an edge. So which one should I go for? First one or second one? If I go for this with the first one, I cannot generate that one, right? See, only one which will have a edge in the beginning from where I left is the second one. Therefore, like this, there is a edge. So no edge, no edge, it is ones, edge, edge, it is zeros. So 1 1 0 0 is represented like this. So one more representation is, instead of starting with this one, you could have started with the other one, which means even this is also representation of 1 with no edge, isn't it? Then again I should not have any edge. Now only representation for 1 is this one, right? And now again I have to represent a 0. So there is no edge here, there is no edge here, therefore they are ones, and for 0 there has to be edge. So what is the only possibility that I could get a edge? I think this one, isn't it? So there is an edge. This one is an edge, right? And what about the next 0? Again there has to be edge. So only option is this one. So again there is an edge, right? So no edge means 1 1, edge edge means 0 0. No edge means 1 1, edge edge means 0 0, right? So that is how we could represent Manchester encoding and differential Manchester encoding, right? And one important point about this encoding techniques is, you should remember that either in Manchester or differential Manchester, this is a formula, you could remember it this way: baud rate equal to 2 into bit rate. Baud rate equal to 2 into bit rate. How to remember this formula is, baud is a letter with, baud is a word with 4 letters and bit is a word with 3 letters. Therefore 4 letters is equal to 2 into 3 letters. So remember this. Maybe that is, you do something and remember that formula, baud rate equal to 2 into bit rate. Whatever, sometimes I'll tell you to by heart something, so you just do something and by heart it, whatever memory mapping techniques you use. What I used is 4 letters equal to 2 into 3 letters. So what is baud is, what do we actually mean by baud is the number of voltages which are changing per second, or the number of voltages that are sent per second. So if you look at this Manchester or differential Manchester, in order to send one bit, I am sending two voltages. Here also, in order to send one bit, I am sending two voltages, high voltage and low voltage in any order, isn't it? Therefore, in order to send one bit, I am sending two voltages. See, I'm telling you in a way in which computer students can understand. The same topic will be explained in electrical using in phase, out of phase, waves and all frequencies. But for us, I'm just trying to keep it as simple as possible. Okay, so try to remember it like this. One bit, in order to send it, we are going to send two voltages, isn't it? So if I send 10 bits, then how many voltages I should send? 20 voltages I should send. If I am sending 10 bits per second, then how many voltages are sent? 20 voltages per second. Therefore, this is the baud rate. Baud rate is nothing but 2 into bit rate. Bit rate is number of bits per second and baud rate is number of voltages per second. So, both in Manchester and differential Manchester, baud rate is equal to 2 into bit rate, right? So, we have seen everything about physical layer. So, what are all the responsibilities of physical layer? First thing is it is going to deal with transmission modes, isn't it? And then it is going to deal with topologies, right? And then it is going to deal with encoding, right? So like that, it is going to deal everything which is related to the physical wires. Now let's move on to the data link layer. Let's now look at network layer. It is also called as layer 3. Network layer in the ISO-OSI hierarchy, it is layer 3. So first layer is physical layer, second layer is data link layer and third layer is network layer. And what are the main responsibilities of network layer are? One is host to host connectivity. Host to host connectivity. So what does this mean? So mainly data link layer operates in one network, and when we have to connect many networks, the actual layer which is very helpful is network layer. So data link layer is limited only to be used in one network. If you want to connect many networks, it is network layer, right? And host to host connectivity means, now later also I'll again take an example and I tell you. Host to host connectivity means this. See, there are two hosts and there are two processes in host. They want to connect, they want to communicate. It is called process to process or end to end. Transport layer will take care of it. And host to host means network layer is mainly responsible for taking a message from one host and delivering it at the other host. And transport layer is entirely responsible for everything from end to end, right? And then data link layer is hop to hop between one host and the next host. One hop is data link layer. So data link layer is hop to hop connectivity, transport layer is end to end connectivity, and network layer is host to host connectivity. Okay, just remember that. So these are the various layers: transport layer, network layer and data link layer, and these are the various responsibilities of these layers, right? So network layer falls in host to host. How is it going to do it? We shall see it now, right? And the next responsibility is logical addressing. Logical addressing means in TCP/IP, IP addresses, or logical address is generally any number which is valid throughout the world. Let us say there are many networks like this in the world, and now internet is what? Collection of all the networks. And what is logical address? Logical address is taking a message and giving it to any host in any of the networks. Physical address is useful only within one network, but logical address is useful in the entire internet, which means if you are operating in one LAN, data link layer is enough and physical address is going to take care. But if you want to send a message from one network to the other network, then we need to identify the host uniquely. Physical address is not going to be enough. Why? Physical address is constant only within your network. If you want to send a message outside your network, logical address is useful or logical address is required. Third one is switching. So switching is nothing but connecting various networks together. So using a switch, we are going to connect various networks like this. Without the concept of switching, if you have to connect all the computers together in the internet, If you have 1 million computers, and if you don't have the concept of switching, if you connect all of them like this, it is completely going to be a mess, isn't it? Therefore, using switches, the organization is simplified. So switching is nothing but how are we going to connect all these stations and how are we going to send the packets, right? So switching is nothing but, see this, now taking the packet from one network and then deciding in which network I want to send it. If it is connected to many networks, in which network I want to send it. The decision is nothing but switching, right? And the other responsibility is routing. So routing is, we have these switches are called routers. Now at the routers, in order to make this decision, right, taking a packet and then deciding which way to send, in order to make this decision correctly, we need something called as routing tables, right? And routing tables are built using a procedure called routing. So routing is nothing but building the routing table, and then using the routing table is nothing but switching, right? Building it is routing, and then using the routing tables is switching, right? So many people get confused between these two. Routing is nothing but the process used to build the routing table. Switching is nothing but when a packet comes in using some method, either by routing tables or some other method, if you decide where to put the packet, that is called switching, okay? Or taking a packet and putting it in the outgoing link is also called as switching. And next thing is congestion control. So congestion control means we generally get lots of packets that our buffers completely get full and we cannot do anything about it. We have to discard the packets. Then there are various congestion control methods generally used, and at network layer we have various methods, but in syllabus we have IP, and IP is not doing congestion control. Therefore, we are not going to talk about congestion at network layer. The reason is we don't have ATM networks where they do congestion at network layer, but we have only IP. At IP we are not going to do congestion control. Therefore, I am not going to talk about congestion control at network layer, but we have congestion control at TCP. At transport layer, again we shall talk about it, okay? And next one is fragmentation. Fragmentation is something like this. So we might have, you have seen that in a, let us say on one side I am having token ring, and token ring is connected to a Ethernet, okay? And I told you that the maximum, I mean, even though I am connecting the stations like this, you can think of it as a token ring, just a token ring network, and this is a Ethernet network, right? And in order to connect two LANs, right, which are of different topologies and different technologies, they have to interoperate with one another. So in Ethernet, I told you that the maximum frame size in standard Ethernet should not exceed 1500 bytes. This is the maximum amount of data that a frame can hold. And what about the maximum amount of data that a token ring, a station can send in token ring? That depends on token holding time. So depending on token holding time, we get a very big data. Let us assume data size is greater than 1500 bytes. And now if that data frame has to be sent to the other side, definitely it cannot go in one whole packet, that has to be divided. That is called fragmentation, right? That is called fragmentation. So these are all the responsibilities of network layer. Now we shall see all the responsibilities one by one, okay? First let's see what is switching, and then routing and fragmentation. I'll show you where about them at IP layer. We are not going to talk about congestion control, and logical address is nothing but IP addresses. We shall see it at IP. When I am talking about the IP, that internet protocol, I'll talk about this host to host connectivity and logical addressing, routing and fragmentation. For now, just see what switching is. Let's see transport layer now. The main responsibilities of transport layer are like this. end-to-end connectivity. So what is end-to-end means, generally the many process will be present in a host, and they will try to communicate with some other process which is present in some other host, and these process may be present in different networks also. If you remember it, I discussed it in the first class. And a process here wants to communicate with a process here. It is called end-to-end connectivity, right? So who takes care of it? Transport layer. And host to host is taken care by network layer. And hop to hop means from your host to the closest router, and from router to router, and again from router to router, and from router to host. It is all called hop to hop, which means one jump. So one jump is taken care by data link layer. I'll take an example and I'll explain it later with a special topic called explanation about all the layers. I'll tell you about it in a special topic, but for now just focus on end-to-end. End-to-end means how message goes from one process to the other process. It is called ends of communication. So generally the method that is being used is using port numbers, which are also called as service point addressing. Service point addressing, SPA, service point addressing. Okay. And about service point addressing, these port numbers, I'll discuss about it in detail at TCP with a special heading called TCP. In that video, I'm going to discuss about this service point addressing in detail. And now, the next responsibility is flow control. So what is flow control is, you already know that the way you control the sender from sending more than what a receiver can receive. And the most popular flow control method which is used at transport layer. So why transport layer is special is, transport layer is mainly from end to end. Therefore, for end to end, if you remember it, I discussed during the discussion of flow control. You go back to that video and watch it. The protocol is SR. SR is the protocol for that. And error control. So error control means we have various error control strategies. One of the error control strategy that we have seen is CRC, and the other one is checksum. I told you that CRC is used at hardware level and checksum is used at software level. Therefore, transport layer is mainly software. So here checksum is used. Next one is segmentation. Segmentation means, if you look at the placement of transport layer will be here, and below the transport layer there will be network layer, data link layer and physical layer, and above the transport layer there will be session layer, presentation layer, and application layer. These three layers are generally user oriented, and these three layers are generally network oriented, and transport layer is going to be a intermediate, or what can I say, mediator between these two. So the main responsibility of transport layer is taking a message from application and then seeing that it passes through the network and reaches the other side. So transport layer is a kind of mediator between these two. Now what is segmentation is, from application, from this part I may get data of any size from application, and now transport layer has to take the data of any size. Sometimes the data will be very big, and now it should divide into small segments and then send these segments over the network. That is called segmentation. And next responsibility is multiplexing and demultiplexing. So what is multiplexing and demultiplexing? In a host, at application layer there can be many processes. Now all these processes want to communicate, and they will all, they will be sending the messages at any time, and all of them will be going through the same channel. Therefore transport layer should take all the messages coming from various applications and send it through the same channel, right? It is called many to one. And on the other side, the messages will come and they have to be distributed to all the processes, right? Therefore it is many to one and it is one to many. So that is done by transport layer. And the next responsibility is congestion control. So congestion control means, okay, I'll discuss about this congestion control in detail at TCP. There we have congestion control algorithm. I'll tell you what congestion control at transport layer means. That is there in the syllabus, very important. I'll discuss it there. So this is already done, flow control you know about it, and this one I'll discuss it about it in TCP. And now error control you know about it. This checksum, error control is checksum, and we have already seen it. And segmentation, I'll again discuss the segmentation in detail in the topic called IP. At IP, when I'm discussing about it, I'll just go to TCP and I'll explain about the segmentation there. And then multiplexing and demultiplexing, again this one I'll discuss it about it in TCP. Congestion control also TCP. So these are all the general properties, right? So that is all about transport layer. Maybe you must be wondering about something. There is already network layer, and which is actually taking a message from a host and then sending it to the other host, and from there the application can pick up, right? So why do we need transport layer once already network layer is available? I'll just explain you that with an example. Let us assume that you are here in some city and it is a long distance relationship and your girlfriend is somewhere here. Okay, and say you are here and your girlfriend is here, long distance, and let us say it is her birthday and you want to send her some gifts. What gifts do you want to send her? Assume that you want to send her one chocolate. Chocolate is too cheap, right? Okay, but anyways, let us say you cannot afford, so Dairy Milk Silk you are sending it. And then maybe you want to send, generally girls love teddy bears, right? So let us say you are sending a teddy bear. It doesn't look like teddy bear, right? I mean, close. This is the best I could come up with. I have been trying it for a long time and this is what I came up with. And then you would like to send a rose flower. It is very difficult. So let's say my rose flower will be like this, kind of sunflower, right? And then one more thing, let us say you want to even send a love letter. Fine, it is not love letter, some letter which contains your lovely words and all, and here you have written everything that you want. Tenu mai love karda, bemadlab karda, baho mein aaja soniye, all this, right? And yours lovingly, so and so. Okay. And now you want to send this love letter and all these gifts to your girlfriend, and what you expect is you are going to give this all to the postal department and you want the postman to deliver all of them there, right? Courier or postman. And now what you want her to do is you want her to first pick up the letter, read it, and then pick up the flower and then keep it in her flower vase, and then take the this teddy bear, hug it, and then finally eat the chocolate. This is the order in which you want her to treat each gift. That is the order you wanted. But the problem is when you give all of them at once to the postman is going to deliver it in any order. It is going to get you may not expect, she may not receive it in order. So when all of them are delivered, in order guarantee is not possible, which means there is no guarantee that all of them are going to be delivered in the order in which you are sending it, right? And sometimes what happens is, let us say you are sending a flower here. By the time the flower reaches there, the petals all will be dropped down and only the stick will go. Let us say the petals, all of them are dropped down and only one petal is remaining, only the stick is there, right? And let us say the chocolate, your postman ate a part of it, so chocolate also only a part, half of it has been received, and he will say that I got only half, right? Therefore the data, when it is going on, it could get corrupted, isn't it? And sometimes he might take away this teddy bear completely. He will take it home and he will say that no, teddy bear is not at all given, sent. Then one of this is going to completely miss out. So how are you going to save yourself from all these problems? How? You think about it. So if it is a practical scenario in which you are there, then what you should do is, and I'll tell you even the worst case. Worst case, what could happen is, maybe she might go out somewhere, birthday party, and at home papa, her dad is there. That is even the worst case, isn't it? Now what happens, you are sending a gift and at home her dad is there and she is not there and all the gifts are for her. Now what he will do is, he will take the letter and he will read it. And what did you write in this letter? Tinnu main love karda, bematlab karda, baho mein aaja, everything, right? Therefore what is he going to do? He is definitely going to trash it, discard it, right? And what about the flower? Trash it. And what about the teddy bear? Sell it. And what about the dairy milk? Eat it. So she is not going to receive any of this in worst case. Therefore what should you do before sending the gifts? Before sending the gifts, you should definitely call her, isn't it? Yes. So if you plan a surprise, that will be a shock for you. So let us say she is at home and her dad is away. Then you call her and say that, see Janu, I am sending all the messages, and you please take the letter first, read it, then take the flower and take this and this. After receiving it, you even acknowledge me, even call me back and tell me that, see, I got everything and I am very happy about it. Okay, so that is what you want to do. So transport layer is exactly going to do that. So transport layer is like telephone service. Now transport layer is similar to telephone service, and network layer generally is similar to postal service. So in TCP/IP, IP uses datagram service, which means there is no reliability and there are no guarantees. Therefore this network layer, at network layer IP, it is unreliable. So if you want the reliability at transport layer, then it is your responsibility to implement it. So transport layer, if you want reliability, then you are going to apply TCP here, and you are going to apply IP, which is unreliable but fast. So what is the main difference between this? It is unreliable and it is datagram service. In general we have TCP/IP. So it is not always true that network layer is unreliable. At network layer, if you use virtual circuits, which is not in the syllabus, if you use virtual circuits, it is going to be reliable and there is no need of transport layer at all. In case if at network layer you are using a connectionless protocol like this IP, and then you want reliability at the application layer, then you go for TCP. That is the main difference between, that is why we need a transport layer. Got it? So we shall see. I'll take a very big example later, and then I'll explain you, putting all these layers together, what is the main purpose of each layer. For now, this is the main responsibilities of transport layer. Let's now look at the next layer, session layer. So session layer is the next layer in the hierarchy after the transport layer. So what is the main response? What are the main response of session layer is? One is authentication and authorization. So generally you see somewhere like username and password. So passwords and usernames, everything will be dealt by session layer. That is the first thing. Authentication and authorization, right? So using digital signatures and all, which is not in the scope of the syllabus, but then we shall discuss it later in the cryptography, right? And next one is something called as checkpointing. So where is this checkpointing going to be useful is, maybe you might have seen like torrents. When you are downloading some movie, what happens is you might lose the internet connection, but then you don't want to go back to the beginning of the movie and again start downloading it. If you are downloading a file, then what happens is it is going to maintain some checkpoints. Let us say after every 10 minutes it is going to have a checkpoint. So if you lose your internet connection anywhere here, then you are not going to start from the beginning, you will be starting from here. That is called checkpointing, right? And next one is synchronization. Synchronization is sometimes video and audio both will come in different files, and now both have to be synced appropriately, otherwise that lip sync will be missing, right? So that is where synchronization is going to be useful. And next one is dialogue control. So dialogue control means, generally in web conferences, what happens is there will be a speaker and there will be various participants, right? And anyone can speak up anytime. but then we should see that only one person is going to speak, and he is going to be the speaker at any time. It is a kind of flow control. Just like how we did flow control, here also some kind of flow control has to be applied. The reason is many people are going to participate in the web conference, right? And everyone, if they all speak at the same time, it is going to be very messy. So what we want to do is, we would like to control some people from speaking, and we like to control the give the access to only one person. So that is where we are going to use this. So what is the main concept is, these links are full duplex, which means at the same time you can receive the messages as well as send the messages. But then we don't want to receive the messages, we just want to send the messages, right? So even though the link is full duplex, we want to use it as half duplex. That is called as dialog control. So all these are the responsibilities of session layer. Along with this, there is one more responsibility called as logical grouping. Logical grouping of operations. Logical grouping means, generally in databases we have a concept called as atomicity. So whenever you send many commands to the database server, all the commands have to be executed or none of them have to be executed. That is called atomicity. We shall discuss this topic in databases, but anyway, session layer is going to collect all the operations and put them together and give all the operations at once to the server, so that it will not it will not do a part of the transactions and it will leave out the other part. So because of this logical grouping, we can ensure that everything that has to be done in a atomic operation will be done. So that is done by the logical grouping. These are all the responsibilities of session layer. So anyway, at practice, all the applications doesn't require this all these facilities, right? Therefore, it is not the responsibility of the computer network software in order to provide all these facilities or functionalities. Then what we did is, if an application needs all these facilities, then we are leaving this to the application, so that application will take care of it. Which means if an application requires all this, it will implement it. We are not going to provide it as a part of the computer network software, which means operating system is not going to provide it. All the other layers are actually provided by the operating system. Now it is the responsibility of the application designer to provide all these applications if it needs it. Not all applications needs it, right? Okay, that is all about session layer. Let's look at the layer, presentation layer. So presentation layer has mainly three responsibilities. One is character translation. So character translation means, in one computer you might have this ASCII code, and in the other computer you might have EBCDIC code. Then if both these computers are going to communicate with each other, both of them have to either follow ASCII code or both of them have to either follow EBCDIC code. So this layer is going to translate the messages appropriately. So if one host is having ASCII in it and other host is having EBCDIC, and if they both want to communicate, then the message is going to go through presentation layer, and presentation layer is going to take care of it, the translation part. And second thing is encryption, decryption. So you know what is encryption and decryption. Again, we are going to discuss it in some other topic with where we are going to see encryption. Encryption means we are going to take the message and then encrypt the message into ciphertext and send the ciphertext to the other side. Other side will take the ciphertext and decrypt and read it. It is used for security, which means when you are sending data, if it has to be, if it should not be seen by anyone or interpreted by anyone, then we are going to use encryption and decryption. And the third one is compression. So if you want to compress the data and then expand the data, compression and expression means that one, zip, right? So if you are going to zip the data or unzip the data, then this is the layer which is going to provide you the functionalities. Again, just like session layer, this layer doesn't have this layer is not required by every application. Therefore, it is not good that operating system implements it. So operating system doesn't implement it. It is the responsibility of the application which needs them to actually have implementing this. Therefore, application layer is going to implement both the presentation as well as session layer. because these are the functionalities which are not required by all the applications. So it is not common, therefore operating system will generally implement something which is commonly required by everyone, right? And next one is, okay, this is all about the presentation layer. In GATE 2014 they are given a question, and before solving this question I assume that you have already watched that video how all the layers work. So I'll just solve this question. It is based on how the layers work. It is really a beautiful question. It is asked in GATE 2014. So what they are saying is, it seems that there are 4 stations. Q is a host, and Q is connected to a router R1. Q is connected to a router R1, and R1 is connected to a router R2, and R2 is connected to router R3, and then R3 is connected to H. Now they are saying that H is a HTTP server, and from Q we are getting a file from this H, and now they are saying that we are even using encryption. So let's see what are all the layers that should be present at the host. All the layers, right? So physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and application layer. I have shown you how all the layers work together without using presentation layer and session layer. In case if you include them, the diagram looks like this. And what will be present at the routers? At the routers it will be physical layer, data link layer, and network layer, right? They are saying that at session layer encryption is used. Normally encryption is used at presentation layer, but anyways, coming to this question, it doesn't make any difference either presentation layer does the encryption or the session layer, but the concept is presentation layer is supposed to do it. By mistake they are giving it as session layer. So anyway, let's now look at what happens here. A message is going to start from here. Message will start from here and it will be given to presentation layer, and session layer is actually encoding the message, encrypting the message. So whenever this encryption is used, the plain text will be converted to ciphertext, which means the message will not be visible anymore. Message will be ciphertext. Let us say it is ciphertext C. And now this will be given to this transport layer. Transport layer is going to add port numbers. Let us say source port number is X and destination port number is 80, HTTP, right? And network layer is going to add IP addresses CX80, and let us say IP addresses added is IP address of Q and IP address of H, that is being added network layer. Now at data link layer it is going to add the MAC addresses, right? So MAC addresses are going to be the same packet. MAC address are going to be, one is MAC address of this Q, that is the source MAC address Q, and the destination MAC address is, since the destination is in the other network, we are going to send the packet to R1. Therefore destination MAC address is MR1, right? And now this one will be given to physical layer. Physical layer is going to send it on the link, right? That is how the question is. And now this packet will go through all the routers and finally it will be received by the destination. Destination will have all the layers like this: physical layer, data link layer, network layer, transport layer, and then session layer, presentation layer, and application layer. So it is difficult to put everything in the board in this diagram, but then if you have seen that question how all the layers work, that video, it is very easy to answer this one. So what they are asking is, at router R2 what are the things which will be visible to an intruder, which means if someone looks into the packet which is arrived at router R2, what could he see? So see this, now at what changes on the way is, I told you that nothing will change till this part. Only thing that keeps on changing as the packet goes hop to hop is the MAC addresses. Therefore in this network the MAC addresses MQ and MR1 is used, and by the time the packet goes from R1 to R2, at R2 this entire part will be same. Only thing that will be changing is the packet's MAC address, right? The frame's MAC address. Frame's MAC address will be changed from initially it was MQ, and the destination MAC address was MR1. Now the new source is MR1 and the new destination is MR2. Therefore, by the time the packet reaches R2, the MAC addresses will be changed, and the changed MAC addresses will be MR1 is the source MAC address and the destination MAC address is MR2, right? So just understand this. By the time the frame reaches R2, these all values will be there. Initially it starts with the message. Message is nothing but the URL of the file that has to be downloaded. So let us assume that is the first message, which is get some URL, right? And now that message is given to this like this, and when this packet is going on at R2, the frame will look like this. Therefore, what will the intruder find out? Intruder will not find out what is the MAC address of Q or what is the MAC address of H, because on the frame only thing that will be visible is MAC address of R1 and MAC address of R2. And second thing is the intruder can find out what is the IP address of the source and what is the IP address of the destination. Why? IQ and IH, they will never change on the packet. The reason is, if you change these IP addresses, the packet will never reach the destination, or the destination will never know who the sender is. Therefore, these two doesn't change. And what about these port numbers? Yes, he will be even be able to find out the port numbers, right? They too doesn't change. What about the message? Message is already encrypted, therefore he will not be able to see the message. So when he looks at this, he will not be able to see the URL which is coming from application layer, but then he will be able to see the port numbers and the IP addresses, but he will not be able to see the source MAC address and destination MAC address. Instead, he will see the MAC addresses of R1 and R2. If you want to understand this very clearly, please refer to that video and then solve it. It's a very simple but beautiful question. Okay, so that is all about the layers, how they work, and this question is an illustration of this, right? Now let's talk about Ethernet. So Ethernet is one of the LAN technologies. LAN technologies means how are you going to connect stations in one LAN? LAN is a local area network. So if you have an office or a college or corporate building, generally if you want to connect all these stations, that is called LAN. And the most popular technology used in 1980s, since 1980s, 1970s, people use this Ethernet. Ethernet was the popular and the sustaining technology. Recently, even now Ethernet is being used. Even though many concepts have been changed, it is used. So now I am going to talk about standard Ethernet, which was proposed in IEEE. So if you look at the IEEE documents, IEEE 802.3 is a document which has standardized this. So if you look at IEEE 802.3, you are going to see all of this. I mean everything about Ethernet. And one thing is, whatever I am going to discuss now is actually used in 1980s and 1990s. Since the late 1990s and in 2000s, everything has changed. So whatever I am going to discuss here is actually in 1980s and early 1990s, right? So keep in mind that whatever is now I am going to teach, it is not actually used in practice now. So later I will tell you about what is being used at practice now. First, let's now focus on GATE, which is about 802.3 standard. So first thing is the topology. The topology used by Ethernet is bus. So previously it was bus, now they moved on to switch. So the standard topology was bus, which means they will connect many stations to same broadcast channel, right? Now what is the problem with this bus topology when they connect these many stations to same thing is, obviously you know there has to be some access control, and the access control method used in Ethernet is CSMA-CD. And Ethernet uses no acknowledgements. So acknowledgements are not implemented in Ethernet. So if you look at the Ethernet packet, there is no facility provided by Ethernet packet in order to send a acknowledgement. If the data has to, which means if the application needs acknowledgement, then the application has to implement it, which means inside the frame format of Ethernet, you will not see anything called as acknowledgement field. It is not supported. But if the underlying application which uses Ethernet, if it wants the acknowledgement, it should send the acknowledgement as if it is data. If you want, you can implement it, but Ethernet has not given us any facilities for that, right? And no acknowledgements are there, and obviously we are going to have CSMA-CD to protect us if in case of any collisions. And now next one is data rates. Data rates means bandwidth. So bandwidth initially was 10 Mbps, and then the technology improved and 100 Mbps is used, and later now the technology has even improved and 1 Gbps is used. So this is 100 Mbps is also called as fast Ethernet, and this Gbps is called as gigabit Ethernet. Gigabit Ethernet, right? And next point is, what is the encoding technique used? Encoding means how are you going to convert the bits into signals. So encoding technique used is Manchester. So you must have heard about Manchester and differential Manchester, I told you, right? So Manchester means this is 1 and this is 0, right? And one thing you should remember is, in Manchester encoding, baud rate equal to 2 into bit rate, right? So these are all the theoretical points about Ethernet. And now you know where this Ethernet mainly operates. Any of the LAN technologies, they will be dealt with by data link layer. So data link layer is the main layer which deals with all the LANs, right? So if you look at all the layers: physical layer, data link layer, network layer, transport layer, application layer. Yes, even though we have two more layers between transport layer and application layer, they are not important. So we have various names for the packets at every layer. So a packet or data will start from application layer, which will be called as a message, and that will be given to transport layer. Transport layer will take the message and put it in a packet, and now that packet will be called as a segment. And now that transport layer will give the packet to network layer, that will be called as datagram. Now datagram will be made by network layer, and now network layer is going to give the datagram to next layer. In that layer, that will be called as a frame, and now frame will be given to physical layer. There it is called as single protocol data unit. These are the standard names. It is also called as single PDU, which means single protocol data unit, right? So at application layer it is called a message, and at transport layer it is called a segment. At network layer it is called a datagram. Data link layer it is called a frame, and at physical layer it is called as single protocol data unit, right? So these are the terminologies available. So this is all about the Ethernet. So Ethernet contains all these 5 points, and now it operates, any LAN operates a data link layer, and at data link layer it is called frame. So frames has to be taken care by Ethernet, or Ethernet has to talk even about frames. Now let's see what is the frame format of Ethernet. Now let's see this one, Ethernet frame format. Why is it called a frame? Is it is operating at data link layer, and it is defined by IEEE 802.3. It is also called as IEEE 802.3 frame format or Ethernet frame format. Both are same. So this is how the frame looks like. In the beginning, frame is going to have something called as preamble and then SFD. SFD means start frame delimiter, right? And these two parts are actually not added by data link layer, they are added by physical layer. So the reason why they are added by physical layer is they are also called as physical layer header. So whatever the data frame is, always it is going to have something called as preamble and SFD, and these two are constant, right? And if you look at preamble is going to be 7 bytes and SFD is going to be 1 byte. Preamble is 7 bytes of 10, 10, 10, 10, so on 10. 7 bytes of 10s will be there. Why these many bytes is used is just that they believed that this one will never match with any data. Preamble should be a special pattern which should indicate that a packet is actually starting, a frame is starting, right? Therefore the concept is we assume that this 7 bytes of 1s and 0s doesn't match with a data. In case if it matches, then it unnecessarily alerts some of the stations saying that a data packet is starting. Then what they do is they will look at the next one, preamble SFD, and at least SFD should be different. Even if these two matches with the data of some other packet, unnecessarily many of these stations will be alerted and they will just see the destination address. If the destination address is not their own, they are not going to read it. I think you remember why preamble and SFD is used. I told you in framing. So if you don't know that, please go back to framing video and watch it. So preamble and SFD are used in order to alert a station or all these stations that data is going to start. And since it should not match with any data, we are having 7 bytes of 1 zeros. And then SFD is 1 byte. 1 0, 1 0, 1 0, 1 1 is SFD, right? So this is SFD and this is preamble. Preamble is alternating 1 zeros and SFD is 1 0, 1 0, 1 0, 1 1, right? Why 1 1? It says that it is the end of SFD. Now why do we have to have two fields SFD and preamble is, initially only SFD was there, later they added preamble. So the reason is, this is a very small pattern. There are many chances that this pattern will match up with some of the data elements. Therefore they added even more and increased it. Anyways, they are not stored anywhere. Whenever you give a packet to the physical layer and if you ask it to send it, before sending the actual data frame, it will send out this pattern and then it will put the data on the link. So these two are not actually counted as a part of the frame, but still, since they are added, I am just writing it. Otherwise you might feel that without SFD how frame is going on. So this is a physical layer header. Now this part is actually added by data link layer header, and this part is also added by data link layer. This is data link layer tail. Why tail? Why is CRC added at the end is, I think you know how to calculate this CRC. Now why is CRC added at the end and why not in the beginning is, you can think of the data packet like this. Let us say this is the data packet. Let us assume that this is the data packet and assume that this is the data link layer, right? And when the data packet is being transmitted onto the link, when it is being transmitted, parallelly CRC will be calculated. Therefore, by the time the entire data packet is on the link, CRC will be available at this part. Therefore, CRC can be added only at the end of the data, isn't it? Which means by the time this entire part is on the link, then only I get CRC. That is why CRC is added at the end, and that is why it is called as tail. And the remaining part is added by data link layer. Now let's see about these two fields. Next field is, so first let us finish about this. Preamble and SFD, they are used for two purposes. One purpose is they are used to alert all the stations about starting of the frame, and second thing is they indicate start of the frame. They indicate start of the frame, as well as they are used for synchronization. So in clocks there is something called as synchronization, right? So they are used for starting of the frame as well as for synchronization. So synchronization, you need not worry about it much. There is something called as physical clocks and physical clock synchronization, which is generally used at physical layer. So don't worry about it much. You just assume that these two are the functionalities of this. That's it. And now let's talk about destination address and source address. Next two fields are DA and SA, destination address, source address. Now we are at data link layer, and data link layer deals with physical addresses, right? Now let's look at that. Let's now look at this destination address and source address. So destination address and source address are 6 bytes and 6 bytes each. Why 6? So they are 6 bytes because they are MAC addresses. So in Ethernet, MAC address is used as physical address. You know that Ethernet uses physical addresses, which means the data link layer uses physical addresses, and we are going to use MAC address as physical address here, right? That is why 6 byte and 6 byte. Okay. Now what about destination address? So whoever you want to send the packet to, their address is going to be here. And what about source address? Whoever is sending the packet, their address is going to be here. So you are going to write your own MAC address if you are sending a packet in this field, and you are going to send the packet to someone else's MAC address. Now how do you know your own MAC address? you can know your own MAC address because it is already present in your computer. It is already present in the NIC, right? So you are going to read the number from that hardware. Your software is going to read the number from that hardware data link layer and put it here. So what you could do is, even though the MAC address is static in your computer, when that is being read and copy pasted here, you could just change it. But actually changing your MAC address is illegal, which means whatever is there in the number is there in your computer as MAC address, you are supposed to use it. But I'm saying that when you are sending out a packet, it need not be the same number. You could change it manually, but changing it is illegal. Remember that. So even though I'm saying that it is permanent, it doesn't mean that it is fixed like that. You can change it, but it is not legal. Okay. And now destination address is whom you want to send the packet. So how do you know that? Since everyone is there in your own network, before sending the packet to someone, you send a broadcast packet asking please send me your MAC address. So you can find out the MAC address of every other station in your own network by there is some procedure available. I'll tell you that later. Therefore you know the MAC address of the destination and you know your own MAC address, and you are going to place them here. Each is 6 bytes and 6 bytes, right? And coming to destination address or coming to MAC address is of various types. So types of MAC address is of various types. So one type is unicast address. So if you want to send a packet from one host to other host, one to one, generally unicasting is used. And second one is multicast. Multicasting means if you want to send a message from one host to many hosts, we are going to use multicasting. And third one is broadcast. So broadcast means if you want to send a message to everyone, it is called broadcasting. Unicast means one to one, multicast means one to many, not to all, and broadcast means one to all. So we have already seen this in IP addresses. Now again we are seeing it in MAC addresses. Now see this. Unicast means if the least significant bit of first byte is 0, then it is called unicast address, which means if I take the MAC address and if I take the least significant bit of the first byte, generally MAC address is a 48-bit number, and generally it is a convention that we represent this MAC address as dotted. Instead of that dotted decimal representation, we are going to use hexagonal number system, which means generally it is not a rule, it is just a convention. So example of a MAC address will be like this: 1A, 2B, 34, 48, something like this. And every two hexadecimal digits, every two hexadecimal numbers will contribute to make up 1 byte. So what is 1A is? 1 is 4 bits, 0, 0, 0, 1, and what is A is 10. So 10 means 1, 0, 1, 0, right? So this is the MAC address, and I'm just converting everything into 6 bytes. What is 2 is 0, 0, 1, 0, and what is B is 11, 1, 0, 1, 1. So if we can convert it all like this, it is a 48-bit number. Now I'm saying that if the least significant bit of the first byte, which means this is the first byte, the least significant bit, this one, the least significant bit of the first byte is 0, then it is called unicasting address, which means every address you send, in your host, any host is going to have only this combination. Therefore, whenever your NIC manufacturer is going to manufacture a MAC address is going to put a MAC address on your NIC, he is always going to see that it is going to end with 0, right? Remember that. And next one is any source address has to be always a unicast address. So inside this field, it should always be this kind of address. So if they give you a packet entirely in bits, and if they ask you whether it is a valid packet or not, just see that the source address should always be unicast address, which means go to this field and you go to that bit that has to be 0, right? And next one is multicast address. Multicast address means if the first bit, if the least significant bit of the first byte if the least significant bit of the first byte is 1, then it is called multicast address. What does that mean? So if you write the entire MAC address, and if you go to the first byte and you take the LSB, that has to be 1. So for example, let us say the MAC address is A3 B4 C5 6 7, something like this, 1 2 3 4 and one more byte, 1 0, something like this. Then look at the first byte. This is the first byte. The least significant bit has to be 1. So what does it mean? A means 1 0 1 0 and B3 means 0 0 1 1. Now the least significant bit of the first byte is 1. Therefore what can you say about it? If the least significant bit of first byte is 1, then it is a multicast address, which means this is a multicast address. Whenever this is 1, it is multicast address. So what is the advantage of using this multicast address is, you can just think about it like this. Just let us assume that there is a LAN, and in this LAN there are many stations, okay? And let us say there are many stations in this LAN, and now I want to send a message to two stations A and B, not just to one station, or repeatedly I want to send messages to some set of stations inside my LAN. So let us assume that A and B are two such stations, and if I send a message, both of them should receive it, and I send repeatedly such messages, then it is always better that you create a group for them, and in that group you can put A and B, and for that group you are going to give a ID, and that group ID should be a multicast address, which means as a system administrator what you could do is, you generate any such number, you need not buy them, no one is going to get this number. The reason is, everyone is going to get a number as unicast address, which means the least significant bit in the first byte will be 0. No one is going to get a multicast address. So what you should do is, as a system administrator, you could create such a number where the first bit in the least significant byte is 1, least significant bit in the first byte is 1, and you assign that as the group ID to A and B, right? And moreover, you should inform A and B. Assigning is nothing but going and informing them. You inform A and B that, see, you both are now present in a multicast group with so and so address. Let us say address is this one, right? Then both of them will configure their NICs in such a way that whenever any packet is sent to that particular multicast address, both of them will automatically read. So please try to understand this. How does it work is, now we are going to create a number with 1 in the least significant bit of the first byte. You need not buy it. As a network administrator, you can use them, right? So there are lots of such numbers available. You take one such number and now you create a group. Creating a group is nothing but going to the host and telling them that, see, you both are present in so and so group, and if anyone sends a message to that group, you both have to read it. Therefore, every NIC is configured in such a way that if a packet is sent to their exact unicast address, they will read it. Or if they are already informed that they are present in a group, and if the packet is sent to that group ID, they will read it. That is how grouping is done. That is how multicasting will work. Therefore, if any packet is sent with a multicast address which is known to A and B, then both A and B will read and others will discard it. Got it? That is how multicasting will work. And now third one is broadcasting. So what is broadcasting is, instead of least significant bit being 1, if all the bits are ones, if all the bits in MAC are ones, then it is called broadcast address. So 48 ones, if I have all ones, 48 ones, then how does the address look like? Like this, right? So all F's. Why? F is nothing but 4 ones. F is 15, 15 means 4 ones. So all ones is nothing but broadcast address. So why is it used is, if you want to send a message to everyone and if you want everyone to read it. Actually, when you send a message to everyone in this in this multi-access link, Everyone is going to get this, but they are not going to read it. The reason is they are not for their own MAC address. Every station will read a packet only if it is mentioned as a destination address as its own IP address. Let us say you want a message to be taken by everyone, as well as that has to be seen as well as accepted. Then you put this one, right? It means that everyone is going to get this, right? So that is how the addresses are classified. If it is 0 in the least significant bit of the first byte, unicast. If it is 1 in the least significant bit of first byte, it is multicast. If it is all ones, then it is broadcast, right? So there is an interesting thing here. Even a broadcast is a kind of multicasting, which means if you take this, so multicasting, broadcasting is a subclass. So multicasting says that there has to be 1 in the least significant bit of the first byte. Broadcasting says that there has to be all ones, right? Therefore, if there are all ones in the MAC address, obviously the least significant bit of the first byte will be 1. So every broadcast address is a multicast address, but every multicast address is not a broadcast. Now let's see about switching. So switching is of these types. Switching is basically of, one is circuit switching, and other is packet switching. And other is message switching. Right? And coming to this packet switching, there are of two types. One is virtual circuits and the other is datagram. Right? So these are all the various kinds of switching. So switching is basically of three types: circuit switching, packet switching, and message switching. And packet switching is of two types. One is virtual circuits and other is datagrams, right? And we shall see about them one by one. And before going to switching, so let me tell you a few things about it. Even though I am talking about switching, which is done at network layer, this switching, circuit switching, is actually not done at network layer. The concept of switching is there even before the layers were invented. So initially we introduced about circuit switching and then we move on to this, right? So you just copy this down and I'll just go on to the next topic. I'll explain about them each one by one. Now see this. So whenever we have any problem in computer networks, generally we look back to the previous network, which was nothing but telephone networks. So just the story is like this. Initially, before this computer networks, telephone networks were there, and before telephone networks, this the network is called the telegram network, right? So there used to be a company called as Western Union. Heard about it? Western Union is now money transfer bank, right? So money transfer agency. Now Western Union was the biggest company in 1800s. In 1800s, this is the only company which used to be useful for communication. So people used to get only telegrams. You might have seen in old movies that if someone dies, people will generally send telegrams, right? So nowadays no one is using telegrams. I don't think there is telegram office anywhere available, right? And when this Western Union was at a very high boom, then what happened was this fellow Graham Bell invented this telephone. And then he went to this Western Union and he told them that he has given a demonstration to the head of Western Union, the president of Western Union. He has given the demonstration. He asked the president to stay in one room and he went to the other room and he called him over a phone and he was able to speak. And this president, instead of getting shocked and surprised about this technology, what he did was he laughed at it. And all the heads of Western Union, they said that why will grown-ups, the adults, why will they speak on a mobile phone? That was their question. They just asked that this is a technology which can be used by children or kids to play, but this cannot be used for serious communication. That is what they said. Even Graham Bell went to an extent that he wanted to sell his license to Western Union for $1 lakh. Just for $1 lakh he wanted to sell it. It was not a very big amount for Western Union back then. They are already doing billions of dollars of business, and it was just $1 lakh. He wanted to sell that great invention telephone to the Western Union, but then they simply rejected. Then what this Graham Bell did was he went out and he sold this telephone to various people like. He has gathered some small merchants and he has given the license, and now those small merchants, they started manufacturing the telephones and the telephone wires, and they started selling them. Initially, people who used to use this telephone were rich people. They wanted to call their domestic help, the maids, right? And therefore they used to have one telephone in their house and the other telephone connected to their domestic service, the maid's house, and they used to call them for work. Or sometimes the rich people, they wanted to talk to their friends anytime of the day. Then people who are rich, the friends, they used to have the telephones in their house. Initially when it was developed, the telephone, the range was very short. It was not able to span long distances. Therefore Western Union didn't feel any threat, because Western Union was operating continents, countries, but telephone was operating only within cities. Slowly what happened was, with the advance of technology, this range for which the telephone could cover has increased, and then it started connecting the cities, entire cities, and then it started operating between the cities, and slowly it became so, the technology became so much easy that they started communicating even across the continents also. And then the telephone company started becoming very big, so big that within just 10 years they started a company called as AT&T. AT&T is nothing but all the merchants who bought the license of telephone from Graham Bell. They all formed a company called as AT&T, and then this AT&T now bought Western Union. Therefore Western Union is now not even existing as an independent company. AT&T bought it. Now I think it is not even in communications, it is in money transfer, right? So that is how the evolution was. So before this computer networks, there was telephone network, and before this telephone network there was telegram networks, right? So what these people did was, whenever we have any problem in computer networks, we go back and look into telephone networks, and then we see how they solved it. So no problem is generally a fresh one in computer networks. Already we get problems which were already there in telephone networks. We look at how they solved it, and then we used to apply it. Even coming to this classful addressing, if you look at class A, we used to have 8 bits of network ID and 24 bits of host ID, isn't it? So how did we get that idea of using 8 bits and 24 bits is, if you look at telephone numbers, in telephone numbers, the big metropolitan cities, they have 3 digits as STD code and then 8 digits as host ID or telephone ID, isn't it? Telephone ID. The Delhi's code is 011, right? Like Mumbai's code is 022 or something, right? So using this only 3 digits, the concept is why telephone networks used only 3 digits for STD and 8 digits for telephone ID is, they wanted to have very less number of metropolitan cities, but within the metropolitan city the number of telephones are very high, right? So similarly, looking at this, we got an idea that we need very small number of networks which will have very large number of stations, right? And then we had class B. Class B was containing 16 bits of network ID and 16 bits of host ID. How did we get this idea from? From telephone networks only. Let us say towns. The towns and other cities, not metropolitan cities, the towns and other cities, they have 4 digits of STD code and then 7 digits of telephone ID. For example, Noida has 0120, which is 4 digits of STD code and then 7 digits of telephone ID. The reason is the number of towns are moderate, and within a town the number of telephones are moderate. So similarly, we needed a moderate number of class B networks, and within the class B moderate number of hosts, right? And then if you look at class C, they classified it as 24 bits of network ID and 8 bits of host ID. How did we get this idea from? Again from villages, the way telephone numbers were assigned to villages is 5 digits is assigned to telephone, this STD code, and then 6 digits is assigned to telephone ID, right? Which means there are large number of villages. Within a village there are less number of telephones. Similarly, there are large number of class C networks. Within a network there are less number of telephones, right? So now within a network there are less number of hosts. Similarly, here in switching also, we have seen how the switching is done at telephone networks, and then we are going to apply it for this computer networks. So whenever we have a problem, we just look back and take the solution from that and we apply here, right? Now let's talk about the switching methods. First one is circuit switching. So circuit switching is, it was used in telephone networks long back. Currently no one is using it. Telephone networks long back. So in 1980s it used to be like this. There used to be something called as telephone exchange, and to the telephone exchange all the telephones will be connected like this directly, and there used to be typically one telephone exchange for one town and there used to be very less number of telephones at every house. And back then in 1980s, having a telephone at home was a privilege, right? And now, right now, everyone is having a mobile phone, right? Back then it was the case, and maybe you might have seen that in movies. They used to hold it like this, one with one hand, like this, and with one hand. Old movies like Sholay. What does that mean? It means that it is half duplex. So you can either send the message in one direction and receive it in other direction, right? So back then in 1980s, so people used to have very less number of telephones, and all the telephones used to be connected to the telephone exchange. And now this telephone exchange will be connected to other telephone exchange, and this telephone exchange will be connected to other telephone exchange like this, and all of them are connected like this. Let us say a person here A wants to contact a person here B. He wants to call him, right? And this is connected to many telephone exchanges, and this is connected to many telephone exchanges like this, right? And now a person A there wants to communicate to a person B here. Now let us assume that these are all connected like this, and back then what used to happen is, at every telephone exchange there used to be a person called as telephone operator like this, right? And now if A wants to talk to B, first A will call the telephone operator and he will tell him that I want to talk to B, but then he will not be able to give the connection right away. So what he will do is, in a log he is going to write your name, saying that so and so person, let us say your number is 100, saying that so and so person wants to talk to so and so person. So whenever the time is right, whenever your number comes, then this fellow will call this fellow and say that he wants to connect to B, and this fellow calls to this fellow and say that he wants to connect to B. Like that, everyone is going to take a physical wire and they are going to connect it like this, connect it like this, connect it like this. Then only A will get a chance to talk to B, right? So I have an uncle, and he was saying that back then in 1980s he used to get phone calls in the midnight, it seems. He is a lawyer here, and he used to get lots of calls from clients, and it seems that always he used to get the phone calls in the midnight, and he cannot ask them to call back in the daytime. He had to talk whenever he gets the chance. The reason is, even though the clients have booked their call in the morning, by the time their number comes it will be midnight. Therefore he has no other choice. He had to talk whenever he receives a call. Otherwise what happens is, again, if the clients, they have to register the call, it will come after a lot of time, which means even though you register it in the morning, by the time your number comes it will be midnight or something like this, right? And in case if you have a emergency call, there used to be something called as trunk calls, it seems. Trunk calls means if you pay some more money, then these telephone operators, they used to give you phone calls, I mean urgent calls. Immediately they will give you the connection, but for that you need to pay more money. And the worst part is, when you are talking to other person, this fellow sitting in the middle, he can also listen to your conversation. That is really worst part. Imagine this. Now let us assume you are talking to your boyfriend or girlfriend, and suddenly this fellow is also listening to your conversation. How weird it will be, right? And now second thing is, sometimes it seems that he will come in the middle of the conversation, and he will say that you are not talking anything important, so we are going to disconnect your call. Isn't it? That is even more weird. So he will call in the, he come in the middle and he will say that I'm going to disconnect it, or sometimes he will say that your time is over, which means you cannot talk on a phone call for a long time. Just see how the things have changed. Now there is no limit like this. You can call and talk to your anyone for any amount of time. There is nothing like this, right? Okay. So, and one more thing is, I had one more uncle. He used to buy, he had a business. He was saying that he used to buy some goods here and take them to the other village, and he had to sell them here. By the time the goods get transferred from that place to this place, the prices they used to get lower, which means the prices used to get decreased, right? But then what my uncle used to do is, he used to bribe this fellow, the telephone operator for this village, and he used to block all the phone calls coming from that place to this place. So no one here will get the news about decrease in the prices until he sells the goods. After he sells the goods, then this fellow will allow the phone calls, it seems, right? So which means information could be blocked right away. Now look at how things have changed. Now even the governments are scared to take any decision financially. If they have to take any decision financially against the interests of the people, within seconds of time the funds will be transferred from one country to other country with the speed of light. Why? The optical fibers, light travels with the signal travels with speed of light. Therefore, the bunch of people who actually control the e-commerce, they could move away your money from one country to other country with speed of light, right? Things have changed so fast that computer networks is actually a revolution, isn't it? Because everyone will know about everything within seconds, and Twitter is actually a news network. Even though you are updating your status during many war times and during many revolutions and all these what is that in Pakistan and other countries, whenever something happens, immediately the first person who reports, news reporters were very scared to go to some places where there are some explosions and all, but people around their surroundings, they are going to take a picture and put it up in the Twitter. Therefore Twitter is the fastest news network as of now, right? So computer networks has completely changed the game. Even the governments are scared to take any decision against the interests of the people. Funds are going to be transferred with speed of light, right? Yeah. Now let's see in those days when the circuit switching was used, let's see what was the scenario. Let us assume that a station A, let us say the same circuit switching is implemented in computer networks, which means A wants to send a message to B, and now there are some switches like in 1980s. In those days computer networks was not there. I'm just assuming that what would have happened if the same technology has been applied to computer networks like in telephone networks. Someone has to sit here, and if you want to send an email, he has to take a wire and connect it, connect it to B, right? Let us assume that it is all happening now, and now see what is the time taken. So the basic assumptions are, let M be the size of the total message that A wants to send to B, so that is the message size, and capital B be the bandwidth of the entire channel. And let us assume there are X number of hops. Hop means from here to here it is one hop, here to here one hop, here to here one hop, here to here one hop. X is the total number of hops, and small d is the length of each hop, which means from here to here the distance is d, like that, and velocity of the signal is v. So if these are the parameters given, then what is the total time taken in order to send a message of size m from the station A to the station B? So can you guess the total time? So now what should happen is, before actually the message gets transmitted, first thing is the connection has to be established, isn't it? Therefore the total time taken is, first one is connection has to be established. For that I call it as setup time. And after establishing the connection, then you have to transmit the message onto the link, that is called transmission delay. So what is the transmission delay here? If m is the total length of the message and b is the bandwidth, m by b. Once you put the data here, there is no stopping. Let us say here. Once the data is kept on this link, there is no stopping. The data is not stopped at anyone, directly it will go. Therefore, Once the entire data is here, now the last bit of the packet has to go to the other end. Then we can say that message is received by the B. Therefore, what is the time? Total distance divided by velocity, propagation time. This is nothing but the transmission time. And now I want to write the propagation time. What is propagation time? D by B. What is D here? D is number of hops are X, and every hop is going to take a distance of D. Therefore, what is the total distance? X into D is the total distance divided by V is the propagation time. So this is TP, right? Now setup total time is setup time plus transmission time plus propagation time, and after that we are going to tear down the link, right? So once the entire data has been transmitted and received by B, we are going to pull down the links. All these links have to be discarded, right? So this is the total time taken in case if I use this message switching. Now let's see some points about it. This is the total time. First point is, are the headers required? Are the headers required? Headers are not required in this case. The reason is, you need not say where you have to go. It is like this. It is like a train, isn't it? The entire rail has been laid down. The entire track has been laid down. Now you need not give any GPS to the driver. Obviously, if he is going to start here, he is going to end up there. You need not say which direction to go. Therefore, you need not give him a GPS or a map. Just ask him to follow the track. So like that, there are no headers required. And now second thing is, will the data go in order, which means will all the entire data go as it is as you are sending, or will the data go jumbled? Since it is just like train, if you are starting a train here, if the first bogie is there, after 1 2 3 4 bogies are there, even by the time train reaches the other side, 1 2 3 4 bogies will be there, isn't it? Therefore no reordering is done. No reordering, isn't it? So no headers are required and reordering is not done. Therefore no sequence numbers are required. You need not actually again arrange them. Therefore nothing is required, and all of the entire data goes in order, right? So entire data will follow the same path, right? So the entire message is going to be sent at one go. This is the total time in message switching, right? Now let's see, it is the total time in circuit switching. Now let's see the next one, which is called as packet switching. So the packet switching is, let's say these are the properties of circuit switching, and now let's see the packet switching. So one thing about this circuit switching was, it is not applied at circuit switching is not applied at network layer. Circuit switching is actually applied at physical layer. So circuit switching, it is applied at physical layer, not at network layer, right? And second thing is, it is obsolete. Obsolete means no one is actually using it now. It was used long back in 1980s in telephone networks, but now we cannot use it. So just imagine a scenario where if someone has to sit at these switches, and for every message you type on WhatsApp, or for every chat you send, or for every email you send, if someone has to sit in these switches and they have to change the wires in order to send your message from A to B, they have to connect the wires. Just imagine what happens. Everything is going to collapse. In the sense, everyone in the world have to work at the routers. There will be no unemployment problem. Everyone will get a job. If you ask anyone what they are doing, they will say that I am working at router, just routing the packets. That even if everyone works at the router, then also we cannot assure that the packets are delivered reliably. So we don't want this manual intervention. We want a automated process. We want the software to take care of it. So then packet switching is going to help us. We are not going to use circuit switching. We are going to use packet switching now. So what packet switching is, we are going to send the message, but then the message is not directly sent to the next one. It will be first saved Message will be first saved, and then it will be having a header. So looking at the header, this switch will decide which way to send it dynamically. So once it decides the path, no one need to actually connect any wire. There they use something called as multiplexers. Multiplexers means many to one and one to many links. So whenever any packet arrives, it will be checked. Or let us say whenever any packet arrives here, one of the outgoing links will be chosen dynamically. So using multiplexing and many concepts, they are going to implement the switches. We shall see that concept later at routing. But now assume that we have the software which can dynamically find out which way to send the packet, right? Now it is like this. Every packet is going to be sent independently, and there is no need of setup. It will go and sit here, and now once this switch receives the packet, now this switch is going to forward it, which is nothing but transmit. And again the switch is going to be here, the message is going to be here in the buffer, and again transmitted. Again it will go and sit in the buffer, and again transmitted, right? Now in this scenario where we have used this kind of packet switching, let's see the total time. Is there any setup time here? No need of setup. Everything is already in place, right? You need not actually take wires and then set them up. Therefore no setup time is required. Then how many times is the message actually transmitted? In the previous case, we transmitted the message once and the message was directly on the go. But then here you have to transmit it once, and then the switch will take it, and again switch has to transmit it, again switch has to transmit it, switch has to transmit it. Therefore in this case it is not just one transmission. The number of transmissions are equal to the number of hops. So let us see how many hops are there. 1 2 3 4. Therefore how many times it has to be transmitted? One time at the source, again at the switch, at this switch, at this switch. Therefore 4 times we are actually transmitting the message. Therefore the total time here is, if x is the total number of hops, then x into m by b. This is the total number of transmissions that have to be taken. And anyway the last bit has to take the last bit is going to take that transmission delay, right? So what is the total time taken? Again the last bit has to cover the entire distance. Therefore the total propagation delay is d by v, x into d by v. Why? X into d is the total distance and this is the total propagation delay. Is there any tear down time? No need of tearing down anything. We didn't set it up at the first place. Therefore there is no setup, there is no tear down, only these are the times, right? So that is the main difference between circuit switching and packet switching. In packet switching it is a store and forward network. So we are not directly sending the packets, we are storing it and then sending it. Now let's examine which one is better and what is the difference between each one. The first equation for total time, this one is actually for circuit switching, and the second equation for total time, this one is actually for packet switching, right? Now let's compare each one. Where are the factors? What are the factors in each one? Now the difference between circuit switching and packet switching is, if you look at circuit switching, the extra factors are setup time and tear down time. These two are extra. So there is setup cost plus tear down cost, right? And if you look at packet switching, the extra factor is, just watch this, I am going to have more than one transmission times. Everything is same, this is same and this is same. The extra factor is this much. How much is it extra? Already 1 m by b is already there, but here we have x minus 1 extra. Therefore x minus 1 extra times actually I am doing the transmission, right? So which one is better? So given a network, which one do you want to go for? So in case if your message size is very big, then this entire time is going to be very big, which means packet switching is not useful. Then go for circuit switching. If you have to send very big data, then it is going for circuit switching, right? And in case if your packet message size is less, which means you want to send only small amount of data, then this one is going to be lower and setup time and tear down time is going to be significant. Therefore you go for packet switching. So for bursty data means very big data, it is better that you go with circuit switching. and for small data or very little data or less data, you can go for this packet switching, right? But then why do we have to go for this circuit switching or packet switching? I already told you that this circuit switching is not existing, it is obsolete, right? But what do I mean by going for this? It means that even though circuit switching is not there, what do I mean by saying that go with circuit switching and go with packet switching is, if you look at circuit switching networks, they look like a single wire, isn't it? They look like a single wire after connection. Therefore, if you have lot of data, then you take a single wire and connect the sender and destination without having any store and forwards in the middle, isn't it? So if you have very small data, then buying this entire wire is a headache. For example, if Google has to move their entire data from one data center to other data center, and let us assume that every day they have to move 1 terabyte of data, then from one continent to other continent, then having lots of hops on the way is going to add lot of delay. Therefore, in that case, Google will buy their own network, their own wire, and they will connect the sender and receiver, which means both the data centers. That is beneficial for them. Let us say you want to make a phone call to your friend, then you are not going to buy a wire and go to his house and then connect it, isn't it? Therefore, for small data, don't connect them with a wire, go with the hop method, right? Take the support of the existing infrastructure. If you have to send lots of data, it is better that you buy your own network, right? There is also called as leased line. Leased line means some people, if they have to send lot of data, instead of relying on the ISP, they will take a lease line, which means they will take a dedicated line and they will use it without any hops, right? That is the meaning what I say. But anyways, for gate you can remember that for bursty data, circuit switching is better. For small data, packet switching is better. Let's now look at this IPv4 header. Just zoom in. So this is the header which is used by the IP layer. Okay. So what I would like to tell you is, you could either Google it out, it is available everywhere, or if you have a textbook, you can look at it. In case if you don't have any textbook and if you want everything to be available in your notes, please take it down and I'll explain you about each field one by one. You can pause the video, write it down, and even write about each one. So first one is version. So version within brackets there is 4. So 4 means the number of bits. And next one is header length. So header length is nothing but HL means header length. What is the length of the header? That is given by header length field. Next one is type of service. Its size is 8 bits. 4 bits, not bytes. Remember it? 4 bits, 8 bits. Total length is 16 bits. Identification number is 16 bits. And this bit is not used. So one bit is simply 0. This is a bit. These are flags. This is one bit which is completely not used. And next one is DF. DF means do not fragment. Write it down. And it is 1 bit. And MF means more fragments. It is also 1 bit. And next one is fragment offset, which is 13 bits. And it is TTL. TTL means time to live, which is 8 bits. And next one is protocol is also 8 bits. Next one is header checksum is 16 bits. And next two fields are source IP address, which is 32 bits. You know about already IP address is a 32-bit number. Destination IP address, which is 32 bits. And next one is called options, and these options are optional. Sometimes there could be no options. In that case 0, and you could go as much as 40. So that is why the header size is variable, right? So it is 40 bytes is the maximum header length, and 40 bytes is the maximum options, and 0 bytes is the minimum options. And after that, data is going to follow, right? And only thing you should remember is, only options I am writing in bytes, and remaining all numbers I am writing in bits. Now let's see what is the total size of it, the total length of it. See this? The first one is 4 plus 4 plus 8 plus 16. Therefore, the first row is 32 bits. So which is nothing but 32 bits is nothing but 4 bytes. And the second row is also 4 bytes. You can count it. You can add them all. It is going to be 4 bytes. 13 plus 3 is 16. 16 plus 16 is 32. 32 bits means 4 bytes. and the next row is also 4 bytes, and this is also 4 bytes, and now this one is variable, right? So now you add all of them, 4 plus 4 plus 4 plus 4 plus 4, it is 5 into 4, 20. So these 20 bytes, these first 5 rows, all of them put together, these first 5 rows, all of them put together is 20 bytes, and this is going to be present in every header. There is no options in this. They should be definitely present. Therefore, what is the minimum header length? Minimum header length is 20. And coming to the options, options can vary anywhere from 0 to 40 bytes, which means options can be 0 bytes or it could be 40 bytes. In that case, if I want the minimum header size is 20 bytes of static header, which means this fixed header, plus 0 bytes of options. Then it is going to be 20 bytes is the minimum header size. 2. Maximum header size is 20 bytes of header, 20 bytes of this fixed header plus 40 bytes of options. Therefore, maximum header size is 60 bytes. So minimum header size is 20 and maximum header size is 60. So that is the size of the header. So since it is variable, generally I told you that whenever the size of something is variable, you should either indicate the first starting and the ending, or you should indicate the starting and the length of it. That is why we have a field called as header length here, header length. So I'll explain you about header length first, then we shall see about all the other fields one by one. So first let me explain you about header length. Now header length is 4 bits. Check this, header length is 4 bits. With 4 bits, what is the maximum number possible? 4 bits, 1, 2, 3, 4. With 4 bits, the maximum number possible is 15, right? So I can save in this field only a number of 15, but my minimum header size itself is 20. The minimum header size is 20 and maximum header size is 60. Therefore, in worst case, I might have to put a number 60 in a field which is able to take only a number 15. That is the problem, isn't it? In worst case, I might have to say that the size of the header is 60 bytes, maximum size of the header, but then this field, this header length field is going to take only a number of 15. Therefore, I am going to use a scaling factor of 4. What is scaling factor is, whatever is the actual header length, you divide it with 4 and the resulting number can be easily kept under 15. Check it, even if the maximum header length is 60, you could divide it with 4 and you get 15 and you could put that 15 there, right? Therefore, the concept is you find out the actual header length and then divide it with 4 and you put that number in the header length field. So for example, in this one, I'll just take this example and show you. Let us assume that header length are, okay, I'll do one thing. I'm going to erase this. You please watch it in your notebook. In case if you have copied it, I'm going to continue this under the assumption that you have already copied it. So you please watch it in your book and I'll just say what is the next field and all, okay? So I'm talking about header length field now. Assume that actual header length is 20 bytes. Then according to the scaling factor, I told you that in the header length field, you are not going to put 20, you are going to divide it with 4 and you are going to put 5. Right? Therefore, what is 5? 5 is the header length field. So, in case the receiver receives the packet with header length field as 5, he will multiply with 4 and he will understand that it is 20, not 5, right? And in case if the header length field is 32, if the actual header length is 32 bytes, then we are going to divide it with 4 and we are going to get 8. Therefore, header length field is scaled down. In case if the receiver receives sometimes header length field as 10, what will he derive? He will derive that it is actually 40 bytes of header, right? So that is how the conversions are going to work, right? Now, given a number, how can you identify whether header length is given or header length field is given? So how can you identify it? Simple. So if header length would have been given in the question, in the exam, if they are saying that header length, you know, how do they mean by this or this? So simple, look at the range. So header length ranges from 20 bytes to 60 bytes, and header length field ranges from 0 to 15, but then 0 is not valid, so minimum header length is 4, isn't it? If the header length is 20, if you divide with 4, I think you will get 5. If you divide with 4, you will get 5, and if you divide this with 4, you will get 15. Therefore, if the range is from 20 to 60, understand that actual header length is given. If the range is from 5 to 15, understand that the scale down is given, which means you have to, if you get this number, you have to multiply with 4 and you have to take the actual header length. Got it? And now assume that if the header length is 30, it is not 32, it is 30, then what should be the header length field? You just think about it. If the actual header length is 30, what are you going to place there? So if you try to divide it with 4, I think you will get somewhere around 7.5, right? But then 7.5 is a decimal number. I mean, with radix point, any number which is not integer cannot be represented accurately in a fixed point notation, isn't it? Which means if I have this number, I cannot represent this accurately inside 4 bits. So it is definitely not possible. So what should I do? I should go use some other method. So if you say it is this 32, maybe you could either use 7. So in case if you use 7, then the receiver will think that 7 into 4, which is 28, is the header length. Then what receiver will do is, he will read 28 bytes from this, and he will think only 28 bytes is header, and the remaining 2 bytes from the header is going to add it to the data. So you cannot put 7. In case if you put 8, then it means that the header length is 32 bits. 8 into 4 is 32 bytes. Then what receiver will do is, he will read 2 bytes from the data as header. Therefore you cannot either go for 7 or go for 8, and you cannot go for 7.5 obviously. So what should you do with this 30? Should I discard the packet? Should I not send it with 30? You think about it. What could be the solution? To the 30 bytes of data, we are going to add 2 bytes of dummy data. It is called padding. Padding is nothing but adding dummy data to make up this size, which means whenever we need more bytes, and if we don't have more bytes, then I am going to add dummy zeros. So if the actual header length is 30, I am going to pad 2 bytes to make it 32 bytes. Now it is 32 bytes, and therefore I can put 8 easily. Got it? So if the header length is not a multiple of 4, then I am going to add some dummy bytes so that it becomes a multiple of 4, and I am going to place it there, 8, right? This process is called padding. In worst case, how many bytes do we pad? How many bytes? And where are we going to pad this? In the options. In the options, we are going to add these extra zeros, these 2 bytes of extra zeros. Anyway, in case if you are using options, what is the worst case number of bytes that have to be added in padding? If the number has to be a multiple of 4, what could be the worst case number that should be added to make a number a multiple of 4? Worst case is 3, isn't it? Either it will be a multiple of 4, or in case if it is not a multiple of 4, you can add a number 3 and you make it a multiple of 4. For example, 21. If a header size is 21, you have to add 3. In worst case, we might have to add 3 bytes of padding. Now let's see the next field. I'll go to the version and I'll do it. I assume that if you already copied the header and see the first field in that, the first field is version, right? And if you look at it, the first field, it is also 4 bits. So header length is over. Now I am talking about version. Version is the starting field in the header. Now it is 4 bits. So what does version mean is, now we have various versions of IP. IP has come across IP v1, v2, v3, v4, v5, v6. So version 1, version 2, version 3, version 4, version 5 and version 6, right? So it has come through all these phases. Now we are using v4 and in future we will go for v6, right? So we are going to have all these versions, we are going to have all these packets. Either a packet will be v4 or v6. Now the problem is, if it is a packet belonging to v4, it will have a different packet structure. Therefore, you need to call a different code on whatever device it is being processed. So if it is v4, we call a different function, and if it is v6, we call a different function. v4 packets are passed by v4 parsers, version 4 parsers, and v6 packets are passed by version 6 parsers. Therefore, depending on the type of packet, the version the packet is following, we are going to call the functions. So one popular version right now is v4, and we are going to v6 also. So v5 has been discarded experimentally, which means v5 has been proposed and then it is not sufficient for many purposes. It has been discarded, and one good thing is we don't have v6 in the syllabus, isn't it? So if it is a good thing, right? So if it is there in the syllabus, you would have to read a lot, and v6 has got lots of features compared to v4. v4 itself is not very easy, and v6 is even more difficult. So don't worry about it, we don't have that in syllabus. And now what I want to say is, depending on these 4 bits, starting 4 bits, if it is 0100, it means that the packet has to be passed by v4 parser. If it is 0110, it means that the packet has to be passed by v6 parser. Therefore version is going to say this. Look at the second row of your IP header. The second row, first element is identification number. So identification number is the field which is having 16. So what about it? Why did we use it? So we use the identification number in order to number every datagram that is going out of a host. Therefore, if there is a host and every datagram coming out of it will get one number called as identification number. This number is used to uniquely identify every datagram, right? And it is going to be even useful, very much useful when we do fragmentation. When we do fragmentation, all the fragments are going to get the same fragment offset. Same identification number, not fragment offset, sorry. And next one is, you will see 3 flags. One flag is 0, which means that is not used, and other flag is DF, and other flag is MF, and MF means more fragments. It indicates that more fragments are following. And other one is DF. So DF we didn't discuss about it. See this. Now DF means sometimes what we want is, we are sending out a datagram and we don't want the datagram to be fragmented at any cost. So we don't want the fragmentation at all. Then what we do is, now let us say this is a network and this is a router, and you are sending a datagram, and for that datagram you don't want it to be fragmented. So when you send such a datagram, on that we are going to say df equal to 1. So which means please do not fragment this datagram. And now let us assume that this router has to send it through a network, other network, and here MTU is different. Here MTU is 1000, and let us say here MTU is less than that, some 100 or something like this. So definitely if the size of this datagram is greater than 100, then definitely it should be fragmented, right? But then you can specify that I don't want any fragmentation to be done, right? Then what happens is, this router will try to fragment it, but then the user settings is saying that don't fragment it, therefore the router cannot forward it, it simply discards the datagram. A router, if it has to fragment it, but you are saying that it should not be fragmented, then it is going to discard it, and it is also going to send an error message saying that I discarded your packet because of your settings. So you are going to send back error message, which is an ICMP packet. An ICMP packet will be sent back saying that your packet has been discarded because you don't want fragmentation, but then here I have to fragment. Then what will the sender do? Sender will understand that, oh, because of this issue my packet is bigger, but there the network size is smaller. So next time sender will decrease he himself will decrease it. He is not going to let anyone else fragment it. He himself will decrease the size of the datagram, and then he will send it through. That is why DF is used. In case if you want atomicity, which means entire datagram has to be sent or nothing has to be sent. There should not be pieces. In that case we are going to use this DF, right? And if you look at the next one is fragment offset. Fragment offset. I told you that fragment offset is number of data bytes ahead of this particular fragment in this particular datagram, which means fragment offset means after fragmenting, let us say this is the third fragment, this one, it is the third fragment. then how many number of data bytes are ahead of this one, right? You have to count the number of data bytes in this and number of data bytes in this. Number of data bytes which are ahead of this particular fragment after fragmentation is fragment offset, right? We have already seen it in the fragmentation. So in order to understand all these fields well, you please go back to fragmentation video and I can come back, right? So this entire row is completely dedicated for fragmentation, the second row. Okay. Now look at the third row of the IP header. The first field in the third row is time to live, TTL, time to live, which is 8 bits, right? So I'll tell you about this time to live, why it is introduced and what is the main advantage of this. Before going to that, let's see some problems while routing. As a router, every router is going to have a routing table. I told you, you must be remembering about this. If you don't remember it, go back to the routing table video, and a routing table is going to contain 3 rows. What is the network ID, and what is the subnet mask, and what is the interface. So whenever it gets any packet, it is going to AND it with the subnet mask, and if the result matches with the network ID, and is going to send it through that interface. That is the actual procedure, right? And now assume that the routing table is having many entries, and if nothing matches, for that case, which means if your router is not connected to a network to which a packet has to be sent, then generally what happens is every router will maintain one entry for every network to which it is connected to. Let us assume that this router is connected to 3 networks, 1, 2, 3, right? And now we have the entries only if a packet has to be sent to this network. It got a packet which is not present in any of the networks it is connected to. Then what it will have is, it is not going to maintain a entry for every network in the world. So it is going to have one more router as the default entry. If you don't know which way to send the packet, or if the networks to which you are connected to is not the actual network to which you should send the packet, then you are going to send it to some other router. That is called default router, and is also called as default entry. Instead of calling default router, you call it as default entry, and that entry will contain 0.0.0.0, 0.0.0.0, and let us say this interface is A. So what does it mean? If you take a packet and if you AND it with this, and if there is no match, then you AND it with this, no match, AND it with this, no match, and finally when you AND it with this, definitely there will be a match. Why? If you AND any number with zeros, you are going to get all zeros, right? Therefore, if you don't know where to send a packet, by default that packet will be sent to this router. That is the concept which is generally used in routers. Because of this concept, there could be some problem. For every router, there will be one specific router which it will use as the default router. Default router means if you don't know where to send, we are going to send it through this, right? Every router is going to have such thing. Now let's see what is the problem this concept might lead to. Because of this one, assume that there is a router and its default router is this, which means if it doesn't know where to send a packet, it will send the packet to this router, and assume that its default router is this. If it doesn't know where to send it, it will send it here, and its default router is this. If it doesn't know where to send it, it will send it here, right? And because of this, there could be a problem of infinite loop. So let us say a packet has arrived here, and now this router doesn't know which way to send, which means no other routes have matched. Therefore definitely this packet will be sent through this one, right? So for this one, the packet will be sent through this, and when the packet is here, assume that even this router doesn't know where to send it, then its default router is this one, right? So it will send it over this. And when the packet arrived here, assume that even this router also doesn't have any suitable route, therefore it will use the default route. So again it will be sent back to this. Now think about this packet. What happens? This packet will continuously be circulating in the loop. No one is going to discard it, and everyone is just going to play like catch. So someone is going to catch it, and again he is going to throw, and someone is going to catch it, he is going to throw, someone is going to catch it. Unnecessarily, because of this packet, bandwidth is wasted, buffers are wasted, and processing time is wasted. Over a period of time, what happens is many such packets will accumulate inside that loop, and thousands of packets will come and fall in this loop, and everything will be revolving. The entire link will be full, and entire routers will be full, and routers will be busy, and many important packets may get discarded. The reason is they are not able to handle it. So it is going to be a disaster if you leave it like that. In order to solve this problem, we introduce the concept of time to live. What time to live is, we are not going to let any packet take more than some number of hops. For example, I'll just tell you, if you are in India, in just one hop you could go to England. From India you can go to England, and in just one hop you can go to Singapore, and in just one hop you can go to Tokyo. Which means in just 1, 2, 3 hops you are able to cover the entire world. You have taken a world tour, isn't it? So that much powerful is one hop. So if you restrict the number of hops taken by a packet before being delivered by the destination, in case if a packet is taking more than those hops, you can obviously discard it. Why? Because any packet which is in the infinite loop will take lots of hops and it will never reach the destination. You can identify that if a packet is taking lots of hops, then you can discard it. In order to count the hops, or in order to restrict the number of hops, we are going to use this field called as time to live field. So how does this time to live field work is, now I'll take an example and show you. Let us say there is a source here. Let us say there is a source here, and there is a router, and destination. And source is going to have some number set on the this packet as TTL. Assume that initial TTL is set to 3. What does it mean? Source is saying that this packet has to be received by the destination in 3 hops. In case if it takes more than 3 hops, and even after taking 3 hops, if it is not at the destination, anyone on the middle has the right to discard it, because source is saying that I don't expect that my packet will take more than 3 hops to go to the destination. That is what source is saying. Now when this packet is received by the router, it is going to decrement the TTL. So TTL is initially 3 and it has taken 1 hop. Therefore now TTL is reduced to 2, which means now the number of hops it can take is only 2, because it is initially supposed to take only 3, it has taken 1, therefore the number of remaining hops it could take is 2. Now when this packet is here, then the TTL is 2 and it has already taken 2 hops, therefore it is going to be reduced to 1, which means at every router this TTL is going to be reduced by 1. Now it is here, its TTL when it received is 1 and it is going to decrement it by 1, and it finds out that it is 0, which means whatever is the number of hops expected, the packet has already reached it. The packet has already taken the maximum number of hops that is decided by the sender. Sender decided that it can take only 3 hops and it has already taken it. 1 hop, 2 hops, 3 hops. Hop is nothing but a link, right? 1 hop, 2 hop, 3 hops. Therefore the packet will be discarded, which means whenever TTL becomes 0, the packet will be discarded, right? So every node or host, which means at your computer, before sending the datagram, that is going to decide what is the number of hops the packet is allowed to take before being discarded. Generally this number will not be too big, either 8 or 16 or 32 is used, not too big, and that depends on the settings. So it varies from implementation to implementation, which is a fixed number, which is not going to be very big. So previously it was 8 and I think later they changed to 16 or 32. So that is not an issue. You can use any number, but remember that your packet will never take more than those many routes. So, and you are not going to set it, your software is already going to set it by itself, right? It is already predefined in your software. Now in this case, if the packet has to be received by the destination, what should be the TTL? So initially TTL is, let us say 4. If you are sending it, then the packet will be 4, it will be decremented to 3, it will be 3 decremented to 2, it will be 2 decremented to 1, and now it will be 1 here decremented to 0, right? So if the destination receives the packet, and even if the time to live at the destination is 0, destination is not supposed to discard it. Why? Because the packet is expected to be received by destination in 4 hops and it has taken exactly 4 hops. That is why its time to live is 0. There is nothing wrong in it. Therefore, whenever it is 0, the destination will decrement the TTL, but it will not discard it, it will accept it. Remember that. If it is 0, destination will accept it, it will not it doesn't mean that if it accepts only 0. So let's take one more example. If the time to live equal to 5, it will be 5 here decremented to 4, it will be 4 here decremented to 3, it will be 3 here decremented to 2, it will be 2 here decremented to 1, still accepted, which means destination will accept a packet if its time to live is either 0 or any positive number. But on the routers, always time to live has to be greater than 0. If it is 0, router is going to discard the packet. Okay, that is how time to live is going to be useful. Now let us see how time to live will solve this problem. Let us assume that the time to live on this packet is 8. So at this router, time to live equal to 8. It will decrement it, which is 7, and send it. It will decrement it, which is 6, and send it. Decrement it 5. Now 5 is here. 4 is here, 3 is here, 2 is here, 1 is here, 0 discarded. So the main purpose of time to live is to discard a packet which falls in infinite loop. It has been asked in GATE many times, so remember that the main advantage of, or the main purpose of using time to live is to discard the packets which are falling in infinite loop, right? So what is the main purpose of time to live is to discard the packet which falls in infinite loop. And there are other advantages or other uses of time to live. We shall see it later at ICMP. When I discuss ICMP, I'll discuss about other advantages, but its main purpose is to discard the packets which are falling in infinite loop, right? So one thing is any device on the way which is having network layer is supposed to decrement the time to live, and the destination is also supposed to decrease the time to live. Just remember it, destination also decreases, and any device on the way which is having network layer will decrease it. And what about the devices and what are the layers they contain, I'll take it later. The next field in the first row is type of service, but we shall see the type of service at TCP. In TCP header, when I am talking about something called as urgent flag and urgent fields, I am going to talk about it there. So for now leave it, and the next field is total length. So let me talk about total length first. Okay, so see how many bits is total length in the diagram. You please do one thing, keep the diagram with you handy and just look at that IP header and look at it when I am teaching about it. So the next field is total header, its length is 16. Total length, its length is 16 bits. Therefore, what does it contain is, now this is, assume that it is the IP datagram, and this is header and this is data. Already header size is given in header length, right? And the total datagram length, this one is given in the total length. So total length contains the total length of the datagram, total size of the datagram, and header length contains the length of the header. So these two are useful in order to find out how much data is present inside the datagram, right? So let's see more about it. Since with 16 bits, what is the maximum number that could be represented? 2 power 16 minus 1. So I told you at IP addresses how to do this. With 1 bit, what is the maximum number? 1. With 2 bits, what is the maximum number? 3. 3 bits, 7. 4 bits, 15, like that, right? With 16 bits, what is the maximum number? 2 power 16 minus 1. And 2 power 16 minus 1 is nothing but 65535. Therefore, what is the maximum size of the IP datagram that could be present in internet these days? 65535. It is not a magical number, it is because 16 bits is allocated for the header length field. And I told you that while this, maybe you could go back to that concept of switching. In this switching, packet switching, I told you that this particular field is used, particular size is used in the packet switching, so that packets are not too big, not too small. And 2 power 16 minus 1 has been proven to be a good number. That is why we are using it. Okay. Now, because of this 2 power 16 that equal to 65535, we have various interesting things here going on. See this? Because of this number, there will be many things happening here. Now, physical layer, data link layer, network layer, transport layer, and application layer. So let's say there are only these 5 layers, And now I'm saying that at network layer IP operates, right? So IP is a protocol which operates at network layer, and now at network layer I'm saying that the maximum size of the datagram is 65535. So what do you understand from that? The total amount of data plus header that could be present at network layer should sum up to 65535, which means this total amount, this one should sum up to 65535. 65535 bytes, and already 20 bytes is going to be the network layer header. Then what is the maximum data that could be present in transport layer packet? Therefore at transport layer packet, what is the maximum size? I already told you that there are some names specific at each layer. At application layer we call it as message, and at transport layer we call it as segment, and at network layer we call it as datagram, and at data link layer we call it as a frame, the packet as a frame, and here single PDU. I already told you that. Therefore what is the maximum size of a datagram in TCP/IP? 65535. So what is the maximum size of a segment at transport layer? So 65535 minus 20, which is nothing but 65515. So if at every layer, if you remove that header, the remaining part is also called as the payload or data. So at every layer we are going to have some packets, and when you remove that header, the header part, whatever is remaining, that is also called as payload or data part at that layer. Therefore what is the maximum payload that could be present at network layer? 65515. And what is the maximum segment layer that could be present? 65515, out of which 20 bytes is going to be again header at transport layer. Why am I taking 20 and 20 is, I am taking the minimum size of the header. Maximum size of the header is 60. If I take the minimum size of the header, then in the total space I can put the maximum data. I am calculating how much maximum data can be accommodated at every layer. So at this layer the maximum amount of payload or this data is 65515, and that entirely is going to hold one segment, and now that segment is going to contain 20 bytes of header and 65515 bytes of data. Therefore the maximum payload that could be present in any transport layer packet segment is 65515. So how much the application layer should give? 65515 only, right? But at practice application layer can give any amount of data to transport layer, which means from application layer we can get any amount of data. Now it is the responsibility of transport layer to divide that packet given by the application layer into parts, so that each part will come and sit here. So what is the maximum amount of data that could sit in this space is 65495 bytes. Okay, so understand it. The maximum datagram size is 65535. Then the maximum payload size inside a datagram is 65515. Then the total segment size in transport layer is going to be 65515. Then the total data that could be present inside the transport layer segment, the maximum data is 65495. So and if an application layer gives more than this amount of data, then it is the responsibility of transport layer to divide into parts and put it here. That is also called as segmentation. Therefore who will do segmentation? Transport layer. At transport layer the procedure called segmentation is done, right? And what about network layer? Now this packet will be given to network layer. Therefore network layer will take maximum load of 65515, and so that the total datagram will never cross a size of 65535. But then there is a problem. I told you that data link layer also has a limitation, that if you look at this Ethernet frame format, I told you that the maximum amount of data that could be present in any Ethernet frame is 1500 bytes. Which means even though this data link layer network layer's datagram is this much size, if the underlying LAN is, let us assume underlying LAN is Ethernet, then what is the maximum data? This is the header and this is the tail. If you remember it, Ethernet frame has header as well as tail, and now if I remove this header and tail, this let us assume is 1500 bytes only, which means Your network layer is giving you a packet of 65535 to data link layer, but then data link layer can hold a packet of size 1500 bytes only. The payload which can be present in Ethernet frame is 1500 bytes. It is just an assumption. Currently we don't have that much that limitation, but anyway this 1500 is not constant. It is going to vary from LAN to LAN. So now if it is 1500 bytes, then what should happen is the network layer should divide the datagram into parts so that each part can go and sit in this 1500 bytes. That procedure is called fragmentation. So clearly understand the difference here. Segmentation is done at transport layer, fragmentation is done at network layer. Why is segmentation done at transport layer? So that the subapplication layer data can come and sit here. Why is fragmentation done at network layer? So that the datagram can go happily in one data link layer frame. So we cannot send more than what a data link layer can carry. So in this case, both we are doing segmentation and fragmentation. And what is framing? Once the data link layer receives the the datagram which is already fragmented, it will take it and add it header and tail along with that preamble and ed, whatever all the required. That is called framing. So framing is done at data link layer, fragmentation is done at network layer, and segmentation is done at transport layer. Now there is a small problem here. See this? Always either network layer is going to be the bottleneck or data link layer is going to be bottleneck. Sometimes what happens is your underlying network, that is the data link layer frame, will be able to hold any amount of data, which means it will be able to hold more than what a network layer can send. In that case, fragmentation is not required. Then what is the bottleneck? Network layer, right? So at the same place or in the same host, if we don't want to do both segmentation as well as fragmentation, what should be done? The question is, doing segmentation one time and again fragmentation next time is a difficult thing, right? So can we do something better so that there is no need of these two divisions? It is obviously a headache at every host if I have to segment and then fragment, right? So what transport layer will do is, it will do something clever. Transport layer will find out what is the capacity of the network layer as well as what is the capacity of the data link layer. It will calculate who is the bottleneck, and accordingly, depending on who is the bottleneck, he will divide, the transport layer will divide the packet in such a way that it will directly go and sit into the data link layer frame without any problem. For example, in this case, bottleneck is data link layer, isn't it? Data link layer is saying that I cannot carry more than 1500 bytes, but network layer is saying that I can carry 65,000. Therefore, bottleneck is data link layer. Now what will transport layer do is, it will take this data link layer's MTU, it is also called as MTU, maximum transmittable unit. The maximum amount of data that a data link layer frame can carry is called MTU, maximum transmittable unit. Okay, maximum transmittable unit. Now transport layer will take that as a constraint and it will do something like this. At data link layer, we know that the maximum size that it will allow is 1500 bytes. Therefore, what will be the maximum datagram size that could sit in this space? 1500 bytes datagram, isn't it? Therefore, 20 bytes if you remove out for the header, every datagram should contain the header and data, right? So what is the maximum payload of a datagram? 1480 is the maximum payload. Now who will sit in this datagram? A segment from transport layer. So from transport layer, if you remove 20 bytes of header, what will be remaining? 1460 bytes of data. So now see this. So how did we get this? We know that the bottleneck is this bottleneck is data link layer frame. So from this I got how much datagram can I put there, and from this datagram I got how much segment can I put there, and from this segment I got that finally how much is the maximum data that a segment could carry. Therefore, if the transport layer could take this application layer data and divide it in such a way that every part is 1460 and put 1460 here, then there is no need of fragmentation again, because if every segment coming from upper layer is 1480, then that will directly go into one segment, isn't it, one datagram, and now that one datagram can directly go and sit here, just one phase, right? Therefore, if transport layer takes into consideration both of these sizes and apply the segmentation wisely, then there is no need of fragmentation. Therefore, segmentation is done at transport layer wisely in such a way that there is no need of fragmentation. So keep it in mind, at a host, at the sender, segmentation is done, not the fragmentation. Then where is the fragmentation done? That is an interesting question. So let's see where the fragmentation has to be done. Let's see the concept of broadcasting. I told you that at IP, when we are discussing about IP numbers, there is a concept called broadcasting, and there are two addresses, directed broadcast address and limited broadcast address. So at IP we have seen something like this. So 255.255.255.255. This is nothing but limited broadcast address, I told you. And the one more broadcasting address which you have seen at data link layer is like this, all ones in the MAC address, 6 bytes of all ones. This is a MAC address which is all ones, and this is IP address which is all ones, right? Along with that we have a concept called as directed broadcasting. If the network is, let us assume 11 is the network, 11.0.0.0. I told you that one more address is 11.255.255.255. Now how does all of these work together? Now there is broadcasting at IP addresses, which means at network layer, and there is broadcasting at MAC addresses, which means at data link layer. So how are all these broadcasting addresses working together, and how is the concept of broadcasting implemented? That is what I want to explain you now. So in this video we shall see the concept of broadcasting. So let us assume that there is a network like this, and this can be easily generated, generalized to any type of LAN. It need not be only this LAN. It can be easily generalized to any type of LAN. Either I'm going to take this bus topology of Ethernet and I'm going to explain you, and the same concept can be generalized even to the token ring and any other LAN in general. Okay, so assume that there is a station here A, and there are all these stations connected to this. Now A wants to send a broadcast message to everyone in the same network. That concept is called as limited broadcasting. If you want to send everyone a message in the same network, that is called limited broadcasting. If you want to send a message to everyone in a different network, that is called directed broadcasting, right? So let us assume that this is station A, and now it has all the layers: physical layer, data link layer, network layer, transport layer, and application layer. Now A has a message to send to everyone. So the message will start from here, and at transport layer it will have port numbers. Actually port numbers are of no significance here, but still assume that there is a port number X and Y. Port numbers are not generally used. Generally what happens is, in case of broadcasting, we don't send a message to any process, we just send the message to the all the hosts, right? So even though I'm putting some port numbers here, no one is actually waiting for it. And now at network layer, this message has to be given to everyone, right? So at network layer, at source IP, let us assume that IP address of A is IA. At source IP we are going to write as IP address of A. This is source IP address, right? And at the destination IP address, the destination IP address is, I want to send this message to everyone in the same network, which is nothing but limited broadcasting. Therefore destination IP address is going to be limited broadcast address, which means 255.255.255.255 limited broadcasting address, right? and this will be given to data link layer. Now data link layer is going to take this message, and now it will understand that, oh, the message has to be sent to everyone. Therefore it is going to add the MAC address like this. The MAC address, source MAC address, is going to be MAC address of A, which it already knows, MAC address of A, but in the destination MAC address it is going to put all F's, right? So now understand the relation. This is the destination MAC address. Destination MAC address. So if any station wants to send a message to everyone in the same network, if the message is coming from application layer, then in that case, in the network layer, the destination IP address is going to be all ones, that is limited broadcast address. And whenever any station wants to send this message, then the corresponding MAC address, the destination MAC address, is going to be all ones, right? Now this message will be given to physical layer, and now the physical layer is going to take this message and put it in the waves, and and that wave forms, and it is going to send it. According to the rules of networking, whenever any packet is sent out with destination MAC address as all ones, it is also called as broadcasting address, isn't it? I told you that MAC address is of two types: unicast, multicast, and broadcast. Therefore it is also called as broadcasting address. So if anyone is going to send a message like this, then obviously this message has to be received by everyone. According to the rules of networking, every station is configured in such a way that they should definitely accept this message. Which message? All ones, right? So this is also called as limited broadcasting. So now how is limited broadcasting implemented? The corresponding network layer broadcasting is converted to the broadcasting at data link layer. Now this packet will be seen by everyone and accepted, and every network is actually bounded by router. Router is kind of a boundary to the network. So where do you say that a network is going to end is whenever you hit the router. Now since it is a limited broadcasting packet, this packet is never supposed to escape the network boundaries. Therefore what the router will do is, router will see the packet, that broadcasting packet, this one, accept it, which means it will also read it, but then it will never forward it. Therefore any device which is bounding the network, which means any device which is having network layer, I told you that this router is going to have physical layer, data link layer, and network layer. So any device which has network layer can act as the network boundary. I mean, apart from the host, there is nothing but a router and gateway. Routers, gateways are going to bound the network, and whenever any broadcasting message is seen, router is not going to forward it, or router is not going to let it go by it, which means it will accept it but will never ever send it, which means it will discard it there itself. So according to the rules of networking, your broadcasting done at data link layer will never cross the network boundaries. Therefore in fact there is no broadcasting which is done at network layer. Even though it is a broadcasting at network layer, it has to be implemented with the support from broadcasting at data link layer. There is no real implementation of broadcasting at network layer. It is actually implemented as broadcasting at data link layer. Now think about how broadcasting is implemented. Directed broadcasting is implemented. This is limited broadcasting, which means you are sending a message to everyone in the same network. That is limited broadcasting. Now just think about how directed broadcasting is implemented. So how do you think directed broadcasting is implemented? Assume that we want to send a message from this host to all other hosts in some other network. Then here we are going to put, in case of this limited broadcasting address, in place of this we are going to put the directed broadcast address, right? And here it will not be broadcasted to the same network. Now whichever network you wanted to send, definitely that is not your own network, right? So depending on the network ID of this, either this part or this part or this part, depending on the network ID, this packet will be given to the router first, which means here the MAC address will be router's MAC address. Then router will take it and router will route the packet as if it is a normal unicast packet. So from here, from this router, the packet will go onto all the routers, and let us say this is the network to which you want to broadcast. Then what will this one do is, it will take that packet, this packet, whichever is having this directed broadcast address, then it will actually change the address to limited broadcasting address, where at the router which is connected to the network, to which you want to send the broadcasting. At this point, the directed broadcast address which you kept here is going to be converted to limited broadcast address, just like this. And now for the corresponding limited broadcasting packet, the MAC address is going to be converted like this. Therefore, again the packet will be sent to everyone in this network, and as I told you, this network will take, this entire network will get the packet and this router will discard it. Therefore, it will never ever escape it. So either it is directed broadcast or limited broadcast, IP is not going to support it, which means internet does not have the concept of broadcasting. Only LANs have the concept of broadcasting. How is that done? By using the broadcasting address which is at the MAC level. Either it is limited or directed, we are taking support from the DLL, right? So keep this in mind. There is no concept of broadcasting in internet. Why do you think that internet doesn't have the concept of broadcasting? If we allow broadcasting to be done in the internet, then every company like Coca-Cola and Lux and all this, they will just send a message saying that, please buy our products. That is the reason why we don't have broadcasting at internet. So we have to implement it as if it is broadcasting at data link layer, right? Okay. Let's see ARP, Address Resolution Protocol. This is a very popular protocol coming to GATE. They have asked about this many times. ARP, Address Resolution Protocol, right? The name itself says that it is going to resolve the address, right? In case if you don't want, you can actually skip this topic. I'm going to take this topic at a implementation level also, but for GATE it is not required at that level. Only question they will ask you is what is the purpose of ARP. So ARP, actually given a IP address, it is going to convert the IP address to MAC address, or if you don't know what the MAC address of a station is and if you know its IP address, then you are going to use ARP not to get the MAC address, right? So I'll just tell you where it is used and why it is required. If this is the network layer, that network layer, heart of the network layer is IP, and ARP is going to be present here. ARP and RARP will be at this level, ICMP and IGMP will be above IP. So what does this mean? An IP packet will go to ARP, and from ARP it will go to data link layer. That is the meaning of it, right? So let me tell you all the points about it. So first thing is, for GATE, simply put, this is the point, and let us go into the implementation. How a packet will be given to ARP and how is it going to see that packet and do something with it. So assume that there is a host A, and it is a router and there is a network in which all the stations are connected. All the stations are connected to the network, and now A wants to send a message to a host called B. So A wants to send a message to B. Then there are various conditions. One condition is B could be present in the same network, or B could be present in the other network. How will it find out? By using the network mask. I told you this many times in the previous videos also. So depending on the subnet mask, A will find out whether it is in the same network or the different network. For the time being, assume that B is present in the same network, which means B is some station here, and now A knows that it is also present, B is present in the same network. How will A know it? By looking at the subnet mask. By using the subnet mask, B came to know that A came to know that B is also present in the same network. Then in order to send a message to B, right, I told you in the example about this using all the layers, I told you that in order to send a message, it is going to come from network layer, data link layer and all this, and we are going to take this network layer datagram and we are going to put it in the frame, data link layer frame. At that data link layer frame, we are going to put the destination MAC address of the destination itself if it is present in the same network. If it is not present in the same network, then we are going to put the MAC address of the router, right? So here what happens is, I'll have a packet will come like this from the above layers and it will be given to IP. Now IP will give it to ARP. So a packet which has to go from A to B will come from all the layers at A to IP, and now IP will give it to ARP. ARP will give it to the data link layer frame. That is how it is done, right? So what is done is, at network layer, this is the packet datagram, and datagram will have source address and destination IP address. As source IP address is how much? IA, what is it, and destination IP address is, let us say, IB. Fine. Now this is the packet which is formed at the IP. Now IP will give it to ARP. Now ARP will decide if this is the IP address, then what is the MAC address it should send it to. So before giving this packet to data link layer in order to put it in a frame, ARP is going to decide if this is the MAC address, this is the IP address, then what should be the MAC address. So whenever you give this packet to ARP, before sending it, ARP is going to do something else. So now ARP wants what is the MAC address of B. So what ARP will do is, it will create a packet. It is called ARP request packet. In this request packet, it is going to say, see, I know your IP address is IB, but I don't know your MAC address. I don't know what your MAC address is. Please send the MAC address if you are in the same network. Then what will it do is, it will prepare this frame. In this frame, the source MAC address is MA. It is coming from station A, but we don't know what the destination MAC address is. That is why we are sending this message. We are sending this message so that we can find out the destination MAC address, right? So in the destination MAC address, we are going to put all ones. So this is called broadcasting. So ARP is nothing but broadcasting. Now this packet will be sent first. Whenever you are sending this broadcasting packet at data link layer, everyone is going to see it, but only the station whose IP address is IB, which means this B, is going to reply it. So what happens is, B will see it and B will prepare the reply. Yes, I got the packet and my IP address is IB and my MAC address is MB, and yes, I got your packet, take this reply. Now what will B do is, it will put in the destination MAC address and source MAC address, these two fields. Now for this data link layer frame, what is the source MAC? Source MAC is, it is coming from B, therefore MB. What is the destination MAC address? MA. How will B know that the destination MAC address is A? How will it know it? Because in the request packet is clearly written, I am coming from MA, therefore the destination MAC address will be MA. So the source is going to send a packet which is called broadcasting, or ARP request is actually a broadcasting packet and ARP reply is unicasting. Therefore that is how it found out that B's MAC address is IB, right? Sorry, MB. Now actual packet will be now kept in a frame. In this frame, the destination MAC address will be MB. How will it know it? Because it just got it, right? And the source MAC address will be MA. That is how it is done. So whenever any packet is given to IP, before IP gives it to data link layer, it will give it to ARP. Now ARP will find out what is the MAC address for that corresponding destination IP address, and along with that packet, ARP is going to give it to data link layer, which means along with the IP packet, ARP is also going to say, see, this is the MAC address. Now when that packet is given to data link layer has everything, all the information. What it needs is a packet from data and IP layer, and along with that the MAC address. So data link layer is not going to find out what is the destination MAC address. Who is going to do that for you? ARP. That is where ARP is. Between IP and data link layer, the ARP is going to work. So let's see now some important points about it. Let us assume that B is not in the same network. Then what happens? This frame has to be given to the router, isn't it? In that case, what ARP will do is, ARP will find out that the destination is not in the same network. How will it do it? Using the subnet mask. After that, after finding out that it is not in the same network, then it understands that the packet has to be given to router and router has to forward it. Therefore, instead of asking for the MAC address of B, it will now ask the MAC address of router, which means we already know that router is nothing but the default gateway, and we already have it. We already have the default gateway's IP address, where in your computer we have something called as default gateway's IP address. Let us say IR, you already have it. And now in this in whatever we have this packet, so in this packet, the request packet, instead of asking for the MAC address of IB, it will ask the MAC address of the router by sending it, and now router will respond saying that this is my MAC address. Then you are going to send the packet to router, then router will analyze the packet, the IP packet, and will forward it, right? So whatever it is, ARP is going to be useful there. So let's see some theory points about ARP. So first point is ARP request. ARP request is broadcasting, isn't it? Check this. ARP request is broadcasting. This is the ARP request, right? It is broadcasting. Second thing is ARP reply. ARP reply is unicast. ARP request is broadcast. ARP reply is unicast. Why? Because we know who is asking for the ARP, that request. Therefore, we only send the reply to them. ARP request is broadcast and reply is unicast. And then third thing is, what are the various cases in which we apply ARP? So one case is a host wants to find out the MAC address of a host, and the second case is a host wants to find out the MAC address of a router, and the third case is a router wants to find out the MAC address of a router. How? Let us assume that this is the host and this is the router, this is the router and this is the host. Now what happens is, host will find out the MAC address of a router and send it a packet, and this router will find out the MAC address of the router and send it a packet, and again this router will find out the MAC address of the host and send it a packet, which means what are various cases? Host will find out the MAC address of a host will find out the MAC address of a router will find out the MAC address of a router, as well as router can find out the MAC address of a host. These are the four cases where ARP is going to be applied. These are the four cases, right? These are all the points about ARP. So why is ARP used? To find out the MAC address of a destination, right? So even we can get into much more depth about it, but then it is not required for you. Whatever I explained is more than sufficient. So one point is ARP, since it is a broadcast request, it can never cross the network boundaries. Therefore, you can find out only the MAC address of the host which are present in the same network. Why? Because your request is never going to cross the network boundaries. Therefore, you cannot find out the MAC address of a host which is not present in the network. That is why I told you that if Google is not in your network, then you cannot find out the MAC address of the network, isn't it? And moreover, so you can only find out here, and moreover, even your MAC address will be dropped here. Whenever your data is going on like this, the frames will be discarded. So data will come in, that IP datagram will come into a frame, and now that frame will be here, and once that IP datagram is taken out, from here it will go in a new frame. Therefore, your source MAC address is also discarded at your network only. So if a source and destination are in different networks, source will never know what is the MAC address of the destination because you cannot get it, as well as the destination will never know what is the MAC address of the source. The reason is that packet is going to be, that MAC address packet, that frame is going to be discarded at the router. You please look at the example where I have shown you about how all the layers are implemented, right? In that example, I clearly explained how the frame is going on, and frame will be going on, and then the IP datagram will be taken out from it, and again it will be kept in a new frame, and again that new frame will go on. At a router, from the frame IP datagram will be taken out, and again in the new frame it will go, right? Therefore, the original frame which contains the MAC address of the source will be discarded at the router itself. So if destination and source both are present in different networks, they will never know the MAC address. Each one, source will never know the MAC address of the destination, as well as destination will never know the MAC address of the source, right? Then how can they trace you out? So if you do something wrong, then how can they trace you out? So first thing is, they will find out the router, and then they will come to your using your this IP address. They will find out the ISP. Now at ISP, the default gateway is going to have, this one, a list, which means it is going to have a mapping saying what is the IP address and what is the MAC address. So every gateway is going to save that information. So from what MAC address we got this packet at what time. Therefore, if someone finds out that you did some fraud, then what they do is they'll complain against your IP address. Then according to the IP address, your ISP will be traced out. Now if you go to the ISP, it will clearly tell say who is the MAC address, who is using this IP address at that particular time. So that is why it is illegal for you to change your MAC address. You could easily change your MAC address, but then it is illegal. If you got caught, then it will be a problem. Otherwise, that is how hackers will do everything. They will just change the MAC address. Okay, fine. Anyway, that is not in the curriculum. We are not going to talk about hacking. So just understand this ARP and all, right? Fine. In this video, I'll talk about a special address called 127. While discussing about class A, we discarded that 0 and 127. In class A, the valid IP addresses are from 1 to 126, if you remember it. And there I told you that 127 is not used because of some special reasons. Now we shall discuss why 127 is not used actually. So let us assume that you are connected here to the network, and here is a router and here is the destination, right? And you are sending, let us say you are here and here there is B, right? So let us say that you are sending a message to B, but B is not replying you for some reason. Then what could be wrong? I mean, where could be the error be? So how do you generally test whether your internet is working or not? I think you are not going to go to this terminal and then see your IP address setting and all this, right? So I think you are going to directly type www.google.com. So in case if Google is working, then it means that internet is working. If Google doesn't work, I think internet doesn't work for you, isn't it? Look at the way that company has built its reputation. So they built it such a way that if it is working, people are thinking that internet is working. If it doesn't work, people are thinking that internet is not working, isn't it? Even you are going to think the same way, right? Let's see how to test your internet connection and all once. So let us assume that you are here and B is here, and A is sending a message to B and B is not replying it. What could be wrong? So one thing is, what are all the points of failure? Let us assume that my website is in Singapore, right? So I hosted website in Singapore. Now let us say I'm trying to send some file to that website, but it is not replying. So what should I do? Should I directly go to Singapore and then in a flight and see if everything is working there, or should I start it from my end? Which means if B is not replying, what are various chances is, one is B could be down, or the network NIC card of B could be down, or the link could be down, or the router could be down, or the link could be down, or NIC of A could be down. These are all the points of failures. So what is the best place at which you should start probing? So one thing where you could start probing is at your end, which means see whether your NIC is working or not. If you have to see this, then what should be done is, you should send a packet, someone should send a packet to you, or if there is no one who could help you out, then you should send a packet to yourself, isn't it? Now if you send a packet to yourself and if you get it, then definitely your NIC is working. Nothing is wrong with the NIC. It is called testing self connectivity. So it is also called as testing self connectivity. Self connectivity means whether you are connected to yourself or not. Testing whether you are connected to yourself, right? So for this reason, you have to send a packet from A to A, which means both the source address and destination address should be A itself. Then what happens to such a packet is, whenever source address and destination address is A and A, then there are a lot of things which are going to be triggered internally, which means one thing is the packet will be sent to the router and then router will again send it back. Therefore it is going to be messed up. So for that reason they have dedicated one address which is 127. If you send out any packet with the address 127, then what happens is the packet will be like this. If you send out any packet with address as 127, the packet will go like this, and again it will come back like this without going on to the network, which means it will go till data link layer and again data link layer will send it. Now it will go till data link layer as if it is going on to the internet, and will come up as if it is coming from the internet. So whenever you send a packet with the destination IP address as 127, the packet will be sent by the sender, which is A, and received by the receiver, which is also A, but the packet will never appear on the network. It will be sent by the sender, received by the receiver, but you will never see such a packet on the network. If you want that to happen, then we are going to use the address 127. So whenever you put on any packet, the destination IP address as 127, then the packet is going to come back. That is how you are going to test the self connectivity. The command to test it is, you can open your terminal and you can type this ping. Ping is the command. So ping, let us say 127. Ping is a general command which is used to find out whether some destination host is working or not. Now you can test whether your host is working or not. How? 127 dot. So when you are using 127, you should not use two addresses. One is 127.0.0.0. This should not be used, and other is 127.255.255.255. The reason why these two are deleted is they have been deleted from use even before this 127 is used for this loopback addressing. Initially 127 was included in class A. Right, then what happened was, in a class A network, all zeros and all ones are not used. That is why we are not using these two numbers. Later they dedicated this 127 completely for this testing. So now ping 127 dot anything, if you do it, then the packet is going to go till the data link layer and again come back. Therefore using this you can test, you can use any other number 127.0.0.1. Using this you can test whether your NIC is working or not, and whether all the layers are working or not. You can even test all the layers also, like this, or you can even test NIC. So using this you can easily say whether your NIC is working or not. So how do you say it is? When you type this, you are supposed to see something called as RTT as 15 milliseconds or something like this. If you don't see anything like this, if you see something as timeout, then it definitely means that something is wrong there, which means either your NIC is wrong or some layers are not working. In that case, you should start troubleshooting at your end, right? So that is how you test your self connectivity. One advantage is self connectivity, and then there is one more advantage. Let's see it now. Since any packet with destination address as 127 is going to come back to the same host, it is also called as loop back address. Why? Because it is looping back, right? And one more advantage of using this 127 is, let us assume that you have written a web application, which means you have written a client and a server, the code, and now before making this server go online, before putting it up server on a host and then making it available to the internet, you just want to test it first, right? So before you do any website, let us say I built my website. So before making it online and then letting everyone know about it, and before giving the address to everyone, you should make sure that it works well on the field, right? So that is why you have to test it. So how are you going to test it? You should have a client, and then client should send a message to server and server should reply it back. That is called testing, right? But then it is no, if that is the case, then you might think that you should have one more host and you should actually put that here, right? So you might think that you should have one more host and you should put that client here and let the client go there and then send the message and then server come back, right? But then in practice, if you have to even test the load means if how the server is responding when you have lots of messages coming in, then it is going to be difficult. You are not going to find those many hosts in which you can run thousands of clients and then test the server. So for that case, we generally run the client and server in the same host and we test the server code, right? Now how could we do that? If I directly communicate with client to the server, then that is going to become inter-process communication. If it directly sends a message and gets the reply, for that you need not require anything from computer networks, isn't it? No support is needed from computer networking software. Already operating system is going to have a concept called as inter-process communication, IPC. Using that you could do everything. You need not actually depend on the computer network software. Now what is the functionality we need is, the client should send a message to server as if the message is coming from outside internet, not from the same host, and the server should reply to the client as if the message is going to outside internet, not from the not message is coming from outside internet, so they should behave as if they are in different hosts. For that reason we use 127. Again 127, the loopback address is used. The loopback address is used in order to test the client and server which are running in the same host, right? So how can we test it is, as a client, first let us assume that client wants to send a message to server. Then what will client do is, client will prepare the message and it will put the port numbers, which means at the transport layer port numbers will be added. Assume that the port number of client is 8080 and the port number of the server is 80, right? Then in the source port number it is going to put my port number is 8080. This is the source port number, right? And the destination port number is 80. I mean, there will be more fields at the transport layer, but the most important fields are this. That is why I am not showing you other fields, right? And now this one will be given to this IP, this network layer. Network layer is going to add the IP addresses, right? So at the IP addresses, the source IP is going to be same. Let us say the IP address of this one is IA. Then source IP address is going to be IA only, but in the destination address we are not going to say IA itself. The reason is we are not going to send a packet with the same source and destination address as equal. That is not allowed. There are various reasons for it, forget about it. But now if someone wants to send a message to itself, we should use a address of 127. So 127.0.0.1 is used here. Now when this message is sent from application layer, and this is added by transport layer, this is added by data link layer, this network layer. Now the network layer will give the packet to data link layer. Data link layer will simply return it back, right? It will take it and again return it back to the network layer. Now network layer is going to give it to the, again the data is going to come up, which means from application layer message started, transport layer, network layer, data link layer. From here the message started like this and again the message will start coming like this, right? So now the transport layer understands that the packet is coming from port number 8080 and the packet has to be given to port number 80. That is how the packet will come out like this and it will go to 80. And what is the layer it will hit? Data link layer. It will never go on to the network, right? And now for as a reply, what the server will do is, server will also prepare a message, and on that message it will say that source port number is 80, why server's port number is 80, and the server's the destination port number is 8080, and the IP address, interestingly, it is not 127, it is IA. Therefore source IP address, wherever it is actual IP address. Only the destination IP address is going to be 127 dot any number. It need not be 0.0.1, any number other than all zeros and all 255. Here also you can use any number, right? Then what happens is, again the message will come from application layer, transport layer, network layer, and again from here it will go up, right? Now when the message is coming from the same host and going to the same host, how will it identify which process to give? For that reason we are having the port numbers, so there is no confusion. Even though the source IP and destination IP is saying that the message has to go from the host to itself, we are having this port numbers to identify it. So what happens is, at this point, now the transport layer is going to give this here from the here the packet is going to come like this and then go to this. Now this is how we are going to see whether client and server softwares are working well or not. If we don't get any problem, then we could as well put directly the server on the internet, and anyone can contact it from internet and it will give the reply. Why? We already have tested it. Got it? In this video, let's see about this RARP, reverse ARP. So what is ARP? If you have the IP address and if you don't know the MAC address, then getting the MAC address from IP to MAC is ARP. Then what is RARP? MAC to IP, which means exactly reverse of ARP. If you remember it, in ARP I have written that if you know the IP address, it will convert it to MAC. Now here, if you know the MAC address, then it will convert it to IP, which means given the MAC address and if you don't know the IP address, you can use the RARP to get it, right? So let's see where it is useful. The main problem is many of the hosts, they don't have the hard disk. So let us assume that it is a company or your college, engineering college. then what happens is many of the hosts, they don't have the hard disk. So entire files, all the files are going to be saved on the central file server using NFS, right? So you could actually sit on any computer. Maybe you might have seen this. So in your laboratory, sometimes you will sit in one computer and sometimes you will sit on other computer, and when you give your credentials, username and password, whatever work you previously saved on other computer is going to appear here magically, right? It doesn't mean that your information is going to be saved on all the computers. The concept is, actual computers, they need not have, or they might not have, the hard disk. The entire data will be stored on a central server called network file server, and from there, whenever you want a file will be retrieved. Nothing will be stored on all the other clients. So network file server is going to save everything. Therefore, there is no need of hard disk, isn't it? Now, without a hard disk, the computer cannot remember anything for long time, or whenever you turn it off and turn it on, everything will be vanished, which means you can compare every host here or every client here to Gajini, right? In Gajini, what happened? So no one remembers, the hero doesn't remember anything, right? So what he could remember is either the pictures or whatever he is written in his body as a tattoo, right? Similarly here also, no station will remember anything. What they will remember is whatever is written on the tattoo if the computer is turned off. What is tattoo here? The ROM, right? Read only memory. So whatever is present on the ROM, they will remember it. Now I told you that MAC address or the physical address will be typed on NIC, right? It will be present in the ROM of NIC, which means MAC address is going to be permanent. But then if you look at IP address will not be present on ROM, it will be present in RAM, isn't it? It is a software number which is not permanent. And whenever you turn off a computer, there is nowhere your computer could save that IP address, like it doesn't have any hard disk to save it. Therefore, this will be lost. That is the problem. Now whenever you turn off a computer and again turn it on, by that time it will forget everything. Or the other scenario is, everyone is going to have this hard disk, but then a computer is newly connected to the network, then it doesn't know what its IP is. So whatever the case, a computer doesn't know what its own IP address is, but then it knows its MAC address. Why? MAC address is already present on the NIC. Then how does a host get its IP address if it doesn't know its IP address, if it knows only its MAC address? That is the main question. Let us assume that this is the host A and it doesn't have the IP address and it wants to get the IP address. Then for that reason, it is going to use the protocol RARP. In the network layer, IP is going to be here, heart of it, and here ARP and RARP will be present. RARP, which means RARP is below IP, and RARP doesn't take any support from IP, nor IP will take the support from RARP, which means they are not independent on each other. Actually, IP will take support from ARP in order to send a packet, but it doesn't talk anything with the RARP. So only purpose of RARP is it has to fetch the IP address of the computer and configure it, right? So how does this RARP work is, now if A doesn't know whom to ask, right? So there will be a central server called as RARP server, right? The main purpose of this server is to remember about what is the IP address given to what MAC, which means it will have a table called as mapping table. In that mapping table, it will have the mapping. If so and so is the MAC address, what is its IP address, like this. If MAC address is M1, what is its IP address? If MAC address is M2, what is its IP address, like this, right? So this table is maintained by RARP server. So if a station A forgot its IP address, it is supposed to ask RARP server to remind its or to tell its IP address, right? But then the problem is, how can this RARP, let us say this network is bounded here, but then the problem is, how can this A know who is RARP? That is the problem. So what happens is, this A is going to have all the layers, right? Physical layer, data link layer, network layer, transport layer, and application layer. And RARP is present in network layer here, right? Therefore, at network layer, a RARP packet will be request packet will be produced. It is nothing but RARP request. RARP request. So in this packet there will be many things, but most important thing is what is its MAC address and it wants its IP. Therefore, it will say, see, my MAC address is MA and I don't know my IP address. Therefore, I am writing 0.0.0.0. I told you that 0.0.0.0 is a I don't know my IP address, which means it is saying that my MAC address is this, but I don't know my IP address. If anyone in this network knows about it, please tell me, which means this packet will be given to data link layer. Now the data link layer has to take this packet and it has to put in the frame, right? Source MAC address is MA, it knows only the MAC address, but now the destination MAC address should be the MAC address of the RARP server, isn't it? But then we don't know the MAC address of RARP server, so we have to, if we don't know whom to ask, the concept is we broadcast. Therefore, here I am going to say F, we are going to broadcast. Right? This is called broadcasting at data link layer. Therefore, this packet will be seen by everyone in the network, but then everyone will understand that, oh, this is a RARP request, and so only RARP server is supposed to reply it, right? And RARP server will search in its table, this mapping table, and it is going to reply it. So one important point here is data link layer or A wants to ask the IP address from RARP server, right? Then it is broadcasting. Why can't it at least remember MAC address of RARP server so that it could get the address? If A could remember the MAC address of the RARP server, it could have remembered its own IP address, isn't it? Then the entire problem would have solved then and there. The entire problem is arising because we don't want to remember anything. We want to get it on the go. That is the reason, right? So we are not remembering anything, right? So who is going to reply? RARP server is going to reply saying that yes, this is the MAC address, please take it. Which means RARP server is going to make a reply packet. It is RARP reply. It will say from its mapping table, let us say there is an entry MAIA, which means MAC address of MA has been associated with IP address IA. So it is going to put, see, yes, I got your request, you are asking for your IP address, and in my table your IP address is showing as IA, so you can please use it. That is the meaning of it, right? And now this packet will be sent from RARP and it has to be sent to A, right? Now the reply is unicast. Why is the reply unicast? Is we know who is asking it, isn't it? So we know that A is asking it because in the request packet it is clearly saying it, therefore it is going to get it. So that is how the A will come to know about its IP address. Now few things you have to note here is RARP is actually running at network layer, which means there is nothing called a server which is running at application layer. RARP works at network layer. So at the RARP server, even though I am calling it as a server, it need not have the application layer. It is simply a device which will take all the broadcasting packets and analyze it, and in case if it is having a request packet, then in the table it is going to see it and send it. So there is nothing called a concept of server or anything. It is just running at network layer. And RARP is used long back in 1980s. Right now no one is using RARP. It is obsolete. But still it is worth discussing about it so that we can understand the next concepts well. Now one thing we understood is RARP request is broadcasting message. Therefore whenever you do any broadcasting at data link layer, that will never cross the network boundaries, which means if RARP server is inside the same network, you will get the reply. In case if the RARP is not in the same network, you will not get any reply. Let us say in your company you have 4 networks like this. One network is here, another network is here, various stations are connected, right? So in this case, if you have more than one network, there is no way the stations in this network could ever communicate with RARP server here. The reason is, even if they send the broadcasting RARP request, that will be discarded by the router. It will never be forwarded. So the main disadvantage of RARP server is, if there are n networks, 4 networks, in every network I need RARP server. which means in every network I need RARP server. Someone has to be represented as RARP server, right? Now what is the problem with this? I have these many RARP servers, and every RARP server is going to have a database, the table, right? Mapping table. Now the problem with this mapping table is, now the entire information is not at one place, it is distributed. And whenever we have a distributed database system, there are going to be various errors with updations. Sometimes what happens is, by mistake, you might assign one IP address here and you might assign the same IP address here. Then automatically two stations are going to get the same IP address. That is IP address conflict, right? So there are going to be various problems because of this distributed data system, right? And the other disadvantage of RARP server is, if you look at the mapping table, it is static. Static means a MAC address is assigned to an IP address forever. So what is the problem with this static mapping is, if I have 100 stations, I should have 100 IP addresses, even if they are using them or not. Let's consider this scenario. Let us say you have an office, and in your office there are 100 computers, but at any time 50 people work in the day shift and 50 people work in the night shift. But still, according to RARP, it says that even though only 50 people are going to be online at any time, every station should be given a IP address statically. So either they use it or don't use it, I don't care, right? At any time only 50 people are going to be online, but still 100 IP addresses are required. That is the problem with this static mapping table, right? So RARP, the two disadvantages of RARP server are, one is many RARP servers are required for every network, which means every network should have a RARP server, right? And the second disadvantage is the mapping table is static, isn't it? So static mapping table, right? What is the problem with the static mapping table? The number of IP addresses required should be greater than or equal to number of hosts, which means number of MAC addresses. So for every host there should be IP address. So even though if the host, even though all the IP addresses are being used by hosts or not, irrespective of their usage, everyone should be given an IP address, even though they are not going to be online, right? So these are the two disadvantages of RARP server. And why do you think that the every network should have RARP server is? The reason is, RARP request is a broadcasting a data link layer, and that cannot cross the network boundaries. Therefore every network is supposed to have its own RARP server, right? And the second one is, the mapping table is static, so which means you are going to update it manually once and everyone is going to use it many times, right? So it is actually obsolete, which means it is not used now, it has been used long back. And now we are moving on to the next protocols. BOOTP and DHCP are currently used. Let's discuss about BOOTP and DHCP. Let's now see a very important protocol, ICMP. And ICMP is very important coming to gate, as well as you know to understand some concepts of computer networks. The layer at which this ICMP works is a network layer. So if you look at this, let us assume that this is a network layer. The heart of network layer is IP, you know that, and now ICMP is present here. Therefore ICMP packets will go in IP packets, which means ICMP will take the support of IP in order to send the packets, right? So every ICMP packet will go in IP packet. And now why it is mainly used is, and ICMP means Internet Control Message Protocol, Internet Control Message Protocol, and it is used in two ways. One is error handling and other is request and reply. Error handling or feedback messaging means whenever something is wrong, then only you are going to get a ICMP packet. That type of ICMP is called as error handling. And what is request and reply is, you can initiate a ICMP message from sender and you will get a reply, which means both directions the ICMP will flow. Which means here, let us assume that source is here, router and destination. Now in this case, how does this ICMP work is, in case if your packet is discarded either at the router, either at the receiver or at the router, you are going to get back ICMP one way direction. And in the other case, if you have source, router and the receiver, how does this request and reply work is, you can send a request packet of ICMP and you will get a reply packet of ICMP either from the receiver or from the routers, right? So you can send if you want some information, then you can send a request packet and you will get the reply packet, right? Either from the routers or from the receiver. Anyway, this entire protocol works at network layer. Now let's see about each one. First let us discuss about this error handling, and then we shall go to request and reply. And once I discuss about this error handling, I'll go in this order. So what I would like you to do is we'll just zoom in into this, and you just pause the video and write this entire thing down so that it will be there in your notes later, right? Please write it down. I'll just pause by pausing it and copy it. Then we shall discuss about each one by one, so that we'll understand better the bigger picture and then where we are, right? Okay. Now coming to this error handling methods, which means ICMP is whenever something is wrong, ICMP is going to send you a error message, right? So I told you that IP is a datagram service which is unreliable. Unreliable means anything can go wrong and you are not you cannot find out that something has gone wrong. It is like this: you are sending a postal letter, and if the postal letter is not received by the destination, you will not even know about it, right? But now I'm saying that IP has an assistant called as ICMP, and whenever any IP packet is lost or discarded, ICMP is going to respond and he is going to send you back the feedback, right? That is error handling. But now there is a router R1, there is a router R2, and there is a router R3, something like this, and there is destination. And the most popular reason why a packet will be discarded is because of the congestion. Congestion means a router is already busy, it doesn't have any space to take in more packets, and you are sending more packets. That is why it is discarding it. So assume that your IP packet is going like this, and it's going like this, and it is here, and now your IP packet is discarded, right? So as a courtesy, anyone who discards your IP packet is supposed to send the ICMP packet to the source saying that I discarded it. That is just a courtesy, right? Not a rule, right? Now what this router do is, it will start sending a ICMP packet. And who is the sender for this ICMP packet? R3. And who is the destination? Yes, the source, isn't it? Now when this ICMP packet is being sent, because of high congestion at R2, assume that this ICMP packet is again discarded. Now this is discarded, right? Now what will R2 do? R2 will say that I have discarded your packet. Now who is the source of this ICMP packet? R3. Therefore whenever, and again ICMP is also present in IP packet, isn't it? Therefore whenever this R2 discards this ICMP packet, it should again send the ICMP packet to R3. The reason is the source of this ICMP packet is R3. Therefore an ICMP packet will be sent from R2 to R3 saying that I discard your packet. What is the reason? Because of congestion, right? Now you have sent a packet. See, initially packet has been discarded by R3, and now ICMP is sent inside IP packet, and now even that IP packet is discarded by R2, and now R2 is sending a ICMP packet again in the IP packet saying that I discard your packet. Now let us say because of huge congestion, this discards this particular packet. Then again one more ICMP packet has to be sent. From whom to whom? From ICMP has to be sent from R3 to R2 saying that I discard your ICMP packet. Now if this packet is discarded by R2, then again it will send the ICMP packet saying that I discarded. Isn't it? It is from R2 to R3. Now just assume, see what is happening here. Now a packet is lost, and if the feedback message is also being lost, and if you want that feedbacking to be reliable, then you should even send a ICMP packet when the ICMP packet is discarded. If you allow that, there will be an infinite loop and everything will come to halt only because of this heavy traffic. That is why the first rule is, whenever any IP packet is discarded initially, ICMP packet will be generated, and whenever ICMP is discarded, which means inside the IP packet, even if there is ICMP packet, and if that ICMP packet is discarded, no ICMP should be ever generated. So understand this. So whenever IP packet is discarded, ICMP will be generated. But if ICMP packet is discarded, no ICMP packet should be generated, otherwise we might fall in infinite loop. That is why even though IP is having the assistant ICMP, still the entire package together is unreliable, which means IP combined with ICMP is still unreliable. The reason is I know for ICMP packet, ICMP is not generated, so IP is still unreliable, so I cannot call it as reliable protocol. So one reason is there is no ICMP generated for ICMP, and other reason is even if the ICMP is there is no guarantee that it will be reaching the other side. So this is the reason why IP is still unreliable, and most of the cases ICMP packets will be discarded by the routers because they are just considered as useless, right? So there is no guarantee that if a packet is discarded you will ever get the ICMP back, right? Now let's see what are the various types of error messages that ICMP will send. Let's see the first ICMP error control message type, TTL exceed. TTL exceed. So you already know about TTL, right? Time to live. Then what happens is whenever the time to live hits 0 at a router or at any station which is having network layer, and if the packet is not at the destination, that station is supposed to discard the packet, and it is generally a courtesy that you send back a message saying that I discard your packet. So as a sender, if the TTL here for a packet is, let us assume that 2, then what happens is the packet will be sent here to the router R1, and now the TTL will be from 2, it will be reduced to 1, and the packet will be sent to the router R2. Here the TTL equal to 1, it will be reduced to 0, and the packet will be discarded. So whenever any packet is discarded at a router, it is supposed to send a ICMP packet, right? And now on this ICMP packet, the type of the ICMP packet will be TTL exceed. So if the sender, in case if he receives it, there is no guarantee that sender is going to receive it. In case if the sender is going to receive that, your IP packet is discarded because of the TTL exceed, then what the sender could do is, sender might increment the TTL and send it, or he can understand that the packet is getting involved in a circular loop. If the TTL is already set more than 32 and still you are getting time to exceed message, it means that the packet is involved in a loop, and there are various troubleshooting methods that are used later, right? So anyways, the main intention of this packet is to inform back that the time to live has been exceeded, and this is the reason why we discarded the packet. And there is no guarantee that this packet ICMP is going to be received by the destination, the sender. In case if it doesn't find out the network layer, then anyways we have the transport layer. Transport layer will find out. Why? There is end-to-end acknowledgement, right? If a packet is discarded, transport layer will not get any acknowledgement. Then transport layer will initiate retransmission, not the network layer. Got it? Next ICMP is source quench. So literal meaning of quench means stop. So whenever the feeling is very severe or whenever the condition is very extreme, then stopping is abruptly stopping, which means stop it immediately. Generally it is used like quench the thirst or quench the fire. If there is fire, we want to quench it, right? Or thirst, quench it. So generally the source quench is used in that meaning, that is literal meaning, right? So what is the source quench here is, at any point, either a router or a destination, someone is going to act as a receiver, isn't it? So let us assume that there is a router here and this network connected, and this router is sending lots of packets to this router, and the router is not, and this R1 is sending lots of packets to R2, and R2 is not able to handle all those packets. Then what could R2 say is, quench, you please quench, I am not able to handle all the packets that you are sending. That is called as source quench. So source quench means stop, I cannot handle it. So whenever R2 says ICMP type as source quench, then R1 is supposed to stop. R1 is supposed to find alternate routes, or it is going to slow down its transmission, right? That is about source quenching. Let's see the parameter problem ICMP packet. So if I have what is parameter problem is parameter problem. So when you are sending this IP datagram, some of the parameters in the header might get changed or might get corrupted. So for example, there is a source, there is a router, let us say this router is R1, this router is R2, and this router is R3, and there is a destination. So assume that you are using source routing, so strict source routing. What is strict source routing? On the packet you are going to put the entire route, and your packet should not stray away from that route, right? So you are going to say that your packet should take the path R1, then R2, then it should go to the destination. Now this packet will be sent to R1, right? And now R1 should send it to R2 only, right? Because it is a strict source routing. Because of some problem, either this link is down or the router is down, then R1 cannot send it to R2, it has to send it through R3 only, right? But then your parameters are saying that you should not send it. So in that case, this router is going to discard the packet and is going to send a packet saying that parameter problem. Because of your parameters, I am not able to send the packet. And other thing is, if the IP datagram is having the header, and if some fields of the header got corrupted, that the checksum is not valid. If the checksum is not valid, then also it will say that parameters got corrupted, which is nothing but parameter problem. So this is one other ICMP type, which is also a error type of ICMP, right? Next ICMP type is destination unreachable. Destination unreachable. So what does it mean? The destination is not reachable, therefore we are not able to deliver the message, right? And how will you find out the destination is unreachable, or who will send the messages? Assume this, there is a sender here and there is a router, and now there is destination, right? So what happens is, in general, a packet will be sent from this sender to router R1 and to R2. Let us assume that the packet is at R2. Then what will R2 do is, whenever it receives any IP packet for the destination D, it will first send out the ARP request. And when it sends out the ARP request asking that, see, I have a IP address, let us say ID, and I don't know your MAC address, you please send me your MAC address so that I will deliver your packet. Then if this station is down, if the host is down, it will not listen or it will not get back any reply, which means it is asking whether, please give me your MAC address, I want to give you deliver a packet. But then this router will not get any reply. What does that mean? The destination IP address is actually in the network, but the destination is down, right? At that point, what should this router R2 do with that packet? See, the packet is starting from source and it has come all the way like this, and now the packet is with the R2, and this datagram, this IP packet which is with R2, it has to deliver it to the destination, but then destination is not responding. It is like this: your post office, your postman has got the post, but then your house is locked and there is no post box also, let's assume that. Then is he going to carry that letter throughout his life? Right, isn't it? He is not going to carry it, he is going to discard it, right? Even the post office, they will discard the letters where the destination is not found. So similarly here also, the router, they should not save the message forever. If they keep on saving all the messages which are for the destinations which are not unreachable, then over a period of time lots of such messages will get accumulated. It is going to be overhead, right? Therefore the message will be, IP packet will be discarded at R2 and an ICMP packet will be sent back. And that ICMP will contain the message as destination host unreachable, which means there are two types of destination unreachables. One is destination host unreachable and other is destination port unreachable, destination port unreachable. So this is one condition where we get this one, and the other condition is, let us assume that the host is present, the D is present, right? And now the message has to be delivered to a process with port number 80. Let us say the packet is taken, it is available, and now the packet is sent to the host. Now packet is with the host. Now the host has to give it to the process with port number 80, but assume that there is no process in this with port number 80, which means the packet is received by the host, but then the receiver, actual receiver, that port number is not there. It is like this. You got a letter, and now letter has reached till the home. It is a registered post, and now it has to be delivered to the exact person, not to the home, right? Then what happens if the person is not there? Then no one should take the message. It should be discarded. So what happens here is the packet is received by the host, but then the required process is not there, or the port number is not there. Then this packet will be discarded by the host itself. In this case, host is going to send a ICMP packet saying that destination port unreachable. This ICMP will contain this. So whenever you have destination unreachable, there are two types of destination unreachables. One destination unreachable is the destination host is unreachable, which means the host is down, and the other unreachable message is the destination port is unreachable, which means the destination host is working, but the process is not there to which you want to communicate, and these two are different. One is generated by the router. So router generally says destination is unreachable, destination host is unreachable, and the destination machine that cannot say that destination host is unreachable. Why? It is reached, and you should only say that destination process is unreachable or destination port is unreachable. Therefore it is of two types. It is very important, and we shall again discuss it later when I talk about trace route. I'll discuss it there, but for now understand that there are two types of it, right? So in case of ICMP error messaging or feedback, whenever a packet is discarded by the router or by the destination, what are the various things that the sender must be knowing? So in the sense, if sender gets ICMP packet, there are various types of ICMP, right? Till now we have discussed that there are various types of ICMP, and now when a packet comes back, ICMP packet comes back, what is that the sender should definitely know? So assume that there is a sender here, there is a router, and somewhere there is a destination, okay, and this router is R1, R2. The IP datagram is starting from here, and on the IP datagram it is having source IP address as IS and destination IP address as ID. Now the packet is sent from here to here, and now the packet is sent from here to here. Let us assume at this point, because of congestion or because of some reason, this router has discarded the packet, right? Then it is going to send back the ICMP, right? So how will this router which discarded the packet knows whom to send the ICMP? By looking at the source IP address. By looking at the source IP address of the datagram that is discarded, the router R2 will find out that, oh, I have to send the ICMP packet to yes. So from here it will find it out. Therefore it is going to prepare this. So before telling about this, what are the various things that the sender should know whenever a packet is discarded? If its packet is on the way and if it is discarded by a router, what are the various things that we should inform the sender? So one thing we should inform the sender is who discarded it, isn't it? I mean, there are various nodes on the network. Who is the node really responsible for this discarding? And second thing we should be knowing is why did you discard my packet, right? And the third thing you should be knowing is what packet did you discard. So you have to answer all these things: who discarded it, why it got discarded, and what is the packet that you have discarded, right? So your ICMP that has to go from this router to the source has to answer these three questions, right? So first thing is, I told you that every ICMP packet travels in a IP packet. Therefore this is the IP packet that will be created first, isn't it? See, for this packet, now this packet is with you. This packet is actually discarded. This packet is going from IS to ID, and assume that this is the IP header and this is the IP data. This is the packet which got discarded, right? And now as a result, one more IP packet is going to start from the router to the source, right? So here we are going to say the packet has to be sent to IS. How will the router know that it has to send the IP packet to ICMP packet to S? Because the packet which got discarded is having IS, that is how. And where is the source? Who discarded? IR2. Therefore here it is going to have IR2. So using this field you can know who discarded it, isn't it? Because now the source of the ICMP packet is nothing but the node which discarded the packet. So you got who discarded it. Next, what you should know, next thing you should be knowing is why did you discard it. So in order to know that, inside this IP packet there will be an ICMP packet. Okay, so this entire thing is IP datagram and this entire thing is ICMP packet inside the IP, right? Now inside the IP there is a head, ICMP there is a header, and on the header there is a field called as type. There is a field called as type. This type will contain the type of the error message. For example, if it is destination unreachable, then that will have a number. Depending on the number that is present on the ICMP packet, you can understand what is the type. So this field is going to say why did we discard it, right? And now what is the last question we are interested in? What is the packet that got discarded? So it is going to be violent now. See, already we killed some person here, and now we are going to say that I killed this person. Now they are asking whom did you kill? Then this router is going to do something really violent here. So whenever it is going to remove the head of the person who got killed, which means head of the person who got killed. So the packet which got discarded, from that packet it will take the header and it will place it here. It will place the entire header, IP header of the packet which is discarded. Along with that, it is going to put 8 bytes of data from the packet, the neck also, which means in the packet which you discarded, along with the header, we are going to put 8 bytes of data. The reason why we put even the 8 bytes of data from the IP datagram into this ICMP packet, ICMP body is, if you look at it, inside the IP packet, let us say this is the IP packet, inside the IP packet there is TCP packet. The first type, generally the most commonly used is TCP packet. In TCP packet, the first 8 bytes are nothing but source port, destination port and sequence numbers. You can look at this TCP in the topic TCP, but for now just keep it simple. Now along with the IP header, we are going to remove the first 8 bytes of IP data, which is generally the TCP header, and the first 8 bytes of TCP header is source port, destination port and sequence number. Therefore, whenever this entire data is delivered to the source can understand who discarded it, why it discarded it, and it can also understand what packet got discarded. Why? Because on the IP header you have something called as identification number. Along with that, the source network layer can also find out that so and so port number got discarded, and can inform the TCP saying that see, the packet coming from this port got discarded, so you please better retransmit. That is why we are even sending 8 bytes of data. Anyway, it is not always true that the first 8 bytes of data in the network layer is always a TCP header. Why? Because IP packet can carry either ICMP or IGMP or UDP or TCP. Anyway, for ICMP, I know no packet is going to be generated, but it could be TCP or UDP most of the cases, right? So in case of TCP, these 8 bytes are going to be useful, otherwise they are just useless. Anyway, we are going to send 8 bytes along with this, right? So now this part is going to indicate what is the packet that got discarded. So from the source IP address on the IP packet, we are going to indicate, and we are going to know who discarded it. From the type of ICMP packet, we are going to know why it got discarded, and from the inside the ICMP, from the IP packet, we can know what is the packet that got discarded, right? Therefore, all the 3 questions have been answered, right? That is what the source wants to know, and that is what we have answered. And one thing you should just if it is confusing, what has really happened is, see, one IP packet is going on that got discarded. As a response, one more IP packet is created. On that IP, in that IP packet, ICMP is kept. In that ICMP packet, whatever is discarded, the header is kept. That is what has happened here. So one IP packet is discarded, for that one more IP packet is created. Inside that IP there is ICMP, and inside that ICMP whichever packet got discarded, its header is kept. That is the concept, right? And few important things that you should remember is ICMP is never generated for a ICMP packet, which means if a packet is discarded and if the discarded packet is ICMP, we are never going to send one more ICMP packet. I already discussed about it. And second point is only for TCP, both for TCP and UDP, ICMP packets will be generated. So ICMP packet will be generated both for TCP as well as UDP packet. Either a TCP packet is discarded, which means inside the IP datagram, if TCP is present, then also ICMP is generated, or inside the IP packet, if UDP is present, then also ICMP will be generated. Keep that in mind. And next point is in case of fragmentation, which means if you have applied fragmentation and if the original datagram has many fragments, then ICMP will be generated only for the first fragment. ICMP will not be generated for all the remaining fragments. The reason is simple. It is waste of time. If you have 100 packets, 100 fragments going on and all the fragments are discarded, or the first fragment is discarded, anyway you are supposed to retransmit the entire datagram. Either one or everything is discarded. In that case, why to tell 100 times that this fragment is discarded? Just say that the first fragment is discarded. It is enough that the receiver will again send the sender will again send the entire one. Which means if the entire datagram is fragmented into many parts, only one ICMP will be generated for the first one, and for all the remaining ICMP will not be generated. In case if the first one is not discarded, second one is not discarded, third one is discarded, then also ICMP packet will not be generated. ICMP will be generated only for the first fragment, which means the fragment with offset equal to 0. If the offset is not equal to 0, it means it is not the first fragment, then ICMP will not be generated. So in case if the fragment is lost, sender will never be informed. Only if the starting fragment is lost, sender will be informed, right? Anyway, it is unreliable. ICMP is unreliable, which means if any packet is lost, there is no guarantee that you will always get the ICMP packet. The reason is even ICMP packet may be discarded, right? So this is how, by looking at the ICMP packet, a sender can find out what is wrong, where it has gone wrong, and which packet got discarded, right? This is all about ICMP error handling. Routing algorithms are of various types. The basic two types are like this. Routing algorithms. The basic two types of routing, you know what is routing algorithm, right? The process of preparing the routing tables is called routing algorithms, and the algorithms which are used are called routing algorithms, okay? So one is static, one type of routing algorithm is static, and other type of routing algorithm is dynamic. So static routing algorithms means if the routing algorithms are manually prepared and uploaded offline, which means if there is someone in the world, central entity, who can know about all the routers in the world, like this, all the routers, and if he can draw this central picture in his computer or somewhere, and if he can compute the shortest paths and he can compute the routing tables at every router and upload them offline manually, then it is called static. Static means manually it is done. Now what is the problem is there is no such entity who can record or who can keep track of all the routers in the world, because every day one router will come up and one router will go down, right? Which means we don't know how many routers are there and how they come up. There is no control, actually there is no central organization which controls, and because of this manual method, obviously the problem is if anything changes, if the topology changes, which means if a router is down or a link is down, then we have to again do manual updation, or if the traffic on one link changes, then we have to change the traffic to other link, which means we have to send the packets to other link. Therefore static algorithms are not actually dynamic, which means depending on the changes in topology and traffic, these algorithms don't change themselves. Therefore depending on traffic and topology, they don't change. That is the problem with this. Everything has to be done manually. if there is something wrong in the network, manually we have to go and change it. So these methods are not used in the internet. The reason is they are not scalable. Who is going to sit and watch all the routers and see if there are any changes? If everything happens automatically by the routers without any manual intervention, then that is beautiful, right? So what we go for is dynamic. So dynamic means there is no manual intervention, everything is done by the routers automatically, and then depending on the changes in topology and traffic, the routing tables change dynamically. So whenever the traffic changes or topology changes, topology means the graph. See, suddenly if you have previously the routers are connected like this, and if suddenly this link is down, then there is a change in the topology. So either if the topology is changing or if the traffic is changing. Traffic means if one route has become highly congested, then we should leave that route and follow the other route, right? So a single route is not going to be the shortest path always. The reason is that route might get congested if you send a lot of the packets, and next we should change the route so that load will be balanced. So depending on the traffic and topology, if the algorithms change, they are called dynamic algorithms, and these algorithms are generally used in our internet. And the most popular two dynamic algorithms, and they do dynamic algorithms which we have in syllabus, is one is DVR, distance vector routing, and the other is LSR, link state routing. Distance vector routing, link state routing. So these are the two popular algorithms which are very important in computer networks, and even it is very important, they are very important for gate also. So let's discuss about these algorithms now. Let's now see the very important routing algorithm, which is DVR, distance vector routing. Very important routing algorithm. It has been used since the invention of routers, and in 1980s it is very popular, and this was very efficient back then. Now we moved on to the other routing algorithms, but then it was the original algorithm. So let's see this. I'll explain you how DVR works with an example. I'll take an example and I'll explain you all these steps one by one. Okay. So assume that we have routers like this. So in one more thing, we are only worried about the routers. We are worried about the shortest distance from a router to the other router. Actually, even though we want to send a packet from a host to host, we are worried about sending the packet in shortest way from a router to router, so that if it could be done efficiently, then anyway networks are directly connected with one hop. So if we can reach a router in a shortest way, then we are obviously reaching all the networks connected to a router in shortest way, and anyway every network is connected to some router. So I am pulling out all the networks out and I am putting only routers, and we shall discuss about shortest path from one router to the other router. Okay, so it means like this. Let us say there are 4 routers, A, B, C, D, and these are the links which are connecting them. Links are nothing but the edges are nothing but the links, and these are the routers. And there will be some numbers associated on the edges, which will either be cost of the edge, or they will either be distance, or they will either be traffic or queuing delay. Whatever the number is, there can be of many types, which means you can interpret the numbers on the edges using many ways. But then what our main intention is to find out a path which has the least edges, least edge weights, that is called the shortest path. So let us assume that the edge weights are like this. Now what does this number mean? Let's see this one. It means that the distance from one A to B is 2. Either this could be distance, or this could be cost, or this could be propagation delay, or this could be queuing delay at B. Whatever, we want to minimize the total distance between every pair of vertices, which means at every node we want to find out how it can reach the other node using the shortest path. That is the main intention of this algorithm. So let's see this. Step 1 is every router will construct the local routing table. So before going ahead, here routing table will have three columns. Routing table will have 3 columns. First column is what is the destination you want to reach, destination. And second column is, if this is the destination you want to reach, what is the distance, what is the distance to the destination. And the third column is, if you want to reach the destination, what is the next immediate node that you want to go, which means if you want to go from A to let us say C, what is the next stop? Either you want to go from B or go through D. So these three are going to be there. So every routing table contains destination, distance and next hop. So now let us see the routing table at B. At B we have three columns. So first one is destination column, and next one is distance column, and next one is next hop column. Okay. Now the first rule is, in DVR every node knows only about its neighbors. It will never know about a node which is not its neighbor, which means it will never know the distance to a node which is not its neighbor. And one more thing is, every node knows how many routers are there in totally. So now assume that B knows that these many nodes are already there, and B knows that B knows its neighbors. A is a neighbor because it is directly connected, and C is a neighbor because it is directly connected, D is a neighbor because it is directly connected. Therefore at B it will have destination A, destination B, destination C, destination D. Now from B to A the distance is 2. How will it know it? Because it is directly connected, therefore it can know about it. And what is the next hop? Next hop is directly A. So understand this one. From B the destination is A and the distance is 2, and the next hop is A. And from B only, distance to B is 0. So B to B it is 0 obviously, and next hop is B itself. And from B to C distance is 3, next hop is C. And from B to D distance is 7 and the next hop is D. Right? So this is all about the routing table which is prepared by B using its local knowledge. Local knowledge means whatever it knows about the neighbors. If it doesn't know, it will not put there. Now let's see what is the routing table that has been prepared by A. At A, what are the destinations and what are the distances and what are the next hops? So destination is A, all, right? We want to reach every node. Now A to A distance is 0, next hop is A, you know that. And A to B distance is 2, next hop is B. And A to C distance is, A is not a neighbor to C, therefore it will not know about it. So it doesn't know about C, therefore it is infinity, there is no next hop. So this is important. A is not a neighbor to C, therefore it will not write anything, it will write it as infinity and it will say I don't know. And now A to D, A to D distance is 1, next hop is D because it is immediate neighbors. So all the other entries have been filled except this entry. The reason is it is not a neighbor, right? And now at C look at how the routing table will be prepared. Destination, distance and next hop. Now C to A distance is, C is not a neighbor to A, therefore it doesn't know what the distance is, so it is going to put it as infinity, and next hop is it doesn't know. And what about C to B distance? C to B distance is 3 and obviously next hop is B. What about C to C distance? 0, next hop is C. What about C to D distance? It is 11, next hop is D. Right? And now check this one. C to A distance is infinity because A is not its neighbor, right? And all the others are same. All the others are neighbors, therefore we fill them. Now what about at D? At D, the routing table will look like this. Destination, distance and next hop. So destination A, B, C, D. So D to A distance is 1 and the next hop is A itself. And D to B distance is 7, next hop is B itself. And D to C next hop, distance is 11 and the next hop is C. D to D it is 0 and the next hop is D itself. So that is how it is, because it is neighbor to everyone. So we are going to put every distance in the routing table. So this is how first round is. In the first round, or the first step, every router is going to prepare the local routing table using the knowledge about its neighbors. Now let's move on to the second round. Now let's look at the second step. Second step is every router will take its distance vector. See, this middle part is called as distance vector. The name of this algorithm is distance vector routing. The reason is vector means in computer science it is not direction, it is array. Computer science vector means array and distance vector means array of distances. So which is nothing but this one. So this column is also called as distance vector. That is why the name of the algorithm is distance vector routing. So here what it will do is it will take the distance vectors. Every router will take their own distance vectors and they will exchange them with their neighbors, which means at C will take its distance vector and it will send it to B as well as D, and at B will take its distance vector and it will send it to C, A and D. So like that distance vectors are exchanged. So every node is going to get a distance vector from all its neighbors. For example, if you look at A is going to get a distance vector from D as well as B. If you look at C is going to get a distance vector from D and B. So everyone is going to get the distance vectors from everyone else. Let's see what happens in this step. Everyone is supposed to take their distance vector and send the distance vector to its neighbors. Therefore, let's see what happens at A. At A, it will get a distance vector from, it will be received from at A from B and D, and at B distance vector will be received from A, C and D, and at C distance vector will be received from B and D, and at D distance vector will be received from A, B and C. So that is what happens. So everyone is going to get a distance vector from every neighbor in parallel. So this is happening, everything is happening in parallel. At the time A is getting the distance vector from B and D, B will get the distance vector from A, C and D. They are full duplex channels. Therefore distance vectors will go in both the directions and in parallel, right? Now at every node, using these distance vectors, the new routing table will be created. So at every place it is going to happen, but then let's take it a particular node and see what happens. So even though it is happening at all the nodes, I am just interested in seeing it one node. Let us see what happens at A. In parallel, the same thing will happen at all the nodes. I am showing you what happens at A. At A, the distance vector it will receive is from 2 points. From B it will receive a distance vector. What is the distance vector it will receive from B? This one, 2, 0, 3, 7. This is the distance vector it will receive from B. And at A, there is a distance vector it will receive from D also, which means from D it will receive a distance vector, and the distance vector will be, look at D, that one, 1, 7, 11, 0. So they are the two distance vectors which A will receive, right? So using these two distance vectors, which means using the knowledge from the neighbors, A will actually compute its new routing table. So how will A compute its new routing table is this way. Look at this. At A, it is going to compute the new routing table. A, B, C, D, everything will be new. So it is not going to use the old routing table to compute the new routing table. Always remember, every router is going to use the information from its neighbors in order to compute the new routing table. It is very important that you understand this procedure well. Otherwise later you might get some more doubts. Okay, so understand this. So we are going to at A, it is going to get the distance vectors from its neighbors, and using the information from its neighbors, it is going to create the new routing table, not based on the old routing table. It is completely based on this information, right? So see this. One thing is, if you look at this point at A, the first entry is distance from A to A. It is obviously 0. We did not do anything, right? And next hop is A. And what about the next entry? Next entry is we want to find out distance from A to B. That is the next entry, isn't it? Now what it will do is, it knows that it has two neighbors and it could take both the paths, which means at A, I want to find out the distance from A to B. A to B, I have two options. Since I have two outgoing links, one is I can directly send it from A to see this. At A, if I want to send a packet to B, I have two options. One is I can directly send it to B, or I can send it to D and ask D to send it to B, right? I can ask D to send it to B. I don't care how it sends. Then it is minimum of it is minimum of, I have two paths, isn't it? A can send it to D and then ask D to send it to B. So it is somewhat tricky. See this, you want to go from A to B, then you are going directly from A to D and then you are asking D to send it to B. So what does this curly edge mean is, this path may contain more than one edge. And what does this straight edge mean means, it is directly one hop. So if you want to send a packet to B, you can directly push it to D and D can push it to B, right? Or what is the other way? You can directly push it to B and then ask B to send it to B. It is just a trivial step, just for the formality I have added it, right? Now how do you know all these distances? One thing is, you know what is the distance to D. Why? It is your immediate neighbor. And what is A to D distance? 1. And now you want to know distance from D to B. So how will you know the distance from D to B? That is where these routing distance vectors are going to be handy. You want to know what is the distance from your neighbor D to B, and already your neighbor has sent all its distances. That is where they are going to be handy here. So from D to B, it is saying that I can take you in 7. Therefore it is 7, right? And now what about this A to B? B is your immediate neighbor. B is your immediate neighbor and its distance is 2. You know that. But then you don't know about B to B. So therefore you look at it. So what is it? B to B is 0, isn't it? Now you add them both. Which one is the shortest path? Shortest path is, this one is saying 8 and this one is saying 2. Therefore shortest path is 2. I get the shortest path when A is directly sending to B as the next hop, isn't it? That is why I am writing it, right? Now look at this one. Next entry is, this entry is A to C distance. So you want to send a packet from A to C, then what are various alternatives you have? So one alternative is, you can send the packet from A to D and then ask D to send it to C, or you can send the packet from A to B and then ask B to send it to C, right? And now what is the distance from A to D? D is your immediate neighbor. You know that its distance is 1. And what is the distance from D to C? You don't know it. Therefore look into the table. So D to C, the distance is 11. So it is saying 11 here, right? And what is the distance from A to B? A to B is your immediate neighbor, whose distance is 2. You know it. But then you don't know what is the distance from B to C. So B to C, the distance is 3. Therefore 3. So did you understand the significance why the second entries are all like curly? Which means in one hop you will be sending the packet to D, and I don't care in how many hops D will send it to C. Therefore this is a path, not an edge. This is an edge. That is why I am putting a straight line so that it signifies a edge, and here I am putting a curly line so that it signifies a path. So D to C is a path, not a single edge, right? So now which one is minimum? The minimum is 2 plus 3 is 5. Right, and the minimum we got it when A will directly send the packet to B and then ask B to send it to C. Therefore the next stop is B. So what the meaning of it is, if A want to reach C, then the distance is 5 and the next stop is B. which means if A wants to reach C, then the total distance is 5 and the next stop is B. That is the meaning of it, right? And now looking at this next entry, this entry is nothing but A to D, isn't it? So we want to compute the distance from A to D. Then what are the various choices I have? Two choices only, right? One thing is minimum of A can send it to D and then ask D to send it to D, trivial step, or A can send it to B and then ask B to send it to D. And you know that A to D distance is 1 and A to B distance is 2 and D to D distance is 0 and B to D distance is 7. Therefore which one is minimum? Minimum is 1. And how did you get the minimum? When you directly send the packet to D, therefore next stop is D. So that is how A will compute the new routing table from the knowledge or from whatever it got from its neighbors. That is how we calculated it. So now just see what is the difference between this routing table and the previous routing table. The previous routing table at A was this, and what is the entries? What are the entries, or what is the entry that changed? The entry that changed is this. Previously it was infinity, now it is 5, which means previously we don't know how to reach C directly from A, but now we found out that if you can go through B, you can reach A, right? So, or previously there is no path of single edge, and here there is a path of two edges. So what has happened in this case is, these are all the distances or lengths of the shortest paths, where every path will contain at most one edge, which means here the path will contain only maximum of one edge. And in the next round we are computing all the shortest paths, where the shortest path may contain at most two edges, which means you can compute the shortest path using one edge or two edges. Whatever is minimum you can take it. That is why, since there is no single edge path, we got infinity before, and since there is two edge path whose distance is 5, we got 5 now. That is the difference between the old table and the new table. So at A previously we got this, and at A now we got this. Let's now look at the next routing algorithm, link state routing. So before watching this video, I expect that you have already watched the video of distance vector. It is just not a continuation but then a comparison. So what happened is, till 1980s the bandwidth was very limited. Therefore people were sending only distance vectors, which means limited information, because bandwidth was already less. And what happened is, after 1980s coming to 1990s, the bandwidth got improved because of the technology, and now we have the freedom to send more information, not just very little distance vector. Now if you look at distance vector, the disadvantage of distance vector was this count to infinity problem that was arising because we are sending only limited, and then the convergence of DVR is very less. Distance vector converges very slowly. Even if it is a good news or bad news, it is going to converge very slow comparatively. Now we could do something better if you can send more information rather than just sending the distance vector. So as the bandwidth increased, this LSR has become more and more popular. So right now both are being used, LSR and DVR, and LSR is somewhat superior to DVR, but then there are some disadvantages for it too. Let's first examine with an example what this link state algorithm is, and then we shall discuss about it properly. I'll take the same running example which we used yesterday. Let us assume that there are four routers. Four routers like this, and there is distances are 1, 2, 3, 7, assume 11, okay, and A, B, C, D. There is the same example which I have taken, this running example for the DVR also. And now what is the main difference between DVR and LSR is, in DVR they have constructed the routing table locally first, but here what happens is, every router will create something called as link state packet. Link state packet. Why is it called link state routing is, here we are using something called as link state information. What is a link? Link is an edge, And what is state of a link? State of a link is either it is up or down. If it is up, what is the distance? That is the state of it, right? So at B, what are the links that B know of? B knows of this link and this link. B knows of 3 links. Therefore, it is going to put all the links, which means it is all happening at B. At B, it will write what are all the links it knows about. So it knows that B has a link to A and its distance is 2, and it knows that B has a link to D and its distance is 7, that is state, right? And it knows that B has a link to C and its distance is 3, that is what B knows. At B, we know this information, right? At C, what is the information we know? At C, we know that C has a link to D and its distance is 11, and C has a link to B and its distance is 3. At A, what will A know? A knows that A has a link to B and its state is 2, which means its distance is 2, and A has a link to D and its distance is 1. What will D know? At D, D knows that D has a link to C and its distance is 11, and D has a link to B and its distance is, D to B is 7, and D has a link to A and its distance is 1. D has a link to A and its distance is 1, that is what D knows, right? So these are all the link state packets. So first round is every node will find out who are their neighbors and what are their links and what is the distances. How? By using something called as hello packets. Hello means before starting this, you will send a hello, it's like just like this. You'll see your neighbor and say hi, and they will say hi. So that is how you find it out, right? So that is called hello packets, using which you will find out who are your neighbors and what are their distances, right? This is the first step. And next step is unlike DVR, in DVR what happened is we are sending the information, a node will send the information only to its neighbors, right? Which means in DVR, A will get the distance vector only from B and D. But in this link state, every node is supposed to flood the information to every other node, which means A is supposed to flood, not just sending the information to B, it is supposed to flood the information to every other routers. Why are we using flooding here? Because we are in a process of creating the routing tables. We don't have routing table set. Therefore, at initial phase we should use flooding, and later also we are using flooding only. Flooding is the efficient method to ensure that some data is received reliably and data is sent fast. Flooding is very efficient, and we are not using flooding for all the packets or the data packets because flooding is very costly. It is going to increase the traffic. So only for this link state packets we are using flooding. So second step is every router is going to flood the packet to every other router. Therefore, at A will receive this link state packet from B and D as well as from C. That is the difference. Previously, A will not receive DVR distance vector from C, but now A will receive distance vector, this link state packet, from all the nodes, which means every node is going to send send this packet, link state packet, and A is going to see everything. Therefore, A have the global database, or A knows everything, which means this algorithm is based on global knowledge, and previous DVR algorithm was based on local knowledge. Local knowledge means you will get only what your neighbors say. So one point worth noting is DVR is based on local knowledge. Local knowledge means whatever your neighbors say, you know only that. But LSR, it is based on global knowledge. Global knowledge means everyone is supposed to flood their knowledge to everyone else. Therefore, every node will know what about the entire network. So let's see what happens at A. At A, what happens is it is going to get the link state packets from every other router, which means from B it is going to get this, from C it is going to get this, and from D it is going to get this. Now let us assume that A is going to get all these link states from all of them. Then what will A understand? A will understand. A, once it gets this packet, once it gets this from B, that this entire packet, what will A understand is, it understands that, oh, there is a node called B. So at A, what is happening is, by looking at this one, it will understand that there is a node called B, and then B to A distance is 2. That is what it understands, right? And then it will understand that B to D distance is 7, which means it will think that there is a node called D, and now its distance from B is 7. And it will understand that there is a node called C, and then B to C distance is 3 from this entry. B to C distance is 3. That is what A will know just by looking at this link state packet from B. And again, it is going to get this link state packet from C, right? When it gets a link state packet from C, it will understand that, oh, C to D distance is 11, and C to B distance is 3. It is already there. And then it will get this D, and understand that D to C distance is 11 and D to B distance is 7. Here I am assuming that is all undirected graph, and that is why all the numbers which are already there are giving the same numbers. But then in case if it is a directed graph, which means if it is asymmetric, sometimes B to D will be a different number and D to B will be a different number. In that case, you are supposed to see the every packet and then put the directed link. But here we are putting undirected links because I am considering that both ways the cost is same. And then it will understand that D to A distance is 1. Right? So what has happened at A, by looking at the link state packets, A is able to construct the entire tree or the entire graph in its own memory. So at A now has constructed the entire graph in its memory, which means A has the global database. Global database means it knows everything about every node and every router, right? Then what will A do is, A will at this point start applying single source shortest path algorithm, which is Dijkstra algorithm. So A will apply single source shortest path algorithm. So Dijkstra algorithm will be applied at A using this global database, and A will find out what is the shortest path from A to every other node, right? Therefore A will construct its local routing table just by using the global data. So what will A construct? It will construct the routing table like this, same. So what is the destination, what is the distance, and what is the next hop? So see this. Now by looking at Dijkstra algorithm will be discussed in detail in the course algorithms, but here I am assuming that you already know how to apply Dijkstra algorithm. If you don't know how to apply it, you can refer to algorithms course and again come back. Okay. So now A will write like this: distance from A to A is 0, next stop is A. Distance from A to B is 2, next stop is B. Distance from A to C is 5, next stop is B. And distance from A to D is 1, next stop is D. How did it prepare it? It has prepared this using the Dijkstra algorithm. I have just written it using intuition, but then the actual procedure is Dijkstra algorithm. This is how every router is going to find out what is the routing table. So simple, right? It is simple, fast. But previously we had to apply that DVR algorithm for n-1 steps. n-1 times we should exchange and then get it and then calculate it. It is going to be converging very slow. So the convergence is fast. This one converges faster compared to DVR. So a link state routing algorithm is really fast compared to DVR, right? Just look at this diagram. This is TCP header. Okay, so just like IP header, TCP also has a header, and then TCP is going to put the data in this. So every segment, TCP segment, is going to have header and data, and the header looks like this. What you could do is you just pause the video. He will just zoom in, pause the video, write it down, copy it down, and then later when I am discussing about each field, it is better that you keep this diagram handy so that you can watch the diagram, and I'll be explaining about each field like source port, destination port, sequence number, acknowledgement number. I'll just read all of them out, and I'll just give you the sizes, I mean the length of each field. You please copy them down, and later we shall discuss about them again at depth, okay, about each one. So in this video, just write it down and keep it handy. So this first one is source port, which is 16 bits, and destination port, which is 16 bits. So here whatever numbers I am writing within brackets are bits except the last one, okay, and sequence number is 32 bits, acknowledgement number is 32 bits, and header length is 4 bits, and next 6 bits are reserved. All these bits are not used, it is simply zeros in most of the cases and in all the cases, okay. And next one is URG. URG means urgent. These are all flags. Each flag is 1 bit each. URG means urgent, ACK means acknowledgement, PSH means push, RST means reset, SFIN means SYN, FIN means FIN. So we shall discuss about it later in various what are the various uses of these flags, but just remember that all these flags are 1 bit each. So when I am discussing about the next topic, you please keep this diagram handy, so that whenever I discuss about sequence number and whenever I discuss about SYN flag and acknowledgement number and ACK flag, you should understand the difference. Acknowledgement number is a 32-bit field and acknowledgement flag is a 1-bit field, okay. So what is the difference? We shall see it later. And advertisement window or window size, it is a 16-bit field. It is used for flow control. I'll explain you when I am explaining about flow control. And checksum is 16-bit field, and urgent pointer is 16-bit field. And options, they can be anywhere from 0 to 40 bytes. So just this is the difference. All the other fields are bits, but only options I am talking about in bytes. Now just see the total length of the header. Every row is 32 bits, which means 4 bytes. So first row is 4 bytes, second row is 4 bytes, third row is 4 bytes, fourth row is 4 bytes, and fifth row is 4 bytes. So all these rows which are definitely required in all the headers. So this is the minimum. So minimum header length is 20 bytes, and in case if you use the options, the maximum options you could go for is 40 bytes. Therefore 20 plus 40, maximum header length is 60 bytes. So every header should definitely have these 5 rows. Therefore minimum header size is 20 bytes and maximum header size is this 20. I have to add 40. The options maximum in worst case that can go up to 40 bytes. Therefore it is going to be 60 bytes, okay. It is all about the header, and please write it down and keep it handy. Now look at the first field of this TCP header. The first row contains source port and destination port. So, and the bigger picture is we are in TCP. So TCP is a protocol at transport layer, and transport layer is responsible for end-to-end delivery. So if you look at the first two fields, there is source port and destination port in the header, and each field is 16-bit number. Each one is 16-bit. So with 16 bits, how many numbers are possible? 2 power 16. So what are they? 0 to 2 power 16 minus 1. So which is 0 to 65535. These are the numbers, port numbers possible completely. Now why do you think that TCP is using port numbers is? Because transport layer is a end-to-end protocol. End-to-end protocol means we are mostly interested in sending a message from one end of the communication to the other end. So what are the ends? Processes. Inside a host there can be any number of processes working at the same time, and now when the host has received a message, we have to appropriately give it to the particular process. So in order to identify that process, we need the port numbers, right? So port numbers are mainly used for multiplexing and demultiplexing. Multiplexing and demultiplexing means taking the incoming message and giving it to exactly one of them, and then collecting the message from all of them and sending it over the same channel. That is multiplexing and demultiplexing. So TCP is a end-to-end protocol because of the port numbers, and port numbers help us in multiplexing and demultiplexing, and port numbers range is 0 to 2 power 16 minus 1. So points you might have to note down here is, one is TCP is a end-to-end protocol because of the port numbers, and second is TCP could do multiplexing and demultiplexing, which means it can take the packet and then distribute it appropriately. Now among the 0 to 65535 numbers, the numbers which are some numbers are very well known, which means if you look at HTTP runs at 80. All the websites, they always maintain the port number 80. And FTP, if you are trying to download a file, you should always contact port number 21. Telnet, which means remote login. If you want to log in onto some other machine, then you should go to 23. SMTP, which means the email transfers. Email transfers are generally done with 25. So some port numbers are well known. The reason is, in order to know the host IP address, for example, if you type google.com, you will get the IP address of Google from DNS, but then you don't get the port number of Google from anyone. Therefore, port numbers are generally well known, like telephone numbers of police station, and the IP addresses they are going to change and you are going to get it. So all the well known services, they generally run from 0 to 1023. This entire range is well known. Well known means like HTTP, like that, okay? And from 1024 to 49151, these numbers are reserved. Reserved means these numbers are not to be used by anyone. These numbers are actually, okay, who is having all these numbers? Any number that you could talk of in computer networks, they are all with the IANA, Internet Assigned Numbers Authority. There is a central organization called as IANA, Internet Assigned Numbers Authority. So this authority is responsible for everything that happens with the numbers. So all these numbers are with IANA, and they have assigned these numbers to well-known services, and these are reserved so that in future if anyone wants to have a well-known service, which means in future, let us say after this 1023 or 1024 services, suddenly a new service becomes well-known and that has to be given some number. In that case, this number is used to be one number from this will be bought by someone, and that will be reserved. And from this 49152 till 65535, these are used by general public, which means if you want to use any number as a source port number, you could take from this range and use it. But then it is not a hard and fast rule that you should not use any numbers from as a source port, but it is better you avoid it. So by default, if your operating system, if you open a browser and if you try to contact Google, by default your operating system is going to give you some port number as the source port number, so that Google can identify you, and that number will generally be not in this range. So if you want to see what are the port numbers which are being used in your computer when your internet is on, you can type this command netstat. If you type the command netstat in your browser, you are going to see what are all the open connections and what are the port numbers, source port number and destination port number, right? And now let's see how port numbers are used to uniquely identify a connection. Let us assume you have opened a connection with Google. So you are here and your host is A, right? And there is a station here, and assume it is Google, and the process at Google is waiting at 80. So there are some complex things like one process will be listening, and once you go to that, it will create one more process assigned to you. But I just want to keep things very simple, so I'll take the simplest one and a very naive kind of implementation. Now at this station A, one process, generally your browser is the client, and it will get a port number. Let us assume the port number you got is some port number X, which is not in the well-known range, or anything. You can take anywhere, but then it is better you avoid some range. Your operating system is going to generate some number from 49152 to the last one, 65535. So when this connection is opened, now TCP is a connection oriented. TCP is connection oriented. So what do I mean by connection oriented is, whenever you want to communicate the messages, generally some buffer will be reserved. So buffers will be reserved, bandwidth will be reserved, and CPU will be reserved for your communication. So whenever I say connection oriented in computer networks, remember that resources are reserved. In virtual circuits also it was connection oriented, but then that was at network layer. Now we are at transport layer, right? So connection oriented means resources are reserved at both the sides, which means here some buffers are allocated for you. Now how are these resources identified? In order to identify this connection is nothing but identifying the buffers, right? So what if I take port numbers in order to identify the resources? In order to identify the buffer which is reserved for your communication or for your connection, if I take the port numbers like X and 80, what happens? Just imagine this. Now if X and 80 is taken, this resource can be uniquely identified, and any packet coming with these two numbers X and 80 at transport layer will be kept in this buffer and then later taken up for processing. Therefore whatever you send, that will directly go and sit in this buffer. How is that packet identified? Just by looking at the source port and destination port. On the packet, source port is X and destination port is 80. It works fine, no problem. But the problem arises if someone else in the world also wants to open a connection with Google, and let us say there is a station B which wants to open the connection with Google, and they can choose any port number inside their computer. It might so happen that the number which they have chosen is also X. There is a probability, right? There is a probability, there is a likeliness that the port numbers which you have chosen and the port number which someone else has chosen may be the same. The reason is port numbers have to be different within a computer, but across the computers port numbers can be repeated, right? Then if they also open a connection with Google, and for these resources which are assigned, if they use the port numbers only to identify, then this buffer will also be identified with X and 80. Then if an incoming packet has gone to this Google, right, and if the incoming packet is containing X and 80, then where should it place it? Either this one or this one. It will get confused, isn't it? Therefore, in order to identify a connection uniquely, port numbers are not just going to be sufficient. The reason is two hosts are going to choose the same port number. Then how can you solve it? So if you think about it, maybe you will say let's not use port numbers, let's use the IP addresses, which means if you don't want to use the port numbers, let us say the IP address of this one is IA, and the IP address of this one is IB, and the IP address of this one is IG. Then instead of using the port numbers, if you use the IP addresses to identify the connection, maybe you could solve this problem, isn't it? So how can you identify the IP addresses, connection using the IP addresses? Now for this one, instead of using X and 80, you could use IA as the source IP address and IG as the source IP address, is a destination IP address. Therefore any packet coming with IA and IG as source and destination IP address, that will go and sit in this buffer. Now this buffer is identified using these numbers, and now if I use the this convention, then here it will be IB and IG. Yes, the conflict is resolved. So instead of using port numbers, if I use only IP addresses, the conflict is resolved, isn't it? But then again one more problem might arise. The other problem is, from the same host, if someone wants to open one more connection, which means from the same host, if one more process wants to open a connection with the same host, then what happens? Then this connection will also get a buffer, and that buffer will get IA and IG, source port and source IP address and destination IP address, and which will be same, isn't it? Already IA and IG is used, now IA and IG. Therefore either you use only port numbers or you use only IP addresses, both are going to be a problem. So you cannot use only port numbers or only IP addresses. The solution comes in terms of using port numbers plus IP addresses as a combination, which means don't use only source port numbers or IP addresses, use a combination of them. So what they say is, use these four numbers: source port, destination source port and source IP address, and destination port and destination IP address. It is not just either ports or this. Now what happens is, if I use these port numbers along with IP addresses, so how can I write it is, see this. Now I am not taking only port numbers or only IP addresses, I am taking IP plus port, both of them together. If I take both of them together, then IP is 32-bit number and port is 16-bit number, and combinedly it is going to be 48-bit number, which is called as a socket. So socket is a combination of these two, which is a 48-bit number, which can now uniquely identify a connection. So we are not going to use only port numbers or only IP addresses, we are going to use a combination of it. So inside the, let us say IP addresses are same, then also connection can be uniquely identified. The reason is, inside the same computer, two processes will not have the same port number. In case if port numbers are same, definitely those two processes are from different machines, therefore IP will be different. So for two connections, IP and port will never be together, will never repeat. So with a 48-bit number, which is called as socket, we are able to implement or identify the connections. So TCP is a connection oriented end-to-end communication protocol because of these port numbers, right? Now look at the next field in the header. After the first row, the source port and destination port, there is a next field called as sequence numbers, right? And sequence number is a 32-bit field. So next field is sequence number field. Sequence number, right? So what is sequence number is, in TCP, TCP is a byte stream protocol. Maybe note this point. TCP is a byte stream protocol. So what is byte stream protocol is, every byte that is being sent out is actually counted. So counting every byte is called byte stream. So every byte is counted, and counting every byte means whatever byte that comes from application layer to transport layer, we are going to put a number on that. That is called byte stream, right? And what is the byte stream and packet stream is, network layer, IP is a packet stream. IP is packet stream. Packet stream means every packet is counted. If you remember that in IP there is a number called as identification number. If you remember that IP, that second row, the first part is identification number, right? So in that IP header, identification number is used to count every packet number. But here in TCP, every byte is counted, and the sequence number is nothing but the byte number. Okay. And at data link layer, the protocols like HDLC. HDLC is not in syllabus. It is a protocol which is used at data link layer. HDLC is a bit stream protocol. Bit stream means every bit is counted. So at TCP every byte is counted, and at IP every packet is counted, and at data link layer every bit is counted. So that is the difference between whatever is the granularity of the counting you have taken, that is called bit stream, byte stream, and etc. Java is a byte stream, right? So which means every byte is counted in Java. Okay, now see this. What does this byte stream actually mean is, now if there is a packet, here we call a packet as segment. See, I am using the name segment, packet and frame interchangeably. Packet is a generic name. Segment is the name which is used at transport layer, and datagram is the name which is used at network layer. Here I am using segment. So since we are at transport layer, I am talking about segment. In a segment, there will be header, and now there will be body, and this will be bytes. All the bytes which are present inside the TCP segment, every byte is going to get a number. For example, if this byte is 100, the next byte is 101, the next byte is 102, the next byte is 103, like that. The last byte is, let us assume, 150, right? So from 100 to 150, all the bytes are present in this segment. Then what is the sequence number that I should put in the header is, the sequence number of the first byte which is present in this packet should be kept in the header. So the header has a field called as sequence number field. In this sequence number field, we are going to put the first byte sequence number 100 in the header, right? Understood that? So what is the sequence number? Every byte is numbered because TCP is a byte stream protocol, and then the sequence number of the first byte will be present in the sequence number of the header, right? And now look at the next one. The next field in this is acknowledgement number. Acknowledgement number is when you send a segment to the other side is going to send you an acknowledgement. Acknowledgement number is always what is the sequence number of the byte expected next, which means in this segment, if you are sending the numbers 100 to 150, then the next byte expected will be 151. Therefore, the acknowledgement for this packet will be, acknowledgement number will be 151. Now the question is, how will, see, the first byte sequence number you are going to put here, and you can know the first byte sequence number, but then you cannot know the last byte sequence number. Once you know the last byte sequence number, then you can calculate the acknowledgement number. Acknowledgement number is nothing but last byte sequence number plus 1, simple. But then given the first byte sequence number, how can you calculate the last byte sequence number? So that is the question. Now this is the TCP segment, this is the header, and the first byte sequence number is 100, which is present inside the header, and the last byte sequence number is 150, but then it is not present anywhere. You are supposed to count it and get it, right? And now how can you get this one? So look at the header. If there is a field called as header length, therefore you can find out the header length, but then there is no field called as total length. If there would have been a field called total length, you could subtract total length minus header length and you can get the body size, and after getting the body length you can find out the last byte sequence number by adding the first byte sequence number plus that one, the total size. But the problem is in TCP header you don't have any field called as total length like in IP header. In IP header you had a field called as total length, right? So now how will the receiver calculate, given this segment, what is the acknowledgement it should send? Why should it calculate? Because acknowledgement number is the sequence number of the byte expected next. How will it do it? Think about it. So I am saying that there is nothing called as total length which is present inside the TCP packet. Then how will the receiver calculate it? It will be calculated from the IP header only. So every TCP segment will actually travel in a IP datagram. IP datagram is going to have header length field as well as total length field. So from the IP datagram, if total length field is present, from total length if I subtract the header length, then I get the entire body length or the segment length of the total segment, and from that segment length if I subtract the header length, then I get the body length of the TCP segment. Then by using this segment, the first byte sequence number and the size of this segment, then I can calculate everything, isn't it? Okay, we shall see a problem later, but for now understand that sequence number indicate the first byte sequence number in the packet, and then the acknowledgement number indicate the next byte expected by the receiver. Once you send some 100 to 150, other side should send the acknowledgement of 151, which means they have received till 150. So those two fields are used like that. Okay, now let's see more about the sequence number field. I told you that sequence number is a 32-bit field. So with 32-bit field, how many sequence numbers are possible? 0 to 2 power 32 minus 1. So now the problem is, if I always start a connection with the sequence number of 0, which means the first data byte is numbered with 0, then there is a small problem which is going to occur. So I'll just explain that with an example. We have 0 to 2 power 32 sequence numbers. Now let us say this is a timeline, and there is sender, there is receiver here, and assume that you are sending the first segment. In the first segment you have all the data bytes, and the data byte of this is 0. The first sequence number is 0. Therefore what will be sequence number of the packet? Always the sequence number of the packet, which means all the data bytes are going to be present in one segment, and for this entire one segment there will be only one header, and on that one header there will be only one sequence number field. Therefore that sequence number field should contain the sequence number of the first byte. So here the sequence number of the first byte is 0. So when you are sending that packet, if it is 0, which means whatever is the sequence number of the first byte, that is going to be on the segment. Therefore on the segment, sequence number is going to be 0. So how many data bytes it contains? Depending on that, let us assume that the data bytes present are 0 to 100, then 99, let us say 99, 0 to 99. Then the data segment will contain 0 to 99 bytes, but the sequence number on the segment will be 0, that is the first byte sequence number. And let us say you are sending many frames like this. The second segment will contain again 100 bytes, and what will be the next sequence number? Sequence number of the first byte of the next segment is 0 to 99 is in the first segment, therefore 100 will be there. So sequence number will be equal to 100. Then what is the range? 100 to 199 is the range, right? And likewise, let us say you are sending the next one also, sequence number 200. Let us assume that this segment is lost. This segment is lost, which means this segment is not received by the receiver. Then after some time you will wait for it, and again you retransmit it. Therefore again the segment with sequence number 100 is sent, and let us assume that the connection is closed, which means the sender has sent 3 segments between these two, sender and receiver, and after that the connection is closed. Only 3 segments are sent. Just for the sake of assumption, it is not true, just for the sake of assumption, let's assume that. And now it will be simple for us to analyze this. Now during this connection, what happens is there will be a random initial port number which is chosen from the range I told you, from the range 491522 this is chosen, and let us say it is HTTP server with 80, port number 80, and the IP address is yes and IP address is all. Now how do you identify every segment in this communication is, one is using the source port and source IP, destination port and destination IP, as well as sequence numbers. Using these numbers, every segment will be identified uniquely, right? And now it is closed, and next time, after some time, assume that both sender and receiver, they want to again communicate, and therefore one more time the connection is opened, and again the segments are being sent. Now already the connection with port number X is closed. Whenever the process with port number X is closed, next time anyone can use the process with port number X, which means next port number could be, there is a chance that it could be repeated as X. Let us assume that next time also when you have chosen the port number, since X is now available, same X is chosen, and here the port number is still 80, so our port number doesn't change, right? And I told you that even though we are using DHCP, Dynamic Host Configuration Protocol, the IP addresses are not going to change all the time. As long as you are using the internet connection, IP address will not change. Once you stop using the internet connection, they might pull it out and then give you a new IP address. Let us say this is happening immediately and your IP address didn't change. Let us say your IP address is IS only and the destination IP address is IR. These two also didn't change. And assume that for the next time also, if you are using the same sequence number starting from 0, which means sequence number is 0 here, and you have sent 0 to 99 bytes, and for the next time sequence number is 100, right? At this time when the second segment is arriving, let us assume that the previous 100 segment which you thought was lost, you thought that it was lost, right? But then let us assume that it is not lost, but it is delayed at some point. Some router is holding that segment, and there are lots of surprises in the networks, right? So it is it is hiding somewhere, and then suddenly it appears. The reason is every packet can be there alive for at least 180 seconds, which means 3 minutes. In today's internet, if you send a packet now, it might appear at the destination after 3 minutes in worst case. Therefore what happens is, let us say after you were thinking that it was lost, but then it suddenly appeared now. So there are 2 segments with the same sequence number 100, isn't it? And how can you distinguish both of them? Both of them are saying that my IP address is IS and IR. Both of them are saying that my port number is X and 80, and both of them are saying that my sequence numbers are 100 and 100. But actually the data which is carried is different, but then you don't know what is the data you should take in. As a process you should make this decision. It is not done manually, right? Therefore there are two segments with the same port number, with the same IP address, and with the same sequence numbers, right? So you can never identify which one is right. That is the reason we don't always start with 0. So what is the solution to such a problem is, what is the problem here? The packet from the previously closed connection is going to be accepted as a packet from the present connection. That is the problem here. The previously closed connection packets may come late, somewhat late, and now that might be accepted as a packet from the present connection. In order to solve this problem, what you should be doing is, don't start from sequence number 0 always. You try to change it, which means don't always start with a fixed number, you start at a random number. So what happens is, the concept is like this: don't start with 0, start with a random initial sequence number. So initially let us assume you have chosen the sequence number 500, then the sequence number on the first packet will be 500, then the sequence number on the second packet will be 600, sequence number on the third packet will be, let us say, 700, and this 600 packet is delayed, therefore you have again retransmitted the packet 600, right? And this is closed, and next time again you open the same connection, even though the port number, IP address are same, but the sequence number is not going to be same. The reason is, we are not going to use the random same starting sequence number, we are going to use random initial sequence numbers, right? So let us say here the random initial sequence number chosen is 500, and here let's not take 500. If if you choose a random initial sequence number, that might come some other number. So let us say the some other number is 1025. Then what will be the sequence number of the first one? 1025. What about the sequence number of the second packet? 1125. 1125. And what about the sequence number of the third packet? If every packet is going to contain 100 bytes, that is the assumption, sequence number will be 1225. So even if this packet, which is having the sequence number 600, arrives late to you, one is containing sequence number 600 and other is containing sequence number 1125. Therefore you can say that this is the packet from the previously closed connection, and you can stop accepting it, right? So how did we solve this problem? By using random initial sequence numbers. But still you could argue that even though you are using random initial sequence numbers, there is a probability that the next time also 500 might turn up. Yes, you are right. But what is that probability? Out of these 2 power 32 numbers, the probability of getting the same number again is 1 by 2 power 32. So which is 0.1, 2, 3, 4, so on, 9 zeros followed by 25. So which is very, very less. So probability of getting the same number again is less. But then there is a probability of getting the number in such a way that there could be conflicts, which means if there is 500, let us assume, and now next time if you choose there could be 600, then the first packet next time could collide with the second packet in the previous one. Therefore the probability of getting a number in a range that could be significant, which means if you are using this 500, what is the probability that next time when you choose a number, that will fall in around plus or minus 1 million numbers, which means in this that is simply mathematics, you can do that probability later. I am just saying that if you choose a number now, one number, what is the probability that you are going to get a number plus or minus 1 million to the 500 next time. So the probability is in this 2 million numbers range out of 2 power 32. So the probability is 2 million divided by 2 power 32, which is also not very high. So the collision probability will be very less if you randomly chose the sequence numbers. What I mean to say is, even if you choose it randomly, the chances of getting a collision next time is comparatively less instead of choosing with 0. We cannot completely solve the problem, but yes, we are able to survive with this, because rarely we get this collision problem after choosing it randomly, right? So the point you should note down is, TCP uses random initial sequence numbers, which means initial sequence number is always going to be random. Why? To just stop accepting the packets from previous connection in the present connection, right? Now let's look at the flags. See, we are done with the source port, destination port, sequence number, acknowledgement number, and we are done with the header length. And after that header length, there is some reserved field which is not used. There are actually 6 bits of reserved which are not used. And after that, if you can see some flags. One flag is URG, and other flag is ACK and PSH push and RST reset, SYN SYN, FIN fin. So we shall see all these flags. Flags are nothing but one bit information. So what I do is, instead of taking about the flags all together, I'll take the flags one by one and then tell you where they are used and what is their main purpose, and then we shall see like that all the flags one by one. Okay. So first one is, if you look at the last but one flag, it is given as SYN flag, SYN, SYN flag. It is also called as synchronization flag. Synchronization flag. Okay. And next flag, if you see, the second flag is ACK flag. ACK flag means acknowledgement flag. Acknowledgement flag. So these two flags are used in such a way that if SYN flag is set, so I'll just take an example and explain you where they are used here. Let us assume that there is a sender or the client and server. It is a TCP connection, client and server. So TCP is a connection oriented protocol. TCP is connection oriented. So connection oriented means before sending the data, you should tell the other side that I am sending the data, so you please reserve the buffers and wait for me. So before you do the actual data transfer, you should do connection establishment. In every connection oriented protocol, before sending the data, you should do connection establishment, and after sending the data, you should do connection termination. Therefore, there are 3 phases. One phase is connection establishment. Connection establishment means before sending the data, tell them that I am sending the data. And second thing is data transfer. Data transfer means where we actually send the data. And the third one is connection termination. Connection termination means after we do the data transfer, we are going to terminate the connection, right? And I'll take some examples here and I'll explain you all this. So maybe note it down. TCP is a connection oriented protocol. It has 3 phases. One is connection establishment, data transfer, and connection termination. And right now I am talking about connection establishment phase. Okay, you please make a note of it. And how to do this connection establishment is, I told you that sequence numbers are not going to be starting from 0. Sequence numbers can start from any initial random number. The reason why I have chosen that is to stop accepting the duplicate or the previous packets as the present packets, right? So before starting this every connection, you should come up with a port number. Let us assume that port number at the server is 80 and your port number is X, right? So what is X? X can be any random number chosen from 0 to 2 power 16 minus 1. And in general, you need not actually go till some range. Some range is generally avoided. Anyway, this number is going to be chosen by your operating system. You are not going to do it. Even you have the control to choose the port number and assign it to a process, but in general, if you don't do such things, operating system is going to provide you a sequence, this port number, some random port number. And next thing what you should do is, you should take some random initial sequence number. And how are the random initial sequence numbers used is, from the time of the day, from the clock, least significant 32 bits are taken, and that is taken as initial random sequence number. And how is that procedure used? We shall see it later. But for now, assume that client has chosen a random initial sequence number 521, which means from client side, it is going to start the communication with the sequence number starting with 521. And at the server side, it doesn't know that someone is going to contact it, therefore it will not do anything as of now. So after choosing these two numbers, client will send the first packet. On that first packet there will be a header, right? So it will contain purely a header. Packet doesn't contain any data, so you are not supposed to send the data immediately. You are just going to send a header which contains the relevant information, which contains the information required for connection establishment. So what are you supposed to say in this first packet is what is the sequence number you have chosen, and you are going to start communication from that sequence number. So in the sequence number field, so there is a field called as sequence number field in the header, right? Just look at the header. In the second row there is a sequence number field. In that sequence number field you are going to indicate that 521 is my initial sequence number that I have chosen. That is what you are going to indicate, right? And along with this you are going to indicate that this is the first packet, or this is the first sequence number. So syn flag is used to synchronize the sequence numbers, which means here there is a different sequence number and here there is a different sequence number, and both of them should know what their sequence numbers are. Syn flag is used for synchronization. Therefore syn equal to 1 is nothing but we are saying that this is the first sequence number I am using. So syn equal to 1, right? And along with this, in the options you are supposed to say few things. If you are present in one network, and if the server is present in other network, in your network according to the data link layer frame, you might have some sizes which are permittable, which means here let us assume that at your data link layer frame, let us assume this client is present inside a LAN which is using Ethernet, and at data link layer the LAN, Ethernet LAN, assume that it has the tail and header and it can carry a data of 1500 bytes, and then in this data link layer frame a network layer datagram is going to commence it. So network layer datagram's maximum size is 1500 bytes, and which should always contain at least 20 bytes of header, right? Therefore transport layer segment can commence it in this. So this size is 1480, isn't it? 1480 is the maximum data that the network layer datagram can carry. Therefore transport layer maximum segment size is 1480, out of which 20 bytes is going to be the header. Therefore what is the maximum data that can be present inside this transport layer? 1460. This is called MSS, maximum segment size. So how did we get the maximum segment size? That depends on the maximum that the network layer can carry and data link layer can carry. In case if the data link layer can carry any amount, let us say 1 GB or 2 GB, then the bottleneck is going to be network layer. You please refer to the concept of segmentation and fragmentation in order to understand it better, right? So let us assume that in your network you found out that the maximum segment size is 1460, and you should say that in my network I am comfortable with maximum segment size of how much? 1460. That is what you are comfortable with. You are telling the other side. Why should you inform it to the other side is, other side will now, whenever it wants to send the data, it will not cross maximum 1460. What happens if the other side sends a data of maximum 1460, more than 1460 in one segment is, when the datagram comes here, it has to be fragmented. The reason is network layer is allowing only how much? 1480 plus 20, which means 1500. So in case if the other side sends more than 1460 bytes in one segment, then anyway that has to be fragmented and then assembled, right? In order to avoid that overhead, it is better that you say, see, in my network the maximum size is 1460, you please don't send more than 1460, otherwise I might have to face this fragmentation and reassembly, which is a headache. The problem with this fragmentation and reassembly is, whenever you fragment a datagram into many fragments, even if one fragment is lost, then again everything has to be retransmitted. That is why, and moreover this sorting and then combining, everything is a headache. So we generally try to avoid fragmentation as much as possible. How? By saying the other side what is your MSS, right? And now other side, along with this you should also say what is your size, what is the maximum size you could hold. So where is this field MSS? If you look at the header, is there any field called MSS? Just look at the header. There is no field which is having MSS. Therefore it is kept in options. This field is kept in options. inside the TCP options we are going to put it. So why are we going to put it in options is, the reason is this: every packet need not contain this MSS. MSS, once it is initially sent, other party will note it down, and MSS will not change all the time. The reason is that depends on your network. As long as you are present in that network, MSS doesn't change. Therefore, it is not a good thing that you include it in every packet. That is why they kept it in the options. If you need it, you can use it. Otherwise, don't use it, right? And now after this MSS, one more option is TCP is a full duplex connection. Full duplex connection means data will go in both the sides. TCP is full duplex. Maybe you could write it down somewhere after copying it down. TCP is full duplex. Full duplex means at the same time, even though I am saying that client is there, server is there, it is not always true that only client will get the data or server will get the data. Communication can go on both the sides. Therefore, it is a full duplex connection. Then what happens is, we have client and we have server and we have the connection established. Sometimes receiver is going to be client is going to be receiver, and sometimes the server is going to be sender, and sometimes client is going to be the sender and server is going to be the receiver. Therefore, there has to be at least 4 windows in order to keep track of what is the capacity of each side. So for that reason, the client, whenever it wants to accept some data, server should not send more data than what it could accept, right? So think about it. Server is going to send some data in terms of MSS, maximum segment sizes, or in terms of segments, and now server should not send more than what the receiver can receive, right? Therefore, it is the responsibility of the client to say to the server that don't send me more than so and so bytes. Let us assume that. So there is a special field called as window size. Check in your header. After the flags, there is a special field called as window size, right? In that window size, why that is used is, let us assume that window size is 14600. So what does it mean is, client is saying that I have a window, which means a buffer which can hold 14,600 bytes. Every MSS can contain 1460 bytes, and total my window size is 14,600 bytes. What does this mean? That the sender can send 10 packets, or 10 segments, each containing 1460 bytes each, right? So how to explain is, see, what I mean to say by this window size is, now there is client and there is server, right? There is connection established, and now the window size is nothing but the amount of buffer the client is reserving for this connection. So this is not the sending buffer, it is the receiving buffer. So now whenever this server sends any data, that data is going to come and sit in this buffer, right? Then how many packets can the server send before it gets any acknowledgement is 10 packets. Now I am saying that the buffer I have reserved for you is 14,600, right? 14,600, and then every packet is of size 1460. Then how many packets can be sent? It means that you can send 10 packets before getting the acknowledgement. So at one go, the server can send 10 packets, and client is having the space to hold 10 packets. And if server sends more than 10 packets, we don't have space to hold it. That is why it is called connection oriented. We are even reserving the buffers, right? So here this window size is nothing but what is the capacity of the client as a receiver, right? So why is this window size field used in that header is for the flow control. So window size is a field which is used to indicate capacity of the host as a receiver. Capacity of the host as a receiver. Why is it used? It is used for flow control. What is flow control? we are never supposed to send more than what a receiver is able to receive. Therefore, this field, this particular window size is used to, is used for flow control. Later I'll show you by taking a separate example how the flow control works. For now, understand that there is a field, special field called as window size, and which will tell you the maximum capacity of the receiver, right? So what did you understand from this first packet? We have chosen a sequence number of 521, and then we are indicating that this is the first sequence number I have chosen by using the SYN flag, and then MSS is actually chosen according to the network, in which network I am present, and then window size is 14600. So how do I know that this is what I am actually dedicating for this connection? So the other party cannot send more than 10 segments, right? Now whenever you send this, the other party is going to reply saying that yes, I got your request and I got everything. Let us say the other side will now choose a random initial sequence number, and the random initial sequence number chosen by the other side, assume that it is some number which is not this one. Let us say 2000. So what does that mean? From the other side, they are starting their communication with sequence number starting with 2000. From this side, we are starting the communication with sequence number starting with 521, right? So now you should even say that other side will say, my side, I am going to start with sequence number 2000, and this is the first sequence number, therefore SYN equal to 1, and in my network the maximum segment size allowed is, let us assume, 500 bytes. So what does this mean? The other side is saying that I will not be able to send 1460 bytes. I can send only 500 bytes, and you too please send me only 500 bytes. If you send more than 500 bytes in my network, there will be fragmentation headache, and I don't want to face it. Therefore, this side is saying 1460 is the MSS in my network, other side is saying 500 is the MSS in my network. Then both of them will come to the minimum, which means now both of them should agree for 500 only. That is, so it is a kind of negotiation going on, right? And the other side will say, I am also dedicating some buffers for you, and the buffers I dedicated for this connection is 5000 bytes. See, why only 5000? I am just picking this randomly. It need not be 5000, it could even be 10,000, right? So let us say 10,000. What does this mean? It means that the server is reserving some buffers, and the buffer is actually 10,000 bytes, and every packet is containing 500 bytes. Therefore, how many packets can the client send at one time? 20 packets, right? So you can send directly 20 packets in one window without worrying about the space at the other side. We are not supposed to send more than 20 bytes. That is the meaning of it. It is nothing but sliding window protocol, right? So sliding window protocol is implemented. So here you are saying that your sender window can be 20 segments, and the other side it is saying that your sender window can be 10. So now, depending on the MSS of 500, both of them will choose how many packets should be sent, isn't it? Now both of them should agree for 500, even though it is saying 1460, but since it has said 500, it is the minimum. So both of them should send only segments of size 500 each. And how many? The other side, the server cannot send more than 14 this much amount of data, and the client cannot send more than this much amount of data put together in all the segments. The reason is they are not able to hold it or handle it. Now, where is this MSS set? Again, in options only. There is no facility in the header. And where is this one? It is in the header, right? Along with this, the other side should also say that I have received the packet you have sent, which means it should even send the acknowledgement. So it is going to say, along with this one, acknowledgement number also. It will say acknowledgement number is, see, you have sent 521, I received it, and I am going to wait for the next byte 522. It is very important. Try to understand it. Whenever you send this SYN packet, whenever you send S5 equal to 1, that is also called as SYN packet. So always remember that SYN packet will eat up one sequence number. What does this mean? It means that whenever you send a packet with SYN equal to 1, whatever sequence number is present in that packet, that is consumed. Therefore, if you are sending the sequence number 521, it means that 521 is over. The next data byte will carry 522. Therefore other side should wait for 522. Therefore other side, when it sends the acknowledgement number, it says that I am waiting for 522. And where is this acknowledgement number present? Look at your header. In the third row below this source port sequence number, there is acknowledgement number. In that field we are going to put 522, and along with that ACK flag will be 1. So there is a flag called as ACK flag. Both are different. Acknowledgement number is a field which is 32-bit field, and ACK flag is 1 bit. So where is this ACK flag present? In the 1, 2, 3, 4. Fourth row you can see that ACK flag. So ACK flag equal to 1 means it indicates that the acknowledgement field in this packet is used. In this one I am not mentioning anything about ACK equal to 1. The reason is, when you are sending the first packet, you are not sending any acknowledgement on the packet, right? Why? Because you don't know what to acknowledge. It is the first time you are sending a packet. Therefore other side is going to send you the acknowledgement, therefore ACK equal to 1, but your side you are not sending any acknowledgement, therefore there is no ACK field here. So just remember that on every packet we are going to put the acknowledgement number on the header. It is also called as piggybacking. Piggybacking means whenever you are sending some packet, on that data packet itself you put the acknowledgement, that is called piggybacking. Therefore TCP uses piggybacking acknowledgements. Piggybacking means on the data you can put acknowledgement, or sometimes it will send only pure acknowledgement. So what does this mean is, if someone wants to send you the acknowledgement on the data packet itself, if it is the data and if it is the header, on the data packet itself they can put the acknowledgement. This is called piggybacking. Or if they want to send only the pure acknowledgement, what they could send is, they could take the header, and in the header they could put the acknowledgement and they can send it without any data. This is called pure acknowledgement. Therefore TCP uses both piggybacking acknowledgements and pure acknowledgements, which means whenever the other side has to send some data, on that data it will put the acknowledgement, that is called piggybacking. If the other side does not have any data to send, still it is supposed to send a acknowledgement. Why? Otherwise there will be a timeout on the other side, right? That is called pure acknowledgement. Okay. So now with this the reply is finished and you are supposed to send acknowledgement. So what is the acknowledgement is, you should say that yes, I got your parameters and I am comfortable with that. Let's go ahead and finish the connection. That is the meaning of it. So what should be the sequence number on this? Sequence number on this is, already you started with 521 and 521 is over for the first SYN packet, and now you should use 522. The reason is, other side is expecting 522, therefore your sequence number is 522. And what is this packet? This is the acknowledgement packet, therefore you should even put acknowledgement number. What is the acknowledgement number? Other side has sent 2000, therefore you should take 2001. 2001 is your acknowledgement number, which means other side you have received 2000 and now you are expecting 2001. And you should even say that this packet contains acknowledgement. This ACK flag indicates that this packet acknowledgement field is valid, please check it. If you put ACK equal to 0, it means that whatever field is present in this acknowledgement on this packet, that acknowledgement field, you please don't look at it, it is not used, right? And almost every packet will use the acknowledgement field. So 3 messages have been exchanged. So what is the main purpose of this? Connection establishment. How is connection establishment done? You are choosing a random initial sequence number and sending that sequence number. Along with that, you are sending some parameters like what is the maximum segment size in your network and what is your capacity as a receiver, so that the other side can send only maximum of this much size in one segment, and they can put all the segments together. Data should not exceed this much amount because you have only that much buffer to hold it, right? And the other side is sending their sequence number. Both of them can start with a random initial sequence number, right? And they should say this is the first sequence number I am using it, and according to their network parameters they can derive this MSS, and then they can say this is the maximum. So what does this mean? It means that you can send the segments of size this much, and all the segments put together they should not exceed this much. That is the capacity of mine. And along with that, they are even sending the acknowledgement. So one important thing which you should be careful about this is, always remember this. SYN packets. SYN packets means any packets which has SYN equal to 1 will consume one sequence number. Please remember it. And second one is, acknowledgement packets, which means if it is a pure acknowledgement like this one, that acknowledgement packet will not consume any sequence numbers, which means even though this acknowledgement packet is using 522, it doesn't mean that 522 is over. You can again use 522, right? So next time when you send any byte, this 522 is still available. 522 is not yet over. That is the second point. And fin packet I'll show you at the end. Fin packet, whenever the packet has fin equal to 1, it consumes one sequence number. And every data byte, one data byte will take one sequence number. Just keep it in mind. Synchronization packet will take one sequence number. Acknowledgement packet will take 0 sequence numbers. Fin packet will take one sequence number, and every data byte will take one sequence number. Therefore, if it is a pure acknowledgement, it means that no sequence numbers are consumed, which means this is a pure acknowledgement, which means that the sequence number which is used, 522, is not yet consumed. It is just sent, but it is not yet consumed, right? So just observe this. The first message which is sent from here to here, it is called first packet or request packet. And the second message which is sent from here to here, it is called a reply packet. And the third message which is sent from there, it is called acknowledgement packet. So after sending these three packets, connection will be established. Therefore, it is also called as three-way handshake. Three-way handshake means first message, second message, third message. After these three are over, then the connection is literally established. So after establishing the connection, we are going to do the data transfer. Now we shall see how the data transfer is going to happen. What I'll assume is, I'm just continuing the procedure. What you could do is, in your book, you can continue this timeline. Timeline is going from top to down. In your book, what you could do is, you can continue this timeline diagram. But then what I'll do is, I'll draw it separately, which means after this connection establishment phase, immediately data transfer will start. But then I'm showing you differently because I don't have space to show here. Okay. Now let's see the data transfer phase. I'm going to continue the diagram just from where I left here, which means whatever numbers we have seen till now, I'm just using the same numbers and continuing it. So data transfer will be like this. You can draw the diagram continuing that one, but I'm just drawing it separately. Say this is the client and this is the server. And now assume that client and server is here. Now client wants to send 100 bytes of data. After the connection got established, client wants to send 100 bytes of data. Then what is the sequence number of the first byte? So see here where we left, the sequence number we used is, we started with 521 and we consumed it for the SYN packet, and then next sequence number we used is 522, but then it is not yet consumed, it is still available. Therefore the first sequence number available is 522 only. The reason why 522 is still available is, it is not yet consumed by the pure acknowledgement, right? And I'm assuming that I'm sending totally 100 bytes of data. Then what will be the last byte sequence number, as you know? So this one will be calculated at the receiver side, but still I'm just curious and I'm finding it out. It doesn't mean that client has to compute it as of now. I'm just asking you that question. So what will be this? 621. So 621 is the last byte sequence number and we are sending 100 bytes. Therefore, when this packet is being sent, on this packet, what are the fields? Sequence number of the packet will always be the sequence of the segment. That segment will always be the sequence number of the first byte. So what is sequence number of the first byte here? 522, right? And along with that, what are the other factors that are required? So next factor that is required is ACK. ACK flag will always be 1, which means every packet is going to carry with it an acknowledgement on this. The reason is, already in the header, either you use it or not, that particular field is reserved. Therefore, it is better that you use it. The reason is, header is always going to contain a reserved field, a field which is reserved for acknowledgement number. So even if you use it or not, that is going to go wasted. So why to waste it? Just use it. That is the reason we are using it. Okay. And what is the advantage of sending acknowledgement on all the frames is, on all the segments is, in case if previous acknowledgement is lost, then the next packet is going to carry it as a backup. Therefore, it is going to be advantageous, right? If one acknowledgement is lost, anyway the next segment which is going to go is always going to carry the acknowledgement, right? Now, sequence number acknowledgement equal to 1. What is the acknowledgement number on this one? So what is the number that you are expecting from the other side? Other side started with 2000 and it consumed that 2000 once for the SYN packet and it did not send anything else. Therefore, you are still expecting 2001 only. So it is not containing any new acknowledgement. It is containing just the previous acknowledgement. But then why are we sending two times? We'll send it every time because it is already available, it is free to use, and in some cases it will be helpful for us in case the previous acknowledgement is lost. Okay, and now this one is received. So the receiver has received 100 bytes of data. Now what receiver will do is, every time whenever receiver receives a packet, it will not immediately send out the acknowledgement, it will wait for some time. That is called acknowledgement timer. We shall see these timers later again, but for now understand that sender is not going to immediately send the acknowledgement, he is going to wait for some time. In that time, if the sender has some more data to send back, on that data it will put the acknowledgement. Now assume that sender has to send that server has to send 100 bytes of data. 100 bytes of data. What will be the sequence number of the first byte? So they started with 2000 and they didn't use anything after that. Therefore 2000 is over, and what is the next number available? 2001. 2001 is the next byte available, and from there we have to go till 100. So what is the last byte sequence number? 2100. So 1 to 100 is 100 bytes. Therefore these are the sequence numbers. On this segment, when it is sent from the server to client, sequence number on that segment will be 2001. So what does that mean? The first byte sequence number in the segment is 2001 and it will carry acknowledgement. Therefore ACK flag equal to 1. What is the acknowledgement number? Which means what is the byte number that the server is expecting next. That depends on what is the byte number that the server has received till now. So server has received from 522 to 621. Therefore what is the next byte sequence number that the server expects? 622. Okay, so how did we calculate it? When you have sent 522 to this one, then it knows that the next one expected is this. How will the receiver calculate it? We have already seen a problem, right? So if you don't remember it, go back to the video where I discussed about the header size. In that header size header length field, I told you how the receiver will calculate what is the acknowledgement number. Whenever it receives the segment, it is going to find out the total size of the segment, and then it is going to see the first byte sequence number. From there it is going to calculate the last byte sequence number. I told you that. Okay, so that is how it knows the acknowledgement. Now the client has received data of 100 bytes and now it has to send the acknowledgement. It will wait for some time for the data to get ready. In case if the data didn't get ready, then you should not wait for a long time. The reason is, if you wait for the data to be sent to the other side, on which if you want to put the acknowledgement, there is a chance that your data might get delayed, because of which there will be a timeout on the other side. See, sender side there will be timeout timer, receiver side there will be acknowledgement timer. Both of them have to be synchronized well. For this concept, you please refer to flow control mechanisms. I think the mechanism is go backend. In go backend I discussed about the timers. Here I am not showing you the timers because it is going to complicate. But then remember that whenever you get any data, if you don't have any data to send, better send a pure acknowledgement. Therefore from this side you are supposed to send a pure acknowledgement. This is pure acknowledgement. Pure acknowledgement will simply contain the header, no data. Therefore it will not consume any sequence number. Even though it is going to carry a sequence number, it is still available for you for the next time, right? So what is the sequence number on this packet? Every packet should contain sequence number. Everything that you send from one side should contain sequence number. Therefore what should be the sequence number on this one? So watch it. We have started with 522 and used till 621. Therefore what is the next available sequence number? 622. that is why. Other side is also expecting 622, that is why you are using 622. And this is the acknowledgement packet, which means the acknowledgement field on this is valid. And what is the acknowledgement number? So what is that you received? You have received from 2001 to 2100. Therefore, what is the next byte that you are expecting from the other side? 2101, right? That is the acknowledgement number. Now after some time, assume that this client has got some data to send, 100 bytes to send. Why only 100 bytes? It actually, we should not send 100 bytes, we should send a complete MSS, maximum segment size, which we agreed upon, 500 bytes. But let us assume that, no, I'm just taking it for the sake of simplicity. But general what happens is, TCP will wait until it gets 500 bytes from the application layer and puts all the 500 bytes in one packet and send it. In case if the sender is sending, application is sending very slowly, then it will send 100 bytes. But for now, just for the sake of simplicity, assume that we are sending 100 bytes. 100 bytes only. What is the sequence number of the first byte? This byte. So where did you start? You have left it at 621. Therefore, the next available sequence number is 622. Even though you have sent the acknowledgement with 622, that acknowledgement is not yet over. Even though you have sent with 622 already, that sequence number is not yet over. The reason is acknowledgements will not take sequence number, right? Will not consume sequence number. Now 622 is the first one. Then what is the last one? 721. So the last byte sequence number is 721, and when you are sending this packet, on that packet sequence number is 622. Why? That is the sequence number of the first byte, and it should contain the acknowledgement. Even though you receive something from the other side or not, you should always be sending acknowledgement on every packet. What is the acknowledgement? You are still expecting 2101 only. The reason is other side didn't send anything yet, right? Now assume that other side is willing to send 100 bytes of data. 100 bytes of data. Then what is the sequence number of the first byte? Sequence number of the first byte is, where did you leave? 2100, right? Therefore 2101. So what will be the last byte sequence number? 2200. So you please work on these numbers. How am I getting 100 numbers from here to here? You should be knowing that. Then what will be the sequence number on that packet? Sequence number on that packet is 2101. And what is the acknowledgement that it should carry? Whatever we got from the other side. So what did we get from the other side? 622 to 721. Therefore, what is the next acknowledgement, next byte acknowledge sequence number you are expecting? The next byte number you are expecting is 722. So that is how the data will be transferred. So what is the data transfer phase? We are sending some packets and getting the acknowledgement, and every packet is going to contain the acknowledgement even if the other side didn't send anything to us, right? So that is how the data transfer phase will happen. Now we have seen two phases of connection management. One is connection establishment, which is three-way handshake, and after that data is being transferred. Now if you look at the packets, all the packets are having some flags set. So one is SYN flag and other is ACK flag. These two flags we have seen till now, right? So now let's see what are the packets or what is the meaning of these flags, right? So I hope that you have already copied these two. If you have not copied, you can pause the video and copy this, and I'll just move on to the next phase. Next phase is connection termination, and before going to this connection termination, we shall examine what is the meaning of these flags. So if you observe it, you can refer to your book. If you have already written this, I just erased it. So some of the packets are containing SYN flag, and some of the segments are containing ACK flag, right? So initially when you are sending the first request, so SYN flag can be 10, or it can be 11, or it can be 01, or it can be 00. Now let's examine what is the meaning or what do you understand with these two flags. So whenever SYN flag equal to 1, ACK equal to 0, it is nothing but the first packet or first segment, right? First segment, and it is called request segment or request. So whenever 10 is used, it is the first segment or request segment, and whenever 11 is used, it is the second segment. You can look at it in your connection establishment phase. The first one is having sin equal to 1, and I didn't talk about ACK at all. When I didn't talk about ACK, assume that it is 0, right? And the second reply, the reply is having sin equal to 1 and ACK equal to 1. So whenever sin equal to 1 and ACK equal to 1, you can understand that that is the second segment, or that is the reply segment, isn't it? And whenever you have 0 1, it means that it is the third segment, or it can be any other segment which contains the acknowledgement. So this indicates that acknowledgement is present. It need not be only the second one. It indicates that acknowledgement is present in the header. That is the meaning of it, right? Therefore, all the packets except the first one, only the first one will contain ACK equal to 0. All the segments except the first segment should always contain ACK equal to 1, always. That is the rule. The rule is everyone is going to carry the acknowledgement. Even if you receive something or not, you are always supposed to carry a acknowledgement, right? And now what about 0 0? 0 0 means this 0 indicates that it is not the first one or second one. It is anything from the third one, and this 0 indicates that it is not the third one also. So it is not at all possible. The reason is, why is it not possible is, if sin flag is 0, then it definitely means that it is not the first one. Anything other than the first one should always contain acknowledgement equal to 1. So that is the rule, and it is not possible. Okay. So using this sin and acknowledgement, you can find out what is the position of the packet, or what does the actual segment mean. 10 means it is the first request segment, 11 means it is the second reply segment, and 01 means it could be any segment other than the first one and second one, and 00 is never possible. Okay. Now let's see connection termination. Connection termination means we want, the client and server, they are done with the communication and they want to close the connection. So how does it work is, I am just starting wherever I left this. I am just using this diagram, and from this whatever sequence numbers are remaining, I am continuing this diagram. So I told you that TCP is a full duplex connection. Full duplex means if there is client and server, data will go in both the directions. Data can go from client to server, as well as data can come from server to client. Therefore it is a full duplex connection. So terminating a connection is terminating this as well as terminating this, right? So both of them have to happen. Now let's see how it happens. Assume that client is done with sending the data, and now client wants to close the connection. Client is done with sending the data and client wants to close the connection. Just see what is the sequence number available next for the client. It has used from 622 to 721. Therefore, what is the next sequence number available at the client side? 722. Therefore, on this packet, sequence number will be 722. And on this one, it should always contain ACK equal to 1. And what should be the acknowledgement number? What is it expecting from the other side? From the other side, we got till 2200. So we didn't acknowledge that one. So here itself acknowledgement has to be sent. Let us say we already sent the pure acknowledgement. Pure acknowledgement. Previously I forgot to send this pure acknowledgement. And in this pure acknowledgement, what should be sequence number? Sequence number available is 722, and it is the acknowledgement, and the acknowledgement number is, how much is the acknowledgement? 2201. Why? We got till 2200, therefore the next sequence number is, next byte expected is 2201. Now what is the acknowledgement number? Again 2201 only, because after that we didn't receive anything. So what happened? We are using the sequence number 722 because that is where we left out. So last sequence number actually sent is 721. Therefore next sequence number which is available is 722. And after that 722, the next sequence number available is 722. After that a pure acknowledgement is sent. Even though that acknowledgement packet is carrying 722, it is not yet consumed. The reason is pure acknowledgements don't consume any sequence numbers, right? So in this one we are sending fin equal to 1. Fin means finish flag. It is used to terminate the connection, right? So whenever I send this packet, then what happens is client is saying this server that I don't have any packets to send, therefore you please free up the resources. Connection establishment means allocate the resources, and connection termination means free up the resources. In C language, how it will be implemented is, whenever connection is established, there will be malloc. Malloc means memory allocation, and whenever connection is terminated, there will be free call. Free means release the buffers, right? So here connection many people misunderstand this to be connection establishment means wired connection and connectionless means wireless. That is wrong. And connection termination is definitely not cutting the wires with any scissors. That is wrong. Okay, connection termination means we are actually trying to free up the buffers here. Now what happens is, whenever you are sending fin, you are saying the server that please free up this buffer. That is what you are saying. So buffers will be freed up. Now after freeing up the buffer, server will say yes, I freed up. For that, server will send the acknowledgement. It will send sequence number with, what is the sequence number that the server is next having? It has used till 2200. So what is the next sequence number available? 2201, and it will contain the acknowledgement. Therefore ACK equal to 1. What is the acknowledgement number? Acknowledgement number on this packet will be, so what is that you have sent? 722, and I told you that fin packet will take up one sequence number. Remember it? Sin will take one sequence number, fin will take one sequence number, and data will take one sequence number. Pure acknowledgement will take 0 sequence numbers, right? Therefore 722 is already sent, and we assume that 722 is consumed. Therefore what is the next sequence number available? 723. That is the meaning of it. So once you get this, it means that connection is terminated. From client to server, only one way. It is a full duplex connection, only one way connection is terminated, which means now client cannot send any data. So let's see the questions which are possible. After client has terminated the connection, which means after client has sent the fin packet, what are the events that are possible and what are the events that are not possible? Can data be sent from client to server? Buffers are not present there, therefore data cannot be sent. It is not possible. Can data be sent from server to client, which means from here to here, can data be sent? Yes. The reason is server to client, data can be sent. The reason is the other side connection is still open, which means the buffers at client is still present. Therefore data can be sent from server to client. Can acknowledgements be sent? Acknowledgements be sent from client to server? Yes or no? So can I send the acknowledgement from here to here? Which means I don't have buffers here, but can I send acknowledgements? Acknowledgements can be sent because acknowledgement doesn't contain any data, therefore you don't need any buffers to store it. And acknowledgements are mandatory because when you are sending the when you are getting the data from the other side, you are supposed to send the acknowledgements. Therefore acknowledgements have to be sent, which are pure acknowledgements. Whenever you get any data from the server, you cannot send the data back, but then you have to send the acknowledgement. Otherwise what happens is there will be a timeout at the other side, right? Can acknowledgements be sent from server to client? Can server send the acknowledgement to client? Not required. The reason is you are not getting any data from other side, then why should you send the acknowledgement? Therefore not required, but then you will send some acknowledgement. The reason is piggybacking acknowledgements are always used, isn't it? Therefore acknowledgements are sent which are piggybacked. In this case acknowledgements are sent which are pure. Piggybacking means whenever this data is sent from server to client, on that data we are putting the acknowledgement. Therefore it is possible, right? So this is nothing but connection termination, terminating the connection one side. Then what happens is after this connection is terminated, if server wants to send some data to client, it can still send it. It can still send it, no problem. But then if it doesn't have any data to send, it can also terminate the connection. At this point only it can send fin equal to 1 and with the acknowledgement it will be closed, or just for the sake of explanation I am taking it separately. You could have actually closed the connection here itself. Which connection? Server to client, by sending fin equal to 1 on this acknowledgement, no problem. But then I just want to do it separately so that it will be clear for you. Okay. So now if the client server wants to close the connection, what it will send is, it will send a packet. On that packet, what will be sequence number? What is the sequence number available next at the server side? 2201. And it should always contain acknowledgement number, right? What is the acknowledgement number that should be present on this? What is the acknowledgement number that it is expecting next? 723. Therefore acknowledgement number is 723 only. The reason is here. And on this one it will send fin equal to 1, which means I too want to close the connection. Then what will client do? Client will free up the buffer. That is how the connection is terminated, right? And client will say, yes, I terminated. Therefore client will send a packet. It is not required, but still. So what will be the sequence number on the packet? What is the next sequence number available? 723. Why? 722 is over, right? Therefore 723, and it will send a acknowledgement. What is the acknowledgement number? We have sent, the server has sent 2201. Therefore what is the next byte sequence number? It is consumed. Fin packet will always consume the sequence number. Therefore what is the next byte sequence number available? 2202. That is what we expect. So that is the acknowledgement. So by sending this, connection will be terminated. This is called connection termination, which requires 4 packets. Connection establishment requires 3 packets, and then data transfer, and in worst case connection termination requires 4 packets. Or if you want to do it in a better way, what you could do is, on the last packet whichever you are sending, here itself you could send fin equal to 1 if the client wants to send the close the connection. In the last packet itself you can send fin, which means you want to close the connection, and on the return packet, the acknowledgement packet, server can send fin, which means it also wants to close the connection, and finally you can send a acknowledgement. In 3 packets also you can close it, but then in worst case we require 4 packets. Therefore 3 packets are for connection establishment, 4 packets are required for the connection termination, and then more packets are required for the data transfer. This is how connection is managed. This is called as connection management in TCP. It contains 3 phases: establishment, data transfer, termination. Therefore fin flag is used for termination. So we have seen about 3 flags. One is SYN flag, one is the ACK flag, and other is fin flag, right? This is all about it. So in the process of connection management, we have seen that we are using mainly 3 flags. One flag is SYN flag, other flag is ACK flag, and other one is fin. Now let's you can write down about these 3. So one is SYN flag, synchronization flag. Why is this used? This is used for synchronizing the sequence numbers. Synchronizing sequence numbers. So what do you mean by synchronizing sequence numbers is, both these sides will have different sequence numbers, and they start with a random initial sequence number, and before anything could start you should say the other side what is the sequence number that you are expecting. What is the sequence number that they should expect from your side, and the other side should also say what is the sequence number that you should expect from their side. So just letting both the sides know what is your random initial sequence number is done by using SYN flag. And then next one is ACK flag. This is used because previously what used to happen is, even though we have this acknowledgement flag, acknowledgement field, see there are 2 things, one is acknowledgement field and other is acknowledgement flag. The third row, I think if you look at the third row is acknowledgement number. That acknowledgement number field is always present on every packet, but then every packet need not carry the acknowledgement. Therefore this ACK flag will indicate whether the acknowledgement number field is containing the acknowledgement or not, which means if ACK, this flag is used to indicate, this will indicate whether this acknowledgement number field is valid or not. It need not be valid all the time, right? So it may be, which means all the packets may not contain, or all the packets need not contain the acknowledgement number. So this is going to indicate that. And next one is fin flag. This fin flag is nothing but it is a request for connection termination. So whenever you want to terminate the connection, you are going to send a packet with fin equal to 1. It is request for connection termination. So what is connection termination? Freeing up the resources. What is connection establishment? Resolving the resources. So these three flags we have seen. Okay. Now look at the checksum field of TCP. If you see that header 1, 2, 3, 4, 5, fifth row first part is checksum. So we are having 16-bit checksum. So checksum here is 16-bit, right? So 16-bit checksum is used, and how it is used is, previously we had seen checksum at IP, but then that was IP header checksum. So already we have seen that IP datagram is also having a checksum field, which was header checksum, which means checksum is computed on the IP header. Now I am showing you that inside this IP there is TCP present. Now in TCP it is simply checksum, not the header checksum, which means in TCP checksum calculation it takes care of TCP header as well as TCP data also. So checksum is calculated both on TCP header and TCP data as well as on IP header too. Already IP header checksum is computed once, and again we are going to compute the checksum on IP header at TCP also. Why is that so? Which means TCP header and then TCP data and then IP header. On these three fields checksum is computed. So why do you think that checksum is computed on this IP header also? So in order to explain you, I'll just take an example and explain you. Just watch it. Let us assume that there is a house here and there is a house here. In some, these two are in different places, different cities, and there is a person here and who wants to write a letter, let us say love letter, to a girl here, right? And let us assume that he has written the entire letter, and then he has written to some Janu and all and everything, blah blah blah, and then yours lovingly he has written his entire address. He has written that my name is so and so and entire address, and he has kept this letter in an envelope. And now this envelope, on the envelope he is going to write the to address. Let us assume that the house door number is 100, so he has written door number 100 and the full address completely, and he has sent it, right? And now by mistake, when this letter is on the way, the address on the envelope got corrupted such that it has reflected a different address, which means instead of having 100, by the time the letter is going on, it reflected a different address, and the address on the envelope got changed to door number 101, and inside that there is this love letter, and therefore it is delivered to a different house which is not this house, right? And assume that there is also one more girl there, right? And the worst case is, let us say she is married now. Now what happens? Now you are sending a letter. Already on that letter there is address, and inside that your address is also there, but now that letter is having a different address, right? So what will happen now? Now if it is found out that you are writing a letter to a different girl, then there is a problem, isn't it? Already there is some person here, there is a problem with that. Now how can you stop it from happening? Which means you don't want the letter to be delivered wrongly to the wrong person, right? So how can you stop it? So one solution is, instead of writing the address on the envelope, you write the address inside the letter, right? Which means on the letter inside the envelope. But then if you write it only inside the envelope, then the postman will not be able to see the address. Therefore write the address on the envelope as well as inside the envelope on the letter. Write the address 2 times. So that is how here also the same thing is happening, which means this envelope is nothing but IP packet, and inside that the TCP packet is nothing but the letter. Now instead of checking the checksum once, instead of using this IP header once, we are using the IP header checksum here as well as here, so that if there is anything wrong, 2 times it will be verified, which means whenever the packet is delivered to the host, If the letter on this, the address on this is going to say that it is the same address, fine, but then again before opening the letter and then reading it, one more time it will be checked whether it is received by the same process or not, which means at transport layer we have one more checking, at network layer we are going to have one checking whether it is given to the same host or not using the IP address, and again at network layer we have one more checking whether it is given to the same host or not. So similarly here, so for that reason what we are going to do is, at TCP, checksum is calculated on the TCP header as well as TCP data, and along with that checksum is calculated on the TCP header also, IP header also. So in the calculation of IP head, this TCP checksum, we are going to include TCP header plus TCP data plus IP header. But there is a small problem if I use the IP header here. The problem is, if I use the entire IP header, at sender we are going to get some value for the checksum, but at the receiver side, by the time this packet is received by the receiver, the checksum might change. The reason is many of the fields in the IP might change. So we are not going to include the total IP header. The reason is many of the fields are going to change. So if you compute the checksum using the IP header at the sender, and again at the receiver if you include TCP header, TCP data, which will not change, but if you take again the IP header and recheck the checksum, then that will show a different value. Therefore we are not going to include all the fields in the IP header in the checksum calculation. So how we are going to use only important fields which are not going to change definitely. So what are the fields that doesn't change is, source IP is not going to change when the packet receives the destination, and destination IP doesn't change when the packet reaches the destination, and along with this protocol field, the protocol field doesn't change, which is nothing but the TCP inside it, and along with that TCP segment length. TCP segment length doesn't change. TCP segment length is nothing but total length minus header length, which is nothing but TCP segment length, and this field is zeros, right? So 8 bits of zeros are used, 8 bits of protocol field is used, and 16 bits of TCP segment is used, and 32 bits and 32 bits. So this is called as pseudo IP header, not the real IP header, pseudo IP header. So while calculating the checksum at TCP, it is calculated on TCP header, TCP data, as well as pseudo IP header, not the complete IP header. Okay, and along with this pseudo IP header, the pseudo IP header is just used in the checksum computation, but this is not actually transmitted. Other side will derive it from the IP header. So this part is actually used only in the computation and not used in transmission. So what will be transmitted is only IP header checksum. Okay, sorry, IP checksum in the header. So that is all about the checksum. So one important question is, they will ask you why IP pseudo header is included in the TCP checksum, even though already IP checksum is computing on the IP header. The reason is we want to have a double checking. One is at the network layer using the IP checksum, and other is at the transport layer using the pseudo header, right? So therefore we are using it 2 times. This will ensure that a packet is by mistake not delivered to a wrong host. So the problem is, if something happens in the IP header, and if this IP address is, let us say, IP1 and this IP address is IP2, and by mistake there is a small error in the IP header and IP1 got changed to IP2 and the IP checksum is not able to catch it, then what happens is the packet will be wrongly delivered to IP2, and inside that IP2, if there is a host with the same port number, if you wanted to send it to port number 80, here also there is a host with port number 80, then the packet will be delivered to this process. So before delivering the packet to this process with 80, we again cross check whether the destination is actually right one or not by using this pseudo header. That is how TCP checksum is going to do double checking before delivering the packet. It is all about the checksum field. Let's now see TCP congestion control. So I'm just pulling out all the routers. Let us say the entire all the routers are kept in this circle. and there are lots of routers in the world like this. This is completely the internet, assume that, and now all of them are connected in some way, so that any packet is in some kind of tree or something. Okay, and let's now say there is a sender here and there is a receiver, right? So assume that the receiver has said that sender can send 1 GB of data in the advertisement window. Therefore, sender window size is set to be 1 GB. The reason is receiver said that I have a capacity to receive 1 GB, right? And assume that MSS, maximum segment size of each segment, is 1 MB, or 1 MB, right? Then how many segments will be there? Totally how many segments will be, the sender can send 1024 segments the sender can send. The reason is, in its window, in the sending window, it can put 1024 and it can send all the segment at once to the receiver. Now in order to send the segments to the receiver, what should sender do is, it should put all of them onto the network, right? Then the problem is, even though the receiver is able to receive 1 GB, the underlying network, it might not be in a position to hold 1024 packets. The reason is, all of them might be heavily loaded that the total capacity of the network put together, it might not be able to hold 1024 packets or 1 GB of data completely. So sender should not dump the data onto the network without finding out the capacity of the network. How can we find out the capacity of the receiver? By using the receiver is going to say it explicitly, is going to send the advertisement window, but then we don't know what is the capacity of the network. So let us say capacity of the network is WC. Then how can we know the capacity of the network? The reason is, we cannot send more than what the network can handle or more than what the receiver can handle. Let us assume that somehow we found out the capacity of the network to be WC and capacity of the receiver is WR. Then a sender should always send a minimum of these two. Sometimes what happens is, receiver can say that I can receive 1 GB of data, but the underlying network can say I have the capacity of only 1 MB. Then what should you send? Actual sender window should be only 1 MB. Sometimes this network can say I can receive 1 GB of data, but the receiver can say I can receive only 1 MB of data. Then what should we send? Only 1 MB. So anyway, whatever is the minimum of these two, we should only send that much amount of data. If you send more than that, either the network will discard it or the receiver will discard it, and we have to unnecessarily retransmit it. So we want to stop the traffic so that the network is safe and the receiver is safe. Now in order to take care of the receiver, we are going to use flow control and advertisement window. So advertisement window field, which is present inside our packet, is going to protect the receiver, and that is called flow control. Now how can we protect the network? For this protecting the network, we need congestion control. So congestion control is used in order to protect the network from dumping the data. See, the problem is, there is no way you can find out the capacity of the network. The reason is, network capacity could be anything, and there is no central authority who is sitting and then observing the entire traffic and who can derive the entire capacity of the network and give it like this so that you can use it. There is no one who is going to do that for you. So it is your own responsibility to find out the capacity of the network. So TCP uses end-to-end congestion control. In 1980s, what happened is, this end-to-end congestion control was not there, and everyone was dumping the data onto the network, and suddenly the network is going down because of the heavy traffic, and it is never recovering. The reason is, no one is stopping. Let us assume that you are sending some data and data is discarded. Then what will you do? You will not wait for more time. You will continuously keep on retransmitting the data, and you will never give the network a time to recover from this heavy traffic, right? So because of this, they faced lots of problems in 1980. That was called as congestion meltdown. Congestion meltdown was a severe problem in 1980s. Now we don't hear about it, but back then it was a severe problem that has been solved by using various techniques. One of the technique is TCP congestion control. Therefore, TCP congestion control is going to be like a protective layer for our network. our network is surviving, our internet is surviving only because of TCP protection. So how does it work is, now the best way to stop the data or the traffic is at the source. So whoever the source is, they should not dump the data onto the network without finding the capacity of the network. Unless they find it out, they should not do it, right? So let's see how this congestion control works. Now I'll take an example, small example, and explain you how we could find out whether the network is in a position to handle these many packets or not. So before going ahead, there are actually various parameters here. One parameter is receiver is always going to receive the packets and then decrease its size of the window. If it is slow, what it does is, let us say its capacity now is 1 GB, and if you send half GB, then next time its capacity becomes half GB. Accordingly, you have to again change many things, including this congestion control algorithm. But for the sake of assumption, I assume that receiver is going to advertise. For the sake of simplicity, I am assuming that receiver is going to advertise some size and it is going to fix that number forever. Forever means for this problem. Otherwise, what happens is, if receiver is going to change its capacity continuously, then it is very difficult to execute this algorithm. So my assumption is that receiver is going to advertise some size and it is going to fix there, which means it is not going to change from there. That is the basic assumption. Let's see about application layer protocols. So application layer is responsible for all these services that the internet will provide. So at user side, application layer will be responsible for the for making things easier for the user. And at the server side, I mean the client side, application layer is for the user, and the server side, application layer is where that particular server is going to provide the service to the client. So anyway, there are thousands of services in the internet, and for every service there is some kind of application layer protocol available. For example, for web service, HTTPS is used, right? Like that, there are thousands of services and thousands of protocols which are running at application layer, lots of them. And every now and then a new protocol will come up every day. Therefore, we are just lucky that we don't have all the application layer protocols in syllabus. We have only few. So to name them, the application layer protocols which are there in the syllabus, they have explicitly given them. So one is DNS, HTTP, FTP, SMTP, and POP. So they have specifically mentioned these protocols in the application layer, in the syllabus. If you look at the syllabus, they'll write application layer protocols within brackets, these 5, and along with that, by mistake, they have even written this ICMP. Remember that ICMP works at network layer, not at application layer. By mistake, they have given it. So now, among all these thousands of protocols available, why do you think that they are interested only in 5, or why do you think that in GATE only 5 protocols are implemented, are asked? There are thousands of protocols at application layer, right? So why do you think that only these 5 are there included in the syllabus? So I'll just tell you the answer. In order to implement any website, if you have to design your own website, then you need all these protocols. So why do you need all these protocols? First thing is, you will have a website name, isn't it? So domain name. Now that domain name has to be mapped into IP address. You are going to give domain name to everyone, but then that has to be converted to IP address. For that we need DNS. And then you will be preparing your web pages in your local host, and those web pages have to be moved onto the server from where people can fetch them. Obviously, you are not going to run a website at your home computer. The reason is, you need 100% availability, right? 24/7 availability. It should be available all the time, and your home computers are very unreliable, in the sense you might have power failure or internet failure, or there are lots of problems. That is why it is better that you take services from some people like GoDaddy, right? Or Amazon Web Services, where you take a machine for rent, and on that machine you are going to host your web server. For that reason, you have to prepare the web pages at home, and now you have to transfer those files to some remote location, right? So that is why you need a file server, because file transfer protocol is used to transfer the web pages which you have built at home, and now you want to put it up at the server so that people can fetch them. And then HTTP is, once you have started a website, web server is on, then using the HTTP people will get the web pages, right? And SMTP is for emailing. Now let us say you want to have a contact us button, and there you have given some email ID. If people email you there, then that email has to be directed to your email or to some point or to some place, so that you can, some people can contact with you. Therefore you need this SMTP services. So SMTP is for emails, right? These are for files, these are for web pages. And now once any email is sent using SMTP, you can open it using POP. Therefore POP is for retrieving the emails. Therefore using these 5 basic protocols, you can build and implement any website. So let's get into details. Let's talk about all these one by one. Okay, let's now see about HTTP. HTTP is the most popular protocol in the internet. Because of the HTTP only, because of the World Wide Web, the entire internet has this much popularity now. So HTTP is a very basic protocol which has been there since 1990s, and even now it is very popular. So HTTP is mainly used for getting the web pages. So some important things, there is lot to be studying about HTTP, but I am going to teach you only important things which are very important for GET. So there is a lot actually only about this HTTP. There are various textbooks written which will contain at least 300 pages. So it is a very big topic, but let's not stick on to only the basics which will be important for GET. So first thing is HTTP runs at port number 80, and if you want to have any web page, you are supposed to contact the server. So there will be some server running, and you are supposed to contact the server at port number 80, and it will send you the web page, right? So web pages, getting the web pages can be done using HTTP. Okay, this is the main thing. And what are the various things about other things about HTTP is HTTP wants reliability. So whatever the underlying at application layer HTTP is running, whatever the underlying ISO-OSI model or whatever TCP/IP or X.25, whatever the underlying network protocols are, they are all supposed to provide reliability to HTTP. So HTTP always relies on reliable support from the layers underlying the application layer. It need not be TCP/IP. Any other protocol suite which is below this application layer which is supporting HTTP should always provide reliability. HTTP doesn't provide reliability by itself. It depends on the underlying layers like TCP. Therefore HTTP uses, very important, HTTP uses TCP at transport layer. The reason is, so whenever application, so HTTP expects that whatever transport layer TCP gives it, that is all reliable data, which means if some packet is lost, or if some data is lost, or if you get duplicate packets, or if the data is out of order, everything has to be taken care by TCP. HTTP doesn't know anything about it. Whatever TCP shows, HTTP will believe it. So there is no inbuilt facility in HTTP to provide reliability. So any service which does not use TCP should have an inbuilt facility which is required by the application to be reliable. So if you are using TCP, it is completely relying on the TCP. And the next one is HTTP is in-band protocol. In-band protocol means both the commands as well as data, they go in only one connection, which means there will be only one connection established between these two, and either the data or the commands, either if you are sending a command or if you are sending data, everything goes in the same stream, and there is no distinction made between the commands and data. Both of them have to go and sit in the same buffers, and both will be processed as if they are data only. So the commands will not get high priority here. It is simply this in-band protocol. In-band means commands and data will go in the same connection. There is no separate connection for commands. And HTTP is stateless protocol. Stateless protocol means it is not going to maintain any information about the users. For example, if there is a website like www.ravindrababuravula.com, if you visit my website, I am not going to maintain any information about you. The reason is there will be millions of visits for a website every day. and if you keep on recording in the logs about every visitor who has visited you, then the database is going to be very high, right? And that database storing is a problem on the server machine. Therefore the server machine will run out of the memory, so unnecessarily we are not going to save any information about the users. But then some websites, they really want to know much about their users, which means they want to know about what are the activities that a user has done on the previous time, and depending on which they want to show the next activities. For example, on Amazon.com, if you have bought the book Harry Potter third part 3, then next time when you visit the Amazon.com website, it is better that they show you part 4, right? So anyways, Amazon is a separate implementation. They are actually logging in every user, but let us say there is some other e-commerce website or some other website which want to know about your previous activities, and depending on which they want to show you the next page. Then what will they do is, they will create a concept, they will create a small packet called as cookie, and they will drop it on the user side, which means as a server there will be no information stored about the client. On the client side, the server will drop a packet called as cookie, and now whenever this client goes to the server for the next time connection, server will see this cookie, which means client will show the cookie, and client will see it, server will see it, and understand that, oh, previously this is the history happened between me and that client, therefore I can continue with him by showing the next pages. Therefore cookies are used because it is stateless. It is very important. Remember that HTTP is a stateless protocol. Stateless means it doesn't have anything about the clients. And two popular versions of HTTP is HTTP 1.0. it was non-persistent. It used non-persistent connection. So non-persistent means if you have 10 objects in a website, what is an object is, the HTML page is an object, and inside that there are pictures, right? All these pictures are generally objects, and all these objects will be fetched in order to show the web page. Let us say in a web page there are 10 pictures, and then in order to organize these pictures, the entire code is present in a HTML file. Now if there are 10 objects, then if you use HTTP 1.0 version, then it is a non-persistent connection. Every object, in order to get every object, one connection will be opened, and after getting one object, that connection will be closed. Therefore if you use non-persistent connections, then for 11 objects, if there are 10 pictures plus the HTML page, for 11 objects, 11 connections will be opened, and from every connection one object will be fetched and then closed. But then HTTP 1.1 is using persistent connection. Persistent connection means there will be only one connection established, and that one connection is going to fetch all the data, right? So what is the advantage of using non-persistent and persistent is, in non-persistent the server need not hold the connection for a long time, and it will immediately close the connection. But in persistent, the server is going to hold the connection for a long time, and what is the benefit out of it is, the consumption window, when it is downloading many packets, then the consumption window will grow very fast. Therefore in persistent, bandwidth will be high, but it is risky for the server. The reason is, it has to open a connection for a long time, it has to keep a connection open for a long time. Anyways, there are many, even these days, this Google and Amazon, they are investing lots of money into the servers, that when you open a connection with the server, they are going to keep you always on, always logged in, which means for you the connection is going to be open all the time. It is not a problem for them because it is their business. And some websites, they don't their business is not making money from your online customers, like IRCTC. So they are not going to have this connection open for a long time. So if you open a connection with IRCTC and you don't do anything for some time, you will say that connection is terminated. The reason is, they have keep alive timers, and using which they are going to cut the connection if you are idle for some time. Their business is not making money out of the online users, isn't it? But if you look at a Gmail account, you can open the Gmail account for days together, and never you are going to get anything like connection terminated or anything like that, because their business is making money from the online users, isn't it? So either, depending on that, either the connections can be persistent and non-persistent, both are currently used. And even though I am saying all these rules like stateless and all, it all actually depends on the server side implementation. Many people are implementing or changing the code of HTTP server in such a way that none of these rules are generally followed. One thing is TCP is used generally, and then the stateless is actually a question mark, because many of the websites are now maintaining the state of the users, which means whenever you log in, they are going to record all your activities, and next time when you log in, they are going to trace you back, like what you did last time and all. So there are various modifications. These are the standard I am talking about, and this is about the all the points. And let's see what are the methods that are supported by HTTP. These are the 8 popular methods which are generally used in HTTP. One is head. So if you use this method, you are supposed to get the header of the web page, which means you are not interested in getting the entire web page. You are just interested in looking about the metadata about the web page. So why is this useful is there are some servers called as HTTP cache. So every country will set up a central server called as HTTP cache or web cache. So whenever you send out the whenever you ask for any web page, before actually going to the server which is in some other country and getting the web page, every country will look into their local cache. So if it is information, if the web page is already present inside your local cache, generally they are maintained by IETF, Internet Intelligence Task Force. They have at every country they will maintain a local cache. So if already some information is present in this local cache, then it is better that you get the information from there. For example, someone has written a blog and you want to get the blog. Then what you do is, as a host, you will be here. Let us say this is the host on which you are there, and you want to read a blog written by someone, and you will initially ask your default gateway for the web page. Now your default gateway will contact the local HTTP cache of your country and see if that web page is present in the HTTP cache. In case if it is present, it will directly get it. It will get it from here and directly give you. In case if it is not present, then you have to go to a different location and then get it from the server, right? Therefore, in order to do this, there is something called as conditional get. So this server HTTP cache, it is a concept which is in a not implemented everywhere, but in case if it is implemented, this is how it happens. Otherwise, your gateway is going to maintain the cache. Your gateway is also going to maintain the HTTP cache. So in India, gateways, every ISP is going to have a HTTP cache, which means whenever you ask them for some web page, they are going to send the web page from their local memory, but still they are going to charge you for that. But actually that is free for them. Why? They are not actually getting it from anywhere else. It is just present in their local memory and they are sending you. Even sometimes, if there is a popular song like if there is a popular trailer, then many people will be watching it on YouTube. Then what your gateway will do is, it will fetch the song once, or that particular advertisement or ad once, that of the new film. Let us say Shah Rukh Khan's film got released and his trailer is there on the internet. Then that trailer will be fetched by the gateway once, by Airtel gateway, and if millions of clients want to watch it, it will not actually go to YouTube all the time. It will just keep on sending the same thing from their cache, but then they will charge you as if they are getting the information from that place, right? So that is one more thing. Anyway, there is also something called as HTTP cache. Now either there is a HTTP cache for every country, or in India, gateways are going to implement them. Gateways means your ISPs at their gateways. Now if the web page is already present in their gateway, they are going to send you. But the problem is, the block might have been modified, which means you have asked for the block now and a blog now, and that blog has been modified after this old copy is there. It has got a old copy, and now the server might have updated the copy to be new one. Then what this will do is, whenever you ask for this copy of the blog, it will first know whether the copy it has is fresh or not. For that, it will ask for the head. So once it gets the head that contains the metadata about that web page. Now in that web page, there is something called as lost modified. Lost modified means when is it last updated. So if it sees that the copy whichever it is having has been modified since it got downloaded, then what it will do is, it will get the new copy and update it. In case if it sees that the copy is not modified, which means the copy has been there and then after that the copy is not modified here, then it will send you that directly. So in that case, head is going to be very useful to get the metadata, and head contains many things like what is the size of the web page, how many objects are there, and everything. That is actually metadata about the web page that you wanted to get. And get is nothing but get the web page or get the resource, whatever. And post is sometimes you will fill in the forms like username and then first name, surname, password, everything. That is called, whenever you fill something, so we want to send the data to the other side, that is called posting. That is where you use post. And put is to upload a object, to upload anything, either a web page or anything. If you want to upload something, then that is called put. Delete is to delete a object. Trace it, sometimes you want to trace out what are the servers that your data is coming from. So whether the data is coming from your HTTP cache or whether it is coming from some other proxy server, or what is the path, which means what are all the servers which are involved in sending you the message. There you can use the trace. And options is you want to find out whether a server is providing all these methods or not. Typically the servers are not supposed to provide all the methods. They are just supposed to provide head and get, only these two, which means you can find out the header and you can get the web page, and all the others are optional. So if you want to find out whether these optionals are provided by the server or not, you can use the options. And next one is connect. So connect is used by HTTPS. So there is something called as TCP tunneling, which is not there in our syllabus, so I'm not going to discuss about it. So in HTTPS, when you want the security, then we want the connect. So what is the specialty of the connect is it will be authenticated. So you will be giving your password, username and password, and in every packet that is being sent, you will be sending the username and password so that the receiver can understand that it is only you. So these are the well-known methods. Anyway, nothing has been asked in GATE about this. So but then still it is good that you know about all this, right? So this is all about the HTTP. There are a lot to learn about HTTP, but then I'm just worried about or I'm just concentrating only on GATE. If you want to learn about HTTP, the best resource is RFC. You please Google out RFC about HTTP, right? Request for comments for HTTP. In TCP/IP, whatever we discussed in the network layer, that IP was actually IPv4, IP version 4. So version 1, version 2, version 3, version 4 and 5 was not there because it has been proposed earlier, and then after performing some experiments they found out that if you go for 5 again you might have to change it. So that is why they discarded it even at the experimental levels, and then they had gone for IPv6. Now let's see what is the need and why should we really need this IPv6 and why IPv4 version 4 is not enough. See, when I talk about IPv4 and IPv6, you might get confused in one way. You might think that I am talking about IP addresses. So addresses are different. Yes, there are IPv4 addresses and IPv6 addresses, but IP is the internet protocol, which means when I am going to talk about IPv6, it is not just about the addresses we are going to talk. We have to talk about the header format and what are the fields in it and what are the options in it. All these things put together, it is going to be IPv6. So IPv6 is not just about the IP addresses, it is much more than that. Just exactly how we discussed about IPv4, now we are going to discuss about IPv6, right? Okay, now what is the need for this? So one problem you clearly know about it. When we are discussing about IPv4 addressing, we have discussed that the addresses are just 32 bits and 2 power 32 is a very small number, and so there was a problem called as IPv4 address depletion, which means whatever addresses are available, they are all over, right? And many people just think that this is the main problem which has driven us to invent IPv6 or to go for IPv6, but this is not the only reason, and to be frank, this is not exactly a reason also. The reason is we are able to overcome IPv4 depletion by using classless and then NAT, network address translation. Now by using network address translation, we are actually safe at least for some few more years. So this is not the only force which is driving the transition from IPv4 to v6. It is one of the reasons we can say, but then it is not the only reason, as it is misunderstood by many people. But there are various other reasons which have forced this transition from IPv4 to IPv6. Let's see them. So one is IPv4 address depletion. This is one of the reasons, not the only reason. And the next one is real-time audio video transmission. Now if you look at IPv4, there was no support for audio video real-time transmission, right? And now in IPv6 it is just enhanced, and we have the support even for that. So I'll explain you how it is being supported when we discuss about the header. And the next one is encryption is provided, which means you can send the data in an encrypted way. Earlier it was not provided. Earlier the application developer at the application layer, they have to encrypt the message and then send it across the network. But now encryption is provided even at the IP level, which means even if the encryption is not provided at the data, that application layer, you can still provide it at the network layer, right? And along with that you can even provide authentication. So what is authentication? If you are sending a message, let us say you got a message saying that it is from some person A, you should be sure that it is definitely from person A, right? Otherwise, if some other person says that I am person A, and if he sends you the message, you should be able to distinguish that, right? So that is where authentication is going to be helpful. And the next one is fast processing. So many things in IPv4 are actually leading us, are actually slowing down the processing at the routers, right? So what IPv6 thought was, we don't do any such processing at the routers, which actually is going to slow down. So instead of doing the things which might slow down at the routers, we completely avoided them, right? So you can, I'll talk about all the ways in which we have avoided. So there is a concept called as flow concept was not there earlier, right? And then even the header length was variable in IPv4, and because of which you might have to do the processing and get what the address header is. But here the header is fixed and there are no options here. Instead of options, there is a concept called as extended headers. So whatever it is, we have done many things, like even deleting the checksum computation is also going to take time, and also we try to avoid going to routing table to find the destination. We are going to use the flow concept, and we are going to use the hashing. So there are various concepts. We will discuss all of them, okay? Don't worry about it. I'll discuss about each one of them, but as a summary you can think of it, they are going to do many things keeping this processing also in mind, so that our routers, whenever they get a packet, they should be able to process it fast and send it away, okay? And the next one is additional functionalities. So apart from whatever we discussed, we can even do some other functionalities, and these functionalities are being enabled by adding a concept called as extended headers. Just like options in IPv4, here we have a concept called as extended headers, using which we can add on some more functionalities. Okay, so we shall take this IPv6 header format, and then we shall see how each of the fields is going to enable all these features, right? And IPv6 is also sometimes called as IPing, IPNG. So NG means next generation. So IPv6 is being designed now with there's so much thinking about future, so much that it is estimated that probably for the next 50 years there might not be any transition for any more for IP at least. So which means from v4 to v6, I think it has taken us 20-30 years. Now from v6 to probably the next version, it might take 50 years. It has been so well designed, keeping everything in mind, that most of the fields are even not use now, which means they have reserved most of the fields for the future use. So when we discuss about it, I'll tell you how long they have foreseen the future and designed it. Just like how TCP was designed, even IPv6 is designed on the same grounds, and still experiments are going on. RFCs, when you refer to RFCs, they have mentioned that, and even now some experimentations are being done in order to improve it. So for even after doing the experimentations, there will not be any change. So they don't know how to use some of the fields. They have just reserved it for the future. Now experiments are being done just to make use of them in an efficient manner. Okay, anyway, we shall discuss about each of them in detail. You just take these points as of now, and we'll go about whatever I talked about now in detail. Fine. So this is the IPv6 header format. Not just the header format, the entire packet format we are going to talk about, but the header is going to look like this. Okay, there are various fields, but comparatively this header is simple compared to the IPv4. Okay, so what you do is you can pause the video, take down this particular header, and then we can continue. You can pause it now. Now see this. First one is version. So the version field of the header, IPv6 header or IPv4 header, anyway it is going to indicate what type of version it is using. I already told you while discussing about IPv4 why it is needed. Since we are in the transition from IPv4 to IPv6, both the softwares are still existing, which means some of the routers are having only IPv6 software, and some of them are having IPv4, and some of them are having both of them. And moreover, when you get a packet, it can either be IPv4 packet or IPv6 packet. Depending on the type of packet you receive, as a router, you are supposed to send the packet to the appropriate software. Then it is going to understand what that particular packet is. So any packet, once it arrives, you are supposed to check its version, right? So if the version is 0110, then it means that it is IPv6. If the version is 0100, it means it is IPv4 packet, right? So the version bits is going to say what version it is. So anyway, this field is going to be 4 bits. Okay, and the next field, it is also called as priority or traffic class. So both the names are equally popular. Either it is called as traffic class or priority. The reason why it is called as priority is, actually it is initially called as traffic class in IPv6, but it is also called as priority because in IPv4 this particular traffic class field is doing the same thing that in that priority was doing in the IPv6, almost the same thing. Anyway, we are going to discuss about this in detail after this video. So just take here what is the number of bytes it is using. So this one is going to use 4 bytes, and this one is going to use 8 bytes. Okay, and the next one is the most interesting and important field which is introduced in IPv6 for the first time in the IP, right? It was not there in any of the earlier versions. It is introduced in the IPv6 for the first time. It is called as flow label. So what is flow label, we shall discuss later, but then take down as 20 bits. Okay, so just now see this. This is 4, this is 8, which is totally it is 12, and then 20, which means the entire row is containing 32 bits. Okay, so what is 32 bits? If you convert it to bytes, 32 bits is nothing but 4 bytes. So this one is going to be 4 bytes. And the next one is payload field, payload length. Unlike IPv4, if you observe IPv4, there was a field called as total length, right? But here it is using a field called as payload length. So the reason why payload length is used is, so okay, try to understand this one. When we were dealing about this IP, we had something called as header length. In the header, let us say IPv4 packet. When I was talking about IPv4 packet, I told you that there are 2 fields. One is what is the header length, and other one is total length. So header length is going to give you what is this total, and the total length is going to give you everything including the header. And now in order to get the payload length, you are supposed to subtract from total length the header length, then you are going to get the payload length. Now two fields were actually used in IPv4. The reason why two fields were used, can you guess the reason? The reason is simple. In IPv4, the header length is not fixed, it is variable, which means it can range anywhere between 20 bytes to 40 bytes, right? So 20 bytes to 60 bytes, I guess. So since it is going to be the header along with the options, since it is going to be a very large number, right, or in flex, it is not going to be constant, you are supposed to know what is the total length and you are supposed to know what is the header length as well. Then only you can know, okay, this is the header and then this is the payload, right? But coming to IPv6, we try to avoid that problem. Instead of having the variable length header, we are having a fixed length header. Therefore there is no need of the field called header length. Since header length field is not there, we don't need the total length because we already know what the header length is, and so what we have to know is only the payload length. That is the reason payload is given, payload field is given. So what is this payload length? It is same as normal length, but it is going to measure the length starting from after the header, right? So whatever follows after the header in the IP packet, if you think that IPv6 packet is going to contain two parts, one is base header and the other one is payload, then that particular field is going to give you the total length of the payload, and this one you need not know about it, the base header length, because the base header length or the header length of IPv6 is fixed. Got it? Okay, so it is 16 bits. And the next one is next header. So what is the concept of next header is, see this, from here till here it is called the base header, and in IPv4 we used to have the options, but here in IPv6 we don't have the options. Instead of options, they have introduced a concept called as extended or extension headers. Okay, so after this there can be any number of extension headers. So you can extension header 1, extension header 2. What are these? We'll discuss about them. And then they can be data finally, right? Data from the upper layer. Even TCP header is also considered as an extension header. So inside a IP packet there can be a TCP packet. Now the last header that is going to be present is also called as the extension header. That is nothing but the TCP header followed by TCP data. Got it? And the next one is this next header field. So next header field is going to be 8 bits. This one is going to say what type of extension header is immediately following this base header, which means it is going to talk about what type of header is this first header. And what about the second header? That will be given by the next header field in this first header. In this first header, again we are going to have one field which is nothing but the next header field, that is going to tell you what this one is. And in case if you have many headers, then each one is going to talk about what the next one is. If the next header is not present, then it can also be indicated. If the next thing is directly data, it can also be indicated. Got it? So anyway, once we get into this extension headers concept, you'll understand all this. For now, you just keep it aside. Okay, so anyway, remember that it is 8-bit field. And the next one is hop limit. So in IPv6 it is called as hop limit. Actually in IPv4 it is called as TTL, time to live. It is going to do the same thing as TTL, time to live, but calling it as the hop limit is actually logical, isn't it? If you think about it, logically what it is supposed to, TTL is not actually the time. Even though TTL is called as time to live, it is not actually the time. It is actually the number of hops that a packet can take before getting discarded, right? So here also, they have just replaced the name, but whatever it is doing is same. Again, it is 8 bits. So right now, just add all of them. It is 16 bits. 8 bits and 8 bits. So the total it is 32 bits, which is nothing but 4 bytes again. Got it? And the source address and destination addresses are IPv6 addresses, right? In IPv6 addresses, unlike IPv4 addresses, the number of bits are increased. They are increased drastically. So from 32 bits in IPv4, here they have increased it to 128 bits. Okay, so 128 bits is nothing but 16 bytes. Alright, and the destination address is also a IPv6 address, which is also 128 bits, and 128 bits is nothing but 16 bytes. Now you add them all. 16 plus 16 is 32, and 32 plus 8 is 40. Therefore, the total length of the base header is 40 bytes, and it is fixed, always fixed. Unlike our IP v4, where it was having, if you remember it, it was having options and then header, and the size of the header was flexible. 20 bytes is the minimum, and then 40 bytes is the maximum, if you remember, right? So no, I think it is 20 plus 40, right? 60 bytes. 20 bytes is the minimum size of the header in IPv4, and along with the options, which were 40, it had 60, isn't it? So 60 bytes, 20 to 60 bytes, it is ranging between them. That is why we had to have what is the header length field and then what is the total length field. But then here, if you observe it, we don't need it, right? So I hope you understood. Just to avoid that header length field and the confusion, they have fixed it, right? In case if you need options, then the options can be included, like extension headers, right? And whether an extension header is required or not, that will be indicated here, and this one will say whether an extension head is required. In case if it is required, it will also say what type of extension header it is. It will play exactly the same role as our options, right? In case if no header is present, then there will be the header of the TCP. Got it? So between that there will be headers. So anyway, we are going to discuss about it. First, you take down this diagram and remember the total size and the sizes of each fields. They might ask you anything here. So one thing you have to notice, 128 bits are used in IPv6 addressing, and we shall get into that addressing later. Okay, so if 128 bits are used, how many IPv6 addresses, or what is the total address space possible? 2 power 128. In IPv4 it was just 2 power 32, right? 2 power 32 is a very small number, but 2 power 128 is a very big number that we might not get out of it. So for next 50 years we might use them. So I mean, it is just a prediction, estimation, so we don't know what happens after 50 years, but anyway it is estimated that for the next many years 2 power 128 is a very large number. That is why they fixed it that way. Okay, so this is very important question. So what are the questions that can be asked here? This one can be asked, and they might ask you whether header length field is present here or not. See, since it is the first time they are going to ask this, definitely they are going to ask one question from this, because they have recently added it. They have to ask, otherwise why did they add it, right? That is the logic I am using. Now what are the questions that you can predict from this? Just what are all the sizes of each one of them, and then maybe they will ask some true or false questions, like which field is present where. So you just by heart what is there in IPv4, and then by heart what is there in IPv6. They might ask you questions like this particular field is present in both of them. Let us say version is present in both of them, true or false. Or they might ask you, is flow label present in IPv4 header as well? No, right? Or they might ask you, which of the following protocols is having a static or fixed length header, IPv4 or IPv6, right? They might ask you questions like this. Okay, now we shall get into the fields one by one. Fine. So we have seen that in IPv4 there is a problem called IPv4 address depletion, which means all the available addresses, how many are totally available with 32 bits, 2 power 32, they are getting over very fast, because Everyone is having at least 2 or 3 devices these days, one mobile phone, one personal computer, and a computer at home. So 2 to 3 devices everyone is having, and also it is estimated that in future every device, every utensil, every electric utensil that you have at home is going to be completely connected to the internet. For example, you can connect your air conditioner to the internet by assigning an IP to it. Then let us say you are at office, and by the time you want to reach home, you want the entire room to be cool. Then you can switch on the AC when you are still at your office through internet connection, right? Also, this is very interesting. You must have heard about this electric cars, which are also going to be self-driving electric cars in future. It is not very far off. In just 3 to 4 years, we are going to see self-driving electric cars in India, not in US. In US, I think in next year they are going to get it. Maybe in India, 4 to 5 years from now, you are going to see this self-driving electric cars. So the specialty of this one is now a car is also going to be a gadget. So what is the difference between a gadget and other electric utensil or car is, if you buy a gadget, every day after buying it, it is going to get new features, and it is going to get upgraded, which means after you buy it, it is going to be newer and newer every day. But it was not like that coming to the cars till now. But right now we are going to get the cars which are self-driving, and the software in these cars is going to be upgraded every day. How is it possible? Every car is going to get an IP address, and during the night when you park it in your basement, it is going to get connected to your internet through Wi-Fi, and it is going to get upgraded. So the manufacturer of the car is going to send some updates, and every day you wake up, your car is going to get new features, more features added. You'll just see that the old problems are vanished and new features and new updates are being done. In the night it will charge itself automatically and it will get upgraded. So this is all the technology that we are going to see. The future is going to be amazing in terms of technology, but the challenges are also going to be there. When every device needs the internet connection, every device, right, almost every device, when it needs internet connectivity, then the problem is, yes, you must have already heard about this, people are getting tagged. So in some offices people are getting tagged in their body, and using those we can even track people. Okay, so that is far off in India. As of now we don't have it in India. Okay, let's get back to this. Now with everyone requiring many IP addresses, 2 power 32 is not going to be enough. Even though we are going to have this NAT, this network address translation, the problem is the translation from public address, from private address we have to convert it to public address, and we have to convert it back. Therefore processing is going to be more because of NAT. Even though NAT is able to solve IPv4 depletion problem, there is a processing overhead in NAT. So that is the reason. Anyway, we want to increase the address space from 2 power 32. How can we increase it? By increasing the number of bits in the IP address. So if you look at IPv6 address, it is going to have 128 bits. Instead of 32 bits, it is going to have 128 bits, which means the new address space is going to be 2 power 128. These many addresses are going to be available for use, and this is a very big number, and for the next, they are assuming that for the next 50 years or for next 1 century, these addresses are going to be enough and there is no need of any upgradation, right? So coming to this, they have defined mainly 3 types of addresses. One is unicast, and the second one is multicast, and the third one is anycast address. So what is unicast is, in this case, every interface, if you assume that a host is having only one interface, you can talk about a host, but let's talk about an interface. I told you that a host can have more than one interfaces, or a router can have more than one interface. Then every interface is going to get an IP address, either a host or a router, right? So for every interface we are going to get one IP address. So that IP address is nothing but the unicast address. So what is unicast address is, every interface is going to be assigned a unique address which is called unicast address, and if any packet is delivered to that address, that particular packet will be delivered to that particular interface. Got it? And then we have multicast address. So what is multicast is, we'll take a group of interfaces and we call it as a group, and these group of interfaces may not be from the computers which are geographically together. They can be anywhere in the world. So we take many people or many interfaces, and we put them all in one group, and then we assign them one address. That particular address is called as multicast address. Now whenever any packet is being sent with destination address as this multicast address, then everyone in this group are supposed to get it, right? Or the packet will be delivered to everyone in this group. And the last one is anycast. In this anycast also we are going to use the same concept, where we are going to have a group of hosts or group of interfaces, and we give them one single address which is called as anycast address, and if any packet is being delivered to this particular address, then this particular packet will be delivered to the closest host possible, and then it is the responsibility of that particular host to deliver it to other hosts, right? But then our IPv6 doesn't define it. So what will our IPv6 define is, if anycast packet is being sent to a group of hosts or interfaces, then the closest host or the interface having one of these is supposed to receive it. And once the packet is delivered, IPv6 doesn't talk about what happens next. Got it? So this is unicast, this is multicast, and this is anycast. In IPv4, the address was 32 bits and it was represented as dotted decimal number system, which means we are taking 88 bits, and then we are converting these 8 bits to decimal, and we are putting a dot in between them. Similarly, in the same way, IPv6 address is 128 bits. So 128 bits means 16 bytes. Are you getting it? IPv6 address is 128 bits, and instead of using this dotted decimal, because if you are going to use dotted decimal number system, it doesn't look that good, because you have to have 16 bytes, which means 16 numbers with a dot in the middle. So instead of that, they have used a different convention, and the convention is this one: colon hexa representation. So colon hexadecimal representation means they will represent an address like this. Okay, EFGH is not there. ABCD, let's say EF. They're all hexadecimal digits. So check this. Now what they did is, they have taken every byte, and every byte is encrypted as, or encoded as 2 hexadecimal digits. Therefore A and B are 2 hexadecimal digits, and this one represents 4 bits and this one represents 4 bits, which means these 4 digits together, these 4 hexadecimal digits together represent 16 bits. 16 bits or 2 bytes. Therefore 2 bytes here, 2 bytes here, 2 bytes, 2 bytes, 2 bytes, 2 bytes. If you count it, there are 8 such 2 bytes. Therefore it is going to be 16 bytes, which means our 128 bit address, which is equal to 16 bytes, is actually represented like this, using colon hexadecimal representation. If you remember IPv4 was using dotted decimal representation. That was the convention, and here the convention is using this. And also, if you observe this IPv6 address, most of the parts of them will be zeros, which means you might see something like this. Let us say here only, you might see that 0 0 0 0, right? And you might see that 0 0 0 0, right? So in order to abbreviate it, in order to write it in a shortcut, what people did is they have deleted all the leading zeros, which means whenever you have any leading zero, let us say here you have a 0, right? Whenever you have a leading 0, they have deleted it. And whenever there are 4 zeros, they are represented using only 1 0, right? So this is the shorthand notation. So even if they represent it like this, it means the actual thing, right? So I'll just give you an example. If they have something like A B C D 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4 3 4 1 2 3 4 5 6 3 4, let us say 1 2 3 4. Let us say this is the IPv6 address. Now if you observe it, there are all zeros only, right? So one way of simplifying it or representing it in a shortcut is, instead of representing 4 zeros in everything, they have just cut it short, A B C D, and then they have represented only 1 0 for this, and only 1 0 for this, 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 and then 1 2 3 4, right? And this is a abbreviated form. Even they have abbreviated this as well. So whenever you have a sequence of zeros, like you have many zeros there, they have represented all, they deleted all the zeros and they represented using 2 columns, which means like this, A B C D colon 1 2 3 4, which means all these have been deleted with just 2 columns, right? So this is called as abbreviation. So whenever you have a sequence of zeros, you can simply substitute it with 2 columns, right? And these 2 columns actually represent that wherever you don't see the bits, which means if this one is representing 16 bits and this one is representing 16 bits, if this one is representing the first 16 and this one is representing last 16, the remaining bits all are nothing but zeros. Now there is one more thing. Let us say, instead of having this continuous zeros, if the zeros are in the beginning and at the end, like this, let us assume that here we have 1 2 3 4, right? So which means here you are going to have some bytes, some ones, and then all zeros here, all zeros here. So in this case, you cannot use 2 columns here and 2 columns here. Instead of that, you can use 2 columns either here or there, right? So what happens is A B C D, and if you choose to use 2 columns here, use it here, right? 1 2 3 4, and don't use 2 columns there. You use that representation where we are not going to use, represent the leading zeros, which means 0 0 and then 1 2 3 4. Alright, now you can understand that this is all 16 bits, and between them there are some zeros. We don't know how many zeros are there. This is all 16 bits, this is 4 bits, this is 16 bits, 16 bits and 16 bits. Now you can estimate how many bits are missing, and you can represent all those bits with zeros. Either you can represent it like this, or you can replace these run of zeros with 2 columns, which means you can have A B C D colon 0 colon 0 colon 0 representing these 3 pairs of 16 zeros, and then this one is 1 2 3 4, and after that you can represent this combinedly using 2 columns, and then 1 2 3 4. Got it? So this is how we are going to represent IPv6 addresses in colon hexadecimal representation. and then this is the abbreviated form of representing it. Just the same way how we represented IPv4 addresses in dotted decimal, here we are using colon hexadecimal number system. Okay, fine. Now we have 128 bits in the IPv6 address, but by looking at the first few bits, you can identify what type of address it is. Just like how we classified the addresses into class A, class B, class C, class J, class E, in class 4 classification also you have seen this. Depending on the first few bits, right, we are able to say whether it is class A or class B or class like 0, 0, 1 like this, right? So similarly, exactly the same way, they have divided again 128 bits into various parts, and then each part they specially assign to some purpose, just like classful, but then instead of calling it as classful, they have given separate names. Now I am going to show you all the classifications, but then don't try to by heart them. Whatever are required, I'll tell you to remember. Okay, so no need to by heart everything, just you have to by heart only the things which are required. So, and one more thing, whatever numbers I have written here, I have taken them from RFCs, and in textbooks they are given as different number, maybe some printing mistake or I don't know which resource they have referred, but whatever I am going to teach you is from RFCs. Okay, now see this, if the first 8 bits are all zeros, then those addresses are reserved for special purposes. And what are those special purposes? We'll see shortly. For example, addresses like loopback address, and addresses like I don't have IP, all zeros, right? So, and addresses like IPv4 mapped IPv6. I'll tell you all about that. But for now, understand that these are reserved for special purposes, and these addresses cannot be used as or cannot be assigned to any interface, which means any node. Okay, and then if it is 7 zeros followed by 1, it is unassigned. Unassigned means as of now no node is going to get this address, and also they are not as reserved for any special purpose. They are just useful in future. For now we are not using it. Similarly, 6 zeros followed by 1, unassigned. 5 zeros followed by 1 0, unassigned. 5 zeros followed by 1 1, unassigned. 4 zeros followed by 1, unassigned. 3 zeros followed by 1, reserved. So again these reserved are for special purposes, we shall see later. And then 0 0 1, reserved. 0 1 0, this is provider based unicast address. So unicast addresses are of two types. One is provider based unicast address, which means these unicast addresses we are going to classify depending on who is your ISP, right? So what is the meaning of it is, if you are going to have IPv6 address, we are going to have a part of it which is going to identify who is the ISP holding that address. So by looking at an IP address, if it is belonging to this particular class, you'll be able to say who the ISP is, right? We'll look at it in detail later. And then next one is, if the address is starting with 0 1 1, it is unassigned. And the next one is 0 0 1. So if the address is starting with 0 0 1, then it means that, okay, this is 1 0 0 and this is 0 0 1. If the address is starting with 0 0 1, it means that this one is geographic based unicast address. So geographic based unicast address means now within the IP address we are going to put that latitude and longitude. So by looking at the IP address, you can see or you can say to which place it belongs, right? So that is the difference between these two. So basically unicast addresses are of two types. What is unicast address? Any address that can be assigned to a single node is unicast address. Normal IP addresses, right? And now there are two types. One is provider based and other is geographic. In provider based IP unicast address, you are going to have the information about the ISP, and in geographic based unicast address you are going to have the information about the location, latitude and longitude. These two we'll again examine in the coming videos. And the next one is, if it is going to start with 101, then it is again unassigned. 110 is also unassigned. 1110 unassigned. 410 unassigned. 510 unassigned. 610 unassigned. 710 unassigned. And now we have local addresses. These are the two types of local addresses: site link local address and site local address. These local addresses, you can consider them as same as private addressing. Like how we use private addressing in IPv4, they are called as local addresses in IPv6. Okay, and the local addresses are like this: 4, 5, 6, 7. 7 ones followed by 0, 1, 0. If any address starts with this number, if the first few bits of 128 bits are 7 ones followed by 0, 1, 0, then that is called as link local address. So we shall discuss what it is later. And then if the address is 7 ones followed by 0, 1, 1, then it is called as site local address. We shall discuss about it later. And these two are actually examples of the private addressing. I mean, the kind of private addresses coming to IPv6. In IPv4 we know private addressing, right? Private and public and NAT, network address translation. Again, the same concepts are implemented using link local and site local addresses. And the next one is multicast address. So if the address starts with 8 ones, then this is called as multicast address. If you observe it, there is nothing called broadcast address, because in IPv6 broadcast address is already included in the definition of multicast address only, right? Now let's see what is the difference between IPv4 options and the IPv6 options headers extensions. So the main difference between IPv4 and IPv6 is, one thing is definitely the size of IP address has increased from 32 to 128 bits, that we have already seen. And the other difference is the options is being replaced with the extension headers. That is the main difference. Now let's see what are the differences between the options and the extension headers. Now in IPv4, no option and no end of options, no operation and no end of options in IPv4 is replaced by pad1 and pad-n options in IPv6. So they are saying that whenever what happens is we are supposed to have the header size in a multiple of 4 in IPv4, and whenever we are going to add the options, we are supposed to add a field called as no options or end of options in order to say that options are over, right? And these are actually deleted, and padding is being introduced into IPv6. That is what they are saying. Anyway, first point is not very important, you can leave it. Let's talk about next one. No record route option in IPv6. So in IPv6 there is no way you can record the route. So instead of recording the route, you are supposed to use the trace route program, which will be implemented using ICMP. So there is no way you can record the route, you have to use the trace route. And next one is no timestamp option in IPv6. In IPv4 there was this timestamp option, but here it is deleted. And the next one is the source route option is called source route extension in IPv6, which means source routing is implemented in both IPv4 and IPv6, but with different names. We called it source routing in IPv4, and here we are calling it source route extension. That's it. And the main difference is one main difference is fragmentation fields are completely removed in IPv6. Earlier fragmentation fields were present in every IPv4 base header, which means even if there is no fragmentation, still every packet is going to carry these fields. So later what they did is they introduced the fragmentation only when it is required, which means from the base header they deleted these fields and they added them as the extension headers. Okay, so see this, fragmentation fields of IPv4 base header are moved to fragmentation extension header in IPv6. Alright, and the next one is there is authentication header added and the encryption header added. These two are anyway we discussed. Got it? So that is the main difference between IPv6 and IPv4. Okay. Wi-Fi is a means by which computers can communicate wirelessly. So you must be knowing about Wi-Fi, right? Even in your colleges, in your offices, everywhere nowadays you see Wi-Fi. Earlier, the problem with this wired network is, if you are either in a university or in office, you are supposed to sit in one place and have the stationary stations. For example, if you had used these desktops, it was really convenient. But then later, with the advent of these mobile devices like a laptop, you can work from anywhere. You can either work from the ground, or you can work from a cafeteria in your office. So you want to basically move from a place to place. So in that scenario, having a fixed location, a workspace which is fixed, is not going to help. So that is why basically this Wi-Fi has been introduced. And also sometimes we want to communicate without connecting the devices. That is why even Bluetooth has been invented. Now Wi-Fi and Bluetooth are the two technologies using which two devices can communicate with each other, right? And later the same technology has been extended to cellular phones as well. But that is a different concept. That is a total different concept. But here let's focus only on Wi-Fi. Bluetooth is also not in the syllabus. Now, whenever we talk about any technology, there has to be some standardization, which means if two devices have to communicate with each other, both of them should understand each other, right? So if they are sending a packet, they should know what part of the packet is having the header and what part of it is representing the data. In header, which field is representing what. So you are supposed to know all these things. That is where standardization is going to be useful. So IEEE has standardized this Wi-Fi, and everything related to this Wi-Fi has been discussed under the section 802.11. Therefore IEEE 802.11 will deal with this particular technology, Wi-Fi, right? And also Wi-Fi is mainly works at data link layer and physical layer. So we don't discuss about Wi-Fi at the network layer. At network layer, as usual, we'll be using IP, and at transport layer you can use any transport layer protocol. But coming to the data link layer, instead of using Ethernet or token ring or any other thing, you can even use Wi-Fi. So Wi-Fi is a total substitution. So you can go with wireless communications. Okay. Now we have only basics of Wi-Fi. We need not get into the details. Just the basics are required. Understanding what Wi-Fi is, it is enough. And now, if you have to understand how a company generally distributes the internet connectivity or connects the devices, you can think of this diagram. This is the basic point. Now if you go to either Reliance or Airtel, if generally a corporate a corporate organization, if they approach Reliance or any other ISP to provide the internet connection to your company, to that organization, then they will send you a data link. So that is the starting point. They will send you a data link from their organization. Generally it will be a wired connection, because you will be requiring high bandwidth. From their organization, from their gateway, they will send a wire. That is the basic thing if you want to understand it that way. And now the wire will come and end at your company. The point where it ends, that is also called as end mile. So it is a normal terminology. You need not by heart it. There is something called as end mile, and from that end mile, your organization will take the internet. Now your organization should set up servers like gateways or firewalls or proxies in such a way that even though internet, your computers are going to get connected to the internet, you want to restrict the access for the outside world, or you want to do some customizations like how much bandwidth you want to get, anything, or which users you want to allow to communicate outside. All these things, just to have the total control, every organization internally will set up something called as proxy servers, or sometimes called as gateways, or sometimes called as firewalls. So any subsystem they will put in place. Mainly firewall has to be there. Now let us assume that this is the point which I am calling as end mile, which means ISP like Reliance has provided you the internet connection, and this is where the connection is ending, and this is where your company will take over it. Now your company will set up a proxy or some gateway, some kind of it, and through the gateway this internet connection will enter your organization. Now this entire thing is called as the distribution network. So using this whatever way you want to distribute it, you can distribute it. Either you can use switches, or you can use a basic Ethernet. Generally people are not using basic Ethernet. Nowadays everything is being used as a switch. So from the gateway there will be a switch, and from the switch it will distribute the connection to the access points. Now these are called as access points. Even in your offices also you can see the access points. Access points are nothing but the how can I describe it? You will see some devices which they will call it as the Wi-Fi devices. They are called as the access points. Now those access points will send you some waves in some frequency so that your computers can connect to them. Got it? Now whatever each access point will address, this one is called as a basic service set. A computer can be present in a basic service set, and all the computers which are present in one basic service set will be connected to a access point, or it will be connected to more than one access point like this computer. Got it? And now if the computers which are present in one basic service set, this is basic service set and this is one basic service set which is being serviced by this access point, and this is other basic service set which is being serviced by this access point. Why do you have to have these many access points? Because as the distance increases, the waves they lose the energy, right? Attenuation. Now because of that, the waves will not be able to carry the information over a long distance, right? It is not like a radio wave. If you look at the radio waves, their frequency is different. They are designed in such a way that they can travel for a longer distance, but the problem is radio waves cannot carry high bandwidth. Now the frequency of these waves used in Wi-Fi is different in such a way that it will give you the high bandwidth, but the range is shorter. Either you have to compromise one of them. If you increase the range, you will not get the bandwidth. If you decrease the bandwidth, or if you increase the bandwidth, you will not get the range, right? Anyway, all these things are related to the communication students like ECE. We don't have to worry about the bandwidth and range and frequency things. They are not required for us. Okay, so what you can understand is a access point has certain limitations, like the number of stations it can service and the range of it. That is why in a company you are going to have more than one access point. Got it? Now as long as all the stations are located close to each other, there will be no need of access point as well. So these two stations can directly communicate with each other. So when will this access point be required is if a station which is present in one range, or let's call it as one basic service set, wants to communicate with a station which is present in other basic service set, then they will have to go through the access points. Got it? That is where access points are going to be useful. And coming to these stations can either be mobile or they can be stationary. What do I mean by stationary is like desktops, they need not move. And what about mobile is laptop or your mobile phones which can connect to it. Now it is up to the organization to design the access points in such a way that when a station moves from one basic service set to other basic service set, it should not lose the connection. It is up to them, right? How they implement it. It is left to the implementers. And what are the other important things is the single unit is called as a basic service set, and this entire thing put together it is also called as extended service set. Got it? So systems, if they are present in the same basic service set, can communicate with each other directly, and access points will be helpful if a system in one basic service set wants to communicate with a device which is not too close to it, right? Then it has to go through the access points, and this one is called as distribution network. So either you can use switches or you can use any other LAN technologies which are generally wired. So all the access points will be connected together using some wired network, so that it will be faster, it will be reliable. And generally if it is wireless, it won't be that reliable. Got it? And yeah, that is about the introduction. Okay, now let's see the topic of network security. So why network security is important is, maybe if you know, I'll just take an example and explain you. Let us say you are going to open a website, maybe net banking website at your home, and you have entered the password of your bank account, and now this password and other information will be passed on to the server. Let's say this is the client on which you are working on, and there is a server, right? And on the way there are various entities, right? One thing is for sure, while entering the password, you will be very sure that no one is watching you. So at your side you will be very secured, and also server is a trusted body, therefore it is also trusted and it is secured. Let us say here also no one is able to get into this system, and we are able to protect the password. But then the problem is, while the data is being transmitted either through wireless means or in wired means, right? So on the way you don't know, you will not be sure what is happening there, which means this entire transmission path is not secured. Anyone can look into the message, right? So for that reason you might have to use security, right? There are various methods that are going to be used. I'll just show you what are all of them, and before that let's see the terminology in this topic, right? So in the terminology we are going to use something called plain text. Plain text means the actual message that is in the readable format, that is what you wanted to send. Generally if you type something, that is a plain text, it is readable, right? And cipher text means generally we try to make the plain text into some other format which is unreadable, right? So cipher text means it is the converted message which is in unreadable format, right? Why do we use it? So that no one will be able to read it on the way. Yes, there are methods by which people will still be able to read the cipher text, but then what we do is we use some strong algorithms so that they will not be able to read it. So cipher text means after encryption whatever you get. Okay, let's look at that. Encryption means the process of converting plain text to cipher text is called as encryption. Are you getting this? There is plain text and there is cipher text and there is encryption. So using encryption you are able to convert plain text into cipher text. The entire purpose is to see that the message is not readable. And the next one is decryption. Decryption means the process of converting cipher text to plain text is decryption. So here let's say there is plain text. Now you encrypt it and convert it into cipher text and you send it, and at the receiving side there will be cipher text which will be decrypted. I'll show you with a diagram. Okay, fine. So that is about the terminology. Now let's see what is cryptography. So the entire purpose of cryptography is a method of storing and transmitting data in a particular form so that only those for whom it is intended can read and process. So whatever the procedures, whatever algorithms and the procedures involved, that entire thing is called as cryptography. So cryptography is a collection of methods using which you are going to convert plain text into cipher text so that only the people whom you want them to read are going to read it. Okay, and this is how it is going to happen. Generally cryptography is going to happen this way. So let us say there is a person Alice, and Alice is going to, okay, let's use some Indian names instead of using some American names. So generally textbooks follow this. Let us say Ram is going to send some plain text. So he will be passing that plain text to the module which is going to encrypt it. That is called as encryption algorithm, right, or encryption procedure. Now encryption is going to convert the plain text into cipher text, right? Now once you get the cipher text, that is what you are going to transmit onto the communication channels. Now even when this cipher text is going to be seen by intruders means these people are someone who is trying to read the message that doesn't belong to them, right? Why? To gain information, right? So for various reasons they are trying to read it, but then they are all called as intruders. Now these intruders can be of two types. One is passive attackers and the other one is active attackers, right? So they will be looking at the information that is getting passed by the way, and now your encryption algorithms should be so strong that even when they are able to look at the ciphertext, they should not be able to guess the plain text. Got it? And now at the receiver end, at the receiver side, once the ciphertext is being received, we are going to use decryption algorithms to convert the ciphertext into the plain text, right? Now this is the plain text what the receiver needs, right? Let us say Bob wants it, and that is the plain text which he is going to use. Got it? So let's see later what is passive attack and what is active attack, and how they are trying to attack the information and how we should be protecting it. Okay, fine. Now let's see this topic of cryptography. Now we can do this in two ways. One is symmetric key and other one is asymmetric key. So if you are going to use a single key, and if the same key is being used by the sender as well as the receiver, then it is called as symmetric key cryptography. Sometimes it is also called as secret key cryptography. And the other one is asymmetric key cryptography. And asymmetric key cryptography means the sender is going to use a key and a receiver is going to use a different key, right? So here it is also called as public key, private key, encryption. So I'll tell you the difference. Now let's first see what is symmetric key cryptography. Now if you have a plain text, see what we are talking about symmetric key first. If you have a plain text, I am going to use the encryption algorithm and I am going to encrypt it, and after encryption I am going to get the ciphertext, right? Let us say the ciphertext is C. Now for this encryption, what I am trying to use is K is a key and M. So if you look at this, now for the encryption algorithm, let's say this is the encryption algorithm. It is going to take two things. One is the message that you want to encrypt, and the other one is the key that you are supposed to use. And from this you are going to get something called as ciphertext. Got it? Therefore, ciphertext is a function of these three things, right? What is the encryption algorithm you are using, and what is the key you are using, and what is the message that you are sending. Depending, if you vary any of this one is going to vary, right? And now once the ciphertext is being transmitted to the other side, at the receiver side, the receiver is going to use decryption algorithm, and the decryption algorithm is going to take the same ciphertext which it is receiving, and it is going to convert it into the message. Now at the decryption side, it is going to look like this. The decryption algorithm is going to take the ciphertext that you have sent and the key, the same key that you are using. So for encryption, whatever key you have used, the decryption algorithm is also going to use the same key to convert it into the message that you had sent. Got it? Now if you observe this, since we are using the same key here and here, that is why it is called as symmetric key. Symmetric key means on both the sides we are using the same key, and this key has to be kept secret. That is why it is also called as secret key, right? And now if you observe it, the problem here is, yes, once you encrypt the message and convert it into ciphertext, it will be difficult for anyone to get the message from it, right? Yes, there are algorithms to break it, but it is not very easy, right? And no one on the way can see it, or even if they see it, they will not be able to get the message if your algorithm is very strong, and only the receiver is going to see the message. Now how will the receiver see the message? Only if he knows the key. Are you getting this? The key is used by the sender, and it has to be seen or it has to be known by the receiver as well, right? Which means if you are sending the data, you are also supposed to send the key. But if you are sending the key, then key is also vulnerable to the attack, right? It is not the data, just the data that you have to protect. You have to even protect the key, but then initially you have to send the key itself. So when you are sending the key over any channel, if it is not using encryption, because you don't have any key to use it, right? So you cannot use any encryption, so anyone can see it and anyone can store it, and later when I was sending the ciphertext, anyone can decode it, right? So that is the problem with the symmetric key encryption. So the key exchange is a disadvantage. Key exchange means how are you going to send the key from here to here without anyone looking at it? If someone looks at it, then that is a disadvantage. then anyone can decode or decrypt the ciphertext that you had sent, and they will see whatever you are sending. So entire purpose will be lost. So only problem here is in this one is how are you going to share the key or exchange the key. That is why we are not going to use these methods very popularly. Now the other one is asymmetric key. We shall see it later. So anyway, this is all about the symmetric key encryption, and we have two popular algorithms. There are many algorithms using this symmetric key, but two popular algorithms are DES and AES, Data Encryption Standard and Advanced Encryption Standard. But in GATE syllabus, it is clearly mentioned that they don't want to deal with any symmetric key encryption techniques. They are only going to ask asymmetric key, which means public key, private key. So we will not be discussing about it further. Okay, fine. Now let's see some theorems on this modular arithmetic. So as of now, I'll just show you the theorems and then explain you the examples, but you will not be able to understand why we are doing these examples till I show you the algorithms where they are applied. Later when I show you the algorithm like RC algorithm, then you will clearly understand the importance of these theorems. Okay. Now let's see the first one, Euler's theorem. If n is a positive integer and a comma n are co-primes, then a power phi of n is congruent to 1 mod n. So this is what Euler's theorem says. So you know what is phi of n. So phi of n is nothing but Euler quotient function. The number of integers less than n which are relatively prime to n is phi of n. Now this equation is important. So a power phi of n is congruent to 1 mod n. This one is important. Given that a and n are co-primes, so these two are supposed to be co-primes. So whenever these two are co-primes, then we can write a power phi of n, we can find out that number, and when you divide that number with n, the remainder is going to be 1, right? Okay, and let's take an example. I'll explain you. Now 8 and 165, if you see these two, they are co-prime numbers. 8 and 165 are co-prime, because if you try to find out the GCD will be 1. That is why these two are co-prime numbers. Now after finding out that they are co-prime numbers, you try to find out phi of n. So what is phi of 165? So phi of 165 can be written as it is product of 15 and 11, and 15 can be written as if it is product of 3 and 5. Right? So therefore 165 can be written as if it is product of 3 prime numbers 3, 5 and 11. Why are we writing it as prime numbers, product of prime numbers is finding out the phi function, the quotient function, given that the numbers are actually prime is easy, right? So now if I try to find out phi of 3 into 5 into 11, it is nothing but phi of 3 into phi of 5 into phi of 11, and as you know, since 3 is a prime number, phi of 3 is p minus 1, which means 2. Phi of 5 is 5 minus 1, which is 4. Phi of 11 is 11 minus 1, which is 10. Now phi of 165 is going to be product of these three, 2 into 4 into 10, which is 80. So we are now able to find out phi of 165, which is 80. Now according to this theorem, you can see that 8 power 80 is congruent to 1 mod 65. So the meaning of this one is you find out 8 power 80, which is going to be a very big number. I'm not going to do it, but then it is going to be right. Okay, so just trust me here. 8 power 80, when you divide it with 165, the remainder is going to be 1. Now you don't calculate what is 8 power 80 because it is going to be a very big number, right? So the entire strength of this public key private key cryptography lies on using numbers like so big. Okay, and the computations are going to be very, very time taking and resource consuming. That is why breaking a key will be difficult unless you know these methods which we are going to use them. So I'll show you later why we are using all this. Anyway, 8 power 80 is the number, and when you divide it with 165, you are going to get remainder 1. That is what this theorem says. Okay, and it is not just that a power phi of n is congruent to 1 mod n. It can be any multiple of phi of n. So which means a power phi of n into t for any number t will also give us the same result, right? Which means it could even be 8 power 160 or 8 power 240 or 8 power 320, any number whatever big number that is, you could take it, and when I divide it with n, then the remainder is supposed to be 1, or remainder you get will be 1, right? Now there is an extension for this Euler's theorem, that is format theorem. Let's see that. Now coming to the format theorem, it is just a special case of Euler's theorem. So it is saying that for any prime number n, and a is not a multiple of n, a power n minus 1 is congruent to 1 power 1 mod n. So here in the earlier Euler's theorem was actually about a and n when they were co-primes, right? But what if n happens to be a prime already? If n is a prime and if a is not a multiple of n, that is what? See this. A is not a multiple of n means when I divide a with n, the remainder is not equal to 0, which means a is not a multiple of n. Therefore, if one of the number is a prime and if the other number is not a multiple of that prime, then definitely both of them will be co-primes, right? Again, the same theory can be applied. Now what did we apply there? A power phi of n is congruent to 1 mod n is what we got, right? Here a power phi of n. So in case if n is a prime number, then phi of n, as you know, is n minus 1. Therefore a power n minus 1 will be congruent to 1 mod n. The same theorem, nothing has changed. Here since n is a prime number, we are going to write n minus 1 instead of phi of n, because anyway phi of n is going to be n minus 1. Got it? So a power n minus 1 is congruent to 1 mod n. And now if n is a positive integer and a comma n are co-primes, then a power phi of n plus 1, a power phi of n plus 1 is congruent to a mod n. It is simple. I am just multiplying both sides with a. As you know that a power phi of n is congruent to 1 mod n, I am just multiplying both sides with a, then what do I get? A power phi of n plus 1 will be congruent to a mod n, right? And now as you know, it need not be just phi of n here, it could have been even phi of n into t. Therefore a power phi of n into t plus 1 is congruent to a mod n, right? Now if you want to see an example, let's take this example. So if a equal to 9 and n equal to 13, see this, n is a prime number and a is not a multiple of n, therefore these two are definitely co-primes. Now I can apply Euler's or format theorem, right? Both of them says that you have to find out phi of n, and a power phi of n is congruent to 1 mod n. Now see this, a power phi of n, which means 9 power 12. What is phi of n here? Since n is 13, phi of n is going to be 12. Why? N is prime number, right? So a means 9 power phi of n means 9 power 12 is congruent to 1 mod 13. Now if you observe this, if I multiply both sides with 9, what do I get? 9 power 13 is congruent to 9 power 9 mod 13. And now if you observe it, you could have even written it as 9 power 24 also, isn't it? Why? You can multiply that phi of n with t and still that equation holds. Therefore 9 power 24 will be congruent to 1 mod 13, as well as 9 power 36 will also be congruent to 1 mod 13, right? Now if you write it as if it is 9 power 24 is congruent to 1 mod 13, right? And now you multiply both sides with 9, you are going to get 9 power 25 is congruent to 9 mod 13. Got it? If n is a positive integer, a comma n are co-primes, then and b is congruent to 1 mod phi of n, then a power b is congruent to a mod n. So it is simply an application of this one, the earlier one. So if you observe this, look at this one, b is given as if it is congruent to 1 mod n. What is the meaning of it? When I divide b with phi of n, I am going to get a remainder of 1. Therefore I could write b as, b could have been written as t into phi of n plus 1. Why? Because it is it is divisible. When I divide it with phi of n, it is going to leave a remainder of 1, which means b could have been a number like this. This number is exactly divisible by phi of n, and we are going to get a remainder of 1. Got it? So now if you assume that b equal to this entire number, and if you try to substitute here, then what is that you are going to get? A power t into phi of n plus 1. Right? Just now we have shown that a power t into phi of n plus 1 is a mod n. So that is what we are showing here. Right? Now if you want to see an example, you can see it here. A equal to 5, n equal to 8, 8 means 2 power 3. Now you can find out phi of n. So what is phi of n? N into 1 minus 1 by 2. Or you can, if you can directly find out phi of n for 8, you can find it out. Anyway, you are going to get 4, right? And if b equal to 17, why 17? Because this is the number which is going to leave a remainder of 1 when divided with 4. So just to apply this one, I am just taking such number. You could have taken even 9 also, not an issue, because 9 also when you divide with 4, it is going to leave a remainder of 1, right? Now 5 power 17 will be congruent to 5 mod 8. So all these rules will be applicable or useful when I show you with the algorithms where we do this public key, private key. Okay, fine. Now let's see this Euler's totient function. So Euler's totient function says that if you have a number, then how many numbers are less than this which are relatively prime to this. Okay, so I'll just read it out, and with an example I'll explain it clearly. The totient function phi of n of a positive integer n is greater than or equal to 1 is defined to be the number of positive integers less than n that are co-prime to n. So for example, if you see 3, phi of 3, how many numbers are less than 3 which are co-prime to 3? Now 1 and 2 are less than 3 that are co-prime to 3. What is co-prime? GCD has to be 1. Now if you find out 1 and 2, the GCD between 1 and 3 is 1 and GCD between 2 and 3 is 1. That is why phi of 3 equal to 2. And now phi of 14, if you want to find out phi of 14, you have to find out how many numbers are less than 14 which are relatively prime to 14, right? So for that reason you are supposed to write down all the numbers and you have to evaluate it. Now if you are trying to find out phi of 14, right, find out how many numbers are less than 14 and which are relatively prime to 14. So I have to start from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So I have to start from 1 to n minus 1, so where n is 14, and I have to see for all the numbers whether it is whether the GCD between this number and that number is 1 or not. Now if I find out the GCD between 1 and 14, it is 1, right? Therefore phi of 1, we have to count it, right? See, one more thing, this function is not actually the set of numbers, it is simply the number of numbers present in this set, right? So for that reason, so 1 is not phi of 14. I have to count all such numbers, and that particular number of numbers is going to be phi of 14, right? Now 1 is relatively prime to 14. 2 is not relatively prime. 3 is relatively prime to 14. 4 is not relatively prime because the GCD between 4 and 14 is 2. So it is it is not relatively prime. And 5 is relatively prime to 14. 6 is not relatively prime because GCD is 2. 7 is not relatively prime because GCD is 7. 8 is not relatively prime because GCD is 2. And 9 is relatively prime to 14. 10 is not relatively prime because GCD is 2. 11 is relatively prime to 14. 12 is not relatively prime because GCD is I think 2. And then 13 is not relatively prime. Now if you observe this, all these numbers, find out the count 1, 2, 3, 4, 5, 6. Therefore phi of 14 equal to 6. Now what does it mean? It means that the number of numbers which are less than 14, which are relatively prime to 14, are equal to 6. That is the meaning of it, right? And next one is, when n is a prime number, then phi of n equal to n minus 1. So why is that so? Because if you take any prime number, then if you try to see how many numbers are less than it which are relatively prime to it, all the numbers less than it will be relatively prime to that, right? Therefore if you take 13, which is a prime number, then phi of 13 is going to be 12. Got it? And this is an important law. I mean, if you can use this law, many things many calculations will be simplified. If m and n are co-primes, which means if two numbers are co-primes, which means the GCD between these two numbers is let's say 1, then phi of m into n can be written as phi of m into phi of n. So what does it mean? It means that if you have, let's say, 15, I need not find out phi of 15 this way, because writing out all those numbers is difficult, isn't it? So simple way is write it as a product of two numbers which are relatively prime. Now if I can write 15 as 3 into 5, since 3 and 5 are prime numbers, they are already relatively prime, right? So I can write it as phi of 3 into phi of 5, which is going to be 2 into 4, which means 8. So why is it 2? Because it is a prime number. Whenever it is a prime number, it is n minus 1. If p is a prime number, p minus 1, right? That is why 3 minus 1 and 5 minus 1, since these two are prime numbers. That is how I got 8. See, this will be useful when this number is very large. See, let us say you want to find out phi of 35, right? Now, it is nothing but I can write 35 as 7 into 5, then it will become phi of 7 into phi of 5, right? So, phi of 7, as you know, is 6. And phi of 5, as you know, is 4, therefore it is going to be 24. Got it? But if you have to evaluate it in this method which I have shown you, then you might have to write all the numbers from 1 to 34, and then you have to test how many are relatively prime with this or not, right? Then that is going to be lengthy, but factorization method, is useful. Okay, now let's see how does this factorization method work if the numbers are repeating. Let's see this one. Now let us say you found out the prime factorization of n. Now if n can be written as product of prime numbers this way, which means p1 power e1 where p1 is a prime number, p2 power e2 where p2 is a prime number, so on pn power en where pn is a prime number, then you can write phi of n as n into 1 minus p1 into 1 minus 1 by p1 into 1 minus 1 by p2 into so on 1 minus 1 by pn. So if you can remember it, you can easily solve some questions. Okay, now look at this. Phi of 36. Now 36 can be written as 9 into 4. 9 is nothing but 3 square and 4 is nothing but 2 square, right? So now I can write it as 36 into 1 minus 1 by 3, right? So why? Because look at this, n into 1 minus 1 by p1, which means 36 into 1 minus 1 by 3 into 1 minus 1 by 2, which means p2 is this, right? Now if you find it out, it is going to be 12. Got it? So that way you can find out, right? Or if you want to use other method, okay, we shall see it later. Okay, fine. Now let's see the main algorithm in this public key private key encryption. So even in your web browsers also, this is the algorithm which is being used for encryption. Now this is RSA algorithm. So it is named after 3 scientists, Rivest, Shamir and Edelman. So names are not important, but let's see the procedure. So the actual procedure I'll just give you here, and later with an example I'll explain you what is happening. Now at the sender side, we are going to encrypt the message and send it, and at the receiver side, he is supposed to decrypt it. Now, what is the message is, whatever text you type, we'll try to convert it into numbers. You can follow any convention, but only thing is, the other side also should follow the same convention. Let us say you are sending some text A, B, C, D, right? Then maybe you can assign 1 digit to each character. Let's say A is 1, B is 2, C is 3, something like this, D is 4, and now this will be 1, 2, 3, 4. See, I am just roughly telling you how to convert it. In general, how you can do it is convert them into ASCII codes and then convert it into numbers and work on that, right? So whatever it is, every text message or even a picture or any kind of message can be converted into numbers using some convention. Now after converting it, your entire message is nothing but a sequence of numbers. Now of this sequence of numbers, you can take each block one by one. Let's say this is a block, right? And you try to encrypt it and send it. And at the other side, they will decrypt this and get these numbers, and from this they will get the text or message, or picture, whatever you are sending. So our main focus is, after this conversion of text into numbers is done, how are you going to encrypt it and you get the ciphertext for it, and on the other side, how are they going to decrypt it and get the plain text. Plain text is nothing but 1, 2, 3, 4 again, right? So after you convert it into ciphertext, the numbers are going to change. Now on the way, when the message is being transferred, no one should be able to understand that the actual message is 1, 2, 3, 4. You are going to send it as a different number, and the people should not be able to crack it back, right? And who should be able to understand it? Only the intended receiver, right? And if you can enable that to happen, that is nothing but the encryption, right? And the strength lies on how hard it is for the people to crack this and get this back. Got it? So let's try to see this. Now we are going to use an encryption, and here we are going to use public key, private key. So let us assume that E comma N is the public key. So E comma N is the public key means if you want to send the message, let us say A wants to send the message to B. A wants to send the message to B, right? Now E comma N is what B has announced publicly. If A wants to send a message to B, then E comma N is what B has announced publicly. Now anyone who wants to send a message to B will always try to use EN to encrypt it. So now how are we going to encrypt it is, represent the message as an integer between 0 comma n minus 1. Now we are going to see that n is very big. Let's say n is 256 bits, and this number is, let's say we'll take 254 bits, so that it will always lie between 0 and n minus 1 without touching n, right? So we can restrict it that way. Now we shall represent, so what is important in this point is represent the message as an integer. That is important. Now once you represent it as an integer, then how does the encryption work is, encrypt the message by raising it to the eth power modulo n. The result is the ciphertext message C. Now what it means is, if you are going to write it this way, see this. If you are going to take the plain text, raise it to the power of E. Why am I raising it to the power of E? Because E and N are the public key is the combination. That combination is the public key which is announced by B. Therefore, since you are sending the message to B, you are supposed to raise the plain text to the power of E mod n, right? And now you are going to get the ciphertext. This is a number and this is a number. Got it? So P to the power E mod n, again this is ciphertext. Now how to decrypt it is, to decrypt the ciphertext C, raise it with another power D mod n. Now what is D mod n is, this is the private key of B. So D comma E is D comma N is a combination which is known only to B. Now this E and D are such a way that once you encrypt something with this one, you should be able to decrypt it only with this one, right? Now how does the decryption here work is, to decrypt the cipher message C, raise it to another power D mod N. So whatever message you got, that is the ciphertext, you are going to take it and again raise it to D mod N. Now what is C? C is nothing but P power E mod N power D. So C is nothing but P power E mod N. Now I am just substituting in place of C this entire thing. Then I got power D mod N. Now according to the modular arithmetic, this entire thing, whenever you have mod n here, this entire thing could be written as P power ED mod n, right? So what did the the receiver get? The receiver has finally got this number. Now this number has to be P. Then only we can say that the plain text whichever is sent by the sender is actually received by the receiver. Now if this one has to happen, then E and D should satisfy one law. According to the Euler's theorem, I told you that whenever this ED is congruent to 1 mod phi of n, whenever this ED is congruent to 1 mod phi of n, this entire thing is going to be P. Okay, you please refer to that Euler's theorem. Whenever the CD is congruent to 1 mod P of n, then this entire thing is going to be P. So how is it possible is, now if the CD is congruent to 1 mod phi of n. Now what is the meaning of it? If I divide this number with phi of n, then the remainder has to be 1, right? Then what should this product be like? Then this product should be like some t into, where t is some number, into phi of n, where phi of n is a number, plus 1. It should be of this form, isn't it? Therefore, if I substitute this one here, if I substitute this entire part over here, then according to the Euler's theorem, I am going to get P. Got it? So this entire algorithm is going to work under the assumption that this is true. And so whenever B is going to declare its public key private key pair, which is nothing but E comma D, E comma N and D comma N, it has to see that E and D are actually multiplicative inverses modulo phi of n. Got it? Which means you should see that E and D are going to follow this rule. Got it? So what is that we are going to say publicly? We are publicly going to announce E comma n. This is what is the public key, right? And what is that we know privately? D comma n, right? Now what is the relationship between E and D? E and D are multiplicative inverses modulo phi of n. Therefore anyone who knows E comma n should not be able to guess D comma n easily. Then when can that be possible? If phi of n, finding out phi of n is difficult, right? See, if I know E and if I know n, I can find out D if I can know phi of n. Why? Because the relationship between E and D is just phi of n. Now if I can know D, then everything is done, isn't it? But then it should be very difficult for anyone to compute, D. If I have to make this one difficult, I should make finding out phi of n difficult. Now how can I make finding out phi of n difficult? If I make n as big as possible, right? That is why people use a very large number, 256 bits. 256 bits means nearly 75 to 80 digits. 75 to 80 digit number they are going to use, and now given that big number you have to find out the Euler's Torsion function, and Euler's Torsion function is nothing but the number of positive integers less than n which are relatively prime to n. So that is going to take a lot of time, right? Even with a very good computer it is going to take a lot of time, right? So that is where the entire strength is going to lie. N has to be very big and n has to be such a number whose phi of n, finding out phi of n is difficult. If you can choose that, even if you declare E and n, D is difficult to find. It is very difficult to find. Now the question is, if others are not able to find out phi of n, how will you be able to find out phi of n? That's the trick. Are you getting this? I am saying that we are going to choose a number n in such a way that no one else will be able to find out phi of n. Fine. If others are not able to find out phi of n, even the same problem will be for you, isn't it? That is why we do a reverse method. Instead of instead of taking the n first and then finding phi of n, we take phi of n first and then find out n. So how is that possible? I'll just show you now. Getting this? Now see this? With this example it will be clear. Alright? Now the algorithm is like this. Choose two distinct prime numbers p comma q, which means we are not actually choosing n first. We are choosing two prime numbers p and q, and then we are multiplying those two prime numbers in order to get n. Now when we know that n is a product of two prime numbers, then finding out phi of n is straightforward, right? P minus 1 into q minus 1 is nothing but the phi of n. Therefore we are not choosing n first, we are choosing the prime numbers first, and these two prime numbers in this example are very small, but in general we take very big numbers, right? Now with such big numbers, when I multiply them, n is going to be very big. Now if I give you n, getting these numbers is difficult. Therefore the entire process is now lying on the fact that prime factorization of any number is very difficult. Prime factorization of a big number is difficult. That is why I am not going to do prime factorization. I am going to take prime numbers and then I am going to find out n from that. Now once I find out n, then finding out phi of n is straightforward. Since I know that n is a product of p into q, now phi of n is going to be phi of p into phi of q, which is nothing but p minus 1 into q minus 1. Got it? Now p minus 1 into q minus 1 is going to be 60 into 52, which is 3120. So this one we are able to find easily, but then given this number, directly finding this number without knowing this p and q is computationally difficult, right? Even with a very good computer, if this number is very large, it will be very difficult to find out. That is where the entire strength of the algorithm is lying. Got it? Okay. Now after finding out phi of n, you are supposed to find out a pair of numbers in such a way that those two numbers are multiplicative inverses modulo phi of n. Got it? Now see this. Choose an integer e, and e should be a number in the range of 1 to phi of n, right? Which is co-prime to this. So let e be 17. So doing all this is simple, straightforward once you know this. Okay, so let us assume that E is 17, right? So since 17 is a prime number and it is less than this, since it is not a multiple of 3120, so both are co-primes. Now you can declare E comma n as the public key. Now once you declare that as a public key, again there is a theorem in which we have seen that there exists at least one number. If these two are, let us say, this one and this one, if these two are co-primes, then we have seen a theorem using which I told you that there exists at least a D which is going to be inverse of this. Right, now you can easily find out what that D is. So D equal to E inverse this one. Now see this. So what does it mean? 17 into some number D has to give us a number, has to give us a remainder 1. Right, now from that we can find out that D equal to 2753. So that is going to be the private key and 17 comma n is going to be the public key. Got it? So either you can declare this one as the public key or the other one as the private key, it doesn't matter, because at the end we are going to raise the same number one time to the power of E and one time to the power of D, right? So therefore you can declare E comma n as the public key and D comma n keep it as the private key, or declare D comma n as the public key and keep E comma n as the private key. Got it? So this is how this RSA algorithm works. So the entire strength of this RSA algorithm lies in the fact that n is a very big number whose prime factorization is difficult. And now how are we breaking it? We are not going to choose n directly, we are going to choose the prime numbers, and from those prime numbers we are going to choose n. Got it? Okay, fine. So whenever you have an organization, let's say a company, and now you are going to have some computers inside the company and you will be having some internet connection from outside world. Now the main problem is, whenever if you have this company, you can secure it or you can protect your resources by having the physical security present there. Like you will have the walls, the normal gates, and you have the security personnel standing outside, and only authorized people will be allowed to enter the building, right? So that is how you are physically going to secure it. But the main problem is, even if you physically protect it, when you have the internet connection from outside world, anyone from outside can access the resources which are present inside your organization, right? So that kind of attacks are possible. So in order to protect physically, we are going to have walls, and the same concept has been applied in internet protection. So if you want to protect your resources, mainly the computer resources from outside world, we are going to apply something called as a firewall. A firewall is nothing but a system, right? So it is a software which is used to protect the access, or which is used to restrict the access. Now using this firewall, you can restrict about who can access the computers from outside, and who can access the the inside people, how they can access the outside world. So you are going to have some restrictions there. You can apply some restrictions, right? Now see this one. So if you see this, let us assume that this is the internal network, which means your organization, and let's say this is the external network. External network means the untrusted party outside, right? And if you are having an internet connection from outside world to the internal network, the problem is anyone can access the resources which are present in your internal network. Now in order to stop that access, you can have something called as a firewall. Now firewall is a software which is going to stop illegal accesses or unauthorized accesses, right? So depending on the rules you frame, it is going to act accordingly, right? Now see this. A firewall forms a barrier through which the traffic going in each direction must pass. Either a packet, if it has to go inside a network, or a packet has to go onto the outside internet, it has to go through this firewall. A firewall security policy dictates which traffic is authorized to pass in each direction. Now whatever you are going to write on this, the rules, they are also called as access rules, right? So according to the rules, you can specify who can go inside and who can go outside. I mean to say, what packets can go inside and what packets can go outside. A firewall must be designed to operate as a filter at the level of IP packets, or may operate at higher layer protocols. So either you can look at, you can write this firewall software based on the information present in the IP headers or based on the information present in the headers above the IP layer. A firewall defines a single choke point that keeps unauthorized users out of the protected network, prohibits potential vulnerable services from entering or leaving the network. So what is the meaning of this one is, why do we actually need it is, sometimes as an organization you might have to protect your let's say code if you are having a repository and you don't want outside people to illegally take it, then you need to protect it, right? So in that case it is going to be useful. And also let's say you don't want anyone from outside to log in into the machines here, then also you can protect it, right? So how we are going to do that? There are various ways. Now depending on what type of information you are going to access or use in order to stop the packets, the firewalls are classified into mainly two types, right? Let's see them. Now the first type of firewall is packet filtering firewall. A packet filtering firewall applies a set of rules to each incoming and outgoing IP packets and then forwards or discards the packets based on information present in TCP and IP headers. Now if you observe this, whenever a packet is coming in, see, let us assume that this is internet and this is your organization, and now you are going to put a firewall here. So any traffic going in or coming out like this has to go through this firewall. Now this firewall will be looking into mainly two headers. One is the IP header and other one is the TCP header. By looking at the IP header, it will be able to know what is the source IP and what is the destination IP, right? And by looking at the TCP header, it will be able to know what is the source port and what is the destination port, right? Now by looking at this information, it will apply some rules, right? Now let's see how the rules are. Now whenever a packet is going to go through this firewall, that packet will be searched across all these entries. If the packet is having matching with any of these entries, then that packet will be discarded. Got it? So just see this. Now let's see the first rule. Now this rule is saying that it is being applied on interface 1. So what is interface 1? This one, right? Which means the packets which are coming from outside into your company, they will all be going through this rule. Whenever I say interface 1, it means the packets coming from outside into the internal network, right? Now if the packets are saying that if the source IP is 131.34.0.0, which means if they are coming from the network 131.34.0.0, it is a network, it is not just an IP address. So you can also specify a network or an IP address here, right? So whenever the incoming packet is saying that it is coming from this network, now I don't care what its source IP is, destination IP is, and what are all the other fields, right? We are going to discard it. Are you getting this? So whenever a packet is coming from this network, like on this interface, that packet will be just discarded or filtered. It is also called as filtering rules, right? So what has happened, you are able to block the packets from a network to enter into our network. Got it? And the next rule is, see this, interface is given as star, which means this rule is applied both on 1 and 2. So both on the packets coming from here as well as here. Now whatever the source IP, destination IP, source port, destination IP is, if the destination port is 23, so what is 23? Telnet, right? Telnet means remote login. Now it is saying that either a packet coming from this direction wants to go for a telnet there, which means someone from outside wants to log in onto a machine there, or a packet coming from this side wants to telnet on the other side, which means someone from inside our company wants to log in onto a system outside. Both will be blocked. Got it? Therefore we are actually blocking a service, isn't it? What is the service here? See, here we are able to block out a network, and here we are able to block out a service. So what is the service here? Remote login, telnet, right? So by using this, we can block out an IP address, which means we can block out a particular system, or we can block out a service, or we can block out a network also, right? Now if you see this next one, this rule is applied on interface 1, so which means it is applied here. right? So the packets coming from outside, right? Now whatever their source IP is, whatever their source port is, the destination IP should never be this. So which means from outside no packet should be allowed to reach this particular node which is inside. Maybe this must be a node which is containing our code repository or some confidential information. Now no packet should reach it from outside. That is the meaning of it. Got it? From outside world no one will be able to reach this host. Therefore we are able to block out a host, right? Yeah, blocking out a host means we are denying the access to that host. Here in this case, here we are blocking out the entire network, entire service, or an IP address, which means one system, right? And if you observe the next one, packets coming from 2, which means from here, if their source port is 80, so what does it mean? HTTP packets. No HTTP packet should go outside, which means we are not providing any web service to the outside world, right? So that means that no packet coming from here with source IP as source port as 80. Source port as 80 means from a web server no packet should go out. Therefore, if there are any websites which are hosted internally, they should be visible only to the people inside the company. They should not be visible to the people outside it, right? Therefore we are able to block out this service completely. So if any packet matches it, that will be discarded, right, or filtered out. Therefore by using the packet filtering firewall, we are able to block out the services at various levels. We are able to block out a host or a network or a service, right? Now if this is the case, then what are the layers, various layers that our firewall should have? Now the firewall should mainly have, definitely it should have network layer, and also it should have transport layer, right? Therefore it is supposed to have physical layer, data link layer, network layer, as well as transport layer. These are the 4 layers it is supposed to have in case if you want to provide all this functionality. Got it? Okay. Now let's see proxy firewall. So till now we have seen the packet filtering firewall, which is actually acting based on the headers which are present in the network layer and transport layer, right? And it doesn't have the higher layers like application layer. Therefore it may not be able to see what is the content present in the application layer in order to take some decisions. Now there are some systems which require even to look into the message, the data which is present in the actual application layer message, right? For example, you may have username and password, right? In case if you want to restrict the users based on username and password, then your this firewall should also understand the username and password, right? So how is it possible? It is possible only if it can look in the application layer data. Generally username and password will come in the application layer data, right? It will not be present in the transport layer header. Therefore if you want to implement such services, then your proxy the firewall should be even more capable. It should even have the application layer as well, right? So I'll just explain you a scenario where we are going to use this proxy firewall. Now the proxy firewall is, it filters the messages based on the contents of the message, and it works at the application layer, right? Now let us say you have the global internet, which means from the outside world. This is the inside world. In the inside world, let us assume that you have a HTTP server. Now if you are going to have HTTP server, right, this server, let us assume that is configured in such a way that it should not provide service to everyone. It should provide service only to those people who have given you a valid username and password, right? For example, let us assume that it is the HDFC net banking server, right? Now it should not provide the web pages concerned to everyone. It should send the web pages only to the customer, which means it should first verify whether the user is having the correct credentials or not. Now for that reason, whenever a packet passes through the firewall, now firewall will not directly send it to the HTTP server. It will internally run one more process which is called as proxy server, right? So in this case it is called as HTTP proxy. So even though I am differentiating these two, actually this process is running inside it, right? Now all the HTTP packets which are coming in will first be tested by this proxy software, and it will see the credentials. If everything is okay, then only the accepted packets will be sent to the server. Now the server will reply to the other party. Now in case if the other party is not able to provide the username and password or whatever credentials are required, then they will simply send an error, right? So whatever the case is, here the main use of the proxy firewall compared to the other firewalls is the packet filtering is we have the application layer here. Got it? Now when the user's client process sends a message, the proxy firewall runs a server process to receive the request, which means it is going to run this one. In this case I am talking about HTTP proxy. It can be any other proxy. If it is all HTTP packets, they will all be sent to this proxy. If there are SMTP packets, they will be sent to the SMTP proxy, right? Now if server opens the packet at the application level and finds out if the request is legitimate, which means the server, this one will open the packet and it will see whether that is valid or not, then only it is going to forward it to this, otherwise it is not going to forward. Got it? Okay.